Hey Vsauce, Michael here. There's a famous way to seemingly create chocolate out of nothing. Maybe you've seen it before. This chocolate bar is 4 squares by 8 squares. But if you cut it like this, and then like this, and finally like this, you can rearrange the pieces like so and wind up with the same 4 by 8 bar, but with a leftover piece apparently created out of thin air. There's a popular animation of this illusion as well. I call it an illusion because it's just that, fake. In reality, the final bar is a bit smaller. It contains this much less chocolate. Each square along the cut is shorter than it was in the original, but the cut makes it difficult to notice right away. The animation is extra misleading because it tries to cover up its deception. The lost height of each square is surreptitiously added in, while the piece moves to make it hard to notice. I mean, come on. Obviously, you cannot cut up a chocolate bar and rearrange the pieces into more than you started with. Or can you? One of the strangest theorems in modern mathematics is the Banach-Tarski paradox. It proves that there is in fact a way to take an object and separate it into 5 different pieces. And then, with those 5 pieces, simply rearrange them, no stretching required, into 2 exact copies of the original item. Same density, same size, same everything. Seriously, to dive into the mind blow that it is and the way it fundamentally questions math and ourselves, we have to start by asking a few questions. First, what is infinity? A number? I mean, it's nowhere on the number line, but we often say things like, there's an infinite number of blah blah blah. And as far as we know, infinity could be real. The universe may be infinite in size and flat, extending out forever and ever without end, beyond even the part we can't observe or ever hope to observe. That's exactly what infinity is. Not a number per se, but rather a size. The size of something that doesn't end. Infinity is not the biggest number. Instead, it is how many numbers there are. But there are different sizes of infinity. The smallest type of infinity is countable infinity, the number of hours in forever. It's also the number of whole numbers that there are. Natural numbers, the numbers we use when counting things like 1, 2, 3, 4, 5, 6, and so on. Sets like these are unending, but they are countable. Countable means that you can count them from one element to any other in a finite amount of time. Even if that finite amount of time is longer than you will live, or the universe will exist for, it's still finite. Uncountable infinity, on the other hand, is literally bigger. Too big to even count. The number of real numbers that there are, not just whole numbers, but all numbers, is uncountably infinite. You literally cannot count even from 0 to 1 in a finite amount of time by naming every real number in between. I mean, where do you even start? 0, okay, but what comes next? 0.000000. Eventually, we would imagine a 1 going somewhere at the end, but there is no end. We could always add another 0. Uncountability makes this set so much larger than the set of all whole numbers that even between 0 and 1, there are more numbers than there are whole numbers on the entire endless number line. Cantor's famous diagonal argument helps illustrate this. Imagine listing every number between 0 and 1. Since they are uncountable and can't be listed in order, let's imagine randomly generating them forever with no repeats. Each number we generate can be paired with a whole number. If there's a one-to-one correspondence between the two, that is, if we can match one whole number to each real number on our list, that would mean that countable and uncountable sets are the same size. But we can't do that, even though this list goes on forever. Forever isn't enough. Watch this. If we go diagonally down our endless list of real numbers and take the first decimal of the first number and the second of the second number, the third of the third, and so on, and add 1 to each, subtracting 1 if it happens to be a 9, we can generate a new real number that is obviously between 0 and 1, but since we've defined it to be different from every number on our endless list in at least one place, it's clearly not contained in the list. In other words, we've used up every single whole number, the entire infinity of them, and yet we can still come up with more real numbers. Here's something else that is true but counterintuitive. There are the same number of even numbers as there are even and odd numbers. At first, that sounds ridiculous. Clearly, there are only half as many even numbers as all whole numbers, but that intuition is wrong. The set of all whole numbers is denser, but every even number can be matched with a whole number. You will never run out of members of either set, so this one-to-one correspondence shows that both sets are the same size. In other words, infinity divided by 2 is still infinity. Infinity plus 1 is also infinity. A good illustration of this is Hilbert's paradox of the Grand Hotel. Imagine a hotel with a countably infinite number of rooms. But now, imagine that there is a person booked into every single room. Seemingly, it's fully booked, right? No. Infinite sets go against common sense. You see, if a new guest shows up and wants a room, all the hotel has to do is move the guest in room number 1 to room number 2, and the guest in room 2 to room 3, and 3 to 4, and 4 to 5, and so on. Because the number of rooms is never ending, we cannot run out of rooms. Infinity minus 1 is also infinity again. If one guest leaves the hotel, we can shift every guest the other way. Guest 2 goes to room 1, 3 to 2, 4 to 3, and so on. Because we have an infinite amount of guests, that is a never-ending supply of them, no room will be left empty. As it turns out, you can subtract any finite number from infinity and still be left with infinity. It doesn't care. It's unending. Banach-Tarski hasn't left our sights yet. All of this is related. We are now ready to move on to shapes. Hilbert's hotel can be applied to a circle. Points around the circumference can be thought of as guests. If we remove one point from the circle, that point is gone, right? Infinity tells us it doesn't matter. The circumference of a circle is irrational. It's the radius times 2 pi. So if we mark off points beginning from the whole, every radius length along the circumference going clockwise, we will never land on the same point twice. Ever. We can count off each point we mark with a whole number. So this set is never ending, but countable, just like guests in rooms in Hilbert's hotel. And like those guests, even though one has checked out, we can just shift the rest. Move them counterclockwise, and every room will be filled. Point 1 moves to fill in the hole, point 2 fills in the place where point 1 used to be, 3 fills in 2, and so on. Since we have an unending supply of numbered points, no hole will be left unfilled. The missing point is forgotten. We apparently never needed it to be complete. There's one last neato consequence of infinity we should discuss before tackling Banach-Tarski. Ian Stewart famously proposed a brilliant dictionary, one that he called the Hyperwebster. The Hyperwebster lists every single possible word of any length formed from the 26 letters in the English alphabet. It begins with A, followed by AA, then AAA, then AAAA, and after an infinite number of those, AB, then ABA, then ABAA, ABAAA, and so on until Z, ZA, ZAA, etc., until the final entry, an infinite sequence of Zs. Such a dictionary would contain every single word, nay, every single thought, definition, description, truth, lie, name, story. What happened to Amelia Earhart would be in that dictionary, as well as every single thing that didn't happen to Amelia Earhart. Everything that could be said using our alphabet. Obviously, it would be huge, but the company publishing it might realize that they could take a shortcut. If they put all the words that begin with A in a volume titled A, they wouldn't have to print the initial A. Readers would know to just add the A because it's the A volume. By removing the initial A, the publisher is left with every A word sans the first A, which has surprisingly become every possible word. Just one of the 26 volumes has been decomposed into the entire thing. It is now that we're ready to investigate this video's titular paradox. What if we turned an object, a 3D thing, into a hyperwebster? Could we decompose pieces of it into the whole thing? Yes. The first thing we need to do is give every single point on the surface of the sphere one name and one name only. A good way to do this is to name them after how they can be reached by a given starting point. If we move this starting point across the surface of the sphere in steps that are just the right length, no matter how many times or in what direction we rotate, so long as we never backtrack, it will never wind up in the same place twice. We only need to rotate in 4 directions to achieve this paradox: up, down, left, and right, around 2 perpendicular axes. We are going to need every single possible sequence that can be made of any finite length out of just these 4 rotations. That means we will need left, right, up, and down, as well as left, 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 up, left, down, but of course not left, right, because, well, that's backtracking. Going left and then right means you're the same as you were before you did anything. So no left rights, no right lefts, and no up downs, and no down ups. Also, notice that I'm writing the rotations in order right to left, so the final rotation is the leftmost letter. That will be important later on. Anyway, a list of all possible sequences of allowed rotations that are finite in length is, well, huge. Countably infinite, in fact. But if we apply each one of them to a starting point, in green here, and then name the point we land on after the sequence that brought us there, we can name a countably infinite set of points on the surface. Let's look at how, say, these 4 strings on our list would work. Right, up, left. Okay, rotating the starting point this way takes us here. Let's color code the point based on the final rotation in its string. In this case, it's left, and for that we will use purple. Next up, down, down. That sequence takes us here. We name the point DD and color it blue since we ended with a down rotation. RDR, that will be this point's name, takes us here, and for a final right rotation, let's use red. Finally, for a sequence that ends with up, let's color code the point orange. Now, if we imagine completing this process for every single sequence, we will have a countably infinite number of points named and color coded. That's great, but not enough. There are an uncountably infinite number of points on a sphere's surface. But no worries, we can just pick a point we missed, any point, and color it green, making it a new starting point, and then run every sequence from here. After doing this to an uncountably infinite number of starting points, we will have indeed named and colored every single point on the surface just once. With the exception of poles. Every sequence has 2 poles of rotation, locations on the sphere that come back to exactly where they started. For any sequence of right or left rotations, the poles are the north and south poles. The problem with poles like these is that more than one sequence can lead us to them. They can be named more than once and be colored in more than one color. For example, if you follow some other sequence to the north or south pole, any subsequent rights or lefts will be equally valid names. In order to deal with this, we're going to just count them out of the normal scheme and color them all yellow. Every sequence has 2, so there are a countably infinite amount of them. Now, with every point on the sphere given just one name and just one of 6 colors, we are ready to take the entire sphere apart. Every point on the surface corresponds to a unique line of points below it all the way to the center point, and we will be dragging every point's line along with it. The lone center point we will set aside. Okay, first we cut out and extract all the yellow poles, the green starting points, the orange up points, the blue down points, and the red and purple left and right points. That's the entire sphere. With just these pieces, you could build the whole thing. But take a look at the left piece. It is defined by being a piece composed of every point accessed via a sequence ending with a left rotation. If we rotate this piece right, that's the same as adding an R to every point's name. But left and then right is a backtrack. They cancel each other out. And look what happens when we reduce them away. The set becomes the same as a set of all points with names that end with L, but also U, D, and every point reached with no rotation. That's the full set of starting points. We have turned less than a quarter of the sphere into nearly 3/4 just by rotating it. We added nothing. It's like the hyperwebster. If we add the right piece and the poles of rotation and the center point, well, we've got the entire sphere again, but with stuff left over. To make a second copy, let's rotate the up piece down. The down-ups cancel because, well, it's the same as going nowhere, and we're left with a set of all starting points, the entire up piece, the right piece, and the left piece. But there's a problem here. We don't need this extra set of starting points. We still haven't used the original ones. No worries, let's just start over. We can just move everything from the up piece that turns into a starting point when rotated down. That means every point whose final rotation is up. Let's put them in the down piece. Of course, after rotating, points named UU will just turn into points named U, and that would give us a copy here and here. So as it turns out, we need to move all points with any name that is just a string of U's. We will put them in the down piece and rotate the up piece down, which makes it congruent to the up, right, and left pieces. Add in the down piece along with some up and the starting point piece, and, well, we're almost done. The poles of rotation and center are missing from this copy, but no worries. There's a countably infinite number of holes where the poles of rotation used to be, which means there is some pole around which we can rotate this sphere such that every pole hole orbits around without hitting another. Well, this is just a bunch of circles with one point missing. We fill them each like we did earlier, and we do the same for the center point. Imagine a circle that contains it inside the sphere and just fill in from infinity. And look what we've done. We have taken one sphere and turned it into 2 identical spheres without adding anything. 1 + 1 = 1. That took a while to go through, but the implications are huge, and mathematicians, scientists, and philosophers are still debating them. Could such a process happen in the real world? I mean, it can happen mathematically, and math allows us to abstractly predict and describe a lot of things in the real world with amazing accuracy. But does the Banach-Tarski paradox take it too far? Is it a place where math and physics separate? We still don't know. History is full of examples of mathematical concepts developed in the abstract that we did not think would ever apply to the real world for years, decades, centuries, until eventually science caught up and realized they were totally applicable and useful. The Banach-Tarski paradox could actually happen in our real world. The only catch, of course, is that the 5 pieces you cut your object into aren't simple shapes. They must be infinitely complex and detailed. That's not possible to do in the real world, where measurements can only get so small and there's only a finite amount of time to do anything. But math says it's theoretically valid, and some scientists think it may be physically valid too. There have been a number of papers published suggesting a link between Banach-Tarski and the way tiny subatomic particles can collide at high energies and turn into more particles than we began with. We are finite creatures. Our lives are small and can only scientifically consider a small part of reality. What's common for us is just a sliver of what's available. We can only see so much of the electromagnetic spectrum. We can only delve so deep into extensions of space. Common sense applies to that which we can access. But common sense is just that, common. If total sense is what we want, we should be prepared to accept that we shouldn't call infinity weird or strange. The results we've arrived at by accepting it are valid, true within the system we use to understand, measure, predict, and order the universe. Perhaps the system still needs perfecting. But at the end of the day, history continues to show us that the universe isn't strange. We are. And as always, thanks for watching. Finally, as always, the description is full of links to learn more. There are also a number of books linked down there that really helped me wrap my mind kind of around Banach-Tarski. First of all, Leonard Wapner's The Pea and the Sun. This book is fantastic and it's full of a lot of the preliminaries needed to understand the proof that comes later. He also talks a lot about the ramifications of what Banach-Tarski and their theorem might mean for mathematics. Also, if you want to talk about math and whether it's discovered or invented, whether it really truly will map onto the universe, Yanofsky's The Outer Limits of Reason is great. This is the favorite book of mine that I've read this entire year. Another good one is E. Brian Davies' Why Beliefs Matter. This is actually Korn's favorite book, as you might be able to see there. It's delicious and full of lots of great information about the limits of what we can know and what science is and what mathematics is. If you love infinity and math, I cannot more highly recommend Matt Parker's Things to Make and Do in the Fourth Dimension. He is hilarious and this book is very, very great at explaining some pretty awesome things. So keep reading, and if you're looking for something to watch, I hope you've already watched Kevin Lieber's film on Field Day. I already did a documentary about Whittier, Alaska over there. Kevin's got a great short film about putting things out on the internet and having people react to them. There's a rumor that Jake Roper might be doing something on Field Day soon. So check out mine, check out Kevin's, and subscribe to Field Day for upcoming Jake Roper action, yeah? He's actually in this room right now. Say hi, Jake.
Hi.
Thanks for filming this, by the way.
You're welcome.
Guys, I really appreciate who you all are. And as always, thanks for watching. Hey, Vsauce, Michael here. And what if every single person on Earth jumped at the exact same time? Could it cause an earthquake, or would we not even be able to tell? Well, first things first, let's talk about the Earth's rotation. The Earth spins, it's why we have night and day, and it spins quickly. At the equator, the Earth is spinning at more than 1,000 miles per hour. Now, a spinning ice skater can speed up by moving mass closer to the center, and the Earth is no different. In fact, if you get down on the ground right now and move your mass closer to Earth's center, technically you will speed up Earth's rotation, making this day shorter. Now, the change that you would make to the Earth's rotation is way smaller than we could even measure, but it is calculatable, and the impact can be quite impressive when you talk about redistributing more mass than just one person. For instance, last year, the earthquake in Japan redistributed so much of Earth's mass towards the center that every day since then has been 1.8 microseconds shorter. But that was a giant geological event. What can us humans do to the Earth all on our own? I mean, there are more than 7 billion of us now. What if we all got together in one place and jumped? Well, what would that even look like? Interestingly, if you took the entire human population of Earth and had them all live in one place with the same density that people live in New York City, you could fit everyone, all of us, into the state of Texas. But that's living, not standing around in a crowd, which is how we would probably want to do the jump. If every single person alive right now on Earth stood shoulder to shoulder, you could fit all of us into the city of Los Angeles. It would be an incredible sight to behold, a mere 500 square miles containing every single person on Earth. Okay, so then we jump. What happens? Unfortunately, not much. I mean, we're all awesome people here on Earth, but our collective mass compared to the mass of the entire Earth, it's like nothing. In fact, dot physics calculated that if all of us were to get together in one location and all jump 30 centimeters into the air at the exact same time, we would push Earth away from us a tiny amount. Earth would only move away from us about 1/100th of the width of a single hydrogen atom. And here's another thing. Because we are all jumping and then going back to where we started, Earth is just going to move back to where it started. So our big jump won't be able to change Earth's position in space, but come on, 7 billion people all jumping together, that's got to be able to cause some sort of seismic activity, right? So let's say you have a lot of people all together in one place, and you have them all jump on 1, 2, 3. Did you feel that? Well, the BBC did this with 50,000 people and discovered that 1.5 kilometers away, it only registered as a 0.6 on the Richter scale. You would need 7 million times more people than even live on Earth right now to jump at once to recreate the earthquake that recently happened in Japan. So, even though we're all awesome, compared to the size of the Earth, we're not much. But don't get too discouraged. Our collective jump would contain a lot of energy. The Straight Dope calculated that even if only the people who lived in China got together and jumped, their jump would be the equivalent of 500 tons of TNT. Of course, 500 tons of TNT doesn't do much to an Earth that weighs 6 sextillion 588 quintillion tons. To make yourself feel more powerful, pick a card. I've got 10 of them here. Let's say you choose this one. Boom, congratulations. We have just decimated this deck of cards. Why? Well, because technically, decimate does not mean obliterate completely. Deci, 10. It means to take away 1/10 of something. So the next time you take a quiz and don't do so well on it, you only get 10%, well sure, that's an F. But by getting 10% of them right, you decimated that quiz. And since we've been talking about crowds, let's talk about YouTube crowds, YouTube audiences, that view count that you see at the bottom of every video, and get some perspective on it. We'll begin with Dunbar's number. It's an estimation of the maximum number of people we can have stable social relationships with at a given moment, and it's based on the size of our neocortex. These aren't just acquaintances, these are people you have social contact with, a network where you know how everyone relates to everyone else, and the number is usually given to be somewhere between 100 and 230. Which means that when a YouTube video receives more than 230 views from different people, more people have seen that video than you could ever realistically hope to know well at a given moment. If a video has more than 100,000 views from different people, More people have seen that video than you will ever meet in your life. And by meet, I mean shake hands with, learn their name, talk to them for a bit. I mean, think of it this way. You and me, we are only statistically expected to live around 28,470 days. So even if you were to meet someone, 2, 3 people every day of your life, including when you were a baby, you still wouldn't meet as many people as have seen that YouTube video with 100,000 views. But keep this in mind, even though you, or even a large group of us, can't do much to change Earth's location or rotation, we can affect it a little bit. Newton's third law guarantees this. If you weigh 150 pounds, the Earth is pulling you down with a force of 150 pounds, but you are also pulling up on the Earth with a force of 150 pounds. If you fall 3 meters, the Earth has pulled you down 3 meters, but you have also exerted a equal and opposite force on the Earth. Of course, it's a lot bigger. So if you fall 3 meters, you pull the Earth up about 1/1000th of the width of a proton, which ain't bad. So the next time you move your body, the next time you jump, Felicia, think about this. You just affected the Earth as much as it affected you. You've got that kind of power. Speaking of power, you all should go check out Geek and Sundry, Felicia's new channel. It's one of my new favorite things. And,
as always,
thanks for watching. Hey, Vsauce, Michael here. In 2003, researchers did the measurements and found that Kansas is in fact literally flatter than a pancake. Of course, the Earth is not flat, the Earth is round. Otherwise, travelers would be falling off the edge all the time. Right? Wrong. If the Earth was not a ball shape, but was instead a flat disk, like this plate, well, with the right density and thickness, living in the middle could feel pretty normal. But as you moved toward the edge, gravity on a disk Earth would slightly skew, pushing at a greater and greater angle back toward the center. My friend Nick from Yeti Dynamics put together this great simulation. The person and buildings obviously aren't to scale, but check out how such increasingly diagonal gravity would work. Although this is a flat disk, it would feel to a runner headed toward the edge like they were fighting to climb up a steeper and steeper hill. The building foundations behind the runner reflect how you would have to build structures closer and closer to the edge so that people living in them always felt like down was at right angles to the floor, the way we feel it on our big round Earth. Now, as you approach the edge, things would get scary. Remember, this is a flat Earth, but it would feel like a sheer drop-off. What's really cool is that contrary to the don't fall off the edge fear, on a flat world, because of gravity, the scary risk would actually be falling away from the edge and rolling all the way back to the center. Once you stepped over the edge, instead of falling off into space, you'd be able to relax. It would be a nice, level place. This model, of course, neglects the fact that such a planet shape would be impossible. Anything as massive as the Earth, shaped like a flat disk, would, under its own gravity, naturally collapse back into a ball. This is why in outer space, everything more than a few hundred miles in diameter is round. Or so we've been told. What if gravity isn't real? What if the Earth is in fact flat and science has been wrong all along? It's a misconception that Christopher Columbus discovered that the Earth is round. Virtually every scholar and major religion in the West accepted Earth's rotundity since at least the time of the ancient Greeks, who, for instance, had noticed that boats disappear bottom first when sailing away, and as you walk north and south, stars pop into and out of view. The misconception that only a few hundred years ago lots and lots of people believed the Earth was flat likely began in the modern era as a sort of insult, well, your people recently thought the Earth was flat, so why should we believe you now? The smear was repeated and published so often it became accepted as historical fact. flat earther became synonymous with anti-science. It might seem flat over short distances, but over longer ones, well, the Earth is pretty darn curvy. The Verrazano Narrows Bridge, connecting Staten Island and Brooklyn, had to be designed with Earth's roundness in mind. Its two towers, separated by 1,300 meters and perfectly vertical, are nonetheless 41 millimeters further apart at the top than at the bottom because of Earth's curvature. In the 3rd century BC, Eratosthenes measured the differences between shadows cast by poles in Syene and Alexandria to calculate, more than 2,000 years before rockets and space travel, the circumference of the entire globular Earth, with, for the time, impressive accuracy. Word got around that the Earth was a round shape after that. But in 1906, Wilbur Glenn Vsauce became head of a slightly bizarre religious sect that pretty much ran the city of Zion, Illinois. Vsauce believed that the Earth was actually flat, and he enforced flat Earth teachings in schools in Zion. He also enforced that belief on really anyone who entered the city. Vsauce believed not only that the Earth was flat, but that the sun was only a few thousand miles away from Earth, not 93 million. He also believed that the sun was only 32 miles across, not 860,000. He sounds crazy. Or does he? You see, the same phenomenon Eratosthenes measured could be explained by a flat Earth if the sun were only a few thousand miles away and 32 miles across. The math would work out the same. Today, with the power of the internet, modern-day flat earthers have picked up where Vsauce left off. They have quite good explanations for any evidence you throw at them that the Earth is round. Circumnavigation is really just a flat circle path. The round shadow Earth casts on the moon during a lunar eclipse could also be made by a flat disk. Time zones are caused by a spotlight sun. And remember how gravity would be totally different on a disk-shaped planet? Well, they argue that gravity as we know it simply doesn't exist. The flat disk of Earth is merely accelerating up at 9.8 meters per second. As for all of the photos and video evidence we now have that the Earth is round thanks to space exploration, well, all of that material is completely fabricated. A hoax perpetrated by Big Globe. Space agencies, airlines, globe manufacturers, they are reaping the rewards of our ignorant belief that the Earth is actually round. They know, of course, that it's flat, and they're hiding that truth from us. Is it merely a coincidence that the logo used by the Flat Earth Society is a projection of Earth centered on the North Pole and also happens to be the projection used by the United Nations? Are these people for real? Probably not most of them. But this is the crux of Poe's law, an adage that states that at their extremes, parody of extremism and sincere extremism are difficult to distinguish. Although clever, flat Earth theories are predominantly ad hoc explanations, excuses made up on the spot that only address one issue and don't fit all the evidence. Science, of course, rejects a theory if a better one fits more of our observations, but why the egotistical obsession with our observations? A cosmic ray particle could use the very same scientific method we use and conclude that the Earth was in fact flat. You see, at speeds near the speed of light, time slows down and lengths contract. One way we know this is that unstable muons created in the upper atmosphere by the collision of cosmic rays with the atmosphere should mostly decay before reaching Earth's surface. But yet, we detect a lot of them down here, because their crazy fast speed literally means that from our perspective, their physics runs according to a slower clock. And to them, the distance they have to cover to the surface during their short lives is, from their perspective, much, much shorter than it appears to us. If you were a cosmic ray proton traveling at 99.99999999991% the speed of light, Earth would appear to be only 17 meters thick in the direction you traveled. So Earth is flat to them, but round to us. It is ball-shaped to some observers and flat to others. There doesn't appear to be a single most correctest in all circumstances answer. Susan Hack compares knowledge to a crossword puzzle. New answers interweave with old ones. They all reinforce one another. The clues are the questions we ask, and the way the answers fall into a predetermined grid, well, that's our confidence that we're on the right track. But that doesn't mean that one day there will be a finished puzzle, a complete answer. Recall the New York Times' famous 1996 crossword puzzle that came out the day before the US election between Bill Clinton and Bob Dole. The clue for 39 across was pretty crazy. You seemed to need to be able to tell the future to answer it correctly. It simply said, lead story in tomorrow's newspaper, blank elected. Well, that blank could be Clinton or Bob Dole. And who's to say which one until tomorrow? There's no way to know. But as it turned out, the answer was Clinton or Bob Dole. No matter which you wrote in, all the other clues fit. For instance, a black Halloween animal could either be a cat or a bat. Our knowledge about the outside world might be the same. A puzzle with no answer key, just the reassurance that the answers we think we know fit together, so they're probably correct, though there's always the possibility that the answer to one clue or all of them will fundamentally not have a single definite satisfying answer. The puzzle may be playable forever. I like what Richard Feynman says about this. Some people say, how can you live without knowing? I do not know what they mean. I always live without knowing. That is easy. How you get to know is what I want to know. You know? And as always, thanks for watching. Hey, Vsauce, Michael here, and today we are going to go inside a black hole. It's not going to be comfortable, but it will be pretty fun. Now, first things first, mathematically speaking, anything could become a black hole if you were to compress it into a small enough space. That's right, you, me, this camera, everything in the universe has what is known as a Schwarzschild radius, a tiny, tiny amount of space that, were you to collapse the entire mass of the object into, its density would be so great that its gravitational pull would be so great that not even light could escape from it. You would have a black hole. If you were to compress Mount Everest into something smaller than a nanometer, you would have a black hole. And if you were to compress the entire Earth down to the size of a peanut, you would have a black hole. But fortunately for us, there is no known way to compress Everest or Earth in that fashion. But a star, many, many, many times larger than our own sun, has a much larger Schwarzschild radius, and when it runs out of fuel and can no longer keep itself hot enough, it collapses to a single infinitesimally small point known as a singularity. Its density will be infinite, and so its gravitational pull will be so strong that nothing can escape, not even light. But enough about ways black holes form, let's jump into one. First question, what would it look like from the outside? Well, we know that gravitational fields bend space and time. Stars behind our sun will actually appear to be in slightly different locations from Earth because the sun's gravitational field bends the light coming from those stars. When it comes to the gravitational fields of larger objects like entire galaxies, or for that matter a black hole, the effect is even nuttier. Light coming from objects behind them is significantly distorted, producing smears and smudges. As seen from Earth, the blue galaxy behind this red galaxy is completely distorted like a funhouse mirror, so rather than appearing as it really should, it looks to us like a ring, a smudge all the way around the red galaxy. This is known as gravitational lensing. Now take a look at this simulation of a black hole with a galaxy millions of light years behind it. The galaxy is not really in danger of the black hole's suck, but the light coming off of that galaxy certainly is. Watch as the galaxy passes behind the black hole, and its light is contorted, twisted, and distorted. Now here's a really fun demonstration. What if the Earth were to orbit around a black hole? Looking from the outside, the Earth would look normal at first, but as soon as it passed behind the black hole's gravitational field would warp the light reflecting off the Earth, producing this. For the sake of simplicity, let's jump into a simple black hole, one that doesn't have a charge and isn't moving, and also isn't already sucking up a bunch of matter, so it's just there on its own. As we approach, the distortion of the sky grows greater and greater. A larger and larger portion of our field of view looking forward into the black hole will be filled with darkness. At this point, where half of our field of view has been swallowed up in darkness, we have reached the photon sphere. At this point, light is not going to necessarily get sucked into the black hole, but it doesn't necessarily leave it either. Instead, at this magical point in space, light, photons, can actually orbit the black hole. If you were to stop here for a moment and look to the side, you could theoretically see the back of your own head, because light reflecting off the back of your head would travel all the way around the sphere of the black hole right back to your face. A gravitational field not only warps space, it also warps time. Now, for most intents and purposes here on Earth, we never have to worry about that. But near a black hole, gravity would be so strong that an observer standing, watching you jump into the hole, would see something quite strange. They wouldn't see you get sucked quickly into the hole. Instead, they would see your approach become slower and slower and slower until you reached a point known as the event horizon. This is a point in space where, once crossed, there's no going back. It is at that point that light can no longer escape. And so to a person watching you fall into the hole, that would be where your journey ended. You would seem almost frozen in space, the light coming off your body becoming increasingly red-shifted until you simply faded into nothingness. They would never see you cross the event horizon. But for you, of course, everything would seem fine and dandy. You would continue past that horizon to your now inevitable death. As you continue to approach the black hole's singularity, your view of the entire universe would get compressed into a smaller and smaller point in space behind you. If the black hole we're jumping into is large enough, things might actually be quite comfortable at that event horizon. We'll know that we're never going to escape and that our lives are pretty much over, but it might take us hours to actually reach a point where things started to hurt. Why would they hurt? Well, the closer you get to the singularity, the more significant the difference in gravitational pull is across space. And so parts of me that are closer to the singularity would be pulled more strongly than parts that were facing away, and my entire body would be stretched toward the singularity. The effect would be so incredible, scientists don't usually call it stretching, they call it spaghettification. Once you reached this point, you would be dead. Your molecules would be violently ripped and stretched apart, and when they got to the singularity, well, we don't really know what would happen. Perhaps they would completely disappear in violation of all the laws of physics, or maybe they would reappear elsewhere in the universe. It's believed that a moving or spinning black hole might actually create what is known as a wormhole, a way of transitioning across space faster than light. Not in any way that violates the laws of science, but in a way that takes advantage of the universe's dimensions. For instance, if I wanted to get from this point to this point, I'd have to travel the distance. But theoretically, a wormhole would do something really crazy. For instance, this. Now, the 2 points are right next to each other and I can travel between them almost instantaneously. But again, this is all theoretical. Luckily, we do have a possible way of analyzing black holes right here on Earth. Enter the dumb hole. Just as a black hole does not permit light to escape, a dumb hole is an acoustic black hole. It won't allow sound to escape. It doesn't have to be nearly as powerful, and scientists have been able to create dumb holes in laboratories using special fluids traveling at the speed of sound. A lot of progress still needs to be made in the world of acoustic black holes, but we may be able to learn an amazing amount of information about how black holes work by looking at how sound is treated in a dumb hole.
Now here's another good question. What would it look like to travel at the speed of light, say, toward the sun? Well, surprisingly, you wouldn't just see the sun immediately rush up toward you. No. In fact, initially, it would look almost as if the sun were receding away from you. Why? Because your field of view would vastly increase in size. You would be able to see stuff almost behind you, and here's why. As you sit there, not moving yet, looking at the sun, there's light coming from stuff behind you. But if you travel the speed of light, you will actually reach that light coming from things behind you. As you reached light speed, your field of view would expand like this, concentrating the stuff in the middle. But where are you in the universe? Or here's a better question, where is the center of the universe? Well, this might sound crazy, but it's everywhere. This is known as the cosmological principle. No matter where you are in the universe, everything else will seem to be moving away from you, expanding at the same rate. The universe is expanding, but not like a balloon getting bigger with all the people inside it. Instead, it's as if we are the surface of a balloon. If you were to put a bunch of dots on a balloon and then blow it up, all of the dots would move away from each other at the same rate. And on the surface of the balloon, there is no center. Take a look at these two layers. They are exactly similar, except the top layer represents a 5% expansion of the bottom layer. Let's say that you live on one of these dots, and you want to measure where everything's moving away from. Well, watch what happens when I line up a dot in the past and the present. Boom. It looks like the center of the expansion. I can do this with any dot. As soon as I choose a dot to be the frame of reference, it immediately becomes the center of the expansion. So while dying in a black hole would be lonely and scary and morbid, when you look up into the sky, think instead about this. No matter where you are or who you are or what your friends or your parents tell you, you really scientifically are the center of the universe. Finally, what if our universe was a Googleplex meters across? It is nowhere near that large, but if it was, it would be so voluminous that statistically, it would be nearly impossible for there not to be an exact copy of you somewhere else out there in the universe. To see why, I highly suggest that you click right there and check out Brady Heron's new channel, Numberphile. It's part of the YouTube original channels, and I've worked with these guys before. They're amazing. They're my favorite kind of geeks. So check out that video, watch their other stuff, and if you like math, I highly suggest that you subscribe. And as always, thanks for watching.
Hey, Vsauce, Michael here. And the year 6009 will be the very first year since 1961 that a year, when written in Hindu-Arabic numerals, can be inverted and still look the same. But you and I probably won't live long enough to enjoy the year 6009. Human lives just aren't long enough. We will miss out on that. What other cool future events will we be missing? Well, first of all, you and I will probably be gone before the completion of the Time Pyramid in Winding, Germany. It will eventually be a pile of 120 concrete blocks, but the builders are only adding one block every 10 years. Since beginning in 1993, they've added only the first 3. At this rate, the pyramid will be completed in the year 3183, the final block placed by our great, more than 30 greats, grandchildren. But even they will miss an opportunity to frolic and play safely in the Chernobyl exclusion zone, the zone of alienation, where radioactive contamination from the 1986 disaster will remain at levels too high for safe human activity until not the year 4000, not the 5000s, not the 6000s. It will finally be safe probably in the year 22,000. Possibly within our lifetimes, but definitely within the next 1 million years, stars like Betelgeuse and Eta Carina will explode in brilliant supernovas visible from Earth. I'm bummed I'm probably going to miss out on these events because for a few weeks it will look almost as if Earth has two suns. Despite being hundreds, thousands of light years away, their supernovas will shine brighter than the full moon at night and be visible even during daytime. But the real sky show comes in 3.75 billion years. Our galaxy is full of stars. Viewed from the surface of the Earth, they look like little drops of milk in the sky, which is why we call it the Milky Way galaxy. But all galaxies are named after milk. Milk, lactose, lactic, galactic, galaxies. And every drop of milk in the sky, every star that you can see, is inside our galaxy, the Milky Way. But there's a blurry, distant shape, this one. It's not a star, it's not a cloud of gas in our galaxy, it is an entirely different galaxy, the Andromeda Galaxy, and it's 2.5 million light years away from our own. It contains twice as many stars as the Milky Way, and it is coming our way, headed toward us at 300 kilometers a second, faster than a bullet. Now right now, the sky looks like this. In 2 billion years, Andromeda will have approached so closely that people will look up at the sky and see this. In 3.75 billion years, the night sky will be like a scene from a science fiction movie or an awesome desktop wallpaper. Incredible. And kind of scary. After this scene, the sky will literally be glowing with the birth of new stars as the Milky Way and Andromeda collide, mixing up into a brilliant cosmic tie-dye. This simulation shows how Andromeda might collide with the Milky Way, but keep in mind that you are watching billions of years pass every second. These galaxies are moving fast, but they're also huge and covering even huger distances. They will collide in the future, but within the briefness of a single human life, they appear almost frozen, unmoving. A couple billion years after colliding, the cores of both galaxies will be married together in a bright glowing center. Earth, now a stepchild to what was once Andromeda, part of a new, bigger family called Milkdromeda. It would be so cool to be alive to see our galaxy colliding with another. But don't get all FOMO, consumed by a fear of missing out. Because whatever life is around then will have plenty to envy us for. They may have spectacular nightly views, but secretly wish they'd been born in our time to experience, say, the beginning of the internet. They will actually miss out on a lot of things. Because the moon moves 1 centimeter further away from Earth every year, 600 million years from today, the moon will no longer be close enough to Earth to completely block out the sun. Future humans, or descendants of humans, will therefore miss out on a chance to ever see for themselves the beauty of a total solar eclipse from the surface of Earth. Long before Earth dries up, Niagara Falls will dry up. Well, not the water part, but the falls part. Every year, the rushing water of Niagara erodes the rock at the top of the falls 1 foot backward. By the year 52,000, it will have eroded all the way to Lake Erie, and our progeny will have no Niagara Falls to enjoy. Granite has an erosion rate of about 1 inch per 10,000 years. So certainly by the year 7 million, Mount Rushmore, especially its faces, will no longer exist. And because they slowly get pulled in or ejected into space, in 50 to 100 million years, Saturn will no longer have its lovely rings. So life on Earth in the future might have awesome supernovas and galactic collisions to look forward to, but they probably won't have Niagara Falls, Mount Rushmore, total solar eclipses, or Saturn's rings. They also won't have you. But you have you. Except not all of it. Babies don't begin to form episodic memories right away, meaning that you missed out on. You don't remember two of the most seminal events in your life, your conception and your birth. But you can experience a bit of those moments right now. First of all, when was I conceived? .com lets you enter your birth date and get back the week your parents probably made you happen, as well as the #1 song and the #1 movie of that week, which may have also been involved. Light travels quickly, the most quickest in fact, but it can take a photon millions of years to escape from the interior of the star it was created in through nuclear fusion. It takes time, just like your own gestation in your mother's womb. Newly conceived photons struggle through a dense stellar jungle of atoms and molecules and electrons that absorb and re-emit the photon, taking a little bit of energy from it as it randomly rolls around like a pinball. Sometimes after thousands or millions of years, its random walk finally leads it to the star's surface, where it pops out into space, in a way, is born. A lucky tiny percentage of the photons that reach the surface of a star find themselves on a path that will intersect with Earth. And if you are lucky, those photons will end their journey by being absorbed onto your own retina. If you enter the date of your birth or the approximate date of your conception into this online calculator, you can find a star that is as many light years away from Earth as you are old. When you look up at that star today, you are seeing light that left the star the very month you were born, or photons that left that star and entered space when your entire body was just one cell. Space is really big, and your life is very short. But space is so gosh darn big, you don't have to miss out on everything. And as always, thanks for watching.
Lagiem? Sosif? Yeah! Hi! Vsauce, Michael here.
You can practice speaking backwards, so when your words are reversed, they're intelligible. But here's something else that is weird. The digits in the speed of light are exactly the same as the latitude of the Great Pyramid of Giza. And, as the anagram genius has revealed, all the world's a stage, but if you rearrange the letters in the meaning of life, it becomes the engine of a film, or more pessimistically, the fine game of nil. What does all of this mean? Are these just coincidences, or are greater powers at work? Why is it so easy for us to find hidden messages? Why can a mere coincidence give us chills? And why is it so fun? When you reverse Neil Armstrong saying "small step for man," you can hear what sounds like "man will spacewalk."
That's one small step for man, baseball, small step for man, baseball, small step for man, baseball.
Lee Harvey Oswald assassinated President John F. Kennedy, and in this interview, he defends the Fair Play for Cuba Committee, of which he was a member.
The fact that I did live for a time in the Soviet Union gives me excellent qualifications to repudiate charges that Cuba and the Fair Play for Cuba Committee is communist controlled.
Now listen to what it sounds like when we reverse him saying, "and the fair play for Cuba."
And the fair play for Cuba. Luis Garcia President.
Luis Garcia President. Luis Garcia President.
Is that a coincidence or a subconscious confession hidden within his own words? It's a coincidence. For crying out loud, if anybody says, "and the fair play for Cuba," and then reverses it, it sounds the same. This app, by the way, is called Virtual Recorder. It's a really easy way to quickly reverse your own speech. Matthew Hudson in The 7 Laws of Magical Thinking points out that if you record yourself saying, "Ooh, you sniff turkey fat," and then reverse it, it sounds a bit like "happy birthday to you." Kind of. If a word can be spelled the same forward and backward, it's a palindrome. But if a word or phrase sounds the same, whether spoken forward or rewound, it is a phonetic palindrome. For example, say yes. Reversed? Say yes. Pretty cool. But check out this poem by Karsten Johansson. "When I wonder why what's never been's never been so, we would lie when we say, yes, you know we all love you. What's never been's never been so, hell, we're nowhere now. I wonder what was never been's that we lie when we say yes, seem to be all that we was never been's that we all were nowhere now." By the way, some people can speak in reverse on the fly. It is really cool to see them in action. Watch Guys Lean Back after this video. It's linked down in the description, and it's full of pretty cool coincidence videos. Apophenia is the perception of connections or patterns in information. One type of apophenia is pareidolia, the seeing or hearing of things that weren't meant to be there. For instance, hearing your name being called or your phone ringing in the sound of running water, or hearing English words in a non-English song, or seeing faces that weren't purposefully placed there. Our brains are good at this kind of work, probably because being hyper-attentive to patterns and faces can save your life. If there's ambiguity as to whether that thing hiding in the shadows is a threat or just a shadow, it's advantageous to err on the side of threat. Organisms with a healthy sense of apophenia live longer, long enough to have kids and raise them and naturally become the norm. We connect with faces so well. Hudson relates a story of a friend who draws faces on things she doesn't want to lose, like her bags. She says the faces make her less likely to forget about them. If you like it, you should have put a ring on it. If you like not losing it, you should have drawn a face on it. We are so good at teasing out patterns and faces from random noise. Actual random sequences don't always feel random to us. Originally, Apple's iTunes Shuffle feature generated complaints from users. They said that similar songs or songs from the same artist appeared in a string, which of course is to be expected from randomness, but it didn't feel random enough. So Apple introduced a smart shuffle that avoided totally random sequences that nonetheless didn't seem random to our pattern-loving brains. As Steve Jobs explained, we're making it less random to make it feel more random. Our impressive ability to imagine patterns also expresses itself when it comes to connecting songs and moving images. This dancing Spider-Man animation will famously sync up with any music you play. Try it. What kind of black magic is going on here? Well, as it turns out, most of it is in our heads. Radiolab reported that Michigan State University explains that the major movements of dancing animations like this one, or this one, move at typical song tempos, but also contain, like most dance, various other different related rhythms of movement, allowing them to seemingly fit many different tempos. Selection bias helps a lot too. We fall prey to this when we reject all the times the animation doesn't really sync up, focusing instead on the more surprising times when it does. The bizarre pyramid coincidence mentioned earlier is a lot less bizarre when you consider the fact that we got to control where we placed the decimal point. and that a number of degrees this precise isn't necessary to locate the pyramid. By the fourth decimal, we're only talking about a matter of a few meters, so it's easy to make the rest fit the speed of light exactly and have still picked a point on the pyramid. Confirmation bias also comes into play here. If you really want two things to sync up, they will. We often look for evidence that supports what we already believe while marginalizing things against it. As Marshall McLuhan said, "I wouldn't have seen it if I hadn't have believed it." These biases also help explain the seemingly mind-blowing coincidence that famous movies and famous albums can line up. One of the most popular states that if you start playing Pink Floyd's Dark Side of the Moon at the same time as The Wizard of Oz, they will eerily line up. Entire communities have sprouted around the syncing of movies and albums. Some of my favorites are the Yellow Submarine soundtrack and The Little Mermaid, Lord's Pure Heroine and Twilight Saga Breaking Dawn 2, and the end of 2001 A Space Odyssey with Pink Floyd's Echoes. There are conspiracies that these were somehow secretly planned, though in reality they're just accidental music videos, the product of selection bias, confirmation bias, and the law of near enough, a behavior of our pattern-sensitive minds. Two things don't have to line up exactly or literally for us to see a connection. This is why vague predictions are a great way to look psychic. These are also actually unsurprising when you consider the fact that the number of narrative paces and rhythms we enjoy and typically use are much smaller than the number possible. In the improbability principle, David J. Hand calls this the probability lever. What may be rare on average, or when considering all possible scenarios, can be less rare for specific scenarios, even if they are only marginally different. Getting struck by lightning is a proverbially unlikely event, but Walter Summerford wasn't just struck by lightning once during his life, he was struck 3 times. It never killed him, but 4 years after his death, his gravestone was also struck by lightning. What are the chances? I mean, clearly Summerford was some sort of robot built out of lightning rods, or had somehow angered Zeus, right? Probably not. You see, while for the average person, the chance of being struck by lightning is quite low, for an avid outdoor sportsman like Summerford, it's not as low. The law of truly large numbers also comes into play here, with lightning striking Earth 40 to 50 times a second. Billions of people for it to strike and thousands of years of recorded history, it's actually not surprising at all that at least once a story like Summerford's would have happened. Given the truly large number of people who visit Disney World every day, and the fact that they take photos and lots of them, it's actually not surprising at all that at least once so far, a story like Alex and Donna Vsauce's has happened. While sorting through old photos before their wedding, Alex and Donna found a photo of Donna at Disney World 14 years before the couple met. But then Alex noticed something. He too had visited Disney World as a child, and there, in the background, was his father pushing him in a stroller. Sometimes coincidences can be tragic. In 1864, Abraham Lincoln's son, Robert Lincoln, was saved from serious injury or possibly even death when a stranger grabbed him by the shirt collar moments before he plunged onto train tracks below. That stranger turned out to be Edwin Booth, one of the most famous Shakespearean actors of the time. So famous, in fact, Robert recognized him and had a letter sent thanking him for saving his life. Less than a year later, Edwin Booth's brother, John Wilkes Booth, undid the favor by assassinating Abraham Lincoln. Strange as they seem at first, math says that given enough time, and psychology says that given enough interest in finding them, coincidences and connections will be found, even unlikely ones. The coincidences between Abraham Lincoln and John F. Kennedy are famous. Both were elected to the presidency in a year ending with 60. Lincoln was shot at Ford's Theater. Kennedy was shot in a 1961 Lincoln Continental 4-door convertible, made by Ford. Both presidents' last names have 7 letters, and both assassins had 15 letters in their names. The list goes on, as it should. If you look long enough, you can find coincidences between any two people or things or events. They may seem strange at first, but tend to wind up being, in the end, pretty expected. For just one example, name length isn't that wildly variable. 7-letter names are pretty common. Lincoln, Kennedy, Michael, Stevens. In the famous Spooky Presidential Coincidences contest held by the Skeptical Inquirer in 1992, one contestant alone found similar lists of crazy coincidences between 21 pairs of former presidents. Given the vast amount of details in any one of our lives, it's pretty easy. This quirk can be exploited to almost comedic heights when it comes to overanalyzing. Of course, hidden messages and signs are often intentionally included in media for fun or to reward attentive viewers. But unintentional, extraordinary things happen all the time. It's not really that extraordinary. There's a famous calculation that is known as Littlewood's law. Given the number of hours we are awake every day, and assuming an event only takes about a second to occur, if you calculate the odds of something happening to you are only 1 in a million, well, you should expect that thing to happen to you about once every 35 days. David J. Hand took this even further with 7 billion people on Earth. The chance that an event with a 1 in a million probability of happening to each of us won't happen today is 1 in 10 to the 3,040. As Percy Diaconis put it, the truly unusual day would be a day where nothing unusual happens. And as always, thanks for watching. You may have noticed a lot of YouTube channels making videos about learning this week. Well, that is not a coincidence. It is School of YouTube Week. Many people are going back to school or college right now, but across the world, millions of children won't be. Either because they work to support their families, or live without a home, or in areas where there is conflict. They may experience overcrowding at school or a lack of teaching and school supplies. But luckily, we can help. Donations to Comic Relief's School of YouTube campaign can help disadvantaged young people all around the world get an education. It doesn't take much to change a life. You can learn more in the description below or donate right now. And as always, thanks for helping and thanks for learning. Hey, Vsauce, Michael here. Attachment. Of two people's lips kissing. The average person will spend about 20,160 minutes of his or her life kissing. And the world record for the longest continuous kiss is 58 hours, 35 minutes, and 58 seconds. But why do we kiss? I mean, if you think about it, it seems kind of weird, right? I mean, sure, today, kissing represents peace, respect, passion, love. But when the first two people in human history kissed, were they just kind of being gross? Well, let's begin with what we do know. Kissing feels good, and it's good for you. A passionate kiss burns about 2 to 3 calories per minute and releases epinephrine and norepinephrine into the blood, making your heart pump faster. Kissing, more often, is correlated with a reduction of bad cholesterol and perceived stress. But these positive effects didn't become widespread by accident. Why did brains and bodies that love kissing become so common? Well, a popular story holds it that Pac-Man's shape was inspired by the shape of a pizza with a slice missing. But Toru Iwatani, the creator of Pac-Man, admitted that this was only half true. Pac-Man's shape was also inspired by rounding out the shape of the Japanese character for mouth. And it's mouths and Pac-Man's favorite activity, eating, which together bring us closer to the heart of the kiss. Evolutionary psychologists have argued that what we know today as kissing may have come from kiss feeding, the exchange of pre-chewed food from one mouth to another. Mother birds are famous for doing this, and many primates are frequently seen doing it as well. Not that long ago, it was common between human mothers and their children. In fact, before commercially produced or DIY baby food instructions were readily available, it made a lot of sense. Recently, Alicia Silverstone uploaded a clip of herself mouth-feeding her child. It seemed strange to some people, but even though, yeah, it exchanges saliva, which, like any contact with an infant, can transfer pathogens, healthy mothers and healthy children can benefit from the fact that kiss feeding provides nutrients, carbohydrates, proteins, iron, and zinc, which are not always available in breast milk. Plus, an adult's saliva can help pre-digest the food, making vitamins like B12 easier for the baby to absorb. So mouth-to-mouth attachment has a history of intimacy, trust, and closeness. Your saliva also carries information about who you are, your level of health, and mucous membranes in our mouths are permeable to hormones like testosterone, making a kiss a way to taste test a potential mate. A good kiss can be biological evidence that your kisser might be a good mate. So as a strategy for mate selection, prehistoric people who enjoyed kissing and did it more often may have made better decisions, picked better mates, reproduced more successfully, and eventually become the norm, giving us, people who love kissing. Any infant could have seen those benefits coming from a mile away. Even though an infant's vision isn't that great, from birth to 4 months, babies can only focus on things about 8 to 10 inches away from their face, which not surprisingly is about the distance to their mother's face while breastfeeding. So faces, especially those looking right at us, tend to be the very first things in our lives we can focus on and see clearly. This might explain why we are so good at detecting faces. Humans are off the charts when it comes to this. In fact, we tend to see faces even when there aren't any. It's called pareidolia. Because humans are so cooperative, it makes sense for us to be good at recognizing faces, and more importantly, detecting when someone is looking directly at us and clearly expressing when we are looking at someone else. A predator who lives by not being seen needs a gaze that's less obvious. In fact, research has shown that our surprisingly white scleras, the area that borders the iris, isn't just an accident, but is a vital piece of human eye morphology that makes it easier for us to ascertain the direction of someone else's gaze at a glance. We also have impressive gaze direction networks inside our brains, containing individual neurons that fire when someone is staring directly at us, but that stop firing if the gaze shifts just a degree or two. So yeah, you can tell when you are being watched. We humans are quite sensitive to it, even those of us with scopophobia, the fear of being stared at. But to be sure, in order for this to work, the other person's gaze must be within your line of sight, your field of vision, that is, you can see them. Otherwise, if the stare is coming, say, from behind, there is no evidence that people can tell they are being watched. The psychic staring effect falls within the realm of pseudoscience. No widely accepted studies have ever found evidence that it exists. Anecdotally, what's more likely is that the very act of rubbernecking to see who's watching causes people to look up and for your gazes to attach. But what about attachment when no one is watching? One explanation for an infant's love, attachment to their mother, doesn't involve vision or staring, but instead food. The idea is that we love our mothers because as soon as we are born, they are a source of life-sustaining nourishment. But what if that nourishment came not from a loving mother, but from a scary wire mother? In the 1950s, Harry Harlow conducted a series of famous but controversial experiments on monkeys at the University of Wisconsin-Madison. Harlow's findings had substantial implications on our understanding of attachment, but by today's standards, his work would largely be considered unethical. In one of his most famous experiments, Harlow separated young monkeys from their mothers as soon as they were born and stuck them in cages with two fake mothers, a soft one wrapped in cloth that did nothing, and a cold mechanical mother made of wire that nonetheless did provide food. But despite being a cupboard mother, the young baby monkeys didn't bond with her. When Harlow or his team scared the baby monkeys with a strange contraption, the monkeys ran and clinged not to their wire source of life-sustaining nourishment, but to the soft, cuddly, and otherwise useless cloth mother. This suggested that warmth and comfort was more important than food when it came to nurturing attachment. Harlow also built a rejecting mother, which used a blast of pressurized air to push baby monkeys away. But instead of finding another source of comfort, these monkeys clung even tighter at all times than monkeys raised without rejecting mothers. And this is what blows my mind. The instinct for warmth and comfort in newborn creatures is so strong, it not only resists attempts to frustrate it, but is paradoxically strengthened by it. Eckhard Hess tested this by using electric shocks to discourage ducklings from following the object they were imprinted on, but it only strengthened the behavior and made them follow more closely than ever before. The fact that a wire mother or a rejecting mother or receiving electric shocks for attaching to your mother would cause more attachment, more love, more dependence seems like a paradox. But paradoxes can teach us. As Oscar Wilde put it, a paradox is the truth standing on its head to attract attention. And what gets our attention here is the effect uncertainty can have. In 1955, A.E. Fisher conducted an experiment on puppies. His team separated puppies into 3 groups. Members of the first group were treated kindly every time they approached a researcher. Members of the second group were punished for approaching the researchers, and puppies in the third group were randomly treated kindly or punished. They grew up never knowing what to expect. Their world was not a world of kindness or punishment, but rather one of uncertainty. What's really chilling is that the study found that that group, the third group of puppies, wound up being the most attached to the researchers. The third group loved the researchers the strongest and was the most dependent upon them. Guy Murchie called this the polarity principle. Stress, including the mental stress of uncertainty, is an ingredient in attachment or love, and perhaps even manifestations of hatred, its polar opposite, somehow enhance love. Uncertainty, psychologically, can lead to some of the greatest feelings of attachment and dependence. Good things and bad things in our lives often seem random and out of our control, so it's no surprise that we often react with blind love and acceptance in the face of an unfair existence, because what else are we supposed to do? We are that third group of puppies. But investigating uncertainty, conquering it so as to make the best decisions possible, is advantageous. So over time, life has favored activities that turn uncertainty into knowledge. Not every person out there is the best mate for you. But if it didn't matter which one you picked, a kiss, a taste test wouldn't be necessary, and it wouldn't need to feel so good or bring us so much pleasure. So go out there and kiss someone today. And as always, thanks for watching. by the way, tomorrow I am headed to the European Space Agency's spaceport in South America with Euronews to watch a rocket launch in real life. Do you have any questions about space or space travel today? Let me know in the comments below and I will ask the experts your questions. Hey, Vsauce! Michael here. Do you have a best friend who is there for you 24/7, 365? Sorry, that's not really good enough. If your friend truly had your back, they would be there for you 24.000067365.2421891. Also, George Washington was born on February 22nd, 1732. At least, that's what we're told. However, his family Bible says he was born on February 11th, 1731/2. So, which is it, Mr. I cannot tell a lie? Oh, and don't even ask about 1752. In Russia, 1752 looked pretty normal, but check out what the British Empire was up to that year. Nothing really out of the ordinary, except Ember. The 2nd was followed by the 14th? Were 11 days just deleted? Where'd they go? What happened then? It is time to question time and how the Earth moves. Reconciling both of these things has led to some pretty strange things. We all love time-lapse videos of the stars moving across the sky. But really, we are the ones who are moving, tumbling through the universe on a giant, wet rock vehicle called Earth with a windshield called the sky. As viewed from above the North Pole, we spin counterclockwise. West chases east. I always remember this by thinking of the US as a weird, mane-headed animal with Texas and Florida legs running forward. But we don't just spin. We also revolve around the sun on a plane tilted 23.4 degrees relative to our spin. It's kind of nauseating at this scale. But from this perspective, you can see that the sun rising and setting is just the Earth pointing you towards and then away from the sun. This motion causes your sunrise, your noon, the moment when the sun is highest in your sky, before your sunset. To more closely investigate this movement, let's talk about meridians. You are on one at this very moment. Your meridian is just a line from where you are right now, straight towards the north and south poles. It's a line of longitude, as opposed to the horizontal lines that lay flat when north or south is up that we call flatitude, or actually, latitude. The sun is highest in the sky to you, your noon, when your meridian is pointed right at the sun. A cool thing happens at this moment. All shadows around you point directly towards one of Earth's poles, unless you're on the subsolar point. The subsolar point is the point on Earth's surface directly below the sun. It's always somewhere. You can check its current location online, links as always in the description. On the subsolar point, shadows fall straight down so they can easily disappear. Twice a year, the subsolar point crosses over Hawaii, the only place in the US where it hits land. And when it does, it is called Lahaina Noon, meaning cruel sun. Straight vertical objects look unnatural during this brief time, like they don't belong, as if they were photoshopped in without regard for reality. In Honolulu, a sculpture by Isamu Noguchi called Skygate casts a twisted shadow all day, every day, except during Lahaina Noon, when its shadow is a perfect circle. You may not live in a place where the sun ever appears directly overhead, but once every Earth rotation, the subsolar point falls somewhere on your meridian, making it noon for you. The technical name for this noon for you is local apparent solar noon. The clock on your wrist and the clock on your phone don't tell you your local apparent solar time, because long ago we realized that if every meridian had its own time, a person just a few kilometers away, seeing different shadows than you did, would disagree with you on what time it was. So towns adopted their own time. Now later on, this trick was standardized and time zones as we know them today came about. But that's not all we didn't like about shadow-based sundial time. To explore deeper, we have to begin by asking, what's a day? I mean, obviously it's just the time it takes the Earth to turn around once, right? But according to what? Everything else in space is moving in some way too. The universe doesn't include a convenient sheet of graph paper at absolute rest we can trace paths on. The best we can do on that front is to look at very, very far, far, far away stars. So far away, like distant features of the landscape out the window of a moving car, they barely move as Earth does. Now, to them, a meridian on Earth completes a trip around about once every 23.9 hours. This is called a sidereal day. Sidereal means pertaining to the stars. Even though the sidereal day seems pretty clear, it's not what our calendars and clocks are based on, because there's a nearer star whose position relative to us has a bigger effect on our lives: the sun. Looking down on the North Pole at Earth's counterclockwise spin, the Earth also moves counterclockwise around the sun. After a sidereal day, the Earth has moved a bit along its orbit, so some more rotation is required for the same meridian to point back towards the sun again. This longer definition of one rotation is what the modern calendar and clock is based on. It is called the solar day. But here's the thing. Exactly how long the Earth has to rotate to complete a solar day changes day to day. Our clocks are just based on the average amount of time this takes, so throughout the year, they fall ahead and behind the sun. This is a solograph, a picture of the sun's path across the sky every single day. If our clocks actually told us local apparent solar time, if you took a picture of the sky every day at noon, you should get a line of suns. But this is what really happens. Over the course of a year, it will appear as though your clock is running slow, and then fast, and then slow again, and then fast again. This problem was known since at least ancient times, even if its cause wasn't. In order to reconcile the two, the equation of time was constructed. In this sense, equation means to reconcile. The equation of time was applied to what a clock said in order to compute the real time, the solar time a sundial would show. Now, some fancy clocks, called equation clocks, were made that would do this for you, but eventually, we gave up. We gave up and just said, no, the real time isn't what the sun says, it's what our inventions say. Now, this transition was a big one. It was humanity growing up. It was like the first time you realize you're stronger than your parents. We realized our timepieces were more regular and turned our backs on the timepieces nature had. But what causes this disagreement in the first place? As it turns out, the answer revolves around revolving, the way the Earth revolves around the sun. If the equator faced the sun all the time and the Earth always orbited at the same speed, the subsolar point would just stay right there on the equator throughout the year, and the amount of extra time spent rotating the Earth needed to do to finish a solar day would always be the same. But those two things aren't the case. First of all, the Earth's orbit is slightly elliptical, so its speed varies throughout the year. When it's moving around the sun faster around the beginning of January, the amount of extra turning time needed to complete the solar day is longer than when it's further away from the sun and moving more slowly. There's more. Because the Earth is tilted, the subsolar point is dragged throughout the year in a circle around Earth that's not the equator, so it changes direction, moving northeast, then leveling out and going southeast, before leveling out and going northeast again. During times of the year when the subsolar point is being dragged by Earth's orbit mostly east, it gains against Earth's spin faster. More time is required for the day to finish. Now, by coincidence, we are alive at a time when both of these phenomena lengthen and shorten days at roughly the same time. So they add up, making September 18th almost a minute shorter than the longest day of the year, December 22nd. For Northern Hemispherians, December has the shortest periods of daylight, but the whole solar day, from sunrise to sunrise, is for everyone on Earth the longest of the year on December 22nd. People in the north just spend most of it in darkness. Earth's tilt, it doesn't just affect how long a day is, it also affects how long a year is. This is because the Earth's tilt is what causes the seasons. For the half of the Earth tilted towards the sun, the same amount of solar radiation is spread across less space than it is on the other half, so there's more heat energy laid down per area. This causes what we call summer and winter for the other half. The amount of time from one of these seasonal orientations of the Earth to its occurrence again is called a solar year, or a tropical year. It's a very useful way to define a year because it contains every single season exactly, since it's based on the very orientations that cause them. But the problem is this: the number of solar days that occur in a solar year is not a whole number. It's almost 365. But after that many solar days, about a quarter of a day more happens before the solar year starts again. This makes designing a calendar more like designing a calendar. If your calendar only ever has 365 days in a year, over time, those dates will drift from the seasonal positions they used to occur during. Unless, this extra quarter of a turn adds up to a full day after 4 years. See, March 1st is coming a day too soon now, so if we just delay March by adding an extra day at the end of February every 4 years, a leap day, we're back on track. Leap days do not add days to your life. You're still going to live the same number of them. They just change what we call them. But really, who cares about being 1 day earlier every 4 years? I mean, 1 day isn't much, you'd hardly notice it. But over time, well, if America's founders had declared not only independence from Britain, but also from leap days, and abolished them from happening, today, 240 years later, their calendar would be a full 2 months ahead of Earth's position, putting America's coldest winter days in April and its hottest summer days in October. Adding a day every 4 years is what the famous Julian calendar does. Introduced in 46 BC by Julius Caesar, it was the de facto standardized Western calendar for a very long time, more than a millennium. But it's not perfect. Look closely. Leap days actually move the calendar just slightly too far each time, because I lied. 365.25 solar days don't occur within one solar year. The real number is slightly less and fluctuates year to year based on long-term changes to Earth and the sun's movements, which means adding 1 day every 4 years is just a teensy-weensy too many. By 1582, Julian calendar dates were 10 days behind the seasons compared to where they used to be. Now, that's not bad, 10 days in more than a millennium and a half. But the Catholic Church cared, because they wanted Easter to occur exactly when it used to centuries ago. Astronomers at the time realized that if leap days pushed the calendar too far behind the seasons, we would just need to celebrate fewer of them to fix the problem. Specifically, we would need 3 fewer leap days every 4 centuries. The rule they wrote to achieve this stated that every 4 years would continue to be a leap year, except if it was divisible by 100, unless it was also evenly divisible by 400. This removes 3 every 400 years. On October 4th, Pope Gregory XIII introduced this new calendar. It took his name, the Gregorian calendar. He also undid the drift that had occurred since the early days of the Julian and declared on October 4th that tomorrow would be October 15th. October 5th to the 14th never happened in 1582 in countries that listened to the Pope. It took the rest of the world centuries to hop on board. England and its colonies, like the soon-to-be United States of America, adopted the Gregorian in September of 1752, by which point their Julian dates were off from the seasons by 11 days, hence the disappearing of the 3rd through 13th. When adopted, the first of the year was also moved from March to January 1st. This explains why George Washington's birthday has 2 answers. Although more closely hitched to the seasons than the Julian, the Gregorian calendar still isn't perfect. Its difference causes dates to become 1 day off from the seasons every 3,216 years. Other calendars have been proposed, like the one Stand Up Math's calculated that drifts off even more slowly. His video is a great watch, by the way. But enough of all of this. Let's sit back and enjoy Earth's movement without trying to divide it up and name it. As a caveat, keep in mind that Earth's oceans and liquid insides and other celestial bodies are always pulling and tugging and sloshing around, minutely changing Earth's movements. Their effect is measurable, but difficult to notice at big scales and also don't look like much in the short term. Short like the length of a human life. Looking from above the North Pole, the equator spins counterclockwise at about 1670 kilometers per hour. Relative to the sun, Earth orbits counterclockwise at 108,000 kilometers per hour, along a path tilted 23.4 degrees to its spin. Within our local neighborhood of stars, our entire solar system is drifting 70,000 kilometers per hour, roughly in the direction of the bright star Vega in the constellation of Lyra. And our solar system is part of a giant galaxy called the Milky Way. On a plane tilted about 60 degrees, approximately like the windshield of a car, looking from above Earth's North Pole, our entire solar system races clockwise around the galactic center at about 792,000 kilometers per hour. Our whole galaxy is also moving through the universe. We know this because when the universe was very young, it was so hot, electrons and protons jumped around and photons of light scattered constantly. They couldn't travel very far before scattering again, so the universe was opaque. But then, around 380,000 years after the Big Bang, the universe cooled just enough for electrons and protons to form hydrogen. Suddenly, abruptly, photons decoupled from this obstacle course and could travel relatively unencumbered. The universe became transparent to light. And since that moment, those early photons have been propagating through space. Every day, ancient photons that last scattered off this opaque fog at the moment of decoupling, a light day further from where Earth currently is, reach us. They are part of the cosmic microwave background radiation. It is visible in every direction. Microwave because although they used to be more energetic, the universe's expansion has redshifted them. Now, some parts of this radiation are more redshifted than others because of our own movement through the universe. Controlling for the movements we've already talked about, relative to this infinite, cooling baby picture of the universe, the first and oldest detectable light, we are headed riding along in the Milky Way in the direction that the constellations of Leo and Virgo are to us, at a speed of 2.1 million kilometers per hour, towards a thing we don't fully understand yet, simply called the Great Attractor. This is how you, on Earth's surface, are moving through the universe aboard spaceship Earth. Okay, now stop. This is roughly 100 years of Earth's movement through space. This path we've traced, from where we began here, is the path you will take through the universe in your lifetime. You didn't buy a ticket for this ride. Your parents signed you up without asking. But nonetheless, it is quite literally the ride of your life. And as always, thanks for watching. It is now time for a major Vsauce announcement. You know how for the last couple of years we've released a holiday box? Well, introducing the Curiosity Box by Vsauce. We created this thing as a quarterly box. This comes to you 4 times a year, and it comes packed with amazing, exclusive Vsauce merchandise and incredible geeky toys picked by myself, Kevin, and Jake. Plus, as always, a portion of the proceeds from this box goes to funding Alzheimer's research. You can get your own by subscribing at thecuriositybox.com. I'm incredibly proud of this. Go check it out. And as always, thanks for watching. Hey, Vsauce, Michael here. This appears blue. This appears yellow, and this appears green. Those of us with normal color vision can probably agree, but that doesn't change the fact that color is an illusion. Color as we know it does not exist in the outside world beyond us, like gravity or protons do. Instead, color is created inside our heads. Our brains convert a certain range of the electromagnetic spectrum into color. I can measure the wavelength of radiation, but I can't measure or observe the experience of a color inside your mind. So, how do I know that when you and me look at a strawberry, and in my brain, this perception occurs, which I call red, that in your brain, a perception like this doesn't occur, which you have, of course, also learned to call red. We both call it red, we communicate effectively, and walk away, never knowing just how different each of our internal experiences really were. Of course, we already know that not everybody sees color in exactly the same way. One example would be color blindness. But we can diagnose and discuss these differences because people with the conditions fail to see things that most of us can. Conceivably, though, there could be ways of seeing that we use that cause colors to look differently in different people's minds without altering their performances on any tests we could come up with. Of course, if that were the case, wouldn't some people think other colors looked better than others, or that some colors were more complementary of others? Well, yeah, but doesn't that already happen? This matters because it shows how fundamentally, in terms of our perceptions, we are all alone in our minds. Let's say I met an alien from a faraway solar system who, lucky enough, could speak English, but had never and could never feel pain. I could explain to the alien that pain is sent through A delta and C fibers to the spinal cord. The alien could learn every single cell and pathway and process and chemical involved in the feeling of pain. The alien could pass a biology exam about pain and believe that pain to us generally is a bad thing. But no matter how much he learned,
the alien would never actually feel pain. Philosophers call these ineffable, raw feelings qualia. And our inability to connect physical phenomenon to these raw feelings, our inability to explain and share our own internal qualia, is known as the explanatory gap. This gap is confronted when describing color to someone who has been blind their entire life. Tommy Edison has never been able to see. He has a YouTube channel where he describes what being blind is like. It's an amazing channel. In one video, he talks about colors and how strange and foreign of a concept it seems to him. Sighted people try to explain, for instance, that red is hot and blue is cold. But to someone who has never seen a single color, that just seems weird. And as he explains, it has never caused him to finally see a color. Some philosophers, like Daniel Dennett, argue that qualia may be private and ineffable simply because of a failure of our own language, not because they are necessarily always going to be impossible to share. There may be an alien race that communicates in a language that causes colors to appear in your brain without your retina having to be involved at all, or without you having to have ever needed to actually see the color yourself. Perhaps even in English, he says, given millions and billions of words used in just the right way, it may be possible to adequately describe a color such that a blind person could see it for the first time. Or you could figure out that once and for all, yes, or no, in fact, you and your friend do not see the same red. But for now, it remains the case that we have no way of knowing if my red is the same as your red. Maybe one day our language will allow us to share and find out. Or maybe it never will. I know it's frustrating to not have an answer, but the mere fact that you guys can ask me about my internal experiences, and the mere fact that I can ask my friends and we can all collectively wonder at the concept of qualia is quite incredible, and also quite human. Animals can do all sorts of clever things that we do. They can use tools, problem solve, communicate, cooperate, exhibit curiosity, plan for the future. And although we can't know for sure, many animals certainly act as if they feel emotions, loneliness, fear, joy. Apes have even been taught to use language to talk to us humans. It's a sort of sign language that they've used to do everything from answer questions to express emotion or even produce novel thoughts. Unlike any other animal, these apes are able to understand language and form responses at about the level of a 2.5-year-old human child. But there's something that no signing ape has ever done. No ape has ever asked a question. Joseph Jordania's Who Asked the First Question is a great read on this topic, and it's available for free online. For as long as we have been able to use sign language to communicate with apes, they have never wondered out loud about anything that we might know that they don't. Of course, this does not mean that apes and plenty of other animals aren't curious. They obviously are. But what it suggests is that they lack a theory of mind, an understanding that other people have separate minds, that they have knowledge, access to information that you might not have. Even us humans aren't born with a theory of mind, and there's a famous experiment to test when a human child first develops a theory of mind. It is called the Sally-Ann test. During the test, researchers tell children a story about Sally and Ann. Sally and Ann have a box and a basket in their room. They also happen to have a delicious cookie. Now, Sally takes the cookie and puts it inside the box, and then Sally leaves the room. While Sally is gone, Ann comes over to the box, takes the cookie out, and puts the cookie inside
the basket. Now, when Sally comes back, the researchers ask the children, where will Sally look for the cookie? Obviously, Sally will look in the box. That's where she left it. She has no way of knowing what Anne did while she was gone. But until the age of about 4, children will insist that Sally will check the basket, because after all, that's where the cookie is. The child saw Anne move the cookie, so why wouldn't Sally also know? Young children fail to realize that Sally's mental representation of the situation, her access to information, can be different than their own. And apes who know sign language but never ask us questions are doing the same thing. They're failing to recognize that other individuals have similar cognitive abilities and can be used as sources of information. So, we are all alone with our perceptions. We are alone in our own minds. We can both agree that chocolate tastes good, but I cannot climb into your consciousness and experience what chocolate tastes like to you. I can never know if my red looks the same as your red, but I can ask. So stay human. Stay curious and let the entire world know that you are. And as always, thanks for watching. Hey, Vsauce Michael here, and when the pyramids of Giza were built, the tallest was 147 meters tall, making them the tallest things humans had ever built. And they remained that way for nearly 4,000 years. It wasn't even until the 1300s that we finally got around to making something taller, a cathedral in England. So, does that mean that the Great Pyramids of Giza are the best, tallest structures of all time? Well, to find out more, all aboard the boat. So, what is a building? Well, technically, a building is a structure in which at least 50% of its height comes from floor plates where people can live, work, chill out. It has to be habitable. Any less than that, and it's not a building, it's a tower. After the Lincoln Cathedral finally surpassed the height of the pyramids, a number of churches continued to be built that kept breaking and setting new records. The next long-term record holder was the Eiffel Tower. It was the tallest thing ever in history that we had built for about 40 years in a row. It was finally surpassed by the Chrysler Building in New York, a personal favorite, which was then quickly bested by the Empire State Building. Now, the Empire State Building is interesting in that it was the first structure ever built by man that was so tall, were you to jump off the top of it, you would actually reach terminal velocity before you hit the bottom. It was the first structure we'd ever built that was so tall, rather than just continuing to accelerate as you fell, you would actually stop accelerating because you would reach the fastest possible speed your limp body can fall at. In the mid-1950s, something weird started to happen. Humans started to build radio and TV towers. These things could be way taller than the buildings that we'd made previously that had to be habitable. And so, ever since the Empire State Building had its record broken by a TV tower, all these other famously tall buildings, the Petronas Towers, Taipei 101, the World Trade Center, the Willis Tower, formerly Sears Tower, none of them have ever within their existence actually held the title for being the tallest thing we've ever built. There was always a radio or TV tower somewhere that was taller. Up until quite recently, and for quite a while, the record for the tallest thing ever built by humans went to the Warsaw radio mast in Poland. It's visually incredibly striking because there aren't any other skyscrapers around it. It's all alone, being very tall. Well, that was until 1991, where some workers exchanging guy wires made a mistake and the whole thing started to bend and then snapped in the middle. There's no video of the event happening, but it would have been similar to this collapse though much, much taller. After the Warsaw radio mast collapsed, the KVLY TV mast in North Dakota became the tallest still standing structure built by man. But recently, buildings have made a comeback, and to check that out, we're going to have to travel to the Middle East.
This is the first time I've ever touched the Nile.
Ta-da!
Okay, so that was me dipping my waterproof camera into the Nile. If you were to take the entire length of the Nile River and stand it up on its edge, perpendicular to the Earth, it would reach into outer space about this far. It's pretty impressive. But where does the space shuttle orbit? And where does the International Space Station orbit? This far away? This far away? Maybe this far away. Actually, if this pink, inflatable, horrible boss's ball was the Earth, the space shuttle would orbit about right there. It's incredible, but it's possible because the shuttle and the International Space Station travel so quickly. They travel so quickly around the Earth that instead of seeing one sunrise and sunset every 24 hours, they see 16. But don't be jealous. You can easily see more than one sunrise and or sunset in a day by taking advantage of tall structures. So let's take a look at the tallest structure, the current record holder for the tallest thing humans have ever built, the Burj Khalifa in Dubai. The height of this building blows my mind. You can literally watch the sunset from the base of the building and then take a super fast elevator all the way up to the top and watch the same sun set again. In fact, the difference in timing between sunset at the base and the top is so significant, the Dubai Islamic Affairs Department actually had to make a ruling about when you can start and break your fast during Ramadan inside the building. People above floor 80 or higher have to actually wait to start eating 2 to 3 minutes after the people at the base because the sun hasn't yet set for those at the top. But before you head to Dubai to watch the sun rise or set twice in a day, keep in mind that the only height you actually need to see 2 sunrises or sunsets is the height of your own body. Try this the next time you're at a beach. Watch the sun rise or set over the water. Water is important because it won't have the terrain and hill issues that land does. Now let's say you're watching a sunset. Begin by laying on your stomach. Watch the sun set, and as soon as the very last little bit of the sun goes below the horizon, quickly pop up into a standing position, and voila, you'll see the sun's back, part of it's back, and it will set another time. If you take a stopwatch and record the time between the first setting and the second setting that you witness, and measure the height of your eyes when you're laying down and when you're standing, you can use those numbers to calculate the radius of the Earth. XKCD took this a little bit further by proposing the double sunset date. Take your date out to the beach in a cherry picker, and sure enough, it was calculated. Given the speed of a cherry picker, all you have to do is move about 6 feet up, and you can watch a beautiful sunset all over again. To put things in perspective, the Burj Khalifa is nowhere near as tall as Mount Everest, but the tallest structure that we could potentially build wouldn't be as tall as Mount Everest. It would be way, way taller, like into space taller. Of course, the problem with building things that are really tall is that they get heavier and heavier and have to support their own weight. But only up to a point. If a structure was so tall that it wound up at the altitude of a geostationary orbit, it would start to feel a new force, not just a gravitational force downward, but all of a sudden this new centrifugal force up and outward. And so a building that tall could be stable through tension and more than 35,000 kilometers high. This kind of structure is known as a space elevator. Unfortunately, there aren't any materials known to science today that are strong enough to make building something that large feasible. with the exception maybe of carbon nanotubes or boron nitride nanotubes. Of course, if we went to a smaller celestial body like the moon, we could build one today out of stuff like Kevlar. There are a lot of different things that we have to be wary of when we build a space elevator. For instance, how do we dodge space debris? One solution is to attach the Earth side of the cable to a boat in the ocean that can maneuver around and move the elevator away from dangerous obstacles. Another interesting point is that the taller the cable, the faster the far end of it will be traveling. In fact, if the cable is more than 50,000 kilometers long, its far end will be traveling near escape velocity, and simply walking outside could take you to the moon. But why build a space elevator? Well, because it would be awesome, but also for better reasons too. For instance, right now, in order to send a pound of material into orbit, it costs about $11,000. But with a space elevator, we could send the same amount of material into orbit for only about $100. That difference is so significant that Philip Reagan has said that the first country to deploy a space elevator will have a 95% cost advantage and will possibly be able to control all space-related activities.
All right, so here you see in the mirror Alex playing guitar while she holds a camera in her mouth and records us. Impressive. I'm here with Kristen from Barely Political. She's visiting London. And if you enjoyed this episode of Boat, check out other episodes. I've got them all up there.
And as always, thanks for watching.
Oh, and check out Kristen's channel right there.
Bye.
Bye.
Hey, Vsauce, Michael here. Down here. But which way is down? And how much does down weigh? Well, down weighs about 1/100 of a gram per cubic centimeter. It is light and airy, which makes it a great source of insulation and buoyancy for water birds. But if you let go of down, it falls down. So that's which way down is. It's the direction gravity is pulling everything in. Now, for someone on the other side of the Earth, my down is their up. But where are falling things going? Why do things fall? Are they being pushed or pulled? Or is it because of time travel? First things first, let's turn the sun into a black hole. We can do that using Universe Sandbox 2. This simulator will blow your mind. I love it. In fact, I love it so much, I put a code to get the game for free in the current Curiosity box. If you're not subscribed to the box yet, you are missing out. Okay, look, for the purposes of this video, we want the solar system. And here it is. Notice that everything's moving pretty quickly around the sun. That's because we currently have the game set so that every second that passes for us is 14 days almost in the game. If I change this to 1 second, we're looking at the solar system in real time. You'll notice that it almost looks like it's frozen. Even though the Earth is traveling around the sun at about 30 kilometers per second, it barely appears to be moving. That is how vast space is. Anyway, let's go back to 14 days. I like that motion. Now look at the sun. It is not currently a black hole, but we can change that. What we need to do is compress the sun. So let's lock its mass so that it doesn't change while we make its radius smaller. Let's make its radius as small as we can. And, oh, where'd it go? Well, it's still there, it's just become a black hole. Pretty spooky, but now let's look at the rest of the solar system. All right, zooming out, and nothing's changed. I mean, something's changed, it's colder and darker, but nothing's flying off into space or getting sucked in. You see, by shrinking the sun, we didn't change the direction of down for the planets. They're always being pulled by gravity towards its middle, and making it smaller didn't move where the middle was. But also, the strength of that force pulling them to the middle of the sun stayed the same. That gives us a clue as to what down is. The clue is the other thing we didn't change: mass. Mass is a measure of how hard it is to accelerate something, to change its motion. Now right now, these two balls have zero motion relative to me. Slapping around this hollow plastic ball is pretty easy, but doing the same to this solid steel ball
is a lot harder. Now, gravity and weight have nothing to do with this. Gravity acts downward, not against my horizontal slapping. Of course, gravity does contribute to friction, but friction works against me when I start moving the ball, but works with me when I stop the ball. And the steel ball is harder to stop than the plastic ball. The difference is mass. The steel ball is more massive. It's more resistant to having its motion changed. Mass is an intrinsic property. It does not depend on what's around or change from place to place. It can sometimes be thought of as the amount of matter something has. Your mass is the same regardless of where you are, on the moon, on Earth, in the middle of intergalactic space floating around. But all of this said, mass does seem to care about what's around. Mass loves company. Things with mass and/or energy are attracted together by a force that we call gravity. The feeling of gravity is just you and the Earth being attracted to one another. Now, every portion of an object with mass attracts other portions towards it. The average of all this pulling is an attraction between centers of mass. Giant things like Earth exert an obvious pull, but everything does, even a baseball. These two baseballs are attracted together by their own gravities. Except their masses are so small the force is minuscule and it can't overcome friction or push air out of the way. They're never gonna come together. But if you put two baseballs 1 meter apart in the middle of empty space where no other forces could act on them, they would literally fall together and collide. It would take 3 days to happen, but it would. Isaac Newton found that the strength of the force bringing two things together is equal to the product of their masses divided by the distance between their centers of mass squared times big G, the gravitational constant. If you make one of two objects more massive or move them closer together, the force will be stronger. And this force of attraction is what we call weight. So mass is intrinsic, whereas weight depends on what's around. Now, a weird thing happens when you weigh yourself on most scales. Weight is a force, but scales display pounds or kilograms, which are units of mass. What's going on is that a scale is activated by a force, any force. It doesn't have to be caused by gravity. The scale then displays what amount of mass near the surface of the Earth would be attracted to the Earth with the force it's detecting. Now, since scales tend to be used on the surface of the Earth by people on which the only force acting is gravity, they tend to not be very far off, but they can be easily tricked. And they further lead to the confusion between mass and weight. Notice that weight is mutual. You are pulled down by Earth with the same force that you pull up on Earth. According to a scale, I weigh 180 pounds on Earth, and the Earth weighs 180 pounds on me. But because the Earth's mass is so much greater than my own, and because the more massive something is, the more it resists being moved, our equal and opposite weight forces accelerate me a lot more than the Earth. If you drop a pencil from a height of 6 feet, the pencil doesn't just fall to the Earth. More precisely, they both come together. They're attracted to each other by equal forces, but the same force moves the pencil a lot more than the Earth. When you let go of the pencil, the Earth is literally pulled up to the pencil by the pencil's own gravity, a distance equal to about 9 trillionths the width of a proton. That same force moves the pencil the remaining distance, which is still pretty much 6 feet. At the height of the International Space Station's orbit, you and Earth are attracted about 10% less than when you're on the surface, about 8.8 times your mass, but not zero. For this reason, weightless astronauts in zero gravity are neither weightless nor in zero gravity. Their weight force fails to bring them and Earth together because they move horizontally so quickly that they fall just as fast as Earth's surface curves away from them.
And even though they're experiencing 90% of the gravity you and I are feeling right now, that's why they don't just fly away, there are no forces, called G-forces, to resist their weight, since everything around them is falling too. It's resistance to your weight force, stress, deformation, that is needed for you to feel weight. What astronauts in orbit actually lack is apparent weight. Likewise, a helium balloon has weight. I mean, it's made out of matter. It clearly has mass, so it's attracted to the Earth. Let's try to measure its weight force. Oh, hey. Okay, it has negative apparent weight. That's because its attraction to the Earth is weaker than the buoyant forces from the air around it that push it up. Now, while it moves up, it pushes air molecules down, but they transfer that force widely, not just directly down onto the scale. Buoyant forces are caused by the fact that whenever you are immersed in a fluid, like water or air, molecules lower down are at greater pressure. They're being pressed by the weight of all the molecules above them and are closer to Earth, so they're pulled to it with a stronger force. Now, having greater pressure means they pack a bigger punch when they collide with things. So, horizontally, those collisions cancel out, but vertically, the stronger collisions from below win out, providing lift, a buoyant force. Now, this even happens on your own body. Across its surface area, air lifts you with a force of about 1 Newton, which is equal to the weight force of an apple. So if you weighed yourself in a vacuum, you would weigh about this much more. But that's not all. Earth's spin causes it to bulge at the equator. So the closer you are to it, the further you are from Earth's center of mass, and the less your actual gravitational weight will be. Down is always changing. I mean, where is Earth's center of mass? It would always be the same as Earth's geometric middle if Earth's composition was uniform, but Earth contains pockets of massive rock at different depths. Water, mountains, it's got moving, changing insides and air and seasonal ice. And though they're far away, gravity extends forever from everything. So the moon, the sun, the planets, all of them pull on you negligibly, but truly. You weigh about 1/1,000,000th of your weight less when the moon is directly above you. This chunky, shifting balance of material on Earth and everywhere else in the universe means that down is always changing. On top of that, Earth's spin skews what you consider the direction of down away from its center of mass, because the push you get from Earth's spin seems to slightly lift you, reducing your apparent weight and bending down towards the equator. The net result is an apparent weight reduction at the equator of about 0.5%. If a scale guesses your mass must be 200 pounds at the poles, it'll guess that you're 199 at the equator. The 9.8 multiplier used so often in physics is calculated based on how these factors affect someone at 45 degrees latitude. All of these influences on the direction of down result in a total vertical deflection that's only ever at most a few arc seconds anywhere on Earth. That's not enough to be felt, but changes in direction and strength can be used to study the shape of the seafloor, determine what's under you, or even help you discover ancient buried rooms. Point is, all of our downs aren't a bunch of radially symmetric lines. Down is an uncombed mess. Now, since solids don't flow, they can have shapes that don't pay much mind to this. But water can flow. So, ignoring influences like wind and tides, the surface of oceans and lakes and puddles is always perpendicular to down. If water could pass through land, or if Earth were submerged in water, gravity would be the same everywhere along its bumpy surface. Such a surface is called a geoid and can be drawn at any altitude. If you wanted to build a table that completely enclosed the Earth, it would have to have rolling undulations, nearly 100 meters at some points, in order to be level, so that a ball placed anywhere on it wouldn't roll. Here is Earth's geoid exaggerated 1,000 times. You'd weigh about 1/100% less, a few grams, here than you would say here, where gravity is a bit stronger. Point is, the strength and direction of down is variable by location and changes over time. So, down is a fluctuating vector. Easy enough, except why should matter attract matter in the first place? Isaac Newton was able to describe attraction, but not explain it. Humanity got closer, however, when Albert Einstein introduced his general theory of relativity. Einstein thought a lot about the fact that everything falls to the ground at the same rate. No matter how massive something is, when dropped, it will accelerate towards the Earth down, gaining about 9.8 meters per second for every second that it falls. That means that a hammer, that's quite massive, and a not so massive feather, when dropped from the same height, will hit the ground at the same time. Okay, what just happened was an error. In order to fall through air, a thing has to push air out of the way. But if it has a large surface area and a low weight force, it will have a lot of air to move, but won't be able to move that air very quickly. In a vacuum, things do fall at the same rate regardless of mass. This was famously demonstrated by Apollo 15 Commander David Scott on the moon.
And I'll drop the two of them here, and hopefully they'll hit the ground at the same time. How about that?
That's weird, right? I mean, if a more massive object is pulled with a greater force, shouldn't it fall faster? Well, Newton's explanation was simple. Larger masses are attracted with greater forces, but will also require more force to be accelerated the same as a less massive thing. Something 100 times more massive might require 100 times the force, but it will be pulled by gravity 100 times more. So everything falls to Earth at the same rate. What a fun coincidence, right? Maybe not. Einstein realized that there's another way for things to appear to fall together regardless of their masses. Imagine a feather and a hammer floating in space, in a room. If the room is suddenly accelerated up at 9.8 meters per second squared, the feather and the hammer will hit the floor at the same time. Furthermore, whether it's the room coming up to meet them or gravity being suddenly switched on, neither object will feel any force pushing them. There's no way to tell which of these happened. This is Einstein's famous equivalence principle. He once admitted that his greatest thought ever was that of a man falling off of a roof. While falling, the man would not feel any forces on him, even though he's speeding up. Free fall is indistinguishable from floating alone in space, from having no forces on you, from not being moved. What if gravity isn't a force at all? What if things fall not because they're being pushed or pulled, but because they're not being pushed or pulled? To see how this could be, we need to talk about straight lines. What I have here is a retractable ID badge holder. This is a great way to test for straight paths because the string is always kept taut. The card I have behind has two lines drawn on it, and if, while I pull the string out, it always stays between those two lines, I will know that I never turned while I pulled it, because any turn will translate into a different angle between the lines on the card and the string. Now, if I put two of these on a flat table and pull them out, always ensuring that they go straight ahead, they will never meet. They will be forever parallel. But now, let's put them on a sphere, a curved surface. Again, I pull both strings forward, making sure that they always are pulled out straight, no turning. Wait, they came together. Well, they didn't turn. Look, maybe there's some kind of weird force that pulled my hands together. And just like gravity, I didn't feel it, but it happened. No. What happened was not the result of a force. It was just a natural result of curvature. You might be thinking, wait a second, are those really straight lines? I mean, they don't look that straight to me. Also, what if they just moved along latitude lines? Then they'd never come together and those look pretty darn straight. But they're not. A straight line never turns. And although latitude lines look straight at first glance, following one requires turning. To find straight line paths on surfaces, whether they're flat like this or curved, I love the ribbon test.
Now you can use an actual ribbon, but I have found that a strip of paper works even better. Let's take a look at this path right here. It's straight at first, but then it curves. Now, if two people are traveling along this curve and they want to stay together, the person on the inside will have to cover a shorter distance than the person on the outside. Since both sides of this strip of paper cannot change their lengths, they'll help us find a straight path. If the strip of paper can lay flat, we'll know that we have found a straight line. And as you can see, the strip can lay flat and follow the straight part of this path. But when it comes to the curve, in order to follow the path now, the strip, well, it has too much material on the inside, and that material bunches up and leaves the plane. Therefore, we know that this part of the path is not straight. Let's use the ribbon test to find straight lines on the surface of a cone. Well, from the looks of it, a line directly from the base to the tip seems like it would be straight, and sure enough, yeah, the ribbon lays flat on that path. But what about a ring around the cone? Nope, doesn't work. Shorter distances around nearer the tip of the cone mean that there's too much ribbon up at the top, so it doesn't lay flat. Let's see, what else is there though besides this? Well, if I start here and just allow the ribbon to lay flat, I get a little curvy looking shape like this. I say curvy looking because while to someone, say at the base, this path might seem to go up, slow down, change direction, and then fall down faster and faster, since a ribbon on such a path is flat, it's actually, for inhabitants on the cone's surface, perfectly straight. If we trace the ribbon's path onto the cone, we can see this clearly because a cone can be flattened. A straight line on a curved surface is called a geodesic. Here is a geodesic on a sphere. The equator is one. Here's another. A line of latitude is not a geodesic, it's not a straight line. To see why, let's try to follow it with the ribbon. You know what? I have to keep kind of lifting it. Yeah, see, distances around the sphere become shorter as we go up, so there's too much material on the ribbon up here and it leaves the surface. This path contains turns, and in order to turn, a force has to act on you. If no forces did, this is the path you would take. Notice that the ribbon begins moving due east, but then falls south. Falls. Einstein realized that curvature could cause things to be seemingly attracted to one another without needing to invent the existence of forces like gravity. But attraction only happens if things move along the surface. If they stay still, they don't come together. So for something at rest, how does falling begin? I mean, the thing has to move in this direction, but it's at rest, right? Well, yes, but it's only at rest in space, and that's not the whole story. Up, down, forward, backward, and left, right are all you need to describe where an event occurred. But a complete description will also need to describe when. Together, these four dimensions form the setting in which everything in our universe happens. Space-time. Since we can talk about a falling pencil using just one spatial dimension, up and down, we can use a piece of paper to model space-time for it. Okay, so we've got up and down, but we have to add another direction the pencil moves in. Time. Now, if no forces act on the pencil, it won't move through space. It will only get older. And as you can see, if all it does is get older, it won't fall. If space-time was flat, when I let go of the pencil, it wouldn't go anywhere. But now let's allow the Earth, which is massive, to manipulate space-time into, say, a cone. Now, with no forces acting on it, every part of the pencil follows a straight line. But on a cone, as we saw earlier, such a path will look like this. It will fall. This is because distances around the cone are shorter higher up. Time runs faster further from a massive object. But to go straight, not turn, every part of the pencil must cover an equal distance in space-time, like this. Only when the pencil hits the Earth does the repulsion of their mutual electrons provide a force pushing the pencil off a geodesic. For the Earth, time is a series of slices from this evolution. The pencil's force-free geodesic is why it falls. Not a push or pull, just the pencil's natural tendency to follow a straight line until something acts on it. Now, we only used one dimension of space and one of time because visualizing our universe's three of space and one of time would take us beyond the limits of what could be shown on paper or screens. But math can take us there. General relativity allows us to calculate how much mass and energy curve space-time, and has been used to explain things that Newton's older theory of falling as the result of forces couldn't, like anomalies in the orbit of Mercury, which orbits nearest the sun and is therefore most affected by the sun's grip on space-time. Many other experiments have confirmed general relativity's picture of the universe, fitting the conclusion that there is no gravity. There's just space-time, its curvature, and us in it. As John Wheeler famously put it, space-time grips mass, telling it how to move. Mass grips space-time, telling it how to curve. Relative to the Earth, we don't move very fast. Even jet airplanes move negligibly close to the speed of light. So relative to Earth, we move almost exclusively through time. As such, we are more affected by the way time is curved by mass than how space is curved. This has led many to claim that for the most part, you feel as though you're being pushed into the ground, not because of a force called gravity, but because time is moving faster for your head than for your feet. Down is relative and always changing, but it exists because of and is always in the direction of slower time. Bertrand Russell called this the law of cosmic laziness. Everything is naturally steered towards where time is slowest. We call this falling, going down. So you don't have to keep anything on the down low. Time will take care of that for you. And as always, thanks for watching. Remember that you can support Vsauce and Alzheimer's research by subscribing to the Vsauce Curiosity Box. The current one comes with a code to get a free copy of Universe Sandbox 2, which is amazing, and a whole host of other science toys and tools picked by myself, Jake, and Kevin. I love it. Also, I hope to see you at Brain Candy Live. We are coming to many, many cities very soon, hopefully one near you. By going to the show, you can see Adam and I doing things that, well, you may not have seen us do before. We also explore the science and common misconceptions behind all things air? Maybe I've said too much, maybe not. I hope to see you there. And, as always, thanks for watching.
Hey, Vsauce, Michael here. About 6% of everything you say and read and write is the is the most used word in the English language. About 1 out of every 16 words we encounter on a daily basis is the. The top 20 most common English words in order are the of and to. A in is I, that it for you was with on, as have, but be they. That's a fun fact, a piece of trivia, but it's also more. You see, whether the most commonly used words are ranked across an entire language, or in just one book or article, almost every time a bizarre pattern emerges. The second most used word will appear about half as often as the most used. The third, 1/3 as often. The fourth, 1/4 as often. The fifth, 1/5 as often. The sixth, 1/6 as often, and so on, all the way down. Seriously. For some reason, the amount of times a word is used is just proportional to 1 over its rank. Word frequency and ranking on a log-log graph follow a nice straight line, a power law. This phenomenon is called Zipf's law. And it doesn't only apply to English. It also applies to other languages like, well, all of them. even ancient languages we haven't been able to translate yet. And here's the thing, we have no idea why. It's surprising that something as complex as reality should be conveyed by something as creative as language in such a predictable way. How predictable? Well, watch this. According to wordcount.org, which ranks words as found in the British National Corpus, sauce is the 5,555th most common English word. Now, here is a list of how many times every word on Wikipedia and in the entire Gutenberg corpus of tens of thousands of public domain books shows up. The most used word, the, shows up about 181 million times. Knowing these two things, we can estimate that the word sauce should appear about 30,000 times on Wikipedia and Gutenberg combined. And it pretty much does. What gives? The world is chaotic. Things are distributed in myriads of ways, not just power laws, and language is personal, intentional, idiosyncratic. What about the world and ourselves could cause such complex activities and behaviors to follow such a basic rule? We literally don't know. More than a century of research has yet to close the case. Moreover, Zipf's law doesn't just mysteriously describe word use. It's also found in city populations, solar flare intensities, protein sequences and immune receptors, the amount of traffic websites get, earthquake magnitudes, the number of times academic papers are cited, last names, the firing patterns of neural networks, ingredients used in cookbooks, the number of phone calls people receive, the diameter of moon craters, the number of people that die in wars, the popularity of opening chess moves, even the rate at which we forget. There are plenty of theories about why language is ziffy, but no firm conclusions. And this video doesn't contain a definite explanation either. Sorry, I know that's a bummer since we appear to like knowing more than mystery. But that said, we also ask more than we answer. So let's dive into Zipf's ramifications, some related patterns, some possible explanations, and the depth of the mystery itself. Zipf's law was popularized by George Zipf, a linguist at Harvard University. It is a discrete form of the continuous Pareto distribution, from which we get the Pareto principle. Because so many real-world processes behave this way, the Pareto principle tells us that, as a rule of thumb, it's worth assuming that 20% of the causes are responsible for 80% of the outcome. Like in language, where the most frequently used 18% of words account for over 80% of word occurrences. In 1896, Vilfredo Pareto showed that approximately 80% of the land in Italy was owned by just 20% of the population. It is said that he later noticed in his garden 20% of his pea pods contained 80% of the peas. He and other researchers looked at other data sets and found that this 80-20 imbalance comes up a lot in the world. The richest 20% of humans have 82.7% of the world's income. In the US, 20% of patients use 80% of healthcare resources. In 2002, Microsoft reported that 80% of the errors and crashes in Windows and Office are caused by 20% of the bugs detected. A common rule of thumb in the business world states that 20% of your customers are responsible for 80% of your profits, and 80% of the complaints you receive will come from 20% of your customers. A book titled The 80-20 Principle even says that in a home or office, 20% of the carpet receives 80% of the wear. Oh, and as Woody Allen famously said, 80% of success is just showing up. The Pareto principle is everywhere, which is good. By focusing on just 20% of what's wrong, you can often expect to solve 80% of the problems. A variety of different, unrelated factors cause this to be true from case to case. But if we can get to the bottom of what causes some of them, maybe we'll find that one or more of those mechanisms is responsible for Zipf's law in language. George Zipf himself thought language's interesting rank frequency distribution was a consequence of the principle of least effort, the tendency for life and things to follow the path of least resistance. Zipf believed it drove much of human behavior and hypothesized that as language developed in our species, speakers naturally preferred drawing from as few words as possible to get their thoughts out there. It was easier. But in order to understand what was being said, listeners preferred larger vocabularies that gave more specificity so that they had to do less work. The compromise between listening and speaking, Zipf felt, led to the current state of language. A few words are used often, and many, many, many words are used rarely. Recent papers have suggested that having a few short, often used, predictable words helps dissipate information load density on listeners, spacing out important vocab so that the information rate is more constant. This makes sense, and much has been learned by applying the least effort principle to other behaviors, but later researchers argued that for language, the explanation was even more simple. Just a few years after Zipf's seminal paper, Benoit Mandelbrot showed that there may be nothing mysterious about Zipf's law at all, because even if you just randomly type on a keyboard, you will produce words distributed according to Zipf's law. It's a pretty cool point, and this is why it happens. There are exponentially more different long words than short words. For instance, the English alphabet can be used to make 26 one-letter words, but 26 squared two-letter words. Also, in random typing, whenever the space bar is pressed, a word terminates. Since there's always a certain chance that the spacebar will be pressed, longer stretches of time before it happens are exponentially less likely than shorter ones. The combination of these exponentials is pretty ziffy. For example, if all 26 letters and the spacebar are equally likely to be typed, after a letter is typed and a word has begun, the probability that the next input will be a space, thus creating a one-letter word, is just 1 in 27. And sure enough, if you randomly generate characters or hire a proverbial typing monkey, about 1 out of every 27, or 3.7% of the stuff between spaces, will be single letters. Two-letter words appear when, after beginning a word, any character but the space bar is hit, a 26 in 27 chance, and then the space bar. A three-letter word is the probability of a letter, another letter, and then a space. If we divide by the number of unique words of each length there can be, we get the frequency of occurrence expected for any particular word given its length. For example, the letter V will make up about 0.142% of random typing. The word Vsauce, 0.00000000993%. Longer words are less likely, but watch this. Let's spread these frequencies out according to the ranks they'd take up on a most often used list. There are 26 possible one-letter words, so each of the top 26 ranked words are expected to occur about this often. The next 676 ranks will be taken up by two-letter words that show up about this often. If we extend each frequency according to how many members it has, we get Zipf. Subsequent researchers have detailed how changing up the initial conditions can smooth the steps out. Our mysterious distribution has been created out of nothing but the inevitabilities of math. So maybe there is no mystery. Maybe words are just the result of humans randomly segmenting the observable world and the mental world into labels. And Zipf's law describes what naturally happens when you do that. Case closed. And as always, thanks for wait a minute. Actual language is very different from random typing. Communication is deterministic to a certain extent. Utterances and topics arrive based on what was said before. And the vocabulary we have to work with certainly isn't the result of purely random naming. For example, the monkey typing model can't explain why even the names of the elements, the planets, and the days of the week are used in language according to Zipf's law. Sets like these are constrained by the natural world, and they're not the result of us randomly segmenting the world into labels. Furthermore, when given a list of novel words they've never heard or used before, like when prompted to write a story about alien creatures with strange names, people will naturally tend to use the name of one alien twice as often as another, 3 times as often as another. Zipf's law appears to be built into our brains. Perhaps there is something about the way thoughts and topics of discussion ebb and flow that contributes to Zipf's law. Another way Zipfian distributions occur is via processes that change according to how they've previously operated. These are called preferential attachment processes. They occur when something, money, views, attention, variation, friends, jobs, anything really, is given out according to how much is already possessed. To go back to the carpet example, if most people walk from the living room to the kitchen across a certain path, furniture will be placed elsewhere, making that path even more popular. The more views a video or image or post has, the more likely it is to get recommended automatically, or make the news for having so many views, both of which give it more views. It's like a snowball rolling down a snowy hill. The more snow it accumulates, the bigger its surface area becomes for collecting more, and the faster it grows. There doesn't have to be a deliberate choice driving a preferential attachment process. It can happen naturally. Try this. Take a bunch of paper clips and grab any 2 at random, link them together, and then throw them back in the pile. Now, repeat over and over again. If you grab paper clips that are already part of a chain, link them anyway. More often than not, after a while, you will have a distribution that looks Zipfian. A small number of chains contain a disproportionate amount of the total paperclip count. This is simply because the longer a chain gets, the greater proportion of the whole it contains, which gives it a better chance of being picked up in the future and consequently made even longer. The rich get richer, the big get bigger, the popular get popularer. It's just math. Perhaps language's Zipf mystery is, if not caused by, at least strengthened by, preferential attachment. Once a word is used, it's more likely to be used again soon. Critical points may play a role as well. Writing and conversation often stick to a topic until a critical point is reached and the subject is changed, and the vocabulary shifts. Processes like these are known to result in power laws. So, in the end, it seems tenable that all these mechanisms might collude to make Zipf's law the most natural way for language to be. Perhaps some of our vocabulary and grammar was developed randomly, according to Mandelbrot's theory, and the natural way conversation and discussion follow preferential attachment and criticality, coupled with the principle of least effort when speaking and listening, are all responsible for the relationship between word rank and frequency. It's a shame that the answer isn't simpler, but it's fascinating because of the consequences it has on what communication is made of. Roughly speaking, and this is mind-blowing, nearly half of any book, conversation, or article will be nothing but the same 50 to 100 words, and nearly the other half will be words that appear in that selection only once. That's not so surprising when you consider the fact that one word accounts for 6% of what we say. The top 25 most used words make up about a third of everything we say, and the top 100? About half. Seriously, I mean, whether it's all the words in Wet Hot American Summer, or all the words in Plato's complete works, or in the complete works of Edgar Allan Poe, or the Bible itself, only about 100 words are used for nearly half of everything written or said. In Alice's Adventures in Wonderland, 44%, and in Tom Sawyer, 49.8% of the unique words used appear only once in the book. A word that is used only once in a given selection of words is called a hapax legomenon. Hapax legomena are vitally important to understanding languages. If a word has only been found once in the entire known collection of an ancient language, it can be very difficult to figure out what it means. Now, there is no corpus of everything ever said or written in English, but there are very, very large collections, and it's fun to find hapax legomena in them. For instance, and this probably won't be the case after I mention it, but the word quizzaciously is in the Oxford English Dictionary, but appears nowhere on Wikipedia, or in the Gutenberg corpus, or in the British National Corpus, or the American National Corpus, but it does appear when searched in just one result on Google. Fittingly, in a book titled Elder Speak that lists it as a rare word. Quizzaciously, by the way, means in a mocking manner, as in, the parodist rattled off quizzaciously, "Hey, Vsauce, Michael here, but who is Michael and how much does here weigh?" It's a little sad that quizzaciously has been used so infrequently. It's a fun word, but that's the way things go in a Zipfian system. Some things get all the love, some get little. Most of what you experience on a day-to-day basis is forgotten, forgettable. The Dictionary of Obscure Sorrows, as it often does, has a word for this: oleka, the awareness of how few days are memorable. I've been alive for almost 11,000 days, but I couldn't tell you something about each one of them. I mean, not even close. Most of what we do and see and think and say and hear and feel is forgotten at a rate quite similar to Zipf's law. Which makes sense. If a number of factors naturally selected for thinking and talking about the world with tools in a Zipfian way, it makes sense we'd remember it that way too. Some things really well. Most things hardly at all. But it bums me out sometimes because it means that so much is forgotten, even things that at the time you thought you could never forget. My locker number, senior year, its combination, the jokes I liked when I saw a comedian on stage, the names of people I saw every day 10 years ago. So many memories are gone. When I look at all the books I've read and realize that I can't remember every detail from them, it's a little disappointing. I mean, why even bother if the Pareto principle dictates that my Zipfian mind will consciously remember pretty much only the titles and a few basic reactions years later? Ralph Waldo Emerson makes me feel better. He once said, "I cannot remember the books I've read any more than the meals I have eaten. Even so, they have made me." And as always, thanks for watching. Hey, Vsauce. Michael here. This is Earth as seen from Saturn. That is us right there. And if you look closely, okay, see this little protuberance? That's the moon. This image was taken by the Cassini spacecraft on July 19th,
2013 at 21:27 Coordinated Universal Time. The thing is, NASA gave the public advanced warning of when it would be taken, which means that this image of Earth was the first ever taken from space that some people on Earth were actually posing for. Our planet looks so small, insignificant, fragile. I recently attended the premiere of Sky One's upcoming You, Me, and the Apocalypse with some cool YouTubers, and it got me thinking. In the show, the characters find out that there are only 34 days left before a comet smashes into Earth that's likely to end humanity. They all react in different interesting ways, but what would I do if I found out that there were only 34 days of human history left? Okay, my first priority would be to get back to America to be with my family. But after that, I don't really have a bucket list, except that is exactly what I would want to spend my last few weeks doing, making a list to put in a bucket that I would then send far out into space away from Earth's impending vaporization. The list would contain information about us, all Earthlings, so that if libraries and monuments and YouTube videos were all destroyed, a record would still exist somewhere of what and who we were. Like a stone thrown into a lake, the ripples your life causes last long after you vanish. The tree you planted is climbed by future generations. The books you donated inform future readers. But what if it's not just your stone that vanishes, but the entire pond? Perhaps it's arrogance or vanity, but getting cosmic messages in a bottle out there before the end diversifies our archive and gives a better chance for future alien visitors, or whatever is left of humanity, to find out that we were once here, to show what we learned, maybe even to warn future life forms of what we did or what we didn't prepare for. We have already sent some messages about humanity out there beyond Earth, and if Earth is completely destroyed, those messages will be all that's left of us. What are they? Okay, first things first. How do you write something for the future? I mean, the distant future. The message might not be found for millions of years or billions. It might be discovered by an audience that's completely different, not only in language, but in senses. What if they can't see or hear or feel or taste or smell like we do? Or at all? What if their bodies destroy the very material we write the message on? What language do you even write it in? Well, in general, math and physics, which are believed to be the same everywhere in the universe, have been what we write outer space-bound messages in. Like the Arecibo message, written by Frank Drake, Carl Sagan, and others, which was blasted towards the M13 star cluster in 1974. It's composed of a semi-prime number of binary digits conveying some info about us, and it should reach the center-ish of the M13 cluster in about 25,000 years. At which point, if something intelligent lives there and detects it, they can respond, and their response will return to us another 25,000 years later. We won't be around for that, but Earth has also been broadcasting its radio and TV signals into space. Currently, it's about 200 light years in diameter. Compared to the Milky Way, it's about this big. Aliens within that bubble could tune in and listen to programs we sent out through our airwaves, but these signals thin out as the bubble expands. Across very large distances, they may be essentially impossible to tune into. Maybe a physical time capsule would be more permanent, but it can't be buried on Earth if Earth is about to be ravaged. A time capsule in orbit might be smart, like Lagios 1, a satellite put into orbit in 1976 that allows for very precise laser measurements of positions on Earth, but also contains a plaque designed by Carl Sagan upon which is written the numbers 1 to 10 in binary and the arrangement of the Earth's continents 250 million years ago, today, and their estimated arrangement in 8.4 million years, which is how long we believe the satellite's orbit will be stable. Drag caused by the thin atmosphere up where it orbits and influences like solar activity will eventually cause it to fall back down to Earth, but its plaque will serve as a time capsule, a message from us today to whatever happens to be alive or intelligent here on Earth 8 million years in the future. To put that in perspective, the pyramids were only built about 5,000 years ago. 8 million years ago, there weren't even humans on Earth. The latest common ancestor of humans and chimpanzees was around, though. 8 million years from today, when Lagios returns, what will intelligent life on Earth look like? If Earth's surface is barren of life at that point, Lagios 1 will be alone. But what about satellites in geostationary orbits? These orbits are far enough out that they're much safer from atmospheric drag and could remain above Earth much, much longer than satellites like Lagios. These satellites are our pyramids. They're smaller than monuments built by past civilizations, but impervious to anything that might go wrong on the less stable surface of our planet. If alien archaeologists come by in 1 billion years or so, these satellites may be what their alien encyclopedias use as the picture for the humans article. So far, we have erected about 450 of these geostationary monuments. When such a satellite wears down and ceases to be operational, it takes a lot of energy to slow it down so it can move out of the way and fall to Earth to burn up in the atmosphere. So instead, they're usually pushed into what's known as a graveyard orbit, a shell around the planet where they can be parked without interfering with important operational satellites. It's fitting that we call these graveyard orbits because tombs are often the most stunning things we have from previous civilizations. These graveyard orbits are tombs, in a way, not for kings, but for machines. Junkyards that will outexist the very societies and people they so largely define. Luckily, a few contain more than just our craftsmanship, they also contain a record. Like EchoStar 16, a communications satellite launched into geostationary orbit in 2012. Aboard it is a silicon disk created by artist Trevor Paglen containing 100 images of Earth and Earthlings. Now, unlike Lagios, EchoStar 16 will likely remain in orbit for billions of years, safe from discord and change down here. But here's the thing. What if our entire solar system is lost? Or what if life out there doesn't decide to ever visit our system? Well, in that case, we have sent interstellar messages. At this moment, so far, there are 11 distinct human-made things on trajectories out of the solar system into interstellar space. They're all related to 5 probes: Pioneer 10, Pioneer 11, Voyager 1, Voyager 2, and New Horizons, the thing that recently made a Pluto flyby. These objects are our most distant hellos. Over the next 10,000 million billion years, they'll pass close enough to other star systems, maybe even planets, to possibly be discovered by other intelligent life forms. We had the foresight to include special messages on these probes. The Pioneer plaques are attached to Pioneer 10 and 11, which, launched in the early 1970s, were the first human-made objects to ever be sent on a trajectory to not just leave Earth, but to leave the solar system entirely. If discovered by other life out there, these plaques, designed by Frank Drake and Carl Sagan, could be our first chance to say, "Hello, we exist," or
depending on how long humanity lasts, our only chance to say, hello, we existed. This is what we were. But will the plaques make sense to aliens? Many human scientists have had trouble deciphering their meaning, but here's what they say. At the bottom is a map of our solar system with a path showing the Pioneer probe itself and where it came from. This element has been particularly criticized for being human-centric. I mean, an arrow? Who's to say aliens will know that this depicts a path and not some structure in our solar system? Also, it's an arrow. Arrows might convey this way only to civilizations that hunted or developed pointy projectiles. Anyway, up here we define units. You can't tell aliens about humans or Earth by using seconds, kilometers, or light years because we made those measurements up.
Instead, the plaque uses hyperfine transitions to communicate distances and time. The hope is that curious, intelligent life forms who find this will understand that this is a hydrogen atom. One proton, one electron. Hydrogen is the most abundant element in the universe, so hopefully its properties will be a common point of understanding. Now, sometimes, if you've got enough hydrogen around, you can catch atoms in the heap transitioning between particles with parallel spins and anti-parallel spins. Now, whenever this transition happens, electromagnetic radiation is released with a period of about 0.7 nanoseconds and a wavelength of about 21 centimeters. It's hoped that aliens equate this tick mark with these two units of measurement.
For example, the woman is said to be, in binary, 8 of these units tall. 21 centimeters times 8 is 168 centimeters. You would think that putting the probe itself behind them for scale would be enough to show our size, but having both might help solidify the connection. This diagram is meant to show where we live. We are in the middle. The direction and proportional length of the lines show where distant pulsars are. A tick mark near the ends of each line shows the third direction, behind or in front of the plaque, that the line should go in. In binary, next to each line is the period of each pulsar, again in the time units described above. If aliens make this connection, they could possibly match the periods with the correct pulsars in real life, triangulate our position, and come say hello. Also, since the period of a pulsar changes over time, they could use our observed periods to date back how long ago this plaque was made. So that's how the plaque works. It kind of feels like we're just sending out a bunch of science homework to space, but how else can you find common ground with something that might not resemble you in any way you could even imagine? Despite heading out first, the Pioneer plaques are not the first physical messages made by us to go interstellar. That title belongs to Voyager 1. Currently moving at 17 kilometers per second, it is the most far-out thing humans have ever made. Literally. In about 40,000 years, both Voyagers will pass within less than 2 light years of other stars. If aliens find them, or if future humans find them, a golden record is attached to both that contains information about humanity. The record is made of gold-plated copper with an aluminum cover containing some uranium-238. Given its half-life, smart aliens could analyze it to determine how long ago the record was made. On the record is the inscription, "To the makers of music, all worlds, all times." The record contains 116 images, as well as audio and video recordings of humans, animals, songs, and greetings in 55 languages. Printed on the record are instructions for playback and info about us. The hydrogen hyperfine transition unit definition and the pulsar map included on the Pioneer plaques, but the record also comes with a stylus and platter to play it. Instructions for using the stylus are on the record. This is a picture of the stylus being used correctly, and then in binary, using the transition units, the record tells the aliens that the stylus should go around the record once every 3.6 seconds to play back correctly, and in total should take about 1 hour to do so. For the video portion, instructions are given in a circle. The first video image is displayed so they know they did it right. Also included on the record is a message from then President of the United States, Jimmy Carter. There's something vulnerable about the message. It's delivered to an unknown recipient, like when someone in a horror movie asks into the darkness, "Is anyone there? Hello?" This is what it says. "We cast this message into the cosmos. It is likely to survive 1 billion years into the future, when our civilization is profoundly altered and the surface of the Earth may be vastly changed. Of the 200 billion stars in the Milky Way galaxy, some, perhaps many, may have inhabited planets and spacefaring civilizations. If one such civilization intercepts Voyager and can understand these recorded contents, here is our message. This is a present from a small, distant world, a token of our sounds, our science, our images, our music, our thoughts, and our feelings. We are attempting to survive our time so we may live into yours. We hope someday, having solved the problems we face, to join a community of galactic civilizations. This record represents our hope and our determination, and our goodwill in a vast and awesome universe." Are these messages enough? Should we send more? Well, why not send everything? We could if we sent the Library of Babel. It's a website built by Jonathan Basile that currently offers everything that has been or could be written. Seriously. Divided into pages, it is built to produce and locate on demand any 3,200 character combination of English letters and the comma, space, and period. Basile has organized it all into hexagon-shaped rooms, each with 4 walls of books containing 5 shelves with 32 volumes of 410 pages each. Everything's arranged in a pseudo-random fashion, so browsing the online library feels like a treasure hunt. Here's how it works. Each page is given a unique sequential page number in base 10. The text on each page is encased inside this number. An algorithm Basile created uses the page number as a seed to generate a unique big number. That output is then converted into base 29 so that it can be represented using every letter in the English alphabet, as well as the comma, the space, and the period. This is what you see on the page. Basile has made sure that the algorithm will produce every possible combination, and the same page number will create the same output every time. Which means that what is on each page is already predetermined. So, in a way, every page already exists. It only needs to be looked up. And here is the really mind-blowing thing. The contents of a page can be converted to base 10, sent through the inverted algorithm, and turned into the exact page number they're found on. It's a truly eerie experience, because you can find the permanent location for any 3,200 character text. You can find in this library the description of your birth, every possible description of your death, every poem, every joke, every lie, anything that could be said can be found on this site. This thing blurs the line between invention and discovery. Did you really discover or invent that thing if its description already existed? 10 to the 5,000 different pages are offered by the Library of Babel. In comparison, there are only 10 to the 80 atoms in the observable universe. I searched for what I've just said, And sure enough, in this hexagon, on this wall, this shelf, in this volume, on this page, it's there. Hello. But deep down, we feel like there's a difference between this program permuting something unknowingly and a person actually meaning it, intending it, saying it because they wanted to with agency. We use a finite number of symbols to say things. For that reason, a library of every finite combination of those symbols can be made. But just because it can be made doesn't mean it has been said. That is the power we have. Perhaps you and I were born too late to explore the world and too early in history to explore the stars, but we were born at just the right time, which is pretty much all times ever, to explore language, to explore what can be said. What should be said? What should we send out to space? What that can be said will you be the first to say? And as always, thanks for watching. To watch the trailer for You, Me, and the Apocalypse, click right up there. And to see some other cool things YouTubers have done inspired by the series, well, you can also click right over there. Colin Furs is building a giant apocalyptic bunker in his backyard, like for real, it's huge. Also, the Dictionary of Obscure Sorrows has weighed in. Check those out, and thanks for watching. Hey Vsauce, Michael here. What is the biggest number you can think of? A Google? A Googleplex? A milli-nillion Olplex? Well, in reality, the biggest number is 40. Covering more than 12,000 square meters of Earth, this 40, made out of strategically planted trees in Russia, is larger than the battalion markers on Signal Hill in Calgary, the 6 found on the Favin badges in England, even the mile of pi Brady unrolled on Numberphile. 40 is the biggest number on Earth in terms of surface area. But in terms of amount of things, which is normally what we mean by a number being big, 40 probably isn't the biggest. For example, there's 41. And then there's 42, and 43, a billion, a trillion. You know, no matter how big of a number you can think of, you can always go higher. So there is no biggest last number. Except infinity? No. Infinity is not a number. Instead, it's a kind of number. You need infinite numbers to talk about and compare amounts that are unending. But some unending amounts, some infinities, are literally bigger than others. Let's visit some of them and count past them. First things first, when a number refers to how many things there are, it is called a cardinal number. For example, 4 bananas, 12 flags, 20 dots. 20 is the cardinality of this set of dots. Now, 2 sets have the same cardinality when they contain the same number of things. We can demonstrate this equality by pairing each member of one set 1-to-1 with each member of the other. Same cardinality, pretty simple. We use the natural numbers, that is 0, 1, 2, 3, 4, 5, and so on, as cardinals whenever we talk about how many things there are. But how many natural numbers are there? It can't be some number in the naturals because there'd always be 1 plus that number after it. Instead, there's a unique name for this amount: Aleph Null. Aleph is the first letter of the Hebrew alphabet, and Aleph Null is the first smallest infinity. It's how many natural numbers there are.
It's also how many even numbers there are, how many odd numbers there are. It's also how many rational numbers, that is, fractions, there are. That may sound surprising, since fractions appear more numerous on the number line, but as Cantor showed, there's a way to arrange every single possible rational such that the naturals can be put into a one-to-one correspondence with them. They have the same cardinality. Point is, Aleph Null is a big amount, bigger than any finite amount. A Googleplex, a Googleplex factorial to the power of a Googleplex to a Googleplex squared times Graham's number? Aleph Null is bigger. But we can count past it. How? Well, let's use our old friend, the supertask. If we draw a bunch of lines and make each next line a fraction of the size and a fraction of the distance from each last line, well, we can fit an unending number of lines into a finite space. The number of lines here is equal to the number of natural numbers that there are. The two can be matched one-to-one. There's always a next natural, but there's also always a next line. Both sets have the cardinality Aleph Null. But what happens when I do this? Now, how many lines are there? Aleph Null plus 1? No. Unending amounts aren't like finite amounts. There are still only Aleph Null lines here because I can match the naturals one-to-one just like before. I just start here and then continue from the beginning. Clearly, the amount of lines hasn't changed. I can even add 2 more lines, 3 more, 4 more. I always end up with only Aleph Null things. I can even add another infinite Aleph Null of lines and still not change the quantity. Every even number can pair with these and every odd number with these. There is still a line for every natural. Another cool way to see that these lines don't add to the total is to show that you can make this same sequence without drawing new lines at all. Just take every other line and move them all together to the end. It's the same thing. But hold on a second. This and this may have the same number of things in them, but clearly there's something different about them, right? I mean, if it's not how many things they're made of, what is it? Well, let's go back to having just one line after an Aleph Null sized collection. What if, instead of matching the naturals one-to-one, we insist on numbering each line according to the order it was drawn in? So we have to start here and number left to right. Now, what number does this line get? In the realm of the infinite, labeling things in order is pretty different than counting them. You see, this line doesn't contribute to the total, but in order to label it according to the order it appeared in, well, we need a set of labels, of numbers, that extends past the naturals. We need ordinal numbers. The first trans-finite ordinal is omega, the lowercase Greek letter omega. This isn't a joke or a trick. It's literally just the next label you'll need after using up the infinite collection of every single counting number first. If you got omegath place in a race, that would mean that an infinite number of people finished the race, and then you did. After omega comes omega plus 1, which doesn't really look like a number, but it is, just like 2 or 12 or 800. Then comes omega plus 2, omega plus 3. Ordinal numbers label things in order. Ordinals aren't about how many things there are. Instead, they tell us how those things are arranged. Their order type. The order type of a set is just the first ordinal number not needed to label everything in the set in order. So, for finite numbers, cardinality and order type are the same. The order type of all the naturals is omega. The order type of this sequence is omega plus 1, and now it's omega plus 2. No matter how long an arrangement becomes, as long as it's well ordered, as long as every part of it contains a beginning element, the whole thing describes a new ordinal number. Always. This will be very important later on. It should be noted at this point that if you are ever playing a game of who can name the biggest number, and you're considering saying omega plus 1, you should be careful. Your opponents might require the number you name to be a cardinal that refers to an amount. These numbers refer to the same amount of stuff, just arranged differently. Omega plus 1 isn't bigger than omega, it just comes after omega. But Aleph Null isn't the end. Why? Well, because it can be shown that there are infinities bigger than Aleph Null, that literally contain more things. One of the best ways to do this is with Cantor's diagonal argument. In my episode on the Banach-Tarski paradox, I used it to show that the number of real numbers is larger than the number of natural numbers. But for the purposes of this video, let's focus on another thing bigger than Aleph Null, the power set of Aleph Null. The power set of a set is the set of all the different subsets you can make from it. For example, from the set of 1 and 2, I can make a set of nothing, or 1, or 2, or 1 and 2. The power set of 1, 2, 3 is the empty set, 1, and 2, and 3, and 1 and 2, and 1 and 3, and 2 and 3, and 1, 2, 3. As you can see, a power set contains many more members than the original set. 2 to the power of however many members the original set had, to be exact. So, what's the power set of all the naturals? Well, let's see. Imagine a list of every natural number. Cool. Now, the subset of all, say, even numbers would look like this. Yes, no, yes, no, yes, no, and so on. The subset of all odd numbers would look like this. Here's the subset of just 3, 7, and 12. And how about every number except 5? Or no number except 5? Obviously, this list of subsets is going to be, well, infinite. But imagine matching them all 1 to 1 with a natural. If, even then, there's a way to keep producing new subsets that are clearly not listed anywhere here, we will know that we've got a set with more members than there are natural numbers. A bigger infinity than Aleph Null. The way to do this is to start up here in the first subset and just do the opposite of what we see. 0 is a member of this one, so our new set will not contain 0. Next, move diagonally down to 1's membership in the second subset. 1 is a member of it, so it will not be in our new one. 2 is not in the third subset, so it will be in ours, and so on. As you can see, we are describing a subset that will be, by definition, different in at least one way from every single other subset on this Aleph Null-sized list. Even if we put this new subset back in, diagonalization can still be done. The power set of the naturals will always resist a 1-to-1 correspondence with the naturals. It's an infinity bigger than Aleph Null. Repeated applications of power set will produce sets that can't be put into 1-to-1 correspondence with the last. So it's a great way to quickly produce bigger and bigger infinities. The point is, there are more cardinals after Aleph Null. Let's try to reach them. Now remember that after omega, ordinals split, and these numbers are no longer cardinals. They don't refer to a greater amount than the last cardinal we reached, but maybe they can take us to one. Wait. What are we doing? Aleph Null? Omega? Come on, we've been using these numbers like there's no problem. But if at any point down here, you can always add 1. Always. Can we really talk about it, this endless process, as a totality and then follow it with something? Of course we can. This is math. not science. The things we assume to be true in math are called axioms, and an axiom we come up with isn't more likely to be true if it better explains or predicts what we observe. Instead, it's true because we say it is. Its consequences just become what we observe. We are not fitting our theories to some physical universe whose behavior and underlying laws would be the same whether we were here or not. We are creating this universe ourselves. If the axioms we declare to be true lead us to contradictions or paradoxes, we can go back and tweak them or just abandon them altogether, or we can just refuse to allow ourselves to do the things that cause the paradoxes. That's it. What's fascinating, though, is that in making sure the axioms we accept don't lead to problems, we've made math into something that is, as the saying goes, unreasonably effective in the natural sciences. So to what extent we're inventing all of this, or discovering it, it's hard to say. All we have to do to get omega is say, "Let there be omega," and it will be good. That's what Ernest Zermelo did in 1908 when he included the axiom of infinity in his list of axioms for doing stuff in math. The axiom of infinity is simply the declaration that one infinite set exists, the set of all natural numbers. If you refuse to accept it, that's fine. That makes you a finitist, one who believes only finite things exist. But if you accept it, as most mathematicians do, you can go pretty far, past these and through these. Eventually we get to omega plus omega, except we've reached another ceiling. Going all the way out to omega plus omega would be to create another infinite set. And the axiom of infinity only guarantees that this one exists. Are we going to have to add a new axiom every time we describe Aleph Null more numbers? No. The axiom of replacement can help us here. This assumption states that if you take a set, like say the set of all natural numbers, and replace each element with something else, like say bananas, what you're left with is also a set. That sounds simple, but it's incredibly useful. Try this. Take every ordinal up to omega, and then, instead of bananas, put omega plus in front of each. Now we've reached omega plus omega, or omega times 2. Using replacement, we can make jumps of any size we want, so long as we only use numbers we've already achieved. We can replace every ordinal up to omega with omega times it to reach omega times omega, omega squared. We're cooking now. The axiom of replacement allows us to construct new ordinals without end. Eventually, we get to omega to the omega to the omega to the omega to the omega, and we run out of standard mathematical notation. No problem. This is just called epsilon naught, and we continue from here. But now, think about all of these ordinals, all the different ways to arrange Aleph Null things. Well, these are well ordered, so they have an order type, some ordinal that comes after all of them. In this case, that ordinal is called omega 1. Now, because by definition, omega 1 comes after every single order type of Aleph Null things, it must describe an arrangement of literally more stuff than the last Aleph. I mean, if it didn't, it would be somewhere in here. But it's not. The cardinal number describing the amount of things used to make an arrangement with order type omega 1 is Aleph 1. It's not known where the power set of the naturals falls on this line. It can't be between these cardinals because, well, there aren't cardinals between them. It could be equal to Aleph 1. That belief is called the continuum hypothesis. But it could also be larger. We just don't know. The continuum hypothesis, by the way, is probably the greatest unanswered question in this entire subject. And today, in this video, I will not be solving it, but I will be going higher and higher to bigger and bigger infinities. Now, using the replacement axiom, we can take any ordinal we've already reached, like, say, omega, and jump from aleph to aleph all the way out to aleph omega. Or heck, why not use a bigger ordinal, like omega squared, to construct aleph omega squared? Aleph omega 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 omega. Our notation only allows me to add countably many omegas here, but replacement doesn't care about whether or not I have a way to write the numbers it reaches. Wherever I land will be a place of even bigger numbers, allowing me to make even bigger and more numerous jumps than before. The whole thing is a wildly accelerating feedback loop of embiggening. We can keep going like this, reaching bigger and bigger infinities from below. Replacement and repeated power sets, which may or may not line up with the alephs, can keep our climb going forever. So clearly, there's nothing beyond them, right? Not so fast. That's what we said about getting past the finite to omega. Why not accept as an axiom that there exists some next number so big no amount of replacement or power setting on anything smaller could ever get you there? Such a number is called an inaccessible cardinal because you can't reach it from below. Now, interestingly, within the numbers we've already reached, a shadow of such a number can be found. Aleph null. You can't reach this number from below either. All numbers less than it are finite, and a finite number of finite numbers can't be added, multiplied, exponentiated, replaced with finite jumps a finite number of times, or even power set a finite number of times to give you anything but another finite amount. Sure, the power set of a milli-nillion to a googolplex to a googolplex to a googolplex is really big, but it's still just finite, not even close to aleph null, the first smallest infinity. For this reason, aleph null is often considered an inaccessible number. Some authors don't do this though, saying an inaccessible must also be uncountable, which, okay, makes sense. I mean, we've already accessed aleph null. But remember, the only way we could is by straight up declaring its existence axiomatically. We will have to do the same for inaccessible cardinals. It's really hard to get across just how unfathomable the size of an inaccessible cardinal is. I'll just leave it at this. The conceptual jump from nothing to the first infinity is like the jump from the first infinity to an inaccessible. Set theorists have described numbers bigger than inaccessibles, each one requiring a new large cardinal axiom asserting its existence, expanding the height of our universe of numbers. Will there ever come a point where we devise an axiom implying the existence of so many things that it implies contradictory things? Will we someday answer the continuum hypothesis? Maybe not, but there are promising directions. And until then, the amazing fact remains that many of these infinities, perhaps all of them, are so big, it's not exactly clear whether they even truly exist or could be shown to in the physical universe. If they do, if one day physics finds a use for them, that's great. But if not, that's great too. That would mean that we have, with this brain, a tiny thing a septillion times smaller than the tiny planet it lives on, discovered something true outside of the physical realm. Something that applies to the real world, but is also strong enough to go further, past what even the universe itself can contain or show us or be. And as always, thanks for watching. Another interesting fact about transfinite ordinals is that arithmetic with them is a little bit different. Normally, 2 plus 1 is the same as 1 plus 2, but omega plus 1 is not the same as 1 plus omega. 1 plus omega is actually just omega. Think about them as order types. One thing placed before omega just uses up all the naturals and leaves us with order type omega. One thing placed after omega requires every natural number and then omega, leaving us with omega plus 1 as the order type.
Hey, Vsauce, Michael here. 93% of all the humans who have ever lived are dead. For every person alive right now, there are 15 people who are no longer alive. The Earth is dangerous, but where is the most dangerous place on Earth? Ignoring freak occurrences, where is the most persistently perilous place on the surface of our planet? Well, let's begin with temperature. Extreme heat and extreme cold can kill within hours, if not minutes. In cold environments, without clothing, the human body by itself doesn't do a very good job of maintaining a high enough temperature to live. It just takes too much work. Even when you feel comfortable and warm, nearly half of your daily caloric intake is used merely to keep your body's temperature where it should be. If you took a human and stripped them naked and put them in an environment at 0 degrees Celsius, they would die from having too cold of an internal temperature within about 20 minutes. We need warmth. But one thing we need more immediately than that is oxygen. And that brings us to the summit of Mount Everest. This place on the surface of Earth has incredibly thin air. At the top of Mount Everest, there is only 1/3 as much breathable oxygen as there is down at sea level. Climbers can endure the conditions for short periods of time if they acclimate for months. But if you were to teleport from wherever you are right now directly to the summit of Everest, you would most likely die within only 2 to 3 minutes because there isn't enough oxygen. Death would come even more quickly if you were at the bottom of the Mariana Trench. There, you would be submerged under nearly 7 miles of water, about 11 kilometers, causing the pressure around your body to exceed 15,000 pounds per square inch. At normal swimming depths, you can always hold your breath. But that far down, with that much pressure, your lungs would collapse immediately. And without oxygen, your brain would go unconscious in 15 seconds and you'd be dead in under 90. You would die pretty much just as quickly as someone who walked into outer space without a suit on. But falling into a molten lake of lava is probably the most spectacular way to go. Contrary to what you see in many movies, your body wouldn't just burn a little bit and slowly sink as if it were in quicksand. Instead, there would be a lot of fireworks. Hot molten lava is liquid rock, 4 times as hot as your oven can ever get. And the human body is mainly made up of water, which when exposed to that kind of heat turns into steam, explosively. There's a fantastic video right here on YouTube where a guy throws a bag of organic material containing a lot of moisture into hot lava. It doesn't just sink in, it causes a miniature eruption. I highly suggest you go watch it. But what if we want to measure danger not by how quickly you would die, but by the actual total number of fatalities caused? Well, for this, we're going to need to get much, much smaller, like microscopic. In 1918, influenza killed nearly 100 million people, which at the time was 3% of the world's entire population. But places where and when the plague has spread rapidly are even scarier. Between 1347 and 1353, 1/3 of everybody in Europe died because of the bubonic plague, an infection caused by Yersinia pestis. It's easy to think of the plague as something from way back in the past, but it is still
here. Of course, now we have antibiotics, which can help in most cases, but believe it or not, in America alone, 5 to 15 people still get the plague every year. In terms of total fatalities, however, the plague and influenza are nothing compared to the danger caused by this guy, Plasmodium. It's a microorganism that can get into our blood because of mosquito bites and causes malaria. Across the totality of human history, the number of deaths attributed to malaria is unbelievable. Researchers like Nobel laureate Baruch Blumberg have studied the history of the human genome and human migration and determined that of all the humans who have ever existed, it is likely that half died from malaria. So in terms of total fatalities across all of human history, a place where Plasmodium could enter the bloodstream because of a mosquito bite, statistically speaking, could be called the most dangerous place on Earth. But let's switch gears for a moment and talk about places that are dangerous not because of Earth or Earth's creatures, well, actually just one specific creature, us. La Orilla is a mining town in Peru where the murder rate is low but pollution is high. The town's smelter emits pollution into the air, and temperature inversions in the atmosphere above the town trap gases within, causing the town to have 85 times more arsenic in its air than is deemed safe. But that's nothing compared to Lake Karachay in Russia. It was named the most polluted spot on Earth by the World Watch Institute on Nuclear Waste. The lake contains so many radioactive pollutants that you can receive a lethal dose of radiation merely by standing for 1 hour near certain parts of the lake. The Global Peace Index ranks countries by how safe they are. It takes into account a number of factors, including crime and political corruption. The safest country, according to the index, is Iceland, and the least safe is Somalia. But for the highest murder rate, you'll have to go to Juarez, Mexico, where out of every 1 million inhabitants, each year 1,477 of them are murdered. I've always found it amazing just how many serial killers Miami seems to have on the show Dexter. But Miami is a big city, and so despite all those serial killers, its murder rate in the show is not the highest of any fictional town from a TV show. That honor goes to Cabot Cove, the town where Murder, She Wrote occurred. An analysis of Murder, She Wrote episodes revealed 274 murders, but a population in the town of only 3,500, making Cabot Cove's murder rate 1,490 per million inhabitants. Until recently, that number was unmatched by reality. But last year, the city of San Pedro Sula in Honduras reported a murder rate of 1,588 murders per million inhabitants. Let's conclude by revisiting pollution, specifically the Chernobyl accident, and a certain oxymoronic danger. For 10 days in 1986, radioactive isotopes spilled out of a blazing reactor core, forcing mass evacuations. It's more than 25 years later now, and many parts of the exclusion zone remain incredibly lethal. But without humans there, many parts of the exclusion zone have seen wildlife flourish, especially endangered species, which can go to the exclusion zone, live, reproduce, and be safe from us. We managed to ruin a place to the point at which it endangered our lives and we had to leave. And in doing so, we left parts of it a little bit safer for other forms of life. You can read more about all of these topics by following links down in the description below. Keep learning, and as always, thanks for watching.
Using GPS, these trails represent pizza delivery in Manhattan on a typical Friday night. And is this a frog or a horse? It's episode 52 of IMG. This lemon looks yellow to me, and it probably looks yellow to you as well, but not in the same way. You see, here in this room, this lemon is subtractively yellow. It absorbs all visible wavelengths of light except for yellow light, which it reflects onto my retina. But the screen that you are using to watch this video doesn't produce yellow light at all. In fact, it can only produce red, blue, or green light. The really cool but kind of disturbing thing about this is that here in the room, I am actually seeing real yellow light, but you are seeing fake yellow. Absolutely no yellow is coming off of your screen and falling on your retina. But it still looks yellow because it's quite easy to lie to the brain. Our retinas contain 3 different types of cone cells that are receptive to color, and each one is best suited to detect a certain color. One is great for blue, the other is great for green, and the third is great for red. Notice that there's no individual cell looking for yellow. So the way we actually see yellow happens like this. The wavelength of yellow light falls between the wavelengths of red and green. And so when an object reflects yellow light onto your retina, both the green and the red cones are slightly activated, which your brain notices and says, well, that's what happens when something's yellow, so it must be yellow. All a computer monitor or a mobile phone screen has to do to make you think you're seeing yellow is send a little bit of red and a little bit of green light at you. As long as the pixels and the little subpixels on them are small enough that you can't distinguish them individually, your brain will just say, well, I'm receiving some red and some green. That's what yellow things do. It must be yellow. Even though it actually is not. Lemons can also produce electricity. A little bit of zinc, a little bit of copper, and boom, you're moving electrons around. But not that many. I mean, the current and voltage are quite low. You could run an LCD, but even a potato could do that. If you wanted to run a flashlight bulb, that would take 3,000 lemons. And if you wanted to run a halogen bulb, well, that would take 37,000 lemons. But artist Caleb Sharland doesn't care. He spent 11 hours hammering nails into 300 living apples hanging on trees. By connecting them to a household lamp, he was able to make it glow just dimly enough to capture this image with a 4-hour exposure. Less alive and more frightening are Steve Shaheen's sculptures, little dudes with bulb heads desperately trying to plug themselves in. Merv Karaman's Revitalizer never dies. It's a light bulb surrounded by wax. Now the wax melts because of the light bulb's heat and drips into a special container into all kinds of weird new shapes. But whenever you want, you can just flip it so that the new cooled wax is at the top. But my favorite is the Fukasada wooden light bulb. It looks like a solid block of wood, but it's actually hollow and chipped to a nearly paper-thin width. When you turn it on, you can see the light coming from inside. Combos. Artist Tang Yo Hung blew my mind this week. We've got clear days and smoke, boats and crocs, whales and hearts, pie bike, brains and boxing gloves, day and night. But don't be scared, you can always paint yourself some light, or just swing on some light. Okay, let's frame it this way: climbing wall. This fitness club in Japan uses frames and other pretty interior elements to create a decidedly less rugged climbing wall. But let's get simple, like minimal. Thanks to Lego, here are their bricks arranged to represent famous characters. Enjoy. Now for some art. Illusions. Here's a cute couple, but can you see in this very same image the baby they will soon have? Or how about these zebras? There's a lion hiding amongst them.
Can you find it? Billboards can be clever, but here's a great one that makes it look like someone is pushing out a section of the building. But how many of you will remember seeing it? If we assume that you don't remember experiencing major cultural events before you're 5 or 6 years old, that means that every year there are fewer and fewer people alive who remember experiencing recent historical events. XKCD made this amazing chart to show when, in the future, the majority, more than half of living Americans will not remember being alive when certain things happened. For instance, he calculated using data from the US Census Bureau that 2012, this very year, is the first year in American history since in which fewer than half of living Americans remember being alive in the 1970s. By 2041, most of us won't remember a time when Pluto was actually called a planet. By 2043, most of us alive won't remember living during George W. Bush's presidency. And by 2047, more than half of living Americans will not have been alive to have remembered anything that you did today. Like when you made that funny face in the yearbook. No, that funny face. If you're not following Vsauce, you are missing out on daily Vsauce content, most of which never makes it to a video. So go follow us on Twitter, and I'm gonna leave you with another combo. A tessellation while you listen to Jake Chudnow's Flawn. He made a music video for this song over on his channel, so check that out, and as always, thanks for watching. Hey, Vsauce. Michael here. Fear gives us life. Being afraid of the right things kept our ancestors alive. It makes sense to be afraid of poisonous insects or hungry tigers. But what about fear when there is no clear and obvious danger? For instance, a teddy bear with a full set of human teeth. Or a smile.jpg. There's something a little off about these images, too much mystery and strangeness. But no obvious threat the way there is with a gun or a falling rock, but yet they still incite fear because they are creepy. But why? What gives us the creeps? What causes something to be creepy? We are now in my bedroom, the bedroom I grew up in Kansas. Like a lot of children my age, I was terrified of scary stories to tell in the dark. But the very first book that ever scared me was The Curse of the Squirrel. To this day, I still haven't finished the book, but that's just me. Psychologist James Geer developed the Fear Survey Schedule 2, which he used to find out what scared us the most. Combined with the results of a more recent Gallup poll, these are the things that scare most of us the most. All of these things are scary, but are they creepy? Let's get more specific. I love the way Stephen King delineates 3 types of scary stuff. The first is the gross out. This is something disgusting, morbid, diseased. The second is horror. Horror to King is the unnatural, a giant spider, or being grabbed in the dark when you thought you were alone. The third, terror, is different, creepier. He says terror is coming home to find that everything that you own has been replaced with an exact copy. Terror is feeling something behind you, its breath on your neck, knowing that you will be grabbed, but then turning around to find that there was never anything there in the first place.
Not a lot of research has been done on that feeling, the creeps. But many theories and ideas involve vagueness, ambiguity. For instance, masks and why clowns are creepy. Claude Lévi-Strauss wrote that the facial disguise temporarily eliminates from social intercourse the part of the body which reveals personal feelings and attitudes. Part of the reason even a neutral or happy mask can be creepy may have to do with ambiguity. A mask hides the true emotions and intentions of the person underneath. I don't know if the person wearing that mask is a threat or not. Vagueness is creepy when it comes to the human form. This is the famous uncanny valley. On a chart of humanness, there's a zone where something can be almost entirely human, but off by just a little. Not so wrong that it's clearly fake or funny, or so good that it's indistinguishable. Instead, it's just troubling. The creepiness of the uncanny valley is wonderfully demonstrated by John Bergeron's Singing Androids. Watch these videos when you're alone. A similar uneasy feeling comes from Shay St. John, a character created by Eric Fournier, funny to some, nightmare fuel to others. Uncanny humanoids, like all creepy things, straddle a line between two regions that we can understand and explain with language. Francis T. McAndrew and Sarah Kohnke describe being creeped out as an adaptive human response to the ambiguity of threats from others. Creepy things are kind of a threat, maybe, but they're also kind of not. So our brains don't know what to do. Some parts respond with fear, while other parts don't, and they don't know why. So instead of achieving a typical fear response, horror, we simply feel uneasy, terror, creeped out. Between the mountains of safety and danger, there is a valley of creepiness, where the limits of our knowledge and trust and security aren't very clear. Will looking at this cause you to die 1 week later? Impossible, right? Maybe. That's the terror of ambiguity. We don't do well with ambiguity. When it involves our own intentions, it can make us lie. And when it involves danger, but no recognizable threat, it can make us think and feel some pretty weird things. Have you ever peered over a ledge, a railing, way high up, like so high up it made you nervous and dizzy, and felt something pushing you? Maybe even an urge to jump. Have you ever stood on a ledge with a loved one and realized that you could push them? It would be that easy. You really could do it. And maybe you do want to do it, or maybe it's just cognitive dissonance. The fact that your brain is having to deal with ambiguity. A recent study by Jennifer Hames at Florida State University dubbed this the high place phenomenon. When approaching a ledge and a dangerous drop, your survival instinct kicks in and you pull yourself away. But your balance and motor systems don't get it. Nothing is pushing you, and you don't normally fall or leap randomly. So what's going on? The part of your brain that processes intention might resolve this by determining that something must be pushing you, or that you might actually want to jump or push your friend, even if none of that is true. Now, we're not done with ambiguity yet, because our language reflects the gray area of terror and creepiness. Take a look at the word terror itself. We have horrible and horrific, terrible and terrific. Why is that? Well, through history, we never really figured out what to call powerful experiences, because they're both. They are full of awe, awesome, and they are full of awe, awful. We need them to survive. We need fears and the creeps to understand our size, our weaknesses. But on the other hand, avoiding them is pretty great too. The creeps is a physical reminder that the world is vague and full of ambiguity, but that we are cunning, always trying to figure things out, but nonetheless fragile. Is that terrible or terrific? Well, it's both, which, as a creepy ghost would say, is kind of boo-tiful. And as always, thanks for watching.
Hey, Vsauce, Michael here. Nyctophobia is the fear of the dark. But there's another fear that's more chilling. It's the fear that darkness will go away. Optophobia, the fear of opening your eyes. Light travels at the fastest speed possible for a physical object. Darkness is erased when light appears and returns when light leaves. The speed of dark is the speed of light, but there are other types of darkness that can move faster than light speed. For instance, a shadow. Across a distance, a shadow can become much larger than the object creating it, but still mimic its source, moving in the same way for the same amount of time. So when a shadow is bigger than the object casting it, it moves a greater distance when the object moves, but in the same amount of time. Make a shadow large enough and it can travel across a surface faster than light. If you, here on Earth, cast a shadow onto the moon, not an easy thing to do, that pointed from, say, point A on the moon's surface, and then you moved your finger so that the shadow moved to point B, your finger would only move a few centimeters in a fraction of a second, but the shadow it cast on the moon would move thousands of kilometers in the same amount of time. Do it right, and you're easily producing a shadow that breaks the light barrier. But nothing's wrong here. The rule is that information can't travel faster than light. You can't cause something to happen somewhere else faster than light could travel from you to that somewhere else. And our superluminal shadow is transferring no information from point A to point B. Sure, point B is being cast into darkness sooner than a light speed message from A could warn him it's coming, but darkness isn't traveling from point A to point B. It's traveling from you to point A and point B at the speed of light. What we tend to call a shadow is really just a cross-section of a three-dimensional region. The darkness you are causing only changes shape when newly unblocked light fills the previous gap. That's all a shadow is, a gap. So in a way, a shadow doesn't travel at all. That's an illusion caused by us thinking that a shadow is a physical thing, when in reality, a shadow is just the lack of physical things, photons, which chug along at the speed limit of the universe. But that doesn't mean two shadows can't kiss, or at least look like they are. Watch as Guy brings two shadows near each other. Right before they actually make contact, the shadows seem to magically bulge toward one another in a sort of smooch of darkness. What's going on is the shadow blister effect, and it has to do with the anatomy of a shadow. The region where an object completely blocks a light source is called the umbra. It's the darkest part of a shadow and the most prototypical part of the shadow. Where only a portion of the light source is blocked, we find the fainter penumbra. But as two or more penumbras approach and overlap, the combined amount of light they block can be enough to produce a perceivable difference, the shadow blister. The Earth has a big umbra. It's 1.4 million kilometers long. That's how far away you'd have to be from the Earth for it to no longer have a large enough apparent diameter to block out all of the sun. Here on the surface of Earth, we are nowhere near that far away, which is why night is so umbral. Night is just the Earth's shadow falling on you.
a U eclipse. Sunsets are cool, they're beautiful to look at, but look the other way and you can see the lumbering shadow of our planet. Our atmosphere scatters shorter wavelengths of light more than longer wavelengths, which makes the sky appear blue. But in Earth's shadow, there's less light to scatter and the sky appears darker. During twilight, you can see the demarcation. While driving east from Denver to Kansas City, I got a particularly great view of it. This is Earth's approaching night-making shadow. The beautiful pink band above it, that's the belt of Venus. It's caused by the sky reflecting the colors of the sunset behind us. You've probably noticed that right after the sun sets and disappears from view, there's still light in the sky, scattered from the no longer visible sun. This is what we call twilight, and there are many different stages of twilight. If the sun is less than 6 degrees below the horizon, it's technically civil twilight. You can still do plenty of stuff outdoors without the need for artificial lights. Down to 12 degrees below the horizon, we have nautical twilight. Artificial lights are more or less necessary, but the sky still scatters enough light to be bright enough for ships at sea to navigate by seeing a contrast at the horizon between dark sea and faintly lit sky. Down to 18 degrees, an astronomical twilight is occurring. It looks like night, but the sky can still get darker. Until astronomical twilight ends, not all nighttime astronomical observations can be made. Below 18 degrees is technically, honestly, night. If you live at greater than 48.5 degrees north or south latitude, during the summer, the sun never goes more than 18 degrees below the horizon. It's never technically night. Places like London only reach astronomical twilight at the most during these months. So if you live in one of these areas and you want to avoid doing something during the summer, just tell people you'll do it tonight. You'll buy yourself a few weeks. But that's slow darkness. Let's cut to the chase because we are looking for fast darkness. When scissor blades snip, the intersection point between both blades moves faster than the blades themselves. Think of it this way. If you had a pair of scissors with blades that were a light year long, and it took 1 second to close them, the intersection point would have traveled an entire light year in not a year, but a second. No laws are being broken here because such a snip would be physically impossible. As I've mentioned before, rigid objects don't move instantaneously all over when a push force is applied to them. Instead, that force moves via electromagnetic forces from one atom to the next and so on down the line, a compression wave that travels at the speed of sound through the material. But what if we ignored that problem by allowing the blades to simply be separately already in motion? Well, their point of intersection can still travel faster than light because it's not a physical thing. It's just a geometric point, and it carries no more information than you could already gather by witnessing the approaching blades. But don't count out that geometric point of intersection just yet. It's the key to another type of darkness that can move faster than light. When waves collide, their crests can fuse into larger crests, their troughs into larger troughs. This is constructive interference. But crests colliding with troughs cancel out. Destructive interference. If these waves are light, the result is darkness. And in certain circumstances, darkness created this way can travel like the intersection between two lines, faster than light. Imagine these concentric circles as waves of light. The lines are wave crests, and the gaps in between are troughs. When they meet, the points where they intersect flee up and down faster than the waves travel, especially in the middle, which in the case of light waves makes them faster than light. The superluminal speeds of these dark patches can be seen really clearly if we make the wave crests of one source black as well as the background. Overlapping regions where red peeks through represent destructive interference, darkness. And you can see how, especially in the middle, this darkness races up and down faster than the waves. In 1995, a man named MacArthur Wheeler robbed a bank in Pittsburgh. He was caught.
because his only disguise was lemon juice. He covered his face with it. He knew that lemon juice could be used as an invisible ink when writing on paper revealed by heating. And he knew so little about why that worked, and he knew so little about how cameras worked, that he assumed with extreme confidence that lemon juice could make him invisible too. Seriously. Wheeler is an extreme example and was the inspiration for the Dunning-Kruger effect. Novices, people unskilled in particular disciplines, will often overestimate their knowledge and abilities in said disciplines because they don't even know how little they know, how much more there is to learn. On the flip side, experts in particular fields will often underestimate their knowledge, have less confidence in their abilities, or think that everyone else has the same level of knowledge that they do. What drives the Dunning-Kruger effect is the fact that often, the more you learn about something, the more you realize just how rich and complex and overwhelming and full of as-of-yet unanswered questions it really is. George Bernard Shaw once famously toasted Albert Einstein by saying, "Science is always wrong. It never solves a problem without creating 10 more." Einstein didn't exactly disagree. He used geometry to illustrate how ignorance grows faster than knowledge, saying, as our circle of knowledge expands, so does the circumference of darkness surrounding it. Learning, studying, shedding light on a field of inquiry also reveals just how in the dark we continue to be, how many shadowy things there are left for us to illuminate. The diameter of light never exceeds the shadowy circumference. But what's the speed of that kind of dark? The speed of the growth of the number of things we know we are in the dark about. What's the speed of ignorance? If we define ignorance as the difference between questions we know to ask and answers we have, the field of agnotology, the study of ignorance, suggests that the amount of things we know we are in the dark about is growing faster than the amount of things we have shed light on. Is it a coincidence that the phrase "in the dark" originated during, of all ages, the Age of Enlightenment? When Leeuwenhoek put a scraping from his tooth under a collection of magnifying lenses he built, he saw, for the first time in human history, little moving creatures, microorganisms. He called them animalcules. The discovery shed light on why food spoiled. Life didn't spontaneously come from old meat. It was already there, we just couldn't see it. But the discovery also showed us that we were in the dark about an entirely new realm of biology. As Philippe Bourdieu has poetically put it, enlightenment leads to benightedness. Science entails nescience. What's really cool about the expanding size of our nescient circumference is what Stuart Firestein, the chair of biological sciences at Columbia University, has said about it. It is there that science begins, where the facts run out, just beyond them. He says it is a mistake to bob around in the circle of facts instead of riding the wave to the great expanse lying outside the circle. If science is a road trip, facts are the photos we take along the way. The fuel that drives it forward is ignorance. Facts? More like facts, part of the past, not the way forward. When it comes to understanding our world, knowing why is obsolesced by asking why. Knowing facts makes you bright, but the equally quick, sometimes quicker, and most rewarding prize is the dark. In admitting that you don't know everything, but that you'd like to know some of it. And as always, thanks for watching.
Hey, Vsauce, Michael here. The Earth is spinning, and we are spinning along with it. But what if the Earth suddenly stopped spinning? Well, first of all, you would gain weight. But that would be the least of your worries. The spin of our planet is important and literally giving you the time of your life. At the equator, the surface of Earth and everything on it is spinning around at 465 meters a second. As you move closer to the poles, you don't have to move as quickly to complete Earth's daily rotation.
Here in San Francisco, the Earth is driving me east at 368 meters per second. If I could float above the surface independent of the Earth's rotation, the Earth would spin underneath me this quickly. Pretty cool.
But of course, when I jump straight up into the air, the Earth doesn't move underneath me because I continue to spin with it. We are all spinning with the Earth, and that is why slamming on a set of magical planetary brakes that caused everything classically called Earth to stop spinning would be catastrophic. Immediately, everything that wasn't Earth and wasn't safely at the poles would continue moving as it had been and be flung due east at more than 1,000 miles an hour. You wouldn't be flung into space because escape velocity is 24,800 miles per hour, but your body would instantly become a 9.5-inch caliber bullet. Well, really more of a supersonic tumbleweed. Because the atmosphere would more gradually slow down, people in airplanes, assuming they could navigate the resulting storms, might have a better chance of surviving. Astronauts aboard the ISS would fare even better, but it is unlikely that anyone would be waiting for them down on the ground. Runways would just be entrances to the new planet-sized graveyard created by the no longer spinning Earth. People really near the poles might be okay, but only at first. Gusts of wind as fast as those near an atomic bomb detonation would blast past the surface and up into the sky, forming worldwide storms of unprecedented magnitude. The friction alone, caused by the now stopped Earth colliding with these winds, would be enough to cause massive fires, unparalleled erosion, and damage to anything strong enough to stay put after the initial braking. The sun would seem to freeze in the sky as days became not 24 hours long, but 365 days long. Without spinning innards, Earth's protective magnetic field would cease to exist, and we would be dosed with deadly amounts of ionizing radiation from the sun. The oceans would surge onto land in tsunamis kilometers high and wash over nearly all dry land before migrating to the poles, where gravity is stronger, no longer held to the ocean basins by the inertia Earth's spin gave them, until Earth itself no longer bulging an extra 42 kilometers around its equator because of its rotation, slowly compressed into a more perfect sphere than it is now, possibly allowing the oceans to eventually return somewhat. That is what would occur if it actually happened. It won't actually happen, but whoa, its rotation is slowing down. More on that later. First, if the Earth really is spinning so quickly, why can't we feel it? Why doesn't the Earth's rotation make us dizzy? Well, lucky for us, the change in velocity is just too gradual. The Earth is too huge. It's like driving in a car that takes 6 hours and 6,000 miles to make one left turn. It's not sudden enough to register with our senses. But that change in velocity is real, and it makes us weigh less because of inertia. On our spinning planet, your velocity is constantly changing, but always tangential to the circular path you are being dragged along. Now, because inertia is a property of matter, which includes your body, without a force acting upon us, we would slowly leave the surface of Earth. Luckily, the Earth is exerting a force on us, a center-seeking centripetal force delivered by gravity. The centripetal force required to keep you along a circular path with Earth is subtracted from Earth's total gravitational pull on you. The remaining force simply pushes you down toward the center of the Earth. It gives you weight. At the equator, if the Earth didn't spin and no centripetal force was required to keep you with the Earth, you would weigh 0.3% more than you currently do. If Earth spun you around 17 times faster than it currently does, all of its gravitational force would go towards centripetal force fighting against your inertia, and you would be weightless. So here's a diet idea. hope that the Earth starts spinning faster, and go back for guilt-free seconds. Seconds. We know exactly how long a second is. The outermost electron of an atom of cesium-133 is alone. When the atom is undisturbed, only the nucleus interacts with this outermost electron, tickling it regularly and rapidly between two levels. After 9,192,631,770 oscillations between those two levels, 1 second has passed. Exactly. That is literally the definition of a second. We can measure and count those oscillations. It's how atomic clocks work, making atomic clocks the most accurate measurement device ever built by humans to measure anything. We can't define a second more simply as, say, 1/60th of 1/60th of 1/24th of a day because of Earth's spin. It's too irregular. Little changes in the distribution of mass on Earth caused by earthquakes or melting ice or man-made dams, or technically even you walking upstairs or downstairs, cause Earth's rotational speed to change, like a figure skater moving their arms further away from or closer to their bodies. Now add on top of that the fact that tides caused by the moon drag against Earth's rotation, and you wind up with an unstable rotation speed that is predominantly slowing down. Now, these changes are incredibly slight, but over time they add up. In 140 million years, a day on Earth will not be 24 hours long, it will be 25. That might not sound like much, but in order to do important things like deliver accurate GPS information, we need a more accurate timekeeping device than that. So as a solution, scientists keep the pace of seconds using atomic clocks, TAI time, and other scientists measure the changing speed of Earth's rotation by observing distant stars and quasars. Now, every few months they find out just how behind or ahead Earth is running, and if it's getting too close to being a second off, they decide to add or subtract a second from the current year. The result is the time used almost everywhere, including your phone, UTC. Since this system began in 1972, 25 leap seconds have been added. What this means is that clock time is and has to be a manufactured product, with upgrades and tune-ups administered periodically after defects are noticed. The time we give to now and the future is only ever approximate. That's weird, but it's also entirely not weird. As Demetrius Matsakis, the chief scientist of time services for the US Naval Observatory, puts it, we save lives and we end lives. We add time and we can take time away, but in both cases we do so without completely understanding exactly what life is or what time is. Regardless, thank you for spending some of yours with me, and as always, thanks for watching. Hey, Vsauce, Michael here, and what do you say we get out of here to space and into an orbit? That way we could just float around and be free from the influence of gravity. Except not really. Astronauts orbiting around the Earth experience pretty much the same gravitational pull that you and I are feeling right now. The major difference is that those astronauts are falling constantly towards Earth, but their angular velocity is so large that they're falling just as fast as Earth curves away from them. Now, of course, this is nothing new. Newton's canon hasn't already taught us.
Gravity makes stuff fall, and in particular, Newton realized that it makes objects accelerate towards the Earth the same amount independently of how fast they're moving horizontally. That's called relativity. And of course, orbiting is just falling, but falling where you move horizontally fast enough that the Earth falls away faster. In order to successfully fall and miss the Earth, unless you dug a tunnel, you'd need to be traveling at almost 17,000 miles per hour, or 8 kilometers every second. So you'd probably incinerate from friction with the air well before you had a chance to enjoy the trip. Of course,
Newton's thought experiment involved the Earth, but on something smaller like the Moon, the cannon wouldn't have to throw its projectile nearly as fast for it to complete an orbit. In fact, if you had a powerful enough gun on the Moon, and you fired that gun at the horizon and then waited a little bit, you could get hit in the back of the head by the same bullet. Henry calculated that the bullet would have to travel about 1,600 meters per second, which is exactly how fast the Paris gun fires. Now that's a powerful gun, it's no squirt gun. But if you had a squirt gun out there in space and you fired a stream of water at the sun, how much water would it take to put out the sun? I mean, in general, putting water on something hot would cause that something hot to lose some heat, especially since the water will be frozen because it's out there in space. But here's the issue. The sun is not a big ball of hydrogen on fire. Instead, the sun is powered by fusion.
fusion of hydrogen nuclei, which is kind of like the chemical bonds between the hydrogen and oxygen that make up water, except on a much smaller and much more powerful scale. Now, before I get tackled by nuclear physicists from one side and chemists from the other, let me explain. A bond of any sort, whether between planets, molecules, atoms, nuclei, or quarks, is just a happenstance where two or more particles together have a lower total energy than when they were apart. Like if you get married and your taxes go down. So when you form a bond, that extra energy that the two solitary particles had is released. And because of a little relation we call E equals mc squared, this actually means that the mass of the pair goes down a little bit too. For example, every fusion reaction turns a little bit of hydrogenous mass into light. Sunlight, for example, amounts to a loss of 100 quadrillion kilograms each year. That's the equivalent of a medium-sized asteroid. But stars have a lot of mass.
And the more massive a star is, the hotter it burns.
And adding a bunch of water to the sun would only cause it to be more massive, so it would burn brighter, not go out. Of course, it would also burn faster, which means that its life would be shorter. For instance, if you were to add 20 solar masses of water to the sun, you would decrease its life expectancy from the current 5 billion years to only a few hundred million more years. But there's a faster way to put out the sun. Take that water or whatever material you want and shoot it into the sun in a way that causes everything to get spread out and scattered so that there's no longer the critical density needed for fusion to occur. Now, no matter which avenue of putting out the sun you pick, both would be a disaster. Literally. Disaster. From dis meaning against and aster meaning star. You would have literally turned our own star against us. If you were somehow able to avoid that disaster by magically appearing in intergalactic space, here's a fun experiment to try. Take out your gun and fire a bullet. That bullet will be forever alone.
That's because the universe is expanding, and if you were a few megaparsecs away from the nearest galactic cluster, on average those galaxies would be 200 kilometers farther away from you every passing second. In space terms, 200 kilometers a second is pretty slow. It's barely as fast as the solar system orbits the center of the Milky Way, and stars closer to the center of the galaxy can orbit 10 times faster. But a measly bullet travels only a few kilometers every second, and would have no chance of reaching the receding galaxies ever.
It makes you realize how tiny we are compared to the scale of the universe. But it also makes you realize how close together we all are here on Earth. Of course, to get from one side of the Earth to the other, you have to fly over half the sphere.
So what if instead there were a tunnel through the Earth? Let's jump over to my channel, Minute Physics, to see what happens. Click here, and I'll see you on the other side. Oh, and as always, thanks for watching.
Hey, Vsauce, Michael here, and my tea is quite hot, but it's not the hottest thing in the universe. So what is? I mean, we know that there is an absolute zero, but is there an absolute hot? A point at which something is so hot it can't get any hotter? Well, to find out, let's begin with the human body. Your internal temperature is not constant. 37 degrees, 98.6, sure, but those are averages. Your body's internal temperature fluctuates by about 1 degree Fahrenheit, half a degree Celsius, throughout the day in a cycle. Assuming you sleep at night, at 4:30 in the morning, your body reaches its coolest, natural, healthy temperature, and at 7 p.m., it reaches its highest. But a dangerous fever is not good. 108 degrees Fahrenheit is almost always lethal. The highest recorded air temperature across all of Earth has happened 4 times in Death Valley, where it has reached 129 degrees Fahrenheit. 180 degrees Fahrenheit is the recommended temperature for water when brewing coffee, and at 210 degrees Fahrenheit, a cake is done. 2,000 degrees Fahrenheit is the temperature of lava fresh out of the ground. But come on, make your own lava like Green Science Pro. This guy uses Fresnel lenses to focus the sun's energy onto whatever he wants. This is a small piece of obsidian, volcanic glass, which he can melt into actual lava right in his backyard. Keep in mind that the sun is having that effect even though it is 93 million miles away from Earth. Right up on the surface of the sun is a different story. The surface clocks in at 10,000 degrees Fahrenheit, but the center, where fusion occurs, is ridiculous. Temperatures there reach 28 million degrees Fahrenheit, which is also known as 15 million Kelvin. The Kelvin scale has units that are the same size as a Celsius degree, but it's an absolute scale, where 0 is absolute 0. When matter reaches temperatures as high as those found in the center of the sun, an enormous amount of energy is radiated away. If you were to heat only the head of a pin to the temperature of the center of the sun, it would kill any person within 1,000 miles of it. Speaking of which, the energy emitted by an object often tells us a lot about the temperature of that object. Any object over absolute 0 emits some form of electromagnetic radiation. You and me, we don't glow visibly, but we do emit infrared light. We can't see it, but infrared cameras can. WBD has great videos, and here he is hiding inside an opaque black trash bag. Now, we can't see him, but his body is infraredly glowing through it. If you want something to be the right temperature to glow in the visible spectrum, you'll have to reach the Draper point, about 798 Kelvin. At this point, almost any object will begin to glow a dim red. We can calculate the expected wavelength of radiation coming off of an object because of its temperature, and that wavelength gets smaller and smaller the hotter and hotter the object gets. It goes from radio waves to microwaves up through infrared to visible, all the way to X-rays and gamma rays, which are created in the middle of our sun. At temperatures as hot as the sun, matter exists in a fourth state. Not solid, not liquid, not gas, but instead a state where the electrons wander away from the nuclei. Plasma. If you've watched my temperature lean back, you know that you can make plasma by microwaving fire. But don't do it. Besides, our sun isn't even close to being the hottest thing in the universe. I mean, sure, 15 million Kelvin is pretty incredible, but the peak temperature reached during a thermonuclear explosion is 350 million Kelvin, which hardly counts because the temperature is achieved so briefly. But inside the core of a star, 8 times larger than our sun, on the last day of its life, as it collapses in on itself, you would reach a temperature of 3 billion Kelvin. Or if you want to be cool, 3 gigakelvin. But let's get hotter. At 1 terakelvin,
things get weird. Remember that plasma we were talking about that the sun is made of? Well, at 1 terakelvin, the electrons aren't the only thing that wander away. The hadrons themselves, the protons and neutrons in the nucleus, melt into quarks and gluons, a sort of soup. But how hot is a terakelvin? Frighteningly hot. There's a star named WR104, about 8,000 light years away from us. Its mass is the equivalent of 25 of our suns. And when it dies, when it collapses, its internal temperature will be so great that the energy emitted, the gamma radiation it flings out into space, will be stronger than the entire amount of energy our sun will ever create in its entire lifetime. Gamma ray bursts are quite narrow, so Earth is most likely safe. But what if it wasn't? Well, when WR104 collapses, even though Earth is 4,702 trillion miles away, the energy it releases would still be bad news. Exposure for 10 seconds would mean losing a quarter of Earth's ozone layer, resulting in mass extinction, food chain depletion, and starvation. From 8,000 light years away. Closer to home, right here on Earth in Switzerland, scientists have been able to smash protons into nuclei, resulting in temperatures much larger than 1 terakelvin. They've been able to reach the 2 to 13 exakelvin range. But we are okay because those temperatures last for an incredibly brief moment and only involve a small number of particles. Remember how we could calculate the wavelength of the radiation emitted by an object based on its temperature? Well, if an object were to reach a temperature of 1.41 times 10 to the 32 Kelvin, the radiation it would emit would have a wavelength of 1.616 times 10 to the negative 26th nanometers, which is tiny. Like, so tiny it actually has a special name. It is the Planck distance, which according to quantum mechanics is the shortest distance possible in our universe. Okay, well, what if we added even more energy? Wouldn't the wavelength get smaller? It's supposed to, but yet it can't. This is where we've got a problem. Above 1.41 times 10 to the 32 Kelvin, the Planck temperature, our theories don't work. The object would become hotter than temperature. It would be so hot that what it is would not be considered a temperature. Theoretically, there is no limit to the amount of energy we could keep adding into the system. We just don't know what would happen if it got hotter than the Planck temperature. Classically, you could argue that much energy in one place would instantly cause a black hole to form. And a black hole formed from energy has a special name, a Kugelblitz. So basically what I'm trying to say is when you want to tell someone you like that you think they are hot, so hot that not even science can understand it, just call them a Kugelblitz. Finally, here is something fun. The sun is about 4.7 billion years old, about halfway through its life cycle. And so far, it has burned 100 Earths worth of fuel. Which sounds like a lot, but the sun is the size of 300,000 Earths. Because of that discrepancy, you can have a lot of mathematical fun comparing your energy output to the sun's. The sun is way hotter than us, and it puts out way more energy than us. Bad Astronomy had a lot of fun with this one, and although it doesn't really mean anything, it is technically true because of the sun's enormous size that 1 cubic centimeter of human puts out more energy than an average cubic centimeter of the sun. Which should make you feel quite warm inside.
И, как всегда, спасибо, что смотрели.
Hey, Vsauce, Michael here. When you call customer service and hear this,
to ensure quality service, your call may be monitored or recorded.
they're not kidding. Over the last year, the Marchex Institute analyzed more than 600,000 recorded phone conversations Americans made to businesses in the United States. Turns out, people from Ohio were the most likely to use curse words, the A word, the F word, and the S word. Washington State residents were the least likely to use bad words. But what makes a word bad? Ooh, well, be careful, because etymologically speaking, even the word bad can be considered a bad word. It began in Old English as a derogatory term for an effeminate man. 80% of swear words overheard in public in 1986, 1997, and 2006 were essentially the same. 1/3 of all counts included the top two, the F word and the S word. Slate's Brilliant Lexicon Valley podcast reported that these 10 words make up about 0.7% of the average English speaker's daily vocabulary, which means socially unacceptable words are used almost as often as socially descriptive words. First-person plural pronouns account for about 1% of the words we say every day. When a bad word is bleeped, it is covered with a 1 kilohertz sine wave, which sounds like this: son of a By the way, the symbols and squiggles that are used to represent a bad word have a name. They're called growlixes. They were named by Mort Walker in his seminal The Lexicon of Kamakana. He names a lot of things, but most of them show stuff. They don't hide stuff. Why the need to hide bad words, especially if we all pretty much know what's being said? Well, there is no one single reason bad words are bad. Steven Pinker, in his excellent lecture on the topic, delineates 5 types of swearing. First of all, some words are bad on purpose. They are created and or used with the intent to hurt others. He calls this abusive swearing, using words to insult, humiliate, objectify, or marginalize disfavored people. Now, if that disfavored person is God, we're talking about supernatural swearing, which was particularly taboo in Victorian times. It was believed that casually or vainly referring to God would physically injure God himself, literally. So, at the time, people were forced to come up with euphemisms like zounds and gadzooks, which originally meant God's wounds, and God's hooks, referring to the nails driven through the hands of Jesus. Historically, swear words often came from things we were afraid of, things we perceived as dangerous, stronger than us, and mercurial, such as death, disease and infirmity, sex and sexually transmitted diseases, as well as body fluids, germy, gross effluvia. Words for those gross things became gross and bad in and of themselves, uncouth to speak. But not all words for gross things are socially unacceptable, which brings us to Pinker's second type of swearing, emphatic swearing. Emphatic swearing is where the tabooness of bad words becomes quite practical. You wouldn't usually use those words, but when you really want to convey that your current emotions matter more to you than proper social conduct, you can use them. Dysphemism. A euphemism is a kind, acceptable word that allows you to talk about something unpleasant while simultaneously letting everyone know you totally get that it's unpleasant and want to respect that. For instance, if you want to be professional, you wouldn't say shit, you might say defecate. If, on the other hand, you really want to drive home just how unpleasant the experience was, dysphemisms can help out a lot. It wasn't a bag of canine defecation you found on your front porch. It was a bag of hot dog shit. Both of these words refer to pretty much the same thing, but they have different levels of social acceptability, and that's very helpful. It means word choice allows us to not only refer to things in the real world, but also to how we feel about them.
If both of these words had the same level of social acceptance, we might even have to find new, badder words so as not to lose the power language currently has to express emotion, repulsion, and disgust. But when it comes to two words referring to the same thing, but with different levels of social acceptance, who decides which one's good and which one's bad? Well, historically, many of the bad words we use today are the result of class differences. In medieval England, the lower class Saxons spoke a Germanic tongue, while the upper class Normans spoke a language related to French and Latin. English, as we know it today, contains many consequences of their differences. The lower class worked with animals, and from them we get animal names. The upper class only ate the animals, which is where the names of the meat come from. Today's swear words are similar. Defecation stems from fancy pants Latin, whereas the less classy is Germanic. There's also idiomatic swearing, where nothing is being emphasized, no dysphomism is meant. Instead, it's an easygoing type of swearing that shows an atmosphere is casual. Bad words can be used, we're all close here. It's okay to swear, we're all cool. Cathartic swearing is a bit different. It gives us lolochesia, the medical term for the relief swearing provides when you're in pain. In the brain, swearing seems to involve different regions than regular language, which may explain why people with aphasia caused by brain damage struggle to comprehend or construct spoken words, but yet are fluent at swearing, or why people with coprolalia control normal language just fine, but involuntarily utter profanity and obscene words. It turns out swearing may be centralized in the limbic system, along with emotions. Many animals make automatic noises when in pain or threatened, to startle or intimidate attackers, or to let others know what's going on. In humans, bad words are great for this purpose. Their tabooness makes them special. People wouldn't use them otherwise, so they are great alarms. Swearing is changing. Some bad words are being used more and more frequently. Of the 7 words George Carlin said you could never say on television, today, every second, 22 of them are sent out on Twitter. So what will swearing look like in the future? It probably won't go away altogether, it's too useful, but the words we don't like will likely change. History has shown that as disease becomes less scary and sex and the supernatural more personal, words related to them become less taboo and more common, whereas words that were common in the past are increasingly unpleasant. Perhaps in the future, spurred not by runaway political correctness but by wider knowledge, words like schizo, mental, aspie, or even depressed will take the swear stage. Or as John McWhorter ventured, words centered around class and the gap between opportunity and disadvantage will become more taboo. Salt of the earth, trash, chav, pikey, urban as a pejorative. When McKay Hatch started a no-cussing club at his school, his campaign became the target of so many online jokes and insults for being lame or anti-free speech. On his book, he literally subtitled his own name, "The Most Cyber-Bullied Kid in the World." People care about this stuff. Is it censorship to tell us what we can and cannot say? Or is it a safety seal, ensuring certain dysphomisms don't get worn down to a quotidian bluntness like every other word? Or is the badness of bad words a boundary, a moving boundary of what we reject? Sometimes arbitrary, sometimes irrational, but always moving in the direction of acceptance, moving forward. Crime and inequality have existed ever since they could. But when NWA released a reaction in the form of a song with a bad word in the title, F the police, the Federal Bureau of Investigations released a statement against the song. It was the only time up until then and since the FBI has ever issued an official statement about a work of art. Bad words have power. If you want to push for change, you'll need something to push. If everything's fine, nothing's cool. So, bad words are the precipitate of a larger reaction. The process of us slowly becoming what we want to become. That's some deep shit. And as always, thanks for watching. Hey, Vsauce, Michael here. Where are your fingers? Seriously, it's a pretty easy question. You should be able to answer it. But how do you know? How does anyone know anything? You might say, well, I know where my fingers are. I'm looking right at them. Or I can touch them. I can feel them. They're right here. And that's good. Your senses are a great way to learn things. In fact, we have way more than the usual 5 senses we talk about. For instance, your kinesthetic sense, proprioception. This is what the police evaluate during a field sobriety test. It allows you to tell where your fingers and arms and head and legs and your body is all in relation to each other without having to look or touch other things. We have way more than 5 senses. We have at least twice as many and then some. But they're not perfect. There are optical illusions, audio illusions, temperature sensation illusions, even tactile illusions. Can you turn your tongue upside down? If so, perfect. Try this. Run your finger along the outer edge of the tip of your upside down tongue. Your tongue will be able to feel your finger, but in the wrong place. Our brains never needed to develop an understanding of upside down tongue touch. So when you touch the right side of your tongue, when it's flipped over to your left side, you perceive a sensation on the opposite side where your tongue usually is, but isn't when it's upside down. It's pretty freaky and cool and a little humbling because it shows the limits of the accuracy of our senses. The only tools we have to get what's out there in here. The philosophy of knowledge, the study of knowing, is called epistemology. Plato famously said that the things we know are things that are true, that we believe, and that we have justification for believing. Those justifications might be irrational, or they might be rational, they might be based on proof. But don't get too confident because proven is not a synonym for true. Luckily, there are things that we can know without needing proof, without needing to even leave the house, things that we can know as true by reason alone. These are things that we know a priori. An example would be the statement, all bachelors are unmarried. I don't have to go survey every bachelor on earth to know that that is true. All bachelors are unmarried because that's how we define the word bachelor. Of course, you have to know what the words bachelor and unmarried mean in the first place. Oh, you do? Okay, perfect, that's great. But how do you know? This time I mean functionally. How do you know? Where is knowledge biologically in the brain? What are memories made out of? We are a long way from being able to answer that question completely, but research has shown that memories don't exist in the brain in single locations. Instead, what we call a memory is likely made up of many different complex relationships all over the brain between lots of brain cells, neurons. A major cellular mechanism thought to underlie the formation of memories is long-term potentiation, or LTP. When one neuron stimulates another neuron repeatedly, that signal can be enhanced over time, LTP, wiring them more strongly together, and that connection can last a long time, even an entire lifetime. A collection of different brain cells, neurons that fire together in a particular order over and over again frequently and repeatedly
can achieve long-term potentiation, becoming more sensitive to each other and more ready to fire in the exact same way later on in the future. They're a physical thing in your brain firing together more easily because you strengthened that pattern of firing. You memorized. This branching forest of firing friends looks messy, but look closer. It could be the memory of your first kiss, a living souvenir of the event. If I were to go into your brain and cut out those cells, could I make you forget your first kiss? Or could I make you forget where your fingers are? Only if I cut out a lot of your brain, because memories aren't just stored in one relationship, they're stored all over the brain. The events leading up to your first kiss are stored in one network, the way it felt or the way it smelled in different networks, all added up together, making what you call the memory of your first kiss. How many memories can you fit inside your head? What is the storage capacity of the human brain? The best we can do is a rough estimate, but given the number of neurons in the brain involved with memory and the number of different connections a single neuron can make, Paul Reber at Northwestern University estimated that we can store the digital equivalent of about 2.5 petabytes of information. That's the equivalent of recording a TV channel continuously for 300 years. That's a lot of information. That is a lot of information about skills you can do and facts and people you've met, things in the real world. The world is real, right? How do you know? It's a difficult question, but it's not rocket science. Instead, it is asking whether or not rocket scientists even exist in the first place. The theory that the sun moved around the Earth worked great. It predicted that the sun would rise every morning, and it did. It wasn't until later that we realized what we thought was true might not be. So, do we, or will we ever know true reality? Or are we stuck in a world where the best we can do is be approximately true, discovering more and more useful theories every day, but never actually reaching true, objective, actual reality? Can science or reason ever prove convincingly that your friends and YouTube videos and your fingers actually exist beyond your mind? That you don't just live in the Matrix? No. Your mind is all that you have. Even if you use instruments like a telescope or particle accelerators, the final stop for all of that information is ultimately you. You are alone in your own brain, which technically makes it impossible to prove that anything else exists. It's called the egocentric predicament. Everything you know about the world out there depends on and is created inside your brain. This mattered so much to Charles Sanders Peirce that he drew a line between reality, the way the universe truly is, and what he called the phaneron, the world as filtered through our senses and bodies, the only information we can get. If you want to speak with certainty, you live in, that is, you react to and remember and experience your phaneron, not reality. The belief that only you exist and everything else, food, the universe, your friends, are all figments of your mind, is called solipsism. There is no way to convince a solipsist that the outside world is real. And there is no way to convince someone who doubts that the universe wasn't created just 3 seconds ago, along with all of our memories. It's a frightening realization that we don't always know how to deal with. There's even the Matrix defense. In 2002, Tonda Lynn Ansley shot and killed her landlady. She argued that she believed she was in the Matrix, that her crimes weren't real. By using the Matrix defense, she was found not guilty.
by reason of insanity, because the opposite view is just way more healthy and common. It's called realism. Realism is the belief that the outside world exists independently of your own phaneron. Rocks and stars and Thora Birch would continue to exist even if you weren't around to experience them. But you cannot know realism is true. All you can do is believe. Martin Gardner, a great source for math magic tricks, explained that he is not a solipsist because realism is just way more convenient and healthy, and it works. As to whether it bothered him that he could never know realism was true, he wrote, "If you ask me to tell you anything about the nature of what lies beyond the phaneron, my answer is, how should I know? I am not dismayed by ultimate mysteries. I can no more grasp what is behind such questions as my cat can understand what is behind the clatter I make while I type this paragraph." Humble stuff. What strikes me is the cat. Cats do not understand keyboards, but they know that keyboards are a fun place to be. It's a great way to get the attention of a human. They're warm and exciting, surrounded by noises and flashing lights. Plus, cats love to get their scent on whatever they can, a mark of their existence. We aren't that much different, except instead of keyboards, we have the mysteries of the universe. We will never be able to understand all of them. We won't be able to ever answer every single question, but walking around in those questions, exploring them, is fun. It feels good. And as always, thanks for watching. Do you want more unanswered questions? Well, you're in luck. Today, 9 other amazing channels on YouTube have made videos about questions we still haven't fully answered. All Time 10s has organized them, and to watch them all, click the annotation at the end of this video or the link at the top of the description. Enjoy. Hey, Vsauce, Michael here. Gravity is a property of matter, anything with mass. This includes the moon, Earth, Jupiter, the sun, and even you, your body. In fact, if you kind of like somebody, have them stand 3/4 of a millimeter away from you. At that distance, cumulatively, every atom in your body and every atom in their body will draw you two together with the same gravitational force that the sun is exerting on you right now. Of course, we don't feel either of those forces because compared to the gravitational influence of the Earth, they are basically nothing. You don't need to concern yourself with the gravitational attraction between you and someone you're hugging, or your individual body and the sun 150 million kilometers away. In fact, the sun may as well not exist. What if the sun disappeared? Well, to be sure, it's not going to happen. The sun will die billions of years from now by expanding, boiling off our oceans, and swallowing the Earth whole. The sun is not going to simply disappear. Matter and energy don't vanish. Of course, matter can quantum tunnel to different locations, but on the scale of the sun, there is not enough time in the lifetime of millions and billions of universes for such a probability to even be worth discussing. But let's discuss it anyway, as a thought experiment, to determine how the Earth would get along with no sun. What will the Earth do and what can it do alone? At the exact moment that the sun disappeared, we would have no idea, because it takes light from the sun 8 minutes and 20 seconds to reach Earth. So for a little over 8 minutes after the sun disappeared, we would have no idea. Once we did, confusion and mass panic would most likely ensue. The sun's gravitational grasp on our planet would also take 8 minutes and 20 seconds to end. This is because gravity waves propagate at the speed of light. So, the very moment we saw our sun disappear, we would also lose its gravitational influence, and Earth would fly out in a straight line tangent to wherever it was in its orbit. The finite speed of light and gravity mean that as panic and fear spread across the Earth at the loss of our sun, we could still, for a while, look up into the sky and see our planetary buddies further out, continuing to operate as if nothing had happened. For instance, Jupiter would continue orbiting and reflecting light from a sun that no longer existed for about 30 minutes after Earth already knew the sun was gone. And depending on where Jupiter was in its orbit, it would take another 30 minutes to an hour for us to watch the reflected light of Jupiter snuff out. With no moonlight or sunlight, the universe itself would be our only source of visible light from space. In 2004, Abdul Ahad calculated that the Milky Way contributes about as much light as 1/300th of a full moon. So there would be enough light from space for us to see around a bit. But of course, electricity and fossil fuels would still be usable for a while, so cities and towns could continue to be lit by man-made sources, just like a typical night. Except it would be night everywhere. Photosynthesis would stop immediately, and this is huge. I had a great discussion about this video with Henry from Minute Physics and the new channel, Minute Earth. If you're not subscribed to Minute Earth, you definitely should be. In one of his episodes there, he mentions that 99.9% of the natural productivity on Earth is done by photosynthesis, which requires the sun. Without the sun, plants would no longer be able to inhale carbon dioxide and exhale life-sustaining oxygen. But don't worry. Collectively, all of us humans, all 7 billion of us, breathe in about 6 trillion kilos of oxygen every year. But our atmosphere contains a whopping quintillion kilos of oxygen. So even without photosynthesis, and including all of the other animals and insects and microorganisms that consume oxygen, it would take us thousands of years to run out. The poor plants themselves would be much worse off. Without the sun, most of them would die within days or weeks. Except for large plants. Giant trees, for instance, contain enough sugar for energy that they could technically live in the dark for years. Their problem is going to be that the Earth will get quite cold. In fact, mighty trees would freeze to death, their blood, the water and sap inside them solidifying, way before they died of starvation. Right now, with our sun, the average surface temperature on Earth, hot places and cold places in different seasons all considered, is an arguably comfortable 14 to 15 degrees Celsius. Without the sun to add energy, the Earth would radiate away heat exponentially, meaning it would go fast at first and then happen more and more slowly. By the end of the first week without the sun, the average surface temperature across Earth would be freezing, 0 Celsius, 32 degrees Fahrenheit. Now, temperatures like this happen all the time on Earth. We're used to it. Panic and fear and looters and anarchy aside, for the first few days or months, we could get by. But by the end of the first year without the sun, the average global surface temperature would be negative 73 degrees Celsius, negative 100 Fahrenheit. The best option, really, would be to move to geothermal areas like Yellowstone or Iceland. These places would be the few safe havens for human life after the sun. Nearly all life on Earth exists because of and is dependent upon extraterrestrial energy, the sun. But the Earth produces its own heat. Despite floating in the coldness of space for billions of years, down below the crust, the Earth is quite warm. 20% of this warmth came from the fact that when the Earth formed, mass crushed so tightly in the middle that the pressure liquefied rock. The other 80% of Earth's internal heat comes from the fact that deep in its core, radioactive elements decay, providing the energy needed to keep the Earth's core at 5,000 degrees Celsius. Anyone who failed to secure a position within one of these bastions of warmth or perhaps underground in a community warmed and powered by nuclear fuel, would likely be dead within the first year of no sun. In the next 10 or 20 years, things would start to get wet with dew. But not with glorious water droplets, instead, droplets of liquid air. The air would literally become cold enough for the gases that make it up to condense, or form clouds and precipitate, first as rain, and then as it got colder and colder, eventually as snow. In Fritz Leiber's famous science fiction short story, A Pail of Air, this has already happened. The Earth was ripped away from the sun, and in order to survive, a family must go outdoors in a special suit and scoop up a pail of just the oxygen snow, bring it back in, and place it over a fire to warm and allow them to breathe. A year or so after the sun disappeared, Earth's oceans will have frozen over, ice all the way across. But ice is less dense than liquid water, which means that ice floats. And ice is a pretty decent insulator. So, for billions of years after the sun disappeared, liquid water could still exist at the bottom of our oceans, protected and insulated from space by miles of ice above it, and warmed by vents on the ocean floor that spew water out, superheated by Earth's interior. This would continue on Earth for a very, very long time, sun or no sun. Instead of becoming frozen and lifeless, extremophiles, like microbes that live around hydrothermal vents deep in the ocean, would be fine. They live deep in the ocean, far below the point where sunlight can penetrate, and they make energy not through photosynthesis, but via chemosynthesis, converting heat and methane and sulfur into the energy they need. They are then eaten by clams and tube worms. Extremophiles deposit minerals back into the vents, meaning that their food chain is complete. It's a circle. It's independent of the sun. Earthlings like them would thrive if the sun were to disappear. They would live just fine without ever knowing that the sun was gone, or honestly, without ever even knowing it existed in the first place. It's amazing to think that life here on Earth, all alone, flying through space with no sun, would kind of be fine. Far from becoming a frozen dead rock or a boring dormant seed, the Earth would be a spaceship carrying living passengers with enough geothermal heat for billions of years of life. If the sun disappeared, spaceship Earth would fly out in a straight line, covering about 30 kilometers every single second. After just 1 billion years, it will have covered 900 quadrillion kilometers, or about 100,000 light years, a trip that could potentially take it all the way across our galaxy, near thousands of stars, and nothing's to say it couldn't fall into orbit around one, thaw out, and allow its still living extremophiles to proliferate life on Earth all over again. Maybe one day developing life intelligent enough to uncover whatever is left of our lives. Maybe they could even find this very video. In which case, hi, you're welcome for this video about your planet's history and journey. And as always, thanks for watching. Hey, Vsauce! Michael here. A few years ago, in Minneapolis, an angry dad stormed into the retail store Target. His daughter, a high schooler, had been receiving coupons in the mail from the store for things like cribs and diapers. Was Target encouraging his daughter, a minor, to go out and get pregnant? Well, the store apologized, but a few days later they heard back from the father. He told them A few things have been going on in my household I was unaware of. My daughter is due in August. I owe you an apology. You see, Target's internal algorithms had been tracking and processing his daughter's purchases, and recently she had started buying different items than usual, things like certain vitamin supplements and scent-free soaps and lotions. Behaviors the system flagged as evidence she could be pregnant. Thus, they sent her the coupons. And they were right. Without being told, Target knew that a girl was pregnant before her own father. We are tracked and followed digitally now more than ever before. We live in a world of 24/7 CCTV, browser cookies, trackable debit cards and cell phones and GPS, fingerprinting and DNA analysis. But despite all of that, every single year in the United States alone, more than 2,000 people disappear and are never found again, dead or alive. Where do missing people go? How do they disappear? What if you disappeared? And how do you know you haven't already disappeared? In many cases, missing persons are the victims of unsolved or unknown crimes. They may have suffered accidents or taken their own lives, and their bodies were never found. Or they may be perfectly fine and have simply escaped their old life, old friends and family, old debt and obligations, to start a new life somewhere else, possibly as someone else. How long would it take for people to notice if you disappeared? Well, think about it. I mean, it sort of depends on who you are, how you live, and how you disappeared. In most jurisdictions, after about 5 to 7 years, if no one has heard anything from you at all, you can be declared dead in absentia. This is what happened to French astronomer Guillaume Le Gentil. In the 18th century, hundreds of people traveled far and wide to observe the transit of Venus from different locations on Earth. They knew that by comparing their measurements, they could calculate more accurately than ever before just how far away the sun was. So, Le Gentil left Paris in 1760 for Pondicherry in India. But after a storm blew him off course and the British-occupied Pondicherry, he was forced to spend the day of the transit on a boat at sea, which rocked too much for accurate measurements to be taken. Now, the next transit would happen in 8 years, but after that, the next transit wouldn't happen for another 100 years. So he stuck around. He didn't return to Paris. Instead, he built an observatory and waited. When he finally returned to Paris 11 years after leaving, he found that he had been declared dead. His wife had remarried, his family had plundered his belongings, and his position at the Royal Academy of Sciences had been given to someone else. He never did see the transit of Venus, by the way. On the day that it happened, the sky above him was overcast. We know the human population of Earth. Kind of. Population figures and counters are only estimations. Individuals are best accounted for by real people in their real lives. But that doesn't always happen. Earlier this year, Janet Veal passed away in her apartment in Ringwood, Hampshire. Large portions of her body were eaten by her pet cats before she was discovered weeks later. And 7 years ago, Joyce Carol Vincent was found dead on her sofa in Wood Green. Or at least her skeleton was found. She had been dead for at least 3 years, and no one ever checked on her. Her television was still on. And 4 days after Timothy McVeigh bombed a federal building in Oklahoma City, taking 168 lives, a severed left leg was found in the rubble. No one knew who it belonged to. the legs of all the other victims had been accounted for, and no one else had been reported missing. DNA analysis showed that the leg belonged to Lakesha Levy, but she had already been buried with both her legs. So they dug up her corpse. She had been buried with someone else's left leg. The legs were swapped, but because her body had been embalmed, DNA in the unknown leg could not be analyzed. To this day, no one knows who that leg belongs to. The 169th victim remains a mystery. Some conspiracy theorists argue that the leg may have belonged to the actual bomber, someone besides Timothy McVeigh who was close enough to the explosion to be obliterated completely except for one leg. Regardless, what it does show is that it is possible for a person to disappear without anyone ever asking where they went. Sometimes people are reported dead or missing even when they aren't. Premature obituaries are common. Many living people already have one on file. If a famous person dies, the media, television, newspapers, magazines, well, they need a full story as soon as possible, so they prepare them ahead of time, locked away, leaving only the dates and circumstances of the death to be filled in. Makes sense, but it's awkward when they leak before the person's dead. In 2003, CNN's website accidentally carried draft obituaries for living people that could be accessed. It's embarrassing, but for the person reading their own obituary, it's a chance to do something that most of us never get a chance to do. See how you will be remembered after you're gone. Alfred Nobel invented dynamite. He made a fortune manufacturing and selling deadly weapons, cannons, and armaments. In 1888, his brother Ludwig died, but many newspapers mistakenly thought that he had died and published obituaries for Alfred Nobel. They weren't very flattering. One French paper declared, "The merchant of death is dead." Nobel read these obituaries and was so ashamed by what his legacy apparently was going to be. When he did die, he left almost all of his money to the cause of celebrating humanity. He created the Nobel Prize. Marcus Garvey wasn't so lucky. The story goes that after suffering a stroke, newspapers ran premature obituaries that were critical of him, saying he died broke, alone, and unpopular. Shocked by how negatively he was being remembered, Garvey suffered another stroke while reading his own obituary and died. In April of 2006, 5 Taylor University students died in a tragic car accident. Another student survived but was in a coma. She was identified as Laura Van Ryn. Her friend, Whitney Sierick, wasn't as lucky. She was pronounced dead. 1,000 people attended her funeral. But over the next few days, as Laura recovered, she began speaking. And when asked her name, Laura said, "My name is Whitney." The girls looked similar. It turned out Laura was the one they had buried. Later, Whitney was married in the very same church that years before had held her funeral. What if you are already missing and just don't know it? It's not known how often hospitals accidentally switch babies at birth. Modern hospital policies make it unlikely to happen, but because we don't all go out and get maternity and paternity tests for fun, there isn't a lot of data on the phenomenon. But it does happen. It's often discovered because of DNA tests administered to resolve child support disputes. Or, in the case of a 35-year-old woman in the Canary Islands, it's because in 2001, an employee at a store you were shopping at mistakes you for her best friend because you look exactly like her. Because she is your long-lost twin, separated from you since birth. And the sister you grew up with thinking was your twin turns out to be a biological stranger. What if you are missing, but the authorities don't know. Such is the life of the unreported missing. People in a country illegally, people estranged from their family and friends with no missing person report ever being filed, children of homeless mothers. These people aren't just missing, they are what is known as missing. The FBI's National Crime Information Database contains approximately 50,000 reported missing children, but Outpost for Hope reports that there are more than 1 million children in America who are missing without anyone knowing they're missing. It is not against the law to go missing under your own volition. You might have debts to pay or contracts to honor, but if you are an adult, the act of disappearing is not illegal in and of itself. You have the right to go missing. But believing that no one would miss you? That is ridiculous and unscientific. Statistics would suggest otherwise. David Wong wrote one of the most powerful articles I've ever read. There is a lot of information out there. There's even a word for it, infobesity. It takes a lifetime to even experience some of it. It's easy to think that everyone knows everything that you know, but every year, more than 100 million new people are born, and not a single one of them is born knowing that they are made out of atoms, or that black holes are awesome. Someone needs to be there to tell them, to show them. How many jokes do you hear every day, every week? How many jokes do you hear every year? Here's a fun thought. By considering average life expectancy and the typical number of jokes a person hears in a year, David Wong posited a thought, rough in its approximation but sharp in its essence. If you are under the age of 38, odds are the funniest joke you will ever hear is a joke you haven't even heard yet. And if you are over the age of 38, odds are you already know a joke that to more people than you could ever possibly meet might be the funniest joke they will ever hear. So wherever you are, we're glad you're there. And as always, thanks for watching. Hey, Vsauce, Michael here. 10 centimeters, about 4 inches. This is how much taller, on average, people are today than they were 150 years ago. Better nutrition and medical care early in life has allowed us to better take advantage of the blueprints within our genes. Blueprints that carry plans for just how big a healthy human being can get given an optimal environment. In terms of height, those plans rarely exceed 7 feet 6 inches. But individuals with endocrine disorders, for instance a tumor near the pituitary gland in the brain, can experience growth that occurs more rapidly and for a longer period of time than usual. For instance, Igor Vovkovinsky, who at 7 foot 8 inches is the tallest man currently living in America. The tallest living person anywhere on Earth is Sultan Kosin, who at 8 foot 3 inches tall also holds the Guinness World Record for largest hands and feet. But the tallest person ever officially recorded was Robert Wadlow. He was the size of an average adult male when he entered kindergarten at the age of 5. When he died in 1940 at the age of 22, he was 8 foot 11 inches tall. Andre the Giant was 7'4". And this is me holding a 12-ounce can. Here's Andre doing the same. Human size variation is fascinating. But what's the maximum? Biologically, how big can a human get? And more importantly, how big are you really? It turns out that today, now in history, average human height is probably quite near
the genetic limit. By manipulating the very genes responsible for height, we may be able to add an extra 15 centimeters or so to that average, but beyond that, we are likely to hit a ceiling. In order to regularly produce people over 8 feet tall, 2.44 meters, those people would probably need to be a different shape, not human-shaped. This is because of the square cube law. As a shape grows, say taller, its volume increases at a greater rate. Take a look at this cube. If we make it 10 times larger, well, sure, it's 10 times as tall, but the area covered by its faces is 100 times larger, and its volume, the space within it, is 1,000 times larger. Now, since weight is connected to volume, this cube only has 100 times the cross-sectional area to support itself, but 1,000 times the weight to support. So if you were 10 times larger and still shaped like a person, that is, your proportions were the same as they are now, you would need to either have a skeleton made out of something stronger than bone, or bones that were monstrously thick, like way out of proportion. But even if you solved the bone and muscle strength problem, there would still be a whole host of other issues. For instance, your heart wouldn't scale up fast enough to keep blood pumping throughout a body that large. Animals can get that big because their proportions and organs are quite different. Chris Howard from Earth Unplugged tipped me off to the giant, not human proportioned legs of the largest land animal ever, known to have existed with the certainty of a complete skeleton, the awesomely named Giraffatitan. Discovered in Tanzania and now mounted in Berlin's Humboldt Museum, it probably weighed 20 to 30,000 kilograms. The Brouhathkeosaurus may have been even larger, but this is controversial because we only have a few of its bones. Estimates put this guy at 140,000 kilograms. Any larger than that, and in order to survive long enough to reproduce, an animal would need more buoyancy to counteract its weight than air can provide. This is one of the reasons blue whales love the water so much. The heaviest blue whale ever measured by NMML weighed in at 177,000 kilograms, making it the heaviest animal we are aware of that has ever existed. It might be the heaviest possible because animal size is limited by simple geometry and the gravity of our planet. Theoretically, humans born on Mars could grow a few inches taller because gravity there is only 1/3 of what it is on Earth. The trade-off, of course, being that their bones and muscles wouldn't grow strong enough for them to ever visit Earth and enjoy it. The point is, in order to have the same shape and proportions that we have now, we can't really get that much bigger. Some of the higher estimates of the upper limit of average human height are around 7 feet tall. A person who is more than 9 feet tall would struggle to move around, and up in the 12 to 15 foot range, it would be difficult to live very long at all. But what does size mean? Where do you really begin and end? So far, we have been measuring people using their rigid boundaries. It's a good one to use, it's very common, but of course, when I speak, I can fill an entire room. And when I shout, I can fill city blocks. That's huge. Of course, my voice is not a part of my physical body. It's not part of the matter that fits within my skin container. But it's relevant to the question of how big a person is. How large of an impact on their environment can a person have using what comes directly from their bodies? Well, Guy Murchie illustrated this quite well in his tome, The 7 Mysteries of Life. The little solid dogs are small, but their sound and smell extend into shapes and sizes no creature could even dream of filling up with their bodies on Earth. Let's begin with sound. How far can your loudest shout travel? How much bigger are you
the volume of space within which people are aware that you exist when you shout. Well, the loudest shout a human can make is about 88 decibels from 30 centimeters away. A shout like that will die out down below the threshold of human hearing in our atmosphere after traveling about 5 kilometers, or 3 miles. A person standing downwind from you might be able to make you out a little further than that, but the point is, in space, no one can hear you scream. And on Earth, from 5 kilometers away, no one can hear you scream. But could they see you scream? Really, could they see you at all? Well, on the surface of Earth, the furthest you can see another person is the horizon. If you and another person are standing on the ground, that distance is about 5 kilometers, or 3 miles. Any further away than that, and you will literally be hiding behind the curvature of the Earth. So what about in, say, outer space, where moving away from another person doesn't mean eventually hiding behind the Earth? Well, as an object moves farther and farther away, it becomes smaller and smaller. Of course, the actual size of the object doesn't change. What does change to you is its angular size. This brilliant measurement describes how much space in your visual field an object takes up. Imagine your visual field as a complete circle, 180 degrees of which go from the horizon in front of you to the horizon behind you. So an object with an angular size of 90 degrees would have to be big enough and close enough so as to take up all the space from the horizon to right above you. Interestingly, your thumb, held at an arm's length away from your face, takes up about 1 degree of your visual field. Its size is 1 degree. The moon takes up about half a degree at all times. It sometimes appears larger at the horizon, but that's because of an illusion that ASAP Science covered really well. The smallest angular size we can see with the naked eye is about 1 arc minute, a 60th of a degree. But given enough contrast, we can see things like sunspots, a mere 20 arc seconds across, a third of a 60th of a degree. Plugging in numbers to do the math will tell us that with perfect conditions, outer space, no air, no obstructions, a lot of contrast because you are wearing bright white, the farthest away a person could see you with their naked eye would be about 10 to 15 kilometers. Any further away than that, and they will have passed the edge of your naked eye visibility existence. But, do you smell that? It might be you. If we consider the senses of other animals, your smell, your scent, might be your largest earthly dimension. You know how animals like cats and dogs have those cute little wet noses? It's called a rhinarium. Rhinariums allow mammals to smell really, really well. They don't just pick up molecules that float by, they localize them. Air cools the wet nose, allowing the animal to tell the source of the smell. It's the same as when you wet your finger and stick it in the air to tell the wind's direction. A bloodhound can pick up and trace to you a scent trail that is days old, making your scent imprint on the earth about as large as you can move in a couple days. But the silver-tip grizzly has a sense of smell that is 7 times stronger than a bloodhound. These guys can smell things from 18 miles away, nearly 30 kilometers. That's probably the largest bubble we could draw around you and still call you, because it contains things that you emitted that can be traced back to you by other living things. But if we include everything you emit, well, fundamentally, we're limited to the edges of Earth's atmosphere. Because with the exception of a few light molecules, hydrogen, helium, which escape into space, not much else leaves. There's no medium in space for your sound and smells to travel through. Which brings us back to light. The human body emits light, electromagnetic radiation. Most of it is infrared light, heat, but some of it lies within the visible spectrum, though it's about 1,000 times dimmer than the dimmest light the eye can see. It seems that what little visible light you do emit is tied in some way to your circadian rhythms, meaning that around 4 p.m. every day, you are literally visibly the brightest you will be all day. But here's the thing about light, about electromagnetic radiation. It doesn't need a medium to travel through. It just keeps going out into and through space. Which of course brings us to Australia. If you're not subscribed to Derek's channel Veritasium, I don't know what you're doing with your life. It is amazing, and he recently made a video that I have not been able to stop thinking about. The smallest possible piece of light is a photon, and the human eye can kind of perceive individual photons a bit better than chance, but some frogs can see individual photons quite well. Now, in his video, he explains that as you move away from the sun, its angular size gets smaller and smaller and smaller until eventually you're so far away from the sun that you can no longer see it. But it's still there, and it is still emitting light that can reach your eye. Except now, that light has been spread so thin, it's not big packets of light you can see, it's just individual photons. The sun is still there, it's just less frequent. Sometimes a photon hits your eye, sometimes nothing, and sometimes a photon again. Well, the same thing happens to radiation emitted by you. I Skyped with Derek this afternoon, and he calculated that the human body, seen at a distance of 168,000 kilometers, would also be reduced to merely a few individual photons. Further than that, and your size would no longer get smaller. It would just remain individual photons flying through space. They are, after all, indivisible. So your physical size is limited by geometry and biology and gravity. Your vocal and fragrance size can be bigger, but it's still limited by the size of Earth. But your light, your personal glow, isn't really bounded by anything. The photons that you are emitting right now, the ones that don't get absorbed by anything, have no reason to ever really stop, and they can continue conceivably past even the observable universe, making you, in a way, completely huge and kind of immortal. And as always, thanks for watching.
Hey, Vsauce, Michael here. Let's take a moment to recognize the heroes who count. Canadian Mike Smith holds the world record for the largest number counted to in one breath, 125. But the world record for the largest number ever counted to belongs to Jeremy Harper from Birmingham, Alabama. In order to set the record, Harper never left his apartment. He got regular sleep, but from the moment he woke up in the morning until the moment he went to bed at night, Harper did nothing but count. He streamed the entire process over the internet and raised money for charity while doing it, but after 3 months of counting all day, every day, he finally reached the world record, 1 million. Now, a million might not sound like a lot, but think of it this way. 1,000 seconds is about 17 minutes, but 1 million seconds is more than 11 days, and 1 billion seconds, well, that's more than 31 years. There's no full video online of Harper counting all the way to 1,000,000, but you can watch John Harchick count all the way to 100,000 if you have 74 hours to spare. John also has some other channels. One involves more than 300 videos of himself eating carrots. Another, more than 3,000 videos of himself drinking water. Many of John's videos literally have no views. They are as lonely as a video on YouTube can get. A great way to find such videos is a website made by Jan Vanderkruisen. This website autoplays videos on YouTube that no one has yet watched. John and Jeremy, as well as Mike, the one-breath counter, counted like this. 1, 2, 3, 4, 5, 6, 7, and so on. But that's not the only way to count, and it doesn't seem to be the one we're born with. Additive counting is the one we're all familiar with, where each next step is just one added to the last. But what if we multiplied by a number instead? Well, that kind of counting is logarithmic, from arithmos, meaning number, and logos, meaning ratio, proportion. On this scale, similar distances are similar proportions. 1 is a third of 3, and 3 is a third of 9. 4 is a third of 12, and so on. Our brains perceive the world around us on a logarithmic scale. It's believed that almost all of our senses are multiplicative, not additive. For example, how loud we perceive a sound to be. Two boomboxes playing at the same volume don't sound twice as loud as one. In order to make a sound that is perceived as being about twice as loud as one boombox, you actually need 10 times as many, so 10. And to double that loudness, you would need 100. And to double that loudness, you would need 1,000. Having an intuitive sense of logarithmic scales built into your brain is probably an advantage when it comes to natural selection and survival, because often proportion matters more than absolute value. For example, is there one lion hiding over there in the shadows, or two? Is a very different question than, are there 96 lions about to attack us, or 97? Sure, in both cases I'm just talking about one extra lion, but adding one lion to one lion doubles the threat. Adding one lion to 96, well, that's basically nothing. Logarithmic thinking and feeling may explain why life seems to speed up as we get older. It seems like I was a child forever, and then college in my early 20s just whizzed by. And logarithmically, that makes sense, because each new year that I live is a smaller fraction of all the other years I've already lived. When you turn 2 years old, the last year of your life is half your life. But when you turn 81, that last year that you've lived, well, that's just a tiny part of the other 80 that you know. Logarithmic thinking isn't always helpful, especially in scenarios where proportion doesn't logically matter, but we nonetheless act like it does. One of my favorite examples is the psychophysics of price paradox. This is something almost all of us do. Research has found consistently that people are willing to put a lot of effort into saving $5 off a $10 purchase, but they won't put much effort into saving $5 off a $2,000 purchase. It's $5 saved either way, but our natural obsession with proportion leads us astray. Take a look at these pictures. Can you tell how many objects are in each of them? You probably can. It's like really easy. You can tell if there are 0, 1, 2, 3, or 4 objects in a photo without even needing to count. How are you doing that? Is it some sort of sixth sense? No. Psychologists call it subitizing. We can intuitively at a glance determine whether there are about 4 or fewer objects in a photo. This has been part of human culture for a very long time. And it may be the reason so many tally systems from all over the world, all through history, wind up having to do something different when counting the number 5. When estimating or comparing amounts above 4, the brain uses what's known as an approximate number system. It's a psychological ability we have that's about 15% accurate. If two amounts are at least 15% different, we can tell. So, for example, 100 objects and 115, or 1,000 and 1,150 or 1,200. If you want to test the accuracy of your approximate number system, Panamath has a pretty good test. We often take linear additive counting for granted, but it's not granted to us. We aren't born with it. We are, however, born with the ability to subitize and use an approximate number system. Children younger than the age of 3 can tell without counting that this line of 4 coins contains fewer coins than this line of 6, even if you spread the 4 coins out into a line that is physically bigger, longer than this line of 6. However, mysteriously, around the age of 3.5, children lose this ability and begin saying that this line of 6 coins contains fewer coins than this long line of just 4 coins. Possibly because around this age, the physical world of objects of physical sizes is more salient in their minds. But then, when they begin to learn linear counting, they reverse back and begin again correctly saying that this line of 6 contains more coins than this line of 4, around the age of 4. The smallest physical thing science could ever hope to observe is the Planck length. In order to look at anything smaller, you would need to have so much energy concentrated in such a small area, a black hole would form and you would lose whatever you were looking at. Okay, with that in mind, here's a question. What number is halfway in between 1 and 9? 5 seems like the obvious answer. There are 4 numbers on either side of 5, it's halfway between, right? Well, if you ask this question of a young child or a member of a culture that doesn't teach a linear additive number line, their answer will be 3. You see, they are exhibiting the human mind's natural logarithmic tendency, because 3, in that sense, makes sense. 3 is 3 times larger than 1, and 9 is 3 times larger than 3. 3 is in the middle, proportionately. But what if we took that logarithmic number line and changed the 1 to be the smallest thing we can observe, the Planck length, and the 9 to be the largest thing we can observe, the observable universe? What would go in the middle? Well, as it turns out, we would. The number of Planck lengths you could stretch across a brain cell is equal to the number of your brain cells it would take to stretch all the way across the observable universe. So, welcome to the middle. And as always, thanks for watching. Hello again. The YouTube channel Field Day recently gave me an opportunity to explore Whittier, Alaska, one of the strangest places humans call home. To see why and to see me investigate and talk to the locals, click the link in this video's description or on the annotation here on this video. It was really fun, so give it a little looky look. Hey, Vsauce, Michael here. This symbol, commonly called a yin-yang symbol, is a taijitsu, meaning diagram of the supreme ultimate. The principle of yin and yang, opposites existing in harmony, is associated with ancient Chinese philosophy, but the very first use of the iconography, the classic symbol, actually comes from a shield pattern used by the ancient Romans, 700 years before its first known use in China. A connection between the two has yet to be found. Regardless of who came up with it first, the symbol was a bright idea. But what's the brightest object in the entire universe? Well, apparent magnitude, commonly used when stargazing, refers to how bright an object appears to us, say when looking up from Earth. It depends on Earth-centric factors like how close the object is to our planet. Magnitudes are logarithmic and arranged like golf, where a smaller number means a greater brightness. But today, I'm looking for absolute magnitude, a measure of how bright things all over the universe, near and far, would be if we looked at them from the same distance. Absolute magnitude will guide us to the most blinding light in the universe, irrespective of it looking faint to us here on Earth just because it's far away. The difference is significant. A 100-watt light bulb placed closer than 8 centimeters, about 3 inches from your eye, will appear brighter than the sun in the sky.
But that's not fair. If you could see the sun and the bulb from the same distance, the sun would be a septillion times brighter. That's bright. But the sun shines punily compared to the rest of the cosmos. If you could line the sun up with everything else out there, giving every star and cosmological phenomenon a fair chance, the sun's absolute magnitude would be 4.8. Not bad, but check out R136A1. This nuclear-fueled beast isn't the biggest star in terms of volume, but it's 256 times more massive than our sun. It's the most massive star ever found, and it's also the brightest. Remember that lower absolute magnitudes are brighter. R136A1 isn't 4.8 like our sun. It is negative 12.6, which means it is 8.7 million times brighter than our own sun. But R136A1 isn't the brightest thing out there. When a giant star dies, it explodes violently in what is known as a supernova or hypernova. As I mentioned in my video, How Hot Can It Get?, supernovas can eject terrifying flashes of radiation known as gamma ray bursts, arguably the brightest electromagnetic events in the universe. A typical gamma ray burst releases as much energy in a few seconds as our sun will release all together in its entire 10 billion year lifetime. If WR104, a gamma-ray burst future candidate, directly struck Earth with such a beam for only 10 seconds, astronomers predict it could deplete 25% of our ozone layer and lead to mass extinction and starvation. The largest thermonuclear bomb ever detonated didn't do anything close to that, and it was exploded right here in our atmosphere. Whereas WR104 is 8,000 light years away. You can't even see it with your naked eye or a pair of binoculars. But gamma ray bursts are merely brief events lasting only a few minutes at most, sometimes just a matter of milliseconds. If you want the brightest, sustained thing, you'll paradoxically have to look at the darkest thing: black holes. To be fair, dark matter is ostensibly darker, but because dark matter has been hypothesized to not even interact with light, with electromagnetism at all, calling dark matter not bright is kind of like calling your peanut butter sandwich a not fast airplane. It's not really even the same category. Black holes, however, do interact with light, reflecting so little, well, they don't let any escape, at least not in a form resembling the way it came in. That's dark. But the intense energies created by black holes in the process of eating things like stars is anything but dark. Gas and debris from the stars they eat swirl into archipluvian cosmic gallows known as accretion disks before making their final death plunge into the black hole. In the disk, debris spins at unfathomable speeds, pulled around by a black hole billions of times more massive than our sun. Friction in the accretion disk generates heat on a level difficult to fully appreciate. Just as hot things glow, the disk does too, so brightly it has its own name: a quasar. Quasars shine thousands of times more brightly than even the brightest stars. I'm kidding. It's scarier than that. Quasars shine thousands of times more brightly than galaxies containing billions of stars. The first identified quasar, 3C273, has an absolute magnitude of negative 26.7, making it 4 trillion times brighter than our sun, about 100 times more luminous than the total amount of light produced by the entire Milky Way. If you put 3C273 33 light years away from us, it would shine as brightly as our sun, a mere 8 light minutes away. Blocking the brightness of a quasar with a coronagraph reveals that quasars exist in the centers of galaxies that are larger than them in area, but are nonetheless drowned out by their light. Such galactic centers are called active galactic nuclei, the bulk of their energy spewing forth in the form of a powerful radiation jet, the length of which puts even our solar system to shame. The visible part of the jet in this photograph, for instance, is so long it could stretch from the Sun to Pluto and back 1.5 million times. Now, specifically, if a large portion of this ejected energy heads toward Earth, it's responsible for what we call a quasar. But if Earth is right in the active galactic nucleus's sights, it's got a scarier name, a blazar. And it's blazar 3C454.3 that clocked in the greatest brightness ever observed. At historically high levels of activity, it registered an absolute magnitude of -31.4. To put the brightness of quasars in yet another perspective, take a look at the 100,000th picture snapped by the Hubble telescope. This is a star a few hundred light years away, and this thing looks just about as bright, but it is a quasar 9 billion light years away. Why are quasars so far away? Well, a quasar is not forever. They are billions of light years away, which means the light we receive from them, the pictures we take of them, are pictures of things happening billions of years ago. They represent a phenomenon more common early in the universe's history, when monster black holes hadn't eaten all the stars around them to fuel their accretion disks, and before those holes became too fat to be active. Neil deGrasse Tyson points out that in order to remain a quasar producer, a black hole must consume about 10 stars a year. Many consume more than 1,000 stars a year, 600 Earths worth of matter every single minute. The more stars a black hole consumes, the larger its event horizon becomes, until eventually it no longer shreds stars apart to fuel an accretion disk. Instead, it just swallows them whole in one dimmer but still terrifying gulp. Quasars are some of the most ancient things in our universe. If you could teleport instantaneously to one right now, faster than light, it would most likely no longer be burning. What we see are just their ghosts, light that left when they were active, that traveled longer than they could live. But quasars can still be born. They can even be born right here, in fact. In my video, What Will We Miss?, I pointed out that the Andromeda Galaxy is headed our way. In 3 to 5 billion years, it will collide with our own galaxy, the Milky Way, and the collision could rearrange stars near the galaxy's central black holes to be consumed, reigniting a quasar right here in our galactic backyard. Funny enough, right now, very few of us even see Andromeda, even though all you need is your unaided eye. Light from our cities drowns out the night sky like a quasar drowns out its host galaxy. Artist Thierry Cohen mocked up what big cities would look like if all their lights were off and the sky above them could be seen fully. New York, Hong Kong, Shanghai, Tokyo, Los Angeles. It's beautiful and rare. In the 1990s, during a blackout in the city of Los Angeles, a number of residents actually called the police. They were afraid of mysterious glowing clouds hovering above the city. They were seeing our galaxy for the first time in their lives. At night, artificial lights allow us to see what's around us, but we lose what's above us. The brightest places have the darkest, emptiest skies. There's yin and yang again. A Taijitu has actually been lurking in this video the entire time. The brightest things in the universe, quasars, are caused by the darkest things in the universe, black holes. The process that unshackles the most light is caused by the thing that best imprisons it. And as always, thanks for watching. Hey, Vsauce, Michael here. Every cloud has a silver lining. Except nuclear mushroom clouds, which have a lining of strontium-90, cesium-137, and other radioactive isotopes. Upon detonation, atoms are literally gutted and gluttoned at temperatures exceeding that of the surface of our sun. In the 1950s, Harold Edgerton's Rapatronic camera caught nuclear fireballs less than 1,000th of a second after detonation. Using a special magnetic shutter, each exposure lasted only a billionth of a second and captured an otherworldly creature. Its energy vaporizing the metal wires supporting its tower into stringy legs of plasma. Watch the target on the ground. Now, roughly visualized, here is a conventional TNT explosion. Now, on the same spot, a similarly sized bomb that uses nuclear fission. When Little Boy was detonated over Hiroshima, only 1.38% of its uranium actually fissioned. The rest was blown away before that could happen. Which means, as Eric Schlosser points out, the fission of merely 0.7 grams of uranium, that's less than the weight of a banknote, was enough to kill 80,000 people and destroy 2/3 of a city's buildings. When a country has tens of thousands of nuclear weapons ready to go, accidents are a possibility. This was a problem during the Cold War, and it still is a problem. What if there is a fire, or a miscommunication, or a rogue officer decides to set one off? Or what if someone just drops a warhead? How much risk is too much? I asked Schlosser. The acceptable probability of a nuclear weapon accident.
Yeah.
What is it now?
The acceptable probability of the detonation of a nuclear weapon in an accident is 1 in a million. In 2012, the odds of your dying in a commercial airliner accident were about 1 in 40 million. So that's even more remote than the accidental detonation of a nuclear weapon.
There have been oopsie-daisy moments with nuclear weapons on US soil. Luckily, none that resulted in critical mass, but accidents nonetheless, just like when you pee your pants, except your pants are the entire planet and the P stands for plutonium. Eureka comes from ancient Greek, meaning I have found it, and in Eureka, North Carolina, you can find it, a giant sign that says nuclear mishap. On my birth date, the year my father was born, a US B-52 bomber carrying 2 4-megaton thermonuclear bombs over North Carolina tumbled from the sky. A loose lanyard in the cockpit snagged the bomb release switch. Each bomb contained a greater explosive yield than all munitions ever detonated by mankind combined. Lieutenant Jack Revell discovered that only one safety mechanism didn't fail that day. A single low-voltage arming switch remained untouched during the crash, and that one switch is why, he explained in 2011, we don't have a bay where North Carolina is today. The bombs were recovered, mostly. The uranium-rich secondary of one of the bombs was never found. To this day, it remains buried underground in North Carolina. Here's something you can try at home. Build a nuclear reactor. In 1994, a 17-year-old David Hahn attempted to build a nuclear reactor in his mother's backyard in Michigan. It wasn't that difficult. For instance, common everyday smoke detectors contain small amounts of radioactive americium, and old glow-in-the-dark paint contains radium. His reactor never reached critical mass, but it did succeed in exposing his neighborhood to 1,000 times the regular dosage of background radiation. It was declared a Superfund hazardous materials cleanup site, and all of his work was confiscated by authorities and buried in Utah. It didn't end there. In 2007, David Hahn was arrested for stealing smoke detectors from an apartment building. His face was covered with sores believed to be caused by constant exposure to radioactive materials. 3 days after Little Boy was dropped on Hiroshima by the Enola Gay, Charles Sweeney was ordered to drop Fat Man on Kokura. He flew boxcar over the city for nearly an hour with the bomb bay doors open, but it was cloudy. Sweeney couldn't achieve visual confirmation of the target and was forced to go to the secondary target, Nagasaki, where 75,000 people died instead. Kokura was spared because of the clouds. We can build a weapon that mimics the furnace of our sun and the winds of Neptune, but yet we can't predict the weather more than a few minutes ahead of time. During World War II, Japanese soldiers fought for their emperor in ways that made Allied troops speechless. Kamikaze planes and torpedoes driven by a single pilot lost after use. When outnumbered, without hope, Japanese soldiers were reported to have thrown themselves off cliffs or swam out to sea to drown rather than surrender. Even after 2 atomic bomb attacks, the Japanese Minister of War urged his people to continue fighting. But on August 14th, 1945, the Emperor of Japan overruled that decision and unconditionally surrendered. Men had leapt off of cliffs for him, but in his own words, the enemy has for the first time used cruel bombs. The heavy casualties are beyond measure. Richard Feynman received the Nobel Prize in Physics in 1965. He also helped develop the first atomic bomb at Los Alamos. In The Meaning of It All, he wrote, "Is science of any value?" And below that, I think a power to do something is of value. He elaborates by talking about keys. Everything we learn about the universe, everything we invent or discover within it, is a key to the gates of heaven. But the same key will also open the gates to hell. The Titan II missile is great for delivering lethal nuclear warheads, but it also sent Gemini astronauts to space, preparing us for a mission to the moon. Science doesn't tell us how to use keys. It finds them or predicts them. How we use keys is up to us. And as always, thanks for watching.
Hey, Vsauce, Michael here. And here, I am the real Michael. This Michael was created by a brilliant young man named Mitchell, who brought it to me at a meet and greet after Brain Candy Live. It is phenomenal and obviously the most handsome Jack-in-the-Box ever. Everest is a mountain that's 8.848 kilometers tall. Its size is impressive. Or is it? Let's cut Earth, the entire planet, right in half straight through Everest and then start zooming out. As you can see, Everest's monumentality quickly disappears against Earth's planetary ginormosity. Compared to Earth's diameter, Everest, in fact all of Earth's ruggedness, barely registers. Now that can seem surprising since we're often surrounded by diagrams and maps and globes that exaggerate Earth's topography. Now there's a good reason to do that, but it leads to a misconception about just how smooth Earth is. Here's a typical example, a cross-section of the United States that I found on Reddit. The vertical axis spans about 10,000 feet, but the horizontal axis represents nearly 14 million. Stretched to the same scale so as to mirror reality, the actual smoothness of the Earth becomes apparent. On this 1-foot diameter globe, Everest is a bump about 2 millimeters high. Feels good, but if the Earth was actually this small, Everest would be a bump only a fifth of a millimeter high. It's 10 times taller than it should be. Only 24 people have seen the Earth with their own eyes as a circle small enough to be looked right at, not as the whole world, but as a little thing suspended alone in space. The further away you are from a ball, the more of its surface you can see. Now, we don't always notice this because in our day-to-day lives, most of the balls we deal with are so small, they're almost always many of their own radii away from us, and the available amount of their surface visible is near a maximum. Or they're so big, like the Earth, that we rarely get far enough away fast enough to notice this property. But the next time you're near a ball, get close to it. You'll see that as you get nearer, more of its surface disappears behind the horizon, but moving back up will make it available again. For most of us, stuck our whole lives on Earth's surface, such an experience is impossible. With nothing around to block your view, 5 kilometers, about 3 miles, is about the furthest you can see. Now, haze can limit your view and atmospheric refraction can slightly extend it, but for the most part, everything you can see happens within an area of just 80 square kilometers. Now, that's not bad, but it's tiny compared with what there is to see. The higher up you go, of course, the further away you'll be able to see. That's why it's great to be a satellite. Here's the International Space Station. Yeah, look at that nice big portion of the surface in view. Unfortunately, this isn't to scale. If the Earth were the size of an apple, how far away would the International Space Station orbit? Like this far away? Maybe this far away. Or maybe this far away. Actually, it orbits here, 2.7 millimeters above the surface. That's how far the stem of this apple sticks up. That's not very far. Oh, here's another fun little to-scale fact. If the Earth were the size of an apple, your eyeball would be about the size of the moon. We often imagine that from the International Space Station, astronauts see the Earth like this, but they're just not that far away. From where they actually orbit, International Space Station residents only see about 3% of Earth's surface at any one time. And that 3% is too wide to all fit within a window. When I was in Pittsburgh, their science museum had a mock-up of part of the ISS, and as you can see, out of the window, Earth is still quite expansive. Using special lenses, images can be taken from the ISS that look like circular disk Earths, but the lens is distorting things here. It's fitting much more into the picture. In order to truly witness Earth's entire shape with your own eyes, you would need to either smash your face right up against a window or just be floating outside the station. And even then, you would have to move your head to see from edge to edge. So how high up do you have to go to see the edges of Earth all at once? And even if you did that, how much would you actually see? How much is there to see? Earth is made of stuff. Lots of stuff, water and dirt and rocks and air, all of which are composed of atoms. Tiny things so teeny that a single drop of water contains not a million atoms, not a billion atoms, or a trillion, or a quadrillion, or a quintillion, but 5 sextillion atoms. Earth is made of even more stuff. Not a septillion atoms, not an octillion, nonillion, decillion, undecillion, duodecillion, tridecillion, not even a quatuordecillion, but 100 quindecillion atoms. But since we live only on the surface of our planet, we unfortunately can't see most of those atoms. If the Earth was shaped like a disk or an icosahedron, or say a cube, or a rectangular prism, or 2 stellated rhombic dodecahedrons, we could see more of the Earth than we normally can. But as things are, we actually see nearly the least of Earth's matter possible. Because of all solids, a sphere, which the Earth approximately is, has the smallest surface area to volume ratio, the most stuff inside and the least stuff outside. So, how many of these 10 to the 50 atoms that make up Earth are on the surface for us to see?
That's not an easy question. For one thing, technically atoms on the surfaces of opaque things, like rocks and dirt, aren't the only parts involved in their appearances. Subsurface scattering can and does happen. Regardless, attempting even a rough approximation is illuminating. I asked Grant from the YouTube channel 3 Blue 1 Brown for some help, and he pointed out that if you calculate the number of circles with atom-sized radii that could, packed optimally, cover a sphere with the surface area of Earth, you get about 1.5 times 10 to the 34th. That's a lot of atoms. But then he pointed out that the Earth's surface isn't smooth. Its roughness provides extra surface area for atoms to occupy. Without a complete description of the shape of Earth's surface, every mountain and valley, every bump on every rock, this is just gonna be hopeless, right? Well, here's the thing. Earth is made of little rugged shapes that from far away make big rugged shapes. In other words, Earth's surface can be described as a fractal. There's a regularity to its roughness. In fact, mathematicians have even assigned a fractal dimension to Earth's surface, 2.3. Now, to see what that means, I highly recommend Grant's video on fractal dimensions. It's fascinating. Using 2.3 and assuming that it applies from the scale of a human hair up to that of a mountain, Grant found that the number of atoms on Earth's surface changes significantly, up from a power of 34 to a power of 37. That's 1,000 times more atoms. So maybe we shouldn't count Earth's roughness out just yet. It's smooth, but not perfectly. To put that number in perspective, the human body contains about 10 to the 27 atoms. That's 10 powers of 10 less than the surface of the Earth. 10 powers of 10 is 10 billion. There are about 7.5 billion humans. So, more or less, it can be said that there are the same number of atoms in every human body right now as there are on the surface of the Earth. As I've shown before, all human bodies piled into one place would barely even fill the Grand Canyon. But all human atoms spread across the Earth would almost perfectly cover it just one atom deep. Fun fact, the mass of the atmosphere is about 2.5% less than what you would get by multiplying sea level pressure, 14.7 pounds per square inch, by the surface area of the Earth, because Earth's terrain displaces about that much air. Earth's surface is pretty cool. Obviously, I mean, it's got lichen and monster trucks and an island in a lake. On an island, in a lake, on an island. But from down here on its surface, we just can't see that much of it. Your view of Earth is obstructed by lots of opaque things. Walls, buildings, trees, rocks, terrain. If Earth was flat, you could see further. But sorry, it's a rough world out there. Or is it? If you could hold the Earth in your hands like this, how bumpy would it actually feel? We already saw that even our planet's biggest bumps barely register relative to Earth's size, but let's go somewhere famously flat, where relative to our size, terrain rarely gets in the way of seeing lots of the planet, the US state of Kansas. I grew up here and took this footage while driving across the state last year. You can probably see why Kansas is often called flatter than a pancake. However, although it is famously flat, Kansas is not the flattest US state. In a fantastic piece of research, Jerome Dobson and Joshua Campbell defined looks flat like this. If, from a given point, any part of the terrain within the horizon rises more than 0.32 degrees up, about the height of a 30-meter hill at the horizon, a typical person would say, well, hey, that part's not flat. By cleverly applying this rule to topographical data, they were able to give every state a flatness score. West Virginia was the least flat. Kansas was only the 7th flattest. Delaware, Minnesota, Louisiana, North Dakota, and Illinois are all, by this method, flatter than Kansas, as was the number 1 flattest state, Florida. Adam Savage and I had the pleasure of visiting Florida with our Brain Candy live show this year, and as this footage from atop the King Center in Melbourne, Florida shows, it's pretty gosh dang flat. Now, even though Kansas is not the flattest, it is the state most often ranked flattest when the general population is asked. It is truly scientifically flatter than a pancake. It's been demonstrated, but there's more to the story than that. In 2003, researchers took a 130 millimeter wide pancake procured from IHOP and analyzed its local reliefs. They found the difference between high and low points was on the order of about 2 millimeters. If a typical pancake like this was the size of Kansas, 5 million times larger, 2 millimeter high peaks would be 10 kilometer high mountains. In comparison, Mount Everest is only about 8.8 kilometers tall. And Earth's deepest scar, the Marianas Trench, is thought to be just under 11 kilometers deep. So, not only is Kansas about as smooth as a pancake, but so is every other state in the Union. And so is the entire world. If you were a giant holding the planet in your hands like this, you and it would be torn apart by the immense tidal forces created by your gravities. If somehow you could avoid that though, the planet would feel not much rougher than running your hands over a pancake. But a soggy one, right? I mean, most of Earth's surface is covered in water. Your hands would get wet. Or would they? Yes, Earth is covered in liquid, but the depth of that liquid, like the mountains above, just doesn't compare to the total size of the planet. As it turns out, if the Earth was the size of a typical classroom globe, like this one, 1 foot in diameter, the volume of water contained in, above, and on it would only be about 14 milliliters. That's this much water. It's kind of hard to believe because at this scale, spreading this much water across all of the ocean's surfaces would be pretty much impossible due to surface tension, but this is it. All of Earth's water compared to all of Earth. 90% of the space on our planet life can live in is in here. The other 10% is dry land. So no, you wouldn't get wrinkly fingers playing with an Earth like this. You could sop it dry just with a paper towel. Despite the incredible area oceans cover on our planet, their depth is just nothing compared to the size of our entire planet. Now, you may have heard it said that if the entire planet were shrunk down to the size of a billiard ball, it would be smoother than a billiard ball. After all we've seen so far, that seems believable, but as it turns out, it's not true. The misconception stems from the interpretation of the World Pool Billiard Association's rules. Now, according to them, a ball must have a diameter of 2.25 inches, plus or minus 5 thousandths of an inch. Now, some writers have taken this to mean that pits and bumps of 5 thousandths of an inch are allowed. Proportionately, on Earth, that would mean a mountain that was 28 kilometers high. So, since Earth has none of those, Earth must be smoother than a billiard ball. Except, if bumps that high were actually allowed on a pool ball, a ball covered with 120 grit sandpaper would be within regulation. Clearly, the 5 thousandths rule is more about roundness, deviation from a sphere, and not texture. In fact, as microscopic photography has shown, imperfections on regulation balls are only 1/100,000th of an inch, or about half a micrometer deep and high. Scaled down to the size of a billiard ball, Earth's Marianas Trench would be 49 micrometers deep. So, Earth is smoother than a pancake, but not smoother than a billiard ball. Nor, as XKCD wonderfully showed, is Earth smoother than a bowling ball. But hold on,
Earlier, we were using the word flat. Now we're using the word smooth. That distinction is important. You see, the Earth isn't flat like a plane. Instead, it curves. It's a ball. Pieces of Earth, like Kansas, might be quite smooth, but they curve along with Earth. If you were to stand in the middle of Kansas, people on the eastern or western edges of the state would appear to be not level with you, but about 8.1 kilometers below you. That's nearly the height of Everest, and if they stood straight up, they'd be tilted nearly 2 degrees relative to where you thought up was. Now here's an interesting coincidence. Generally speaking, 1 mile from where you are, Earth curves down about 8 inches. 1 kilometer from where you stand, it curves down about 8 centimeters. Now the rate of drop due to curvature isn't a linear one. You can't just multiply any distance by 8 to get the drop due to curvature. Instead, use an online calculator like the one I've linked down in this video's description. You can put in any distance you want. Anyway, the visibility limit caused by Earth's curvature is your horizon. It encircles you like a visual cage, but it's a cage whose radius is determined by how high up your eyes are. Conan O'Brien, at 6 foot 4 inches tall, can see up to 5 kilometers in any direction. But Snooky, at 4 foot 8, can only see about 4.3. To find out how far away your horizon is, geometrically, just use the online tools I've put down in the description below. Earth's texture can get in the way of your horizon, but can also cause things beyond the horizon to peek into view. HeyWhat'sThat.com factors all of this in. Now, if Earth was a smooth sphere, the view from atop Ben Nevis, the highest mountain in the British Isles, would end at the horizon 131 kilometers away, about 80 miles. Such an area would look like this. But factoring in Earth's ups and downs, here's a more precise boundary of what you can see. Loch Traig, Scottish Gaelic for Lake of Death, is only about 10 miles from the peak. That's within an 80-mile radius, but it can't be seen because terrain in the way blocks it. Parts of the Atlantic Ocean and the North Sea, 8 times further away, can be seen. They lie at the limit of Earth's curvature, just before it bends the surface out of sight. These spikes extending beyond the geometric horizon are caused by things beyond it that are tall enough to peak above Earth's curvature. In the case of Ben Nevis, this includes high elevation parts of Northern Ireland. Okay, enough about the surface and what it's like close up. Let's go further away and see more. This will be fun, but there will be a trade-off. The further away you are from something, the smaller it will appear to be. Moving away from Earth will make more area available to see, but that area will take up less of your field of view. It can be difficult to illustrate this in a YouTube video because your field of view, the shape and size of what you can see with your head still, just by moving your eyes around, is about 120 degrees up and down and more than 180 degrees horizontal. A screen is just a window of that space, nowhere close to filling it unless you get uncomfortably close. To help us visualize large apparent sizes, let's replace the spherical Earth with a flat disk that's always the same distance from the observer. This disk can be given an apparent size equal to Earth's from any altitude, and the disk can contain on it everything that would fit within your horizons from any altitude. Okay, so standing on the surface, looking straight down, Earth will take up nearly a full 180 degrees of your field of view. With your arms extended straight out parallel to Earth, your fingers will point to the edges of the planet, your horizon. From 400 kilometers up, about where the ISS orbits, 3% of the Earth's surface is within your horizon, but the Earth will only take up about 140 degrees of your vision. Your fingers would point to Earth's edges if you narrowed your arms' angles each by the width of 2 outstretched fists. One fist is about 10 degrees across at arm's length. Now, you can move your eyes from edge to edge horizontally here, but you can't quite take in the full width vertically. But from more than twice this altitude, 1,000 kilometers away,
Earth is only 120 degrees across. That's one less fist width each. This is perfect. That fits within our narrower vertical field of view. So, from 1,000 kilometers up, about 620 miles, you can just start to see Earth as a complete disk right in front of you at once. However, only 7% of Earth fits within the horizon from up here. Images of Earth taken by satellites this far up, like the Vsauce NPP, look kind of weird. I mean, North America doesn't actually take up this much of the globe. Earth's 120-degree width has been compressed to fit in an image much narrower. Compare Africa from its height to the famous blue marble picture taken from 45,000 kilometers away. The latter looks more realistic, like looking at a globe on your desk. Geosynchronous satellites are about 35,000 kilometers high. From their altitude, 43.4%, nearly a whole half of Earth's surface is visible, but the Earth only takes up a meager 17 degrees. You could completely cover it with 2 outstretched palms. That's incredible. But what about from the moon? Well, from that far away, Earth is only about 2 degrees across. You could block it out with your outstretched thumb. However, you can see more of Earth, you can see further around its curvature. From the moon, 49% of Earth's surface is visible. Just 49. If you want to see 50, half of Earth's surface at once, you have to go even further away. In fact, you have to go infinitely far away, which you can't. The most of a sphere you can see at once with your own eyes is just half. But in the real world, way before you were actually infinitely far away, the amount of light reaching you from Earth's surface would become so small and infrequent that you wouldn't be able to see anything at all. Stars, like our sun, are much brighter and bigger than the Earth, but only a handful have, even with our best technology, been resolved as anything larger than just a single point. From 1,000th of a light year away, our own sun would look like every other star in the sky, a single point to the naked eye, only about as wide as R Doradus, the widest star in our sky, from 91 light years away. The point of our sun would dim to a level undetectable by the naked eye. It would disappear. Most of the stars in the night sky you can see with your naked eye are further away than that. We can see them though because they're brighter and bigger than our own sun, which means if there's life out there, living in systems around the stars we've marveled at and written stories about since humanity began, chances are we are not part of their constellations or folklore. We're a dark patch in the sky to them, an ignorable emptiness framing other stars, the ones they marvel at, while not knowing we're here or that there's anything here. And as always, thanks for watching. If you don't follow me on Twitter or Instagram, you are missing out on a treasure trove of premium content. So check that out. And know this, I love you. Oh, and this Vsauce shirt is only available to Curiosity Box subscribers. This shirt comes in the latest box. If you sign up now, you will get this shirt, so long as you sign up before it sells out. The Curiosity Box is good for all brains. It comes to your door 4 times a year, full of science gear and toys that I want you to have. I want you to hold and learn from. Also, a portion of the proceeds from every box goes to Alzheimer's research. I'm incredibly proud of it. But what's going on this shirt? Well, it's modular multiplication around a circle. We have the numbers 1 to 40 around the outside of a circle connected to their product with the number 4. So 1 is connected to 4, 2 is connected to 8, 3 is connected to 12, and so on, even past 40. You could keep imagining the numbers continuing. For instance, 1 can become 41, 2 can become 42, and this emerges, the Vsauce V. Many other shapes can be made by using different multipliers or different numbers around the circle. Mathologger has a fantastic video on this topic, which you should check out. I've linked it down in the description. Thank you for being curious, and as always, thanks for watching. Hey, Vsauce, Michael here, and today we are going to talk about color.
Green, 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 green.
Hold on, let me just pink this up. Yellow.
Michael, aren't you going to come to the concert this evening?
I read about that. There are going to be a lot of purple there.
I didn't tell you about this earlier?
Well, look, I have to go brown town first, but I'll be white, black. Colors.
Did you know that the human eye can differentiate 10 million different colors?
But what color is a mirror? You might say silver because mirrors are often illustrated that way. And to be sure, they are made out of silver or silvery things like aluminum. But a mirror, in reality, is whatever color you point it at.
In this green room, the mirror is green.
And if you look inside a mirror, it becomes you-colored. An object is whatever color it doesn't absorb. These sticky notes are orange because when hit with typical white light, they absorb every other wavelength of visible light except for orange, which they diffuse into your eyeballs. But a perfect mirror reflects all colors equally. So in a way, you could say that a mirror is white. Except a mirror doesn't reflect colors in the same way that pigment does. A mirror reflects incoming light in a single outgoing direction. Specular reflection, not diffuse. This kind of reflection creates an image of the very thing in front of the mirror. So as bad astronomy jokes, a mirror is more of a smart white. But wait a second. That is a perfect mirror, and we live in the real world where there are no perfect mirrors. Every mirror absorbs a little bit of light. Not enough that it matters, looks pretty clear to me, but when you take a look at the spectrum of light reflected by a typical mirror, you will find that it best reflects light within the 510 nanometer range, which we perceive as green light. So technically, a mirror is a tiny, tiny, tiny bit green. You may have noticed this yourself when investigating a mirror tunnel. This happens when two mirrors face each other, reflecting the same scene back and forth and back and forth and back and forth. With each new reflection, a little bit more visual light is lost, but green least of all. That's why the reflection way down the tunnel is dimmer and greener. So maybe real-world mirrors aren't smart white, they're actually kind of green, but we should talk about white.
En español, white es blanco.
En français, white se dit blanc.
And in English, we have a word that comes from the same root, black, which is the opposite of white. How did that happen? Well, it turns out that all of those words come from the same ancient Proto-Indo-European root word, black, which meant shine, burn, flash. Some languages took it to mean the brightness of the flash, white, while others took it to mean what's left behind, the burned black darkness. If you have blue eyes, your eyes aren't actually blue in the sense that the molecules inside them are absorbing all other wavelengths of visible light and diffusing the blue. No. Instead, your eyes are blue for the same reason that the sky is blue, interference. In our sky, light from the sun encounters molecules of air, and because of the size of those molecules, light of longer wavelengths can slip on by, but shorter wavelengths crash into the particles, like blue light, and scatter, which is why we see blue when we look at the sky away from the sun. Without the air molecules, that space would just be black. And when direct sunlight has to travel through a lot of air, almost all the colors get scattered out except for the longest wavelengths, the red, which is what gives a sunrise and a sunset their color. The iris of your eyeball contains a hazy layer where light can be scattered just like the sky. Through a similar but slightly different process, shorter wavelengths are scattered more, making your eyes look blue. Unless, of course, you have some melanin in that iris, in which case your eyes are going to be green, hazel, or brown. Enjoy those colors, and as always, thanks for watching. Hey, Vsauce, Michael here. But now, I'm not. I'm gone, like 90% of the original silent films ever made. 6 of the 7 wonders of the ancient world deleted, like that text you thought twice about sending, or a Snapchat photo. Right? When Stalin decided that Trotsky was an enemy of the state, he had Trotsky removed from photos he appeared in with Lenin. Plenty of software tools and professional services allow you to do the same. Don't just forget the actual attendees of a moment in time, delete them. But where do things go when they're deleted? The Google Ngram Viewer allows you to search words and phrases in 5.2 million books published between 1500 and 2008. It's a great way to see how the words we use have changed over time. 1979 was a significant year. According to the Ngram Viewer, it was the first year we began to use the word delete more often than the word erase. Biological deletion still wins, though. Forget is by far more pervasive in our communication. But how does a computer forget? Moving a file to the trash is just the beginning. To protect against accidental deletion, when thrown in the trash, a file remains on your computer in a temporary directory, a sort of purgatory, where it awaits a more ultimate deletion, but can be resurrected if you wish. When you empty the trash, you are warned that you cannot undo the action. But when you empty the trash, the physical space inhabited by the file isn't actually emptied. It's marked as empty, available if and when new data needs to be stored somewhere. The file's home has become available real estate, but the file itself hasn't moved out. Only the pointers have gone away. Pointers are another type of data on your drive that point to places in memory where the actual file they are referencing can be found. They're a bit like the table of contents, which means that on most operating systems, deleting a file and emptying the trash is like deleting a chapter from a book by turning to the table of contents and marking the chapter as empty. There's nothing here, do what you want with the pages. To a computer reading the table of contents, it looks like the space is empty, but of course that doesn't change the fact that the contents of the chapter are still there. Special data recovery tools look through memory marked empty, available, to see what's actually there. If you're lucky, they can even find a file and save it, bring it back, mark it not available, undeleted. But if some of the file has already been overwritten, there can be problems. The file can be corrupted, melded together with other data like some kind of digital Frankenstein's monster. A couple years ago, a laptop that belonged to photographer Melanie Wilhide was stolen. It contained many of her recent digital photos. Luckily, police were able to return the laptop to her. They found it in a car they pulled over, but the thief had wiped the laptop's hard drive clean and had been using it for his own purposes. Data recovery experts were able to find some of her files still there on the now empty space, but the files had been slightly overwritten by things the thief had done. They'd been corrupted, but in a really cool way. So cool, Wilhide decided to exhibit the work. She titled the show after the thief who made it possible, "To Adrian Rodriguez, with love." If you want to delete a file so completely it can't even be recovered in a cool, weird way, like Wilhide's photos, you will need to overwrite the unwanted file completely. Deny the file a proper burial and rearrange its corpse with new data. One overwrite should be fine, but some people do as many as 35. Even 35 overwrites might not be enough. Sure, the overwritten data is hidden, but what about bad sectors? These are parts of a drive that devices can't access because of failed transistors or physical damage. An overwrite won't be able to reach them, meaning any data that was ever put there stays there.
So, if you are the United States Department of Defense and you don't want to take any risks, you will also shred, physically pulverize unwanted drives. The US, Europe, Japan often send such electronic waste to dumps in Ghana, like this one. This city in Ghana is known as Earth's digital dumping ground. Why Ghana? Well, it is cheaper to send unsalvageable electronics to Africa marked as a donation than it is to properly recycle them. But there, in these electronic dumps, the files can still be brought back to life. Organized criminals operating in Ghana have managed to successfully recover data from unregulated e-dumps. They have been able to find confidential multi-million-dollar agreements involving the Defense Intelligence Agency, Homeland Security, and the TSA. Shredding paper to get rid of whatever used to be on the paper isn't even safe either. It's not easy and it doesn't always work, but by scanning shreds of paper, computer software can match the pieces together. But in the past, shredded documents have been unshred by hand. In 1979, Iranian students seized the US Embassy in Tehran. With the help of local carpet weavers and years of hard work, they managed to reassemble thousands of pages of confidential documents shred by the CIA. The smaller the shredded particles are, and the more of them there are, the more difficult the task. So, the Department of Defense requires that the majority of shredded particles not exceed 5 square millimeters. If you really want to delete something, destroy it, erase it, time is on your side. In about 5.4 billion years, the sun will become the ultimate shredder, a red giant large enough to swallow Earth whole. Everything will be fine for billions of years, but many accepted models of the universe predict that in 10 to the 100 years, whatever intelligence is left will witness the universe's dark era and its final heat death. The end of the universe, the end of any file or photo or memory of you ever being accessed again. Every time something happens, a little bit of energy is lost. For instance, friction through sound or heat. That energy goes out into the universe a little bit at a time, slowly, more and more. Eventually, in a closed system, energy becomes homogeneous, evenly distributed, the same everywhere. There's no gradient, maximum entropy. In a little glass of ice water, it's pretty quotidian, but given enough time, our entire universe may be no different. A gradient, a difference in energy from one place to another, is necessary for things to happen, for files to be created and read, for life to exist. And in 10 to the 100 years, there may not be any usable energy left. In Isaac Asimov's short story, The Last Question, humans are concerned about this. As the story leapfrogs billions of years into the future, their list of solutions doesn't get any longer than none. So if we think across a grand timescale, is cosmic deletion, the freezing of everything, heat death, all we have to look forward to in this universe? We went to the moon. We brought flags with us that we planted on the moon representing a place on Earth. But those American flags on the moon are likely erased now, their symbols and colors bleached by the intense radiation of the sun on the lunar surface, unfiltered by any atmosphere. The flags are still there. We didn't take them back with us, but now they are empty. White flags. White flags representing our surrender to the inevitability of deletion in the universe. But we, today, are preoccupied with just the opposite. What really saturates our language, what we really seem to talk about, is creation. Things happening, not loss. Compared to erase, forget, and delete, make practically deletes deletion. The flags on the moon are bleached out. But is that bleak? Are they deleted or blank? Like a fresh sheet of paper ready for new stories? Really, it just depends on what you make of it. So thanks for making things, and as always, thanks for watching.
Hey, Vsauce, Michael here. Earlier this month, I traveled to Kourou in French Guiana with Euronews to watch the launch of a Vega rocket. If it happened while I was there. Waiting at the observation point with only minutes to go, the launch was postponed because of weather. Even though the rocket scientists were using Comic Sans, the rocket didn't take off until the day after I had to be back in London. But it made me think, we can send satellites into orbit and people to the moon and predict solar eclipses thousands of years into the future, but yet we cannot reliably predict which way the wind will be blowing in the next hour or so. How can such monumental cosmic movements, light minutes or light years away from us, be understood, whereas the weather, which happens in the very same layer of the atmosphere we live in every day, remains such a mystery? Well, it has to do with the limits of what we know and what we can know. Planetary positions and terrestrial weather in the future are determined by their initial conditions. But over a short timescale, predicting the future position of a planet involves fewer variables than the weather. In order to accurately predict the weather, you need to know the complete and exact conditions of every molecule of air on Earth, how those molecules will interact with each other and the Earth, and how they will feed back and influence themselves by changing other molecules. This makes it incredibly difficult to predict the weather more than a week in advance. And this problem isn't going to go away. It is fundamental to our relationship with the universe. Given enough time, small, unnoticeable, unmeasurable, unknowable factors get magnified again and again, slowly, until eventually their impact is vastly significant and our predictions today are hopeless. Neil deGrasse Tyson mentions this in his brilliant Death by Black Hole, where he points out that the recoil from the launch of a single space probe can influence our future in such a way that in about 200 million years, the position of Earth in its orbit around the Sun will be shifted by nearly 60 degrees. Edward Lorenz gave this phenomenon its popular name: predictability. Does the flap of a butterfly's wings in Brazil set off a tornado in Texas? The butterfly effect. A small change, like a butterfly deciding to flap its wings, can lead to a whole chain of events where bigger and bigger processes change just enough to lead to even more significant changes until finally an entire storm occurs somewhere different or not at all. The discipline that such thinking kickstarted is known as chaos theory, when the present determines the future, but the approximate present does not approximately determine the future. To us, the universe is full of if, but all things considered, we are pretty good at predicting the future and preparing for it. But some things are or were prepared for a future that hasn't occurred yet or never did. And knowing more about those things sheds amazing perspective on the limits of our knowledge. Speaking of limits, let's begin with your life. Carpe Diem, an online tool that, when given your birth date, uses the latest life expectancy data to give you back a grid of squares. One square represents 1 week, 7 days. The lighter ones are the weeks that you have already been alive. The darker ones are what you have left. Check sleep to see how many of your previous and future weeks will be spent sleeping. Of course, it's just an approximation. It's difficult to know if you will have more or fewer weeks to come. It's hard to know when it will all end. It's even more difficult to document unless you are Reynaldo Dagsa, a councilman from the Philippines who took this photo of his family on New Year's Day, at the very same second that he was assassinated. The photo was later used to catch the killer. We can't predict everything, but in the event of an anticipated catastrophic event, severe weather, an incoming nuclear attack or asteroid, how would we all know what was going on? Well, many countries have systems in place to allow them to speak to as many people as quickly as possible. The United States has the Emergency Alert System. When triggered, the system interrupts all programming on radio and television with messages generated using text-to-speech automated voices. The warning tones are known, so what's kind of scary is that today we can take a peek and see what it would look like and what it would sound like if a catastrophic event occurred. In this example, a nuclear attack that threatened life across the entire country. First of all, you would likely hear sirens. And then, as you went to tune in to, say, TV, this is what you would hear and see.
We interrupt our programming. This is a national emergency. The following message is transmitted at the request of the United States government. This is not a test. A nuclear attack is occurring against the United States. 4 nuclear missiles have been launched from unknown locations and are expected to strike the United States within the next 15 minutes. Due to the uncertain tracks of these missiles, all residents of the United States should seek out and prepare to take shelter immediately.
Stand by for a message from the President of the United States.
If a catastrophic event occurred of global proportions, what would humanity do next? Well, there might be survivors, people hidden away in fortresses that we have built, like the North American Aerospace Defense Command, NORAD, built into solid granite, shielded by steel plating to protect computer systems from electromagnetic pulses, and supported on springs so as to safely sway in the event of an earthquake. NORAD can protect humans and equipment from a 30 megaton nuclear blast just a mile away. After the event, it's places like this that would literally be humanity's last best chance of continuing life. The Svalbard Global Seed Vault is on the Norwegian island of Spitsbergen. Buried 390 feet inside a mountain, it safely stores and protects 250 million individual seeds for growing plants and crops if their vulnerable living relatives on the surface are all destroyed. Soviet technology existed to put people on the moon. Of course, they never did.
If Russia had sent men to the moon, they would have walked around on it looking like this.
The Krishit 94 was designed in 1967 but never used for Soviet manned lunar excursion. Russia did, however, send the first man into space and the first woman into outer space. They also sent the first dog into orbit around Earth. Unfortunately, the dog died soon after launch due to overheating, but later they sent Belka and Strelka, dogs on a rocket full of living organisms that became the very first to orbit the Earth and return to Earth alive. You can still see them today. The Moscow Cosmonautics Memorial Museum has the 2 dogs preserved, stuffed and on display as physical relics of Earthlings growing up and leaving their planet. I was also lucky enough to visit a restaurant in Moscow with menus, that used Comic Sans. Oh, and I ate a star dog, which in the Cyrillic alphabet looks like it's called crapdosis. The United States, of course, did send people to the moon, but recently we have learned that NASA, at the time, didn't know with the same certainty as other variables whether the first men on the moon would be able to leave. Just 2 days before humanity's historic moon landing, William Safire was asked to prepare a speech for President Nixon to read on television to the world if Buzz Aldrin and Neil Armstrong became stranded on the moon. 30 years later, William Safire explained that Aldrin and Armstrong were supposed to reunite with the command module orbiting the moon.
But if they couldn't, and it was a good risk that they couldn't, then they would have to be abandoned on the moon, left to die there. And mission control would then have to use their euphemism, close down communication. And the men would have to either starve to death or commit suicide. And so we prepared for that with a speech that I wrote. And the president was ready to give that.
Luckily, Nixon never had to deliver the moon disaster speech, but to read it today, thinking of those two guys still alive on the surface of the moon, knowing that they will never get back to Earth, is chilling. Included in that speech were these lines: "Fate has ordained that the men who went to the moon to explore in peace will stay on the moon to rest in peace. These brave men, Neil Armstrong and Edwin Aldrin, know that there is no hope for their recovery, but they also know that there is hope for mankind in their sacrifice." In ancient days, men looked at the stars and saw their heroes in the constellations. In modern times, we do much the same, but our heroes are epic men of flesh and blood. For every human being who looks up at the moon in the nights to come will know that there is some corner of another world that is forever mankind. And that's what I took away most from my trip to Kourou. Space isn't just a place for zero-G tricks or imagining sci-fi technology. Space is ever expanding and full of corners of other worlds that could one day become mankind's, if we choose to. And that doesn't minimize Earth. The Vega rocket I went to see sent up satellites designed to test electric solar wind sails for interplanetary travel, as well as satellites built to analyze the health of Earth's vegetation or to predict natural disasters. Just as our bodies benefit from having doctors and instruments beyond them that can probe, investigate, and diagnose, so does the Earth. Launch pads like the one in Kourou I got to visit are really just hospital waiting rooms for Earth, a place where our planet can wait for researchers and scientists to put their tools, their instruments, into use, into orbit. We may never know if something will or will not happen, but by pursuing space, corners of other worlds, we gain a perspective that can help us shrink the size of that mysterious and often frightening if. And as always, thanks for watching. Hey, Vsauce, Michael here. This is a completely still image, but as your eye reads what I'm saying and jumps from word to word, the paragraph will appear to slightly, just subtly, wave and boil. The illusion is called anomalous motion. It's neat, but to say it's fun is a tautology, because the word illusion literally means to have fun, to mock, to play with. But illusions aren't just fun and games, they also teach us about our brains. Anomalous motion, for instance, demonstrates that our brains process things at different rates and piece by piece. After a saccade, a quick eye movement, higher contrast elements are perceived sooner, than lower contrast ones. When arranged in just the right way, this delay is exploited and your visual system only has one explanation. Low contrast parts of the image didn't get processed later because this myelinated machine is wrong, but rather because the image itself must be moving. Akiyoshi Kitaoka's brilliant out of focus causes nearby neurons to disagree about the little slices they each detect. Some see big changes after a saccade and some see hardly any. This makes it difficult for our brains to calculate and factor in the effect of our own eye movements, so the image itself appears to be moving. But illusions aren't just about moving. They can also be moving. Poignant, significant, practical. They can mean the difference between life and death, like in nature, or during World War I as dazzle paint on ships. This form of camouflage doesn't conceal the object, but rather makes it difficult for an enemy to ascertain its prey's true shape, and thus where it's heading or how fast it's going. In 1955, the Soviet Union displayed their new Bison and Bear long-range bombers at an air show. It looked like they had a lot. Afraid of falling behind, the US ramped up production on their own B-52 bomber. But the whole thing was an illusion. In the Soviets' film of the air show, the same few planes had been flown past the camera multiple times in formations that gave the illusion of them having more bombers than they really did. By the end of the 1950s, the Soviet Union only had about 150 long-range bombers, whereas the Americans, fooled by the illusion, had built nearly 2,000 at a cost of $900 million. Architecture is full of examples of real-world, practical optical illusions. My favorite are Disney castles. They appear huge, but it's forced perspective, a lie. The tops appear further away from us because they are actually quite tiny. Illusions also tell us about ourselves culturally. The Mueller-Lyer illusion is classic. The horizontal lines are all the same length, but the bottom ones appear longer to people from Western cultures familiar with our rules of perspective and man-made straight lines. However, Bushmen from southern Africa and tribespeople from northern Angola or the Ivory Coast aren't fooled at all. Akiyoshi Kitaoka is using optical illusions to discover glaucoma earlier than current techniques can, and anamorphic illusions are used to save lives. They look weird from any perspective but one, from which they seem to pop out, defying the environment's actual shape. Hoping to remind drivers to always pay attention, traffic safety organizations in West Vancouver, Canada placed a skewed decal on the road. From the right perspective, the perspective of a driver in this case, it becomes a 3D illusion of a child you are about to hit. Slow down. Bruspup has made some incredible examples of the 3D effect such illusions can have. This object? Just an anamorphic projection. Anamorphic illusions have also been used to safely practice political dissent. In 1746, supporters of the Stuart claim to the British throne had to be quiet about it. It was treasonous. So, sympathizers served things on trays that looked like this. Innocuous enough until only supporters were around, and it was safe for someone to place a reflective goblet or cylinder on the tray, revealing the tray's anamorphic secret, a hidden portrait of their illicit love, Charles Edward Stuart himself. The Encyclopedia Titanica lists descriptions of every body recovered from the Titanic. It's quite macabre. Why was the iceberg not seen until it was too late? And why did the nearest ship, the Californian, not come to the Titanic's rescue sooner? Tragic questions whose answers might be optical illusions. The Titanic was sailing through conditions perfect for mirages. This theory points out that the Titanic sank at the border of the warmer Gulf Stream and the frigid Labrador Current, where the normal case of cooler air at higher altitudes was inverted, a thermal inversion. Now, because the temperature of air affects its index of refraction, a thermal inversion means light bending in atypical ways. If light reaches the eye from higher up than usual, objects can appear to float. Seriously, like this ship off the coast of Australia. A thermal inversion can also render objects completely unrecognizable, hidden within a haze, like this ship, or like an iceberg, or a sinking ship in need of help. The Delbuff illusion may be causing teeth to split and crack more often than they should when dentists drill holes in them. Dr. Robert O'Shea observed 8 practicing dentists and found that they were all drilling holes that were too big, even though they knew the correct size to be drilling. Why? Well, it may be the same reason people eat more food when they're given a bigger plate. Objects appear smaller when enclosed by larger areas. Holes of the same size may appear different sizes on bigger teeth. Dentists may be deciding that correctly sized holes drilled into teeth need to be made larger, not because they do, but because perception is a tricky thing. Illusions affect not only big ships and teeth, but also your future. The end of history illusion is our tendency to think of ourselves today as somehow done. Sure, I went through a lot of personal growth and changes in taste in the past, but today, who I am now, this is pretty much the final me. But that's not true. Studies have consistently shown that people underestimate just how different they will be, say, 10 years in the future, even though they can easily point out how much they've changed since 10 years ago. I like how Daniel Tomasulo puts it. We believe we are going to live, love, and long for where, who, and what we are thinking about right now. But the research says it just ain't so. This too is a transient state. Yogi Berra put it even more succinctly. The future ain't what it used to be. Their advice is, don't imagine your future. Look at other people and their experiences instead. Take their advice. Your imagination is just that. Their experiences are actual data. Well, of course, it's not that simple, which brings us to our final illusion, the illusion of control. Named by psychologist Ellen Langer, it's our tendency to believe we control the outcomes of things we demonstrably don't. It can help motivate us to not give up, and in healthy people at a healthy level, it is optimistic self-appraisal. But it's a lie. In one study, traders in the City of London's investment banks were shown a graph of a real-time stock price and given 3 buttons that secretly didn't do anything to affect the price. But they were told the buttons might have an effect. Try them out, see what you can do. Afterwards, the traders were asked to rate how much they felt they had been able to control the stock price with the useless buttons. And it turns out, the traders who reported the greatest sense of control over the stock price were the ones who scored lowest on risk management tests, and in the real world contributed the least to their company's profits, and in terms of salary, made the least money. It's kind of a bummer. The illusion of control is a nice feeling, but sometimes it's fine. Sometimes it even pays handsomely to admit you don't have control. And as always, thanks for watching.
Hey, Vsauce, Michael here. If every single one of us held hands together in a chain of unity around Earth, would there be enough of us to go all the way around the planet? There are about 7.5 billion of us, and that's a lot, but remember that many human bodies thrown together into one big pile would barely fill the Grand Canyon. This is all of us in one place. The physical bulk of all living human flesh on Earth today would only make a cone about 7,000 people tall and 2,000 across. That's it. But that's a three-dimensional shape. What if we made a one-dimensional, single-file line of people, each with, say, 1 meter of room, and we stretched that around the planet? Well, we would make it all the way around and still have 99.5% of the human population left. If we made a circle that included everyone, the ring of people would be more than 2.4 million kilometers in diameter, dwarfing the orbit of our own moon. Now that's not just a circle, that is a circool. Let's talk about circles today, specifically something that they do: roll. But what is rolling? Well, rolling occurs whenever something moves with respect to something else and is always in contact with that something else, and the contact points have instantaneous velocities of 0. That is, there's no sliding. In mathematics, the path traced by a point on a rolling object is called a roulette, French for little wheel. The center of a disc produces a roulette that's just a smooth, straight line while rolling on one, and this is why discs are good wheels. A square, on the other hand, would be bumpy, but square centers can make straight, smooth roulettes across the right surfaces. This is the principle behind square wheels, which I recently had the pleasure of enjoying at the Museum of Mathematics in New York City. Stan Wagon wrote a fantastic and famous article about wheels, which I've linked down in the description below. It's a great read. He also contributed a fantastic interactive tool to the Wolfram demonstration project that allows you to build a wheel and then find the corresponding road shape that allows it to roll smoothly. The roulette traced by a point on a disc as it rolls on a straight line has a special name. It's called a trochoid, from the Greek word for wheel, trokos. Now, trochoids can be curtate or prolate, depending on whether the tracing point is inside or outside the circumference. If the point is on the circumference, the resulting curve is called a cycloid. Cycloids are very special, and they are the star of this episode. Now, I've been working with Adam Savage a lot lately as we gear up for Brain Candy Live, our 40-city tour that I hope to see you at. Recently, I asked Adam for some help with roulettes. Adam, do you have a favorite polygon?
The whole group. I'm literally an actual big fan.
You can't, they're like your children, you can't pick a favorite. I don't have a favorite either. I do have a favorite thing that you can do with a polygon.
Okay.
Make a cyclogon.
A cyclogon is an actual thing?
Yeah,
that's
it's
not
an actual
a superhero.
thing. It's an actual thing. Do we have a polygon around here? Here, here's a square, right?
Right.
Say this is a square.
Yeah.
If I take one of the vertexes of this square and I start rolling this square, and you follow where that vertex, oh shoot. Let me roll this better. Are you ready?
Yeah.
All right, the actual path.
It describes a curve.
Described here, yeah, that curve is called a cyclogon.
Oh.
And as you pick polygons with more and more sides, you get closer and closer to what I want from you today.
Okay.
A cycloid.
A cycloid.
Now, I could have just done this in Photoshop and done like an animation like I normally do, but you have a shop.
We can actually build this.
And you can build things.
Okay.
Why did I want to build a cycloid? Well, let me ask you this. With only gravity to move you, what's the fastest way to roll or slide from a point to some other point below, but not directly below? Would it be a straight line? Well, that would certainly be the shortest path, but when you fall, gravity accelerates you, and falling vertically a lot right away would mean having a higher top speed during more of the journey. And that can more than make up for the fact that a path like this is much longer than a straight line. But of these two considerations, accelerate quickly and don't have too long of a path, what's the optimal combination? Finding the answer, the path of least time, is called the brachistochrone problem, and it's been around for a while. Galileo thought the answer was a path that's just a piece of a circle, but he was wrong. There's a better one, and in 1697, Johann Bernoulli came up with the answer using a very clever approach. To see how he solved it, let's start with a similar problem. You are standing in some mud and you want to run to a ball in the street as quickly as possible. Now, a straight line would be the path of shortest distance, but if you can run on pavement much faster than you can run in mud, the path of shortest time would be one in which you spend less time moving slowly in mud and more time on the surface you're fast on. The angle you should enter the pavement at depends on how fast you move on both surfaces. As it turns out, when the ratio between the sines of these two angles equals the ratio between your speeds across both surfaces, the resulting path will be the optimal, quickest route. This is called Snell's law. Light always obeys Snell's law. When it changes speeds, like when it leaves a material in which it moves more slowly, like water, and enters one in which it moves more quickly, like air, it always refracts according to Snell's law. In other words, light always follows the route that is the fastest for it to take. Bernoulli used this fact to tackle the brachistochrone problem. Light changing speed is analogous to a falling object changing speed. But of course, a falling object doesn't just speed up once, its speed is always increasing, it's accelerating. To mimic this, using light, which Bernoulli knew would always show him the fastest possible route, all he had to do was add more and more thinner and thinner layers in which the speed of light was faster and faster and faster. And, well, what do you know? There it is, the brachistochrone curve. The path of least time. Roll down a track like this, and you will beat anything rolling down any other path every time. Bernoulli was clever enough to realize that this curve can be described in another way, as a roulette. Specifically, he noticed that it was a cycloid, the path traced by a point on a circle rolling along a line. A cycloid satisfies Snell's law everywhere. To see why, I highly recommend watching this video on the brachistochrone problem. This channel is fantastic, by the way. I'm a huge fan. The visuals and explanations are top-notch. Anyway, a cycloid provides the perfect balance between keeping the journey distance short and picking up speed early. Now, I told Adam all of this, and I told him that it would be really fun to have a cycloid curve we could roll things down, and he said,
clearly we should start building.
We should just start building it. What we need is a circle.
Okay.
That's of the height that we want. And then we're going to use that circle to trace
and
out
make
the
a cycloid curve. I want to do a race, right? So if we're gonna do, like, if you have point A here and point B here, and you say that there's some kind of curve that's better than a straight line in terms of something traveling between those two, then I want to also make a straight line from A to B.
Yeah, and maybe also a really extreme curve, like that.
Right, okay. Got some protractors there.
Ooh.
I have.
You have a compass extension.
I do. I have all sorts of.
I've never seen such a thing. Is that it?
Yeah. That connects to that, and that connects to that. That's gonna be 9, give or take.
I almost I feel guilty that this is like a dream of mine coming true.
Oh, really?
But it's such a nerdy dream too. It's not like I want this, Red Ryder BB gun. It's like I just want a curve that things roll down.
Okay, so then clearly when we're done with this is my Christmas present to you. I think I'm currently like working out a way to do this in my head that actually makes it fairly compact and not super complicated.
Yeah.
Take a blade and cut out like an inch around this whole thing.
And how are you gonna do the finishing?
I'm going to cut this, unless you would like to, on the bandsaw.
You can start.
Okay, here we go. Okay. Now, that's a little bit rough, so we're going to finish it on my disc sander.
Oh, wow.
And this will just allow us to get right up to the line. That's close enough.
That's
for
pretty
round,
good, yeah.
So now you want to use this to draw a cycloid.
Yeah.
So you'll need a little hole.
That's what yeah, so that the point of our drawing implement is on the rim, not above it.
I'm doing this right inside. Oh, I messed that up. Let's try
I don't think so. It doesn't.
No? You
Yeah,
think that's
it
all
can
right?
be- I mean, that's even better than having the rim whole because we want the line to be right on the edge.
Okay, so what we're going to do is we're going to create a pattern for the cycloid curve that I'm then going to transfer to acrylic, to clear acrylic.
Great,
and that'll
great.
allow us to see things really clearly.
Yeah.
So, clip this in here. And this allows you to roll your cycloid, right? Because we're just doing, it is literally like that, right?
Oh yeah, see this is perfect, yeah.
Pushed against here, I shouldn't slip.
This is like a Ouija board for geometry nerds.
It is a Ouija board for geometry nerds. Okay, there we go. That's
It's spelled out Brachistochrone.
That's
it.
That's the curve that we're talking about.
Yeah.
That's the beginning, that's the end, and this is our pattern.
Yeah.
Isn't that cool?
That's cool.
Okay. So, I'm gonna end up with a piece of plywood. Let's say 3/4 of an inch thick, but it's gonna have channels table sawed out of it that travel its length, and in those channels will sit my clear acrylic curves, and it'll also have an upright that also will have the channels milled out of it on the table saw, and that will allow the curve to sit and be supported.
Yeah, a little backstop here
Easily.
at the bottom. That'll allow us to hear that they all hit at the same time.
There's a couple things going on. One is that we've got cycloid, straight line, and then we've got extreme curve.
Right, and are these, you had mentioned bending the acrylic so we could adjust the,
No,
or not
actually,
now?
I have, you'll like this. So
Okay.
the acrylic will just be a fin of acrylic, just a thin sheet of it. Traveling on that will be, and I have material for this, some Delrin or acetyl rollers that look like this. So from the side, they'll look like this. They'll look like an H. In which the acrylic sits in there, and the roller is self-supporting on the acrylic, but rolls down it. Ah, that is tolerance. I love it.
I like those curves.
While Adam and I build a real-life cycloid track, let's take some time to appreciate other kinds of roulettes. As mentioned before, trochoids are curves made by discs rolling on straight lines. But an epitrochoid is made when a disc rolls around the outside of a circle. Roll a disc inside a circle, and what you've made is a hypotrochoid. These are the mathematical names for the curves you make when using a spirograph toy. Notice that the holes don't lie on the circumference of the discs, though some do come close.
There's a special name for epitrochoids and hypotrochoids traced by points on circumferences. Analogous to disks rolling on straight lines, they are epicycloids and hypocycloids. Now, if two circles have the same radius, a point on the rolling one will touch the stationary one exactly once, always in the same spot, creating a cusp. This cute heart-shaped epicycloid is also known as a cardioid. If the rolling circle has half the larger's radius, you'll get a two-cusped epicycloid, the shape of which is called a nephroid, because it apparently looks like a kidney, I guess. 1/3 the radius gives you 3 cusps, 1/4 4 cusps, and so on. As for hypocycloids, if the inner circle's radius is 1/4 of the larger's, the resulting roulette curve is called an asteroid because it looks like a star, which the ancients also thought about asteroids. 1/3 the radius, and you've got a deltoid, named after its resemblance to the Greek letter delta. 1/2 the radius, and, well, you get a straight line. This fun relationship is called a Tusi couple, rotational motion turned into linear motion. Follow a number of points on the rolling circle and you'll get the famous illusion where every individual point moves in a straight line, but the whole thing describes a rolling circle. Put a handle on it, and you've built a trammel of Archimedes, aka an ellipsograph when used to make ellipses, aka a hillbilly entertainment center when bought in Osceola, Missouri. Anyway, let's get back to Adam and I's curve comparison build.
I have a finish line.
Oh, beautiful.
Okay.
Okay.
There's your finish line. You ready?
I'm ready. All right, I'll count us down. 3, 2, 1, go.
Okay.
Right? Here we go. 3, 2, 1, go. 1, 2, 3.
With the
steep was second, straight was last.
The straight was last.
Yeah.
The shortest distance between 2 points
Was last.
The slowest way to get there.
Yeah, it certainly was. Let's try it one more time.
Yep.
Because it was super close. The brachistochrone curve was by far the winner.
Yeah.
What a mouthful of a name, by the way.
Brachistochrone?
Brachistochrone. Not related to the brachiosaur. I looked it up. They're different roots.
I once looked up the difference between ingenious and ingenuity, and they don't have the same
And they're not
root.
related.
No. All right, you
All
ready?
right, I'm ready.
Count
Okay.
it in.
3, 2, 1, go. Yeah.
Same results?
Same result.
1, 2,
But
3.
these are so close, it's hard to tell.
Well, we're answering the main question, which is that the brachistochrone curve is the fastest way to get there.
Well, a brachistochrone curve is also known as a todochrone curve that has another property that we should test.
Which is?
And that is, it's also
Wait,
known...
Hold on, before you
Yeah,
get
yeah.
to this, we've established between these 3 curves that the cycloid-made brachistochrone curve is by far the fastest.
It's by far the fastest.
Okay, great.
You get steep, and
Yep.
unfortunately, you pick up a lot of speed right away, but then you've got a lot of this with little acceleration.
Yep.
You go straight down, and, you know, funny enough, what you want is that perfect balance of gravity's acceleration, but also moving to where you need to be. And
That's
this
That's fascinating
shape-
to me that a geometry, which is the cycloid curve, would yield such an efficient exploitation of the forces involved.
Yeah, exactly. Because if there was no acceleration, if there was just one force in the beginning, straight line would probably be the fastest.
Right. Okay. What is the other quality of the todochrone curve?
You just said it. Todochrone means same time. So, as the geometry and math tells us, no matter where you start an object...
Yeah.
Whoops, the clamp just fell off.
That was your fault.
It was my fault, but also, come on, clamp.
No, it's actually...
Do you know how to do this?
These tables are a pain in the ass because they have these lips on them and they actually...
Oh, that's like a
Yeah,
thin...
they drive me nuts. It's actually my fault.
Good. I'm glad we got that resolved.
Okay.
So I'm going to remove the straight line guy as well. So we're left with a cycloid, which is called a brachistochrone curve, but it also has a bizarre property where no matter where I start an object on it, when I let go, they always reach the bottom in the same amount of time.
Wait a second. So if I start it here, the amount of time it takes for this to get to the end is the same amount of time it takes for it to get to the end from here?
Yeah, and the same from right here. Well,
wow. Okay.
So starting from here, it's going to be tough because of friction.
Yeah.
Now, if you do this in software, it's perfect, but that's boring.
Yeah.
This is the real world, and maybe we won't start them that low.
I mean, if we do 1, 2, and 3, where we actually have
and
some
I feel like
gravity
we could
working for us.
we could probably get one to work from here. Like that, there might be a lot of friction involved, but we could always see. We could always see. We've got enough of them. We've got to
That's
peel
why
these.
we made 3 curves, so we could test this property.
And these were all cut and sanded, clamped together, so they are incredibly similar.
I will have to chamfer the edge, as I did on this one.
Yeah, that's
and
true.
And we'll hit it with some Scotch-Brite and who's it? Steel wool. Okay. The little known fact that once you've torn paper off of plexiglass, it crumples into a really nice ball and can be thrown long distances.
Hey. How did they get this paper on the plexiglass in the first place?
That's a good question. I've never seen it happen.
Because it doesn't really feel glued.
Well, they've got some kind
There's
of
no glue
3M glue on it, right?
Yeah. I think this is going to be really cool.
I hope it's cool because in theory and practice, theory and practice are the same thing, but in practice...
I went to the University of Chicago where one of their sayings is, well, that sounds good in practice, but how is it in theory? It's the life of the mind there.
So let us see if I do one up here and you do one there, and okay, yeah, so this has got to be without this.
I think the same person should release them, because then you can time it better.
So here, put that one here.
Okay. All right, so 3 different positions. This one has longer to go.
Yep.
This one has the shortest path. So who's going to reach the bottom first?
Okay,
well,
here we go.
Let's see.
Intuition would say the one in this one would go first. Ready?
Yeah.
Dude!
Good. Pretty good.
That was awesome!
That was so
They all
nice
they lined right up.
All right, let's switch it up.
Okay.
I think you're going to have to be the one to release them, because otherwise it won't be easy to time.
Here we go. 3, 2, 1. I watched them lining up.
Yeah, they line up like they're waiting for each other. I'm going to stand further away because I want to see the full path.
Okay. Ready?
Yeah.
3, 2, 1.
How cool is that?
They totally line up to hit at about the same periodicity they would for here. So given the vagaries of some extra frictions here and there, they're actually hitting this at the same sort of periodicity that they are when they start at the same point. So there's that, and then... Is this the Todachrome curve demonstration rig of your dreams?
It really is. It really is. It's also the brachistochrone rig of my dreams and the cycloid rig of my dreams.
So check that out.
Keep doing that, yeah. That is really cool.
Another one. Yeah, that was exactly on point.
Wow. Racia. See, in this game, no matter where you start, no matter who you are, you're always a winner.
Everybody's a winner.
There's always a tie. So this is brain candy for me, Adam.
Totally.
This is something that was previously abstract and only seen in animations and in text, made real. Yeah. Now I can put these wherever I want. I'm not stuck with what someone else did. I can physically hold it, and that's
That's what makes Brain Candy exciting for me.
It is. It is like, I love taking the theoretical and making it physical. And actually, honestly, we've always had what seemed to me like sister enterprises, and it's nice to join them together.
Yeah, this is a little child of ours, isn't it? Maybe one of us wasn't so good at sanding, and maybe the other of us kind of saved the day. But it's real now, and it's alive, and I think it's loving its life.
That was fun.
Hey, it was really fun. Thank you. This is my dream come true. Adam, thank you so much for your help. Working with you is always amazing. I hope to see all of you out there watching at Brain Candy Live. It's going to be incredible. And in your daily lives, may you always find the Tadachrome, the solution that brings you and others together, even if you started in different places. And as always, thanks for watching. Hey, Vsauce, Michael here. How many people are in space right now? .com tells us that the answer is 6. Ever since the first person reached outer space 52 years ago, more than 500 humans have left Earth. And they've gone as far as the moon, an impressive distance. I mean, space stations, which we use in outer space today, are way cool, but to scale, they only orbit about this far away from Earth. Whereas the moon, where Apollo astronauts went, is way out here. For the last 12 years, there has been a continuous and uninterrupted presence of humans living in space. Different people at different times ever since November of 2001. But so far, all of us, every human who has ever existed, was born right here on Earth. Of course, Earth is a giant collection of matter that got together in space, held together by its own gravity, so technically we were all born in space. But I want to talk about outer space. What is our relation to it and within it? How suited is our biology for the larger universe we were born into? More specifically, if you were born and raised beyond Earth, what would you look like? First things first, where is outer space? Well, outer space happens to be about 100,000 meters above your head. At that point, the atmosphere is so thin that in order to achieve lift, an aircraft has to travel at a speed so quickly that that speed is the same as an orbital speed. An orbital speed is a speed that is so fast, even with no lift, even while falling, you don't. Because the Earth literally curves away from you as fast as you fall towards it. This is what astronauts in the International Space Station are really doing. They're falling. It's a common misconception that astronauts float around weightless in space because there is no gravity there. But there's plenty of gravity. In fact, there's pretty much the same amount of gravity operating on them that there is operating on you right now while you watch this video. Believe it or not, if we built a tower all the way up to where the International Space Station orbits, 370,000 meters high, and you walked out onto the top of that tower, it would feel kind of like this. You would just be walking around like I'm walking right now. You wouldn't feel that much different. But the International Space Station would be whizzing by at 17,000 miles per hour. It has to, because they are falling. So to say that astronauts float around in orbit because they are experiencing zero gravity is very misleading. Really what they are feeling is zero G, where G is acceleration felt as weight. G hurts so good.
because gravity's limiting influence ensures that we develop correctly and healthily. After all, it is what we were born to thrive in. So asking what a human would look like if conceived, gestated, delivered, and raised in orbit would look like requires a discussion of weightlessness. Realistically, people building colonies on planets beyond Earth or traveling through space for long periods of time who expected new humans to be born would utilize technology that helped mimic conditions here on Earth. But until artificial gravity is perfected and can be easily implemented, it's important to understand the effect weightlessness has on our biology and other things. For instance, in a zero-G environment, hot air doesn't rise. So a candle flame is not shaped like a stretched ball of glowing gas that's drawn upward. Instead, it's just a round ball of hot gas. We are not sure we can make babies in space. The logistics of merely hugging are difficult enough. A recent invention called the two-suit might make it easier. The two-suit provides effortless intimacy in weightless environments, such as outer space or on planets with low gravity. But will it be enough to ensure that conception happens? The enzyme responsible for stopping the movement of a sperm cell's tail doesn't work very well when they're zero G. In space, sperm swim faster. One thing we know about babies inside mothers in space involves the development of the vestibular system, canals in the inner ear that use the flow of fluid to determine movement, up versus down, and balance. In a zero-G environment, the fluid in the vestibular system just floats around. It's confused, and this can lead to motion sickness, visual illusions, and disorientation. It's called space adaptation syndrome, and it affects about 50% of astronauts. Confusion about motion can make you vomit, carsick, seasick, zero-G sick because of survival. It's believed that motion sickness, a confusion about acceleration, is similar to the effects caused by the consumption of poisonous plants, in which case vomiting can save your life. Pregnant rats taken to space give birth to babies back on Earth that struggle with directions. Unlike rat babies that gestated here on Earth, the ones that gestated in space have trouble righting themselves when thrown into water. They do tend to be better at processing orientations common during weightlessness, which is a good sign for humans, gestated and born and raised in space, but it's some of the only good news. Vestibular fluid isn't the only fluid to be affected by a zero-G environment. All of your body fluids are. On Earth, gravity pulls those fluids down. But in orbit, the fluid is free to evenly distribute, giving astronauts their characteristic bird legs and puffy faces. Cosmetically, it's kind of a bummer. And all of that new fluid pressure in your face can compromise vision. Of 27 astronauts studied after long space flights, 9 had fluid expansion around the optic nerve, 6 had eyeballs flattened in the back by fluid pressure, and 4 had bulging optic nerves. More fluid pressure in your head causes an errant message that your body must have too much fluid. So the bodies of zero-G travelers respond by producing less blood. Astronauts can lose up to 22% of their total blood volume while in space, leading to weaker, atrophied hearts. Away from Earth's protection, radiation from the sun and the rest of the universe is incredibly dangerous, and we're still not exactly sure how to best guard against it. Mice exposed to levels of radiation expected during interplanetary journeys showed signs of different brain blood flow and larger plaques of the type found in patients with Alzheimer's. Psychologically, feelings of isolation in space, thinking about just how far away you are from the rest of humanity, can affect you physically. Scientists working at the South Pole have developed compromised immune systems with fewer T cells. As for the shape of your body, fully grown astronauts in orbit, no longer pressed down by Earth's typical G-force, experience spinal expansion, sometimes growing by as much as 3% before they come back to Earth. A 6-foot-tall human can go to space and come back as a 6-foot-2-inch tall person. Without usual and necessary stress, bones in space atrophy at a rate of about 1% per month. Given enough time, total bone mass lost can be as high as 40 to 60%. And when weightless, you don't need as much muscle strength to move around. This causes the muscles of people weightless in space to atrophy. Those that you use to fight gravity can shrink 5% per month for a total muscle mass loss of 20%. It's all kind of scary and sad, but don't bother crying over it because without 1G to pull them down, tears don't work the same way in space. Astronaut Chris Hadfield makes excellent videos about how things happen differently in orbit. For instance, tears just pool up on your face due to surface tension. In space, you can cry, but as he says, the tears don't fall. We know that these problems exist for adults in space. Theoretically, they would affect developing children in space even more so. Parallels have been drawn between the way a child's skeleton would likely develop in orbit and diseases that cause weak and soft bones here on Earth, bones that break and heal according to different forces than the typical downward ones, like rickets. It's tenable to say that without proper precautions, exercise, and care, like adult astronauts already take, children developing in space could look like this. Not because of rickets or a lack of vitamin D, but because the usual forces and active use required for healthy bone development just wouldn't be there. Added to the other threats, imagine a body shaped like this, but with thinner legs, thin, weak muscles, a puffier face, poor eyesight, and a higher than usual proclivity to dementia later in life. Doesn't sound very good, does it? Remember though that a lot of this is speculation. Few studies have been done on the topic, and few are planned for the future. We don't even know if a healthy fetus can develop in the first place, or if conception can even occur in space. When I think about how little we know about our bodies and how our bodies might grow and develop in the larger universe beyond Earth, I like to think about plankton. These little guys live in the ocean, and they exist in staggering numbers. Many varieties are too small to even see individually, but collectively, they can be seen from space. It's estimated that there are more plankton in the oceans of Earth than there are stars in our galaxy. More plankton on Earth than there are galaxies in the observable universe. And these guys wander around at the whim of ocean currents. They're wanderers. In fact, they get their name from the Greek word for wanderer, a name that they share with objects seen wandering in the sky. Planets. Plankton on a planet. Wanderers on a wanderer. Maybe, like ocean plankton, we humans are destined to wander far and wide, eventually also becoming more numerous than the stars in our galaxy. It's within the realm of what we can achieve. But before we start feeling too excited, too proud, keep in mind that we know very little about how our bodies grow and develop outside of this wanderer, this planet. And even though we know a lot of older words that sound like body, fundamentally, we don't even know why we call these things bodies in the first place. And as always, thanks for watching. Hey, Vsauce! Michael here. The dog that played Toto in The Wizard of Oz was credited as Toto. But in reality, the dog's name was Terry. And when Terry died in 1945, her owner and trainer, Carl Spitz, buried her on his ranch in Los Angeles. But in 1958, the Ventura Highway was constructed right through Terry's grave. Her remains were disturbed and have never been found. 53 years later, a memorial was erected in Hollywood Forever Cemetery in her honor. But because she isn't buried there, the memorial is not a grave. It's what's known as a cenotaph, an empty tomb. I was reminded of Toto's cenotaph when I saw the cenotaph of Philippopos atop the Hill of the Muses in Athens. You see, I was recently in Greece talking about YouTube with YouTube creators. The all-seeing eye of Guy came along and we visited the Acropolis, a lion gate nearly 1,000 years older than the Acropolis, the earliest known analog computer, plenty of beautiful cats, and I even took a selfie in Delphi. Seeing all of these things and how old they were made me wonder, how will we be remembered? How will future archaeologists react to the ruins of today's society they find thousands of years from now? Will they do a good job piecing it together? Will anything about you in particular be remembered? And for that matter, how do we even know that the past really happened? Not just the way we think it happened, but at all. Seriously, can you prove that the universe wasn't created last Thursday? That everything, every person, every memory you have, every photo you've taken didn't just pop into existence last week or 5 minutes ago? Last Thursdayism is the belief that the universe was created last Thursday. It doesn't have actual followers or rituals, but proving it wrong is impossible. Not because the universe actually was created last Thursday, but because last Thursdayism is not falsifiable. It cannot be shown to be false. Any evidence you bring up against it can be explained away as part of the everything that was created last Thursday. Many people believe that in order for a theory, an explanation, to be scientific, it must be possible to refute it, to prove it wrong, to test it. So instead, last Thursdayism falls into the domain of philosophy, where luckily there are razors, little rules of thumb that help shave off unlikely explanations. The most famous is Occam's razor. When faced with a choice between explanations, choose the one that requires the fewest assumptions. Occam's razor can shave off last Thursdayism because it requires fewer assumptions to believe that, say, this beehive tomb was constructed way back in the Bronze Age and that I just visited it later than it does to believe that the tomb, my memories of it, and this footage of me inside it just happened to coincidentally pop into existence at the same time last Thursday. One of my favorite philosophical razors cuts off so much stuff, it's not even called a razor. It's called Newton's flaming laser sword. It states, if something cannot be settled by experiment, then it is not worthy of debate. So let's move on to the past. What does Newton's flaming laser sword tell us about the past? I mean, it doesn't exist in the same way gravity or light or protons do. We can't do experiments on it, build control groups, run trials. The past just is what it was. We will one day be the past, and no matter how well we try to record our stories, ourselves, without time machines, future archaeologists are going to have to make a lot of guesses about us. But that's kind of cool. Future humans will likely know way more than us today about medicine, about exoplanets, about physics. But one thing they almost surely will not know more about than we do is today. Will your great-great-great-great-grandkids know your name? Will aliens who visit Earth millions of years after humans leave or go extinct understand that Animorphs was just fiction and not a history of our people? You are destined to become whatever the future thinks you were. If you're lucky, vandals, fire, natural disaster, conquerors, thieves, all of these forces obscure facts over time. But no matter how well we try to preserve today for future history books, there's one type of fog we are unlikely to avoid: apathy. Ira Glass put it well when he asked his listeners a simple question: name 10 people from the 15th century. We have records of more than 10 people, but to most of us, they don't matter. In 500 years, radio hosts will be making the same jokes, but about us. However, there is a legacy you leave behind that is irreversible, immutable, and in a way, unforgettable. To conserve energy, turn off when not in use, or just keep them on. Energy will be conserved no matter what you do. Even if you leave lights on all year, there will be no less or more energy in the universe. What's really being conserved when we turn off lights are the resources we turn into energy the lights can use. But if you counted up all the energy in the system before and after turning the lights on, it would be the same. Energy also does something else. Unless hindered from doing so, energy will spread out. It will disperse. That is, in so few words, the second law of thermodynamics. It's how our universe works. It's why things that happen spontaneously do. Energy spreads. Even when a process locally concentrates energy, like when a crystal forms or life grows, the second law isn't violated because these processes aren't independent from the larger world around them. They aren't 100% efficient. Hindrances can hold back the inevitable spread of energy for a long time. The second law doesn't say when energy will disperse, just that when it can, it will. Balloons will deflate. Objects will fall. Hot objects will cool down, and perfume sprayed across the room will eventually migrate to your nose, even in really still air. How much or how widely energy has spread out is measured in entropy. Entropy is often called disorder, chaos, but entropy is very different from macroscopic messiness. This deck of cards is themed after Greek philosophers. It's also arranged by value and suit, the entire deck. But if I take the deck and shuffle it, that is, disorder it, I haven't actually increased the deck's entropy, because nothing about this deck of cards' energy is different than it was before. However, entropy in the greater world around us has increased, because in order to shuffle the cards, my body has to do work. It has to take energy concentrated in my cells and change and disperse that energy into kinetic energy, movement, and a little bit of heat from my body and from the cards, friction, and a little bit of sound energy, that rustling noise. So there's your real legacy, your contribution to the universe's growing entropy. No process will be able to undo the net increase in entropy you accomplish in your life. History may forget you or misinterpret your accomplishments or what you stood for. The ripples you leave behind may get redirected, but the universe will never be able to forget the entropy you add. That's the law. The second law of thermodynamics. Many scientists believe that this means that eventually energy, heat, will be completely spread out evenly throughout the universe. It will be the same temperature everywhere, and at that point, nothing will be able to happen. Because in order for something to happen, entropy needs to increase, energy needs to spread, to move, to change. This may be the ultimate fate of the universe. Thermodynamic equilibrium. The heat death of the universe. It's been estimated that at the rate things happen, this end of the universe will occur in about a Google years. And you're contributing to it by simply existing. A funny consequence of all of this is the fact that people who aren't very active, people who don't do much but lay around, aren't just being lazy. In a way, they're being considerate. Sloth may be a vice, but to the universe, it's a fountain of youth. Choosing to do as little as possible means consciously limiting your contribution to the inevitable dispersal of energy, and thus, in a teeny tiny way, postponing the heat death of our universe. Relaxing adds time to the universe's life. An amount of time, to be fair, almost indistinguishable from zero, but still theoretically real. Being lazy will make the universe last longer. So thanks for chilling out. Thanks for taking it easy. And as always, thanks for watching. Hey, Vsauce, Michael here, and bananas are fantastic. They're actually one of the most radioactive foods we regularly eat. Sometimes they're difficult to peel from the top. One of my favorite ways to avoid that is to simply hold the banana and snap it in half. Boom, now it peels itself. It's a wonderful little trick, except when you drop it on the ground. This is unfortunate, but if I picked it up quickly, would it be safe enough to eat? I mean, how quickly do the bacteria on the floor move onto the food? Some people call it the 5-second rule, others the 10-second rule, and still others the 2-second rule. But is there any truth to it? Or is it just something that we say to allow us to eat food off the floor? In 2003, Gillian Clark famously investigated this question. She found that 50% of men use the 5-second rule to eat food off the ground, but 70% of women do. More importantly, she found that even brief contact with a contaminated floor will contaminate food, wet or dry. The Mythbusters found similar results, and a paper published in the Journal of Applied Microbiology got even more technical. The researchers contaminated various floor surfaces with salmonella, and they found that 5 seconds is way too long to wait. Bacteria adhere to dropped food almost immediately, but time does matter. After 5 seconds, they found that the food had acquired anywhere from 150 to 8,000 bacteria, but if left for a full minute, the number they found was 10 times greater. Now, considering it only takes about 10 bacteria of certain strains of salmonella to infect you, you should probably think twice before eating off the ground. Oh, and don't complacently think that you're safe because the floor looks clean or the food that fell on it does. Floors make great homes for bacteria. Also, floors come in contact with the bottoms of our shoes, and the University of Arizona has found that 93% of our shoes are contaminated with fecal bacteria. I've linked all of these studies down in the description. They're great reads, very thorough. But is it true that food dropped on a dirty floor becomes contaminated immediately? I mean, sure, practically speaking, that makes a lot of sense, but instantly? Is there a limit to how quickly bacteria can move from one object to another? Is there an amount of time, short enough, that were I to pick the food up within it, there would be no way for what it touched to contaminate it? Well, we're going to need to define touch. I've talked about this before on Vsauce and on Thinker, and Minute Physics has a great quantum perspective. But when we say touch, we tend to think of two objects contacting each other with no space in between. Unfortunately,
that's not really what happens. At a subatomic level, atoms resist smashing together because their electrons repel. Electrons can be modeled as waves that overlap and interact, but they never touch. There's always space between them. When I touch something or someone, I'm really just feeling their electrons react to mine at a distance, a subatomically small one, but a real one. So if that's the case, how come glue can stick things together? How come lipstick sticks to lips? And how can bacteria on a dirty floor stick to food that's been dropped on it? The positive charge from the protons in an atom or molecule isn't always balanced perfectly in space by the negative charge from electrons. Sometimes a molecule is asymmetrical and this imbalance is permanent, which gives the molecule a constant dipole, so it's like a tiny little magnet. But even in symmetrical molecules, electrons are mobile. At any one point in time, they might happen to find themselves more towards one end of a molecule than the other, creating rapidly fluctuating dipoles, causing the molecule to act like a magnet. If molecules have a lot of energy, they will simply whiz by one another, and their dipoles and those of their neighbors won't matter much. But if you cool them down, slow them down, the dipoles will have more of an effect, which is why molecules tend to stick together as they cool, going from a gas to a liquid to a solid. That's a lot of information about molecules, but it's incredibly important. It's the reason things can get wet. In fact, when you get out of the shower, you on average weigh about 1 pound more than you did before you got wet. It's also the reason capillary action happens. If you dip a napkin in a glass of water, you can watch the water climb up the napkin against gravity. That's because the molecules of water have very strong dipoles, and they're attracted to each other, cohesion, and they're attracted to the molecules of the paper, adhesion, more strongly than gravity pulls them down. If you want to learn more about intermolecular forces, I've put a bunch of links down in the description. But here's my question: how quickly do those forces act? Can two surfaces come into contact briefly enough that their molecules don't have time to be influenced by intermolecular forces? Well, for this, we're going to need molecular dynamics. Molecular dynamics is the computer simulation of the physical movements of atoms or molecules. For instance, this is a simulation of a single copper atom depositing on a copper surface. Notice that the timer up there is counting off hundredths of a picosecond. These simulations need to have a narrow enough time step to account for the fastest molecular vibrations of the material, including everything from wagging to scissoring. Typically, time as brief as a quadrillionth of a second is taken into account. So the 5-second rule may be true if we rename it the 1 femtosecond rule. Spend less time on the floor than that, and it's unlikely that room temperature molecules would have time to be influenced by intermolecular forces. Except, oops, I think we've been thinking too small. Intermolecular forces are fun, but objects can become entangled with each other on a macroscopic level. Glue and makeup and other sticky stuff often take advantage of the tiny imperfections, ridges, and nooks and crannies on an object's surface. Sticky things can seep inside and hold on. Even surfaces that seem smooth to us, when you really get down to it, aren't smooth at all. 2 sheets of paper from a phone book may slide across each other quite easily, but multiply that friction by the number of pages in 2 phone books by interleaving the pages, and you've got yourself a monster capable of lifting an entire car. I was recently lucky enough to see this happen in real life. You can check out my adventure over on Fast, Furious, and Funny. It's a new channel. Stay tuned, because we lifted cars with more than just phone books. The adhesion between 2 objects caused by the shapes of their surfaces contributes to friction and is known as mechanical adhesion. It plays a pretty big role in getting floor germs to stick to dropped food. In fact, if 2 surfaces can mechanically adhere but aren't close enough to do so, we wouldn't say they were touching. And so if by definition touching means that you can mechanically adhere to the other object's surface, well, then maybe the 5-second rule shouldn't be known as the 1 femtosecond rule, because if they're touching, it's already too late, and instead the rule should be known as the don't touch food that's fallen on the floor rule. But come to think of it, maybe we shouldn't be eating food that's touched anything, because bacteria are everywhere, including on you right now. There are more bacteria on your body right now than there are people living in America. There are 40 million bacteria in 1 gram of soil and 5 non-million bacteria on Earth. It's been found that 1 out of every 10 bank cards and 1 out of every 7 bills has fecal bacteria on it. Here's something fun. Go down to the comments section and type the letter V. If you used a mobile phone to do that, congratulations, you just touched 6,281 bacteria. If you're using a desktop keyboard, you're a little safer. You probably only touched about 180. Cell phones are actually one of the most bacteria-ridden things we frequently encounter. If you want to estimate about how many bacteria are specifically on your phone based on how clean you are, the Oatmeal has a really great quiz. You can find that in the description. But honestly, what amazes me the most isn't how dirty our world is or how much bacteria there is. Instead, it's the fact that despite those numbers, we don't get sick more often. Our immune system is amazing, but it relies on the same principles of adhesion that bacteria do. The forces that cause food dropped on the floor to pick up germs are the same forces that we need to fight them. They're the same forces that bring us closer together whether we like it or not. So keep adhering, and as always, thanks for watching.
Hey, Vsauce, Michael here. When something becomes part of the past, can it ever truly be experienced again? Obviously, my beard will grow back, but it won't be the same beard, and it won't be on the same person. It will be on a slightly older, different Michael. But of course, the bearded Michael of the past isn't completely gone. No, he still exists in our minds as a memory, and in the form of records of the past, like images and video. Hi, I'm the slightly older, different Michael you heard about. I am 130 days older than that guy. Wow, 130 days. You know, it really doesn't seem like it was that long ago. Just as an optical illusion is a distortion of our sense of sight, a temporal illusion is a distortion of our sense of time. Some seem small, like how a minute spent waiting in line can seem to take forever, but an entire day with friends can just fly by. Some seem deeper, like the uncanny feeling we get from recordings that make people from long ago seem more real than usual. Or the strange way time seems to sneak by. For example, the songs I liked as a kid, Wannabe, Mbop, Semi-Charmed Life, are as old to kids born today as the literal oldies were when I was born. How can that be true? Am I really that old now? I mean, I shouldn't be surprised. I know how time works, but yet I don't. Far from being just mistakes, these illusions are the edges of another dimension of space-time. Not one given to us by physics, not one given at all, but one made by our minds. Let's begin with the different ways there are to feel time. Actually sitting down and consciously tuning into the passage of time as it happens is called feeling time prospectively. You can't do that to time that's already happened, except you can. If I were to ask you, without looking, to guess how long you have been watching this video, you'd probably be able to come up with a guess you were reasonably confident in. Well, you arrived at that guess by feeling time retrospectively, by measuring it as it appears in your memory. Now, with that in mind, we are ready to approach our first illusion, the holiday paradox. A 4-hour delay at the airport before your holiday can feel unbearably long while it's happening. But once you arrive, an exciting day at your destination can seem to fly by. Those feelings are all prospective timing. A week later, retrospectively, the delay often feels like a blip in your mind, and the day of sightseeing feels like a much longer, bigger part of your life. These are the long-short and short-long patterns of felt time. Which one you feel depends on whether what you are doing is empty or full. An empty activity is monotonous, unstimulating, unimportant to you, whereas a full activity is packed with sensations, novelty, significance, context change, and challenge. Now, I experienced this during my 3 days in isolation. While I was there, time dragged very, very slowly.
A fear I have right now is that it's just Friday, and that there's still a lot of time left.
But now, years later, it's hard to believe that I spent 3 full days in that room? Jeez, seems like something I barely did. Well, it's believed that prospective time feels fast when an activity is full because you're not busy thinking about time. If you're not attending to it, you're busy with something else, well, you won't notice how much time has passed. But to understand retrospective illusions, let's ask a different question. Does time speed up as we get older? Many of you may feel the same way. Looking back, my childhood feels like it lasted so long, but my 20s went by faster, and my 30s are going by even faster than that. A popular explanation is the proportion theory. It suggests that time seems to speed up as we age because each new unit of time that we live is smaller relative to all the time that came before. The year you lived as a 9-year-old was 10% of your entire existence up to that point. But when you're 30, another year is just 3% more life. Studies have found little evidence that weeks, months, or even years are retrospectively remembered as passing faster by those who are older. But decades? Yes. And while it's true that the older we get, the faster we tend to think the last 10 years went by, that only appears to be the case until about the age of 50. After that, the speed of decades appears to plateau. A leading explanation is that how long a duration feels depends on how many things in it can be recalled. In my normal life, lots of different things happen every 3 days. But during the 3 days I was in isolation, so little happened that I have few distinct memories from it. My mind sees that emptiness and perceives that it was brief. So, perhaps a decline in new experiences and rapid novelty as we age means fewer events our brains decide to commit to memory. So then, looking back, because there are fewer distinct memories from more recent decades, we assume they were shorter. Reflecting on all of this, it's striking just how many moments are forgettable. John Koenig, the author of the Dictionary of Obscure Sorrows, calls the awareness of how few days are memorable oleka. Over time, our specific daily perceptions of what happened conglomerate into generalized ideas about how things were. Themes, moods, the big picture. What was perceptual becomes conceptual. And concepts are good. They lower cognitive load by wringing out details, leaving us with the broader, lighter gist. But they can also obscure reality, which brings us to our second distortion, chronological illusions. The world of our experience is not made of distinct entities. It's a continuity of fuzzy, overlapping blobs, and we impose concepts on it. For example, is a hot dog a sandwich? Is cereal soup? How many holes does a straw have? Those aren't questions about reality, they're questions about words we made up. Periodization is the chopping up of time into contrived pieces like the Stone Age, the Renaissance, the 80s, the 90s. But here's the thing, when did the 80s or 90s really happen? Mathematically, they refer to years that have 8s or 9s in the tens place. But conceptually, Well, it's not like on January 1st, 1980, people woke up and were like, whoa, 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 guys, it's the 80s, quick, everyone, change your clothes. Concepts say too much and too little. Facts that expose their imperfections are perennial favorites on social media. I made an entire video about them, in fact. But what hasn't been discussed yet is the mechanisms by which we allow them to do their dirty work. Let's dig in and see what we can find. If I asked you to lay down on the floor of a windowless, clockless room and get up after you thought a minute had passed, you'd probably do a pretty good job. But if I asked you to get up after you thought 10 years had passed, that'd be hard. We lack an ability to sense and grasp long periods of time. Also, we can't remember everything that happens. So instead of comprehending history's correct scale and structure, I believe that our minds often just use how we think about past events to place them relative to each other in time. One way we do this is through what I call the conceptual comparison heuristic, a technique whereby we use the similarity of elements in our conceptions of things to judge their temporal distance. If our concepts of two things suggest wildly different times, it's natural to assume that a lot of things happened between them. And if a lot happened, the duration separating them must be large. Alternatively, if our concepts aren't too different, the time between them must be bare of events, and so it feels brief. It's not a bad strategy, but tyrannosaurs died out 66 million years ago, and when T-Rexes began roaming the Earth, stegosaurs had already been extinct for more than 80 million years. To a T-Rex, the Stegosaurus was even more ancient than we think T-Rexes are. Here's another example. When we think of Marilyn Monroe, we think of a young woman, old Hollywood, mid-century glamour, Americana, black and white. When we think of the Queen of England, we think of an old woman in color in England and news headlines. Because those conceptions are quite different, we mentally place each woman in a different time. So it can come as a surprise to learn that they were both born in the same year. Similarly, it can be surprising to learn that Anne Frank and Martin Luther King Jr. were also born in the same year. And if they were alive today, they would both be younger than the Queen of England. When Harriet Tubman was born, Thomas Jefferson was alive. And when she died, Ronald Reagan was alive. This is surprising to many of us because our concepts of these people are anchored to them as adults. But Harriet Tubman was a 4-year-old when Thomas Jefferson died, and when she died, Ronald Reagan was a 2-year-old. Far from just being amusing, chronological illusions can often have teeth. America can feel like an idea fixed long before any of us by the overwhelming bulk of events that came before. But Barbara Walters has been alive for more than a third of America's entire history. And if you were 25, you have already lived through and been a part of more than 10% of America's history. Chronological illusions may also be caused by what I call the construal level heuristic, a technique whereby we place things in time based on whether we construe them concretely or abstractly. In social psychology, construal level theory describes how abstract and concrete thinking relate to psychological distance. That is, how distant something seems as opposed to how distant it actually is. Now, unsurprisingly, it's been found that people tend to think about things that are psychologically distant more abstractly. But studies have also found that if people are asked to think about an event abstractly, they'll consider it more distant than if asked to construe it concretely. This may explain why things can turn out to be longer ago or more recent than we thought. If an event recedes especially quickly from relevance or is suddenly replaced in our daily thoughts by other more urgent events unconnected to it, our minds may shift its construal to a higher level, making it feel further back in time than it really is. Conversely, if attending to the low-level details of an event continues to be important, our construal level heuristic will make it feel closer in time than it really is. Our third illusion of time comes from the fact that time is always moving forward. Because of that, the psychological distances we feel towards things should also always be changing. But not all of them do. The belief that your place in time is stable is what I call the chronostatic illusion. Tim Urban pointed out that it is now the case that Jurassic Park, Forrest Gump, The Lion King were all released closer to the moon landing than today. As a person who remembers The Lion King being brand new, and remembers feeling at that time that the moon landing was old, this is all very weird. The Lion King seems so much more recent than the moon landing ever did to me. The conceptual comparison heuristic places them far apart. My concept of the 90s will probably always stray from my concept of the present a little less than it should, because the 90s and now have something in common that the 90s and the 60s never did or will: me. Also, my construal level of The Lion King may resist becoming abstract because The Lion King continues to evolve and happen. The mechanisms I use to place things in time have sunk hooks into The Lion King, creating a sort of chronostatic cling that fools me into believing it's more near. The music that was new when I was young has also been tethered in my mind to the idea of new stuff only us kids get, even as it has actually been drifting away, as far away as the stuff I used to think was far. A chronostatic illusion is spectacularly broken when you realize that you have become as old as your parents were when you were born. It doesn't always seem quite right. They came first, and as such, should always be older, but suddenly you're aware of a way in which they aren't. Your age gap with people in the past is not static. Your parents keep getting older right along with you, but the people they were don't. This can lead to empathetic realizations. They weren't any wiser or more folded into the world then than you are now. Considering the temporal perspectives of other people leads us to a fourth distortion: the chronocentric illusion. The belief that our own relationship to time is the best or only frame of reference, or that it's more important and more real than any other. My grandparents used to tell me about how when they were kids, they didn't have television. And I always thought that sounded so weird. I mean, obviously, I knew it was true, but like, what the heck did they do with their free time? It wasn't relatable at all. People back then must have been so different, not real in the same way I was. But I remember a time before the internet, before mobile phones, and it wasn't that weird. The internet and cell phones are still, in my mind, an additional thing we now have. But for my daughter, they will be what we've always had. And when I tell her about a time when no one had the internet and didn't even know they needed it, it will likely sound to her just like the old stories I heard about growing up with no TV. And that's bizarre. My grandparents' childhood was weird. It was the olden days. Mine was totally normal. Protagonist syndrome is the belief that you are the main character of the universe. Recognizing that you aren't is what John Koenig famously called Sonder, the realization that other people, like that stranger over there you will never see again, have full lives, just as important and consuming to them as yours is to you. I'd like to add to protagonist syndrome the concept of ab ovo syndrome. Ab ovo means from the egg, from the very beginning. In literature, it describes a story that begins at the start, ab ovo, as opposed to in the middle, in medias res. Ab ovo syndrome is the belief that the movie of the universe began when you began, that the times of your life are the plot and contain the climax, and that everything before you was just backstory, everything after merely sequels. When you realize that that's not true, that you were not born ab ovo, but in medias res, that you'll die before the credits, and that everyone who has ever lived was a fully fleshed out protagonist in their own minds, that feeling is what I call chronosonder. Sonder not just for people over there, but for people over then. Overcoming the chronocentric illusion isn't always easy. It doesn't help that people from the past are finished. Unlike us who still have choices to make, they tell the same story over and over again. They're also separated by barriers made of their own evidence. The world wasn't actually black and white in the past, and it didn't suddenly become vertical in the present. Obviously, we all know that, but the arbitrary technical properties of a time's recording media can influence our perception of the past nonetheless. If silent films didn't look so much different from what could be done just a few decades later, would it be nearly as surprising to learn that Charlie Chaplin lived long enough to watch Star Wars? When I was in high school, I saw 2001's Pipe Dream for the first time, and it blew my mind. My friends and I honestly believed that it was a real thing someone had built. But recently, I looked it up on YouTube, and I was like, this is clearly a computer animation. What the heck was wrong with us? And what do you know? The top comment was exactly that sentiment. Our perception of the past is constantly evolving as technology does. And that's significant. We don't just think about the past, we also thing about the past. The material properties of an artifact can influence our relationship with what came before and push it further away. Faded yellowy color, sepia, SD pixelated video. Technological features can make the past seem like it was never as real as the present. But some kinds of evidence collapse that chronocentric divide. One way they can do it right now is by being demotic, ordinary, personal, candid. Such recordings are much more similar to the media we exchange with each other right now in the present. This footage of people goofing around in a 7-Eleven in 1987 has more than 6 million views, not just because of nostalgia, but because it's like visiting past people in their natural habitat at a time zoo. This isn't some pageant with timeless ambitions. It's a view out the window of a time machine they don't know is there. Another way evidence can corrode chronocentric illusions is by containing a convention more normal than we expect. People in old photos look like serious robots because back then you had to stay in the same pose for a long time to get a picture taken. But also, a long-standing trope in the world of images up to that point was that smiling or looking goofy wasn't a sign of happiness, but of drunkenness or stupidity. But every so often, this image pops up online, and people vehemently debate whether it's actually old or not. Sure, it's black and white, but the expression seems too normal to really be on a person from the past. It is, however, actually an honest-to-gosh picture taken in the early 1900s, one of the earliest known photographs of a human smiling, in fact. The juxtaposition of an expression someone today might make with a medium that suggests a technology of the past creates an opportunity for chronosonder. The subject is both dead and undead, gone, but not as unrelatably far as we may have thought the past was. Finally, the chronocentric divide can fade when we find the past captured in a medium that was rare at the time but more common now. This is footage taken by an early HD camera of New York City in 1993. It's pretty cool, but there's something almost uncanny about it. Watching it isn't exactly like time traveling back to 1993, but it looks more like video taken today than many of us expect. It's like peering through a telescope. We can see them, but they can't see us. They appear closer, more actual than usual. We lean in to get grasps of what it was like. That's part of the allure of time travel. As L.P. Hartley said, the past is a foreign country. They do things differently there. But it hasn't always been that way. Time travel wasn't a common feature of fiction until the 19th century. Not because people hadn't thought of it before, they had, but the past and future weren't rich with interesting destinations in the same way they are to us now. In the year 1008, it wasn't an insult to call someone 1000 and late. 1,000 years ago, the culture and technology around you was unlikely to be foreign to your parents, or grandparents, or great-grandparents, and outside of an act of God or gods, you didn't expect them to be foreign to your children or their children either. 1,000 years ago, there were no 80s parties because the 980s weren't interestingly different. Pre-modern societies viewed the present as a continuation of the past. Changes were interpreted as temporary disturbances of the natural state. But today, we see the present as something special. Change is significant enough and rapid enough now that we would imagine ourselves quite differently had we been born 10 years earlier or later. Zachary Sayre Schiffman points out, "We fail to realize that people before the 18th century did not see themselves this way. Instead of having a history, they regarded themselves as having an unchanging nature or essence, whose full realization might be impeded or impelled, but not otherwise shaped by events." Nostalgia existed, but for moments and places gone simply because they were prior to or away from here and now, not because they were fundamentally different and categorically irretrievable. As the discovery of antiquities and new worlds and new species accelerated, as the invention of new technologies and new ways of recording accelerated, the present became less and less like the past. Reinhard Koselleck has argued that between 1750 and 1850, the acceleration of history reached a speed at which static or cyclical views of time had to be replaced with our modern view, which understands the past to be essentially different from the present. It used to be that things passed. Now, there is a past. As technological and social change accelerate, the window of time within which things can be trusted to remain stable shrinks. In such a world, to stand still is scary. Hartmut Rosa observed, "The pre-modern experience of being excluded is replaced in modernity by the constantly present, fear-inducing possibility of becoming excluded, in the sense of getting left behind." Things change faster, and we keep keeping up because we are afraid to die. Whoever lives twice as fast can realize twice as many worldly possibilities, and thus, as it were, live two lives in the span of one. Whoever becomes infinitely fast no longer needs to fear death, the annihilator of options. Acceleration becomes a secular substitute for eternity. To achieve this salvation, we try to make things faster and easier to save time. But one of the greatest hoodwinks we ever pulled on ourselves was not noticing that the things we do to save time leave us with less of it and more alone in it. No technological change is only technological. The car allowed people to travel more quickly and whenever they wanted, but once available, it meant people could live further from where they worked. So cities and towns changed, personal associations changed, roads divided neighborhoods, created new opportunities, while ending others. Jobs and industries and cultural forms of expression and a whole different society sprang into existence simply because we found a way to move faster. Likewise, smartphones and the internet made information access and communication easier and faster, but that's not all they did. Along with them came new social conventions, new communities, new levels of exposure to ideas and conflict, a new understanding of what it meant to be available. That's a lot to have to adapt to. They even redefined what now is made of. Digital spaces are filled with not just what's being said, but also what has been said. And it's all right there, not tucked into a library across town or on a tiny plaque on a statue covered in bird poop. It's in our hands and outside of time. Things used to acquire signs of age, veneers that tucked them appropriately into their place in time. Now, they're automatically updated to always look like now. Digital spaces are so packed with timeless messages between bygone people that we don't even ask, "Is anyone here?" anymore. Instead, we ask, "Is anyone now?" In order to adapt to all of this, we have to consume information in an increasingly dehumanized, decontextualized, and decentralized way. Each next bit is often unrelated to the last. Our participation is not acknowledged or assumed, and it's all fed to us by machines we don't know and didn't build that only put it in our eyes and ears. The sheer weight of all of this accreting information and its growing accessibility is awe-inspiring. It may even be our purpose. I mean, what else produces such detailed records? Purposefully or not, we record, save, collect, organize, and preserve events like nothing else in the universe. I've said before that if humans were to go extinct, the sun would still shine, the universe would keep expanding, Jupiter would continue being gassy, but the universe would lose its best autobiographer. But the technologies of this project have yet to address our bodies. Enter the TV paradox. Remember the short-long and long-short patterns of time? Well, a new pattern has been emerging and growing in frequency. Short-short. It was first observed in people watching TV alone. They reported feeling like time flew by quickly. Oh, wow, have I really been watching for 4 hours? But later, they didn't remember their TV session as a major moment of significant import or duration. They didn't attend to the passing of time during it. They didn't feel bored or like time dragged, but they also didn't accumulate a lot of new, significant, memory-worthy experiences. Rapid, stimulating streams of experience provide a fullness that makes time fly by, but fractured, desensualized, one-way experiences feel unconnected to ourselves and our larger life histories. Retrospectively, they don't fill up a lot of space. They burn our time on both ends. It feels shorter during and after. Interestingly, short has not been found when people engage with content they have connections with. For example, things they own memorabilia of, made friendships through, attended conventions about. So the pace of life may be taking your life from you, but standing could give you your life back. In the future, we will surely find other ways to overcome the negative side effects of the faster experiences we crave. The development of digital media that engage the other senses, more linked as they are with long-term memory, or that build contexts for us could help. So could surgical solutions, like removing the parts of the brain that make us not like doom scrolling. Probably first, any anxieties will be recognized as a condition treatable with medication. Now, this is all to say that we live in a transitional period. The conquest of space made the world smaller, and now the conquest of time has made our lives smaller. We live after the conquering of time, but before its resurrection. In the meantime, make some time for time to control you. Be bored, miss out, fall behind, feel time passing. Lose track of time while experiencing only what your body can alone. You might not have the time of your life, but you'll have more time of your life. I'll see you next time. And as always, thanks for watching. A great way to engage all of your senses is a subscription to our Curiosity Box, a seasonal delivery of viral physics toys, puzzles, books, games, all curated and cooked up by us. Our winter box comes with a kinetic torus knot, a device for creating electricity out of produce, try bananas, and lots more. Our mission at the Curiosity Box is to be good for all brains. So we donate a portion of all proceeds to Alzheimer's research and our Inquisitive Fellowship, which just gives money and resources to educational creators so they can make the kinds of videos they want to make. Do your brain a favor and sign up today. I'm really proud of it and I appreciate all of your support. And as always, thanks for watching. Hey, Vsauce, Michael here, and the iTunes store contains 28 million different songs. Last.fm carries 45 million songs, and the Grace Note database of artists, titles, and labels contains 130 million different songs. That's a lot. If you were to listen to all of the songs in the Grace Note database one after the other in a giant playlist, it would take you more than 1,200 years to complete. But since there are a finite number of tones our ears can distinguish, and because it only takes a few notes in common for two musical ideas to sound similar, will we ever run out of new music? Will there ever be a day where every possible brief little melody has been written and recorded and we are left with nothing new to make? A good rule of thumb might be to say that if modern recording technology can't distinguish the difference between two songs, well, neither could we. So let's begin there,
with digital downloads, MP3s, CDs, and a calculation made by covered in Bs. Digital music is made out of bits. Lots and lots of bits, but each individual bit exists in one of two states, a 0 or a 1. Now what this means is that for any given, say, 5-minute long audio file, the number of possibilities, mathematically speaking, is enormous, but mind-blowingly finite. A compact disc, which samples music at 44.1 kilohertz, is going to need about 211 million bits to store one 5-minute song. And because a bit can exist in two states, either a 0 or a 1, the number of possible different ways to arrange those 211 million bits is 2 to the 211 millionth power. That value represents every single possible different 5-minute long audio file. But how big is that number? Well, let's put this in perspective. A single drop of water contains 6 sextillion atoms. 6 sextillion is 22 digits long. It's a long number, but the total number of atoms that make up the entire Earth is a number that is about 50 digits long. And estimations of the total number of hydrogen atoms in our universe is a number that is 80 digits long. But 2 to the 211 millionth power, the number of possible different 5-minute audio files, is a number that is 63 million digits long. It is a number larger than we can even pretend to understand. It contains every possible CD-quality 5-minute audio file. Inside that amount is everything from Beethoven's Fifth to Beck's Loser. It even contains a 5-minute conversation you had with your parents when you were 3 years old. In fact, every one of them. It even contains every possible conversation you didn't have with your parents when you were 3 years old. But it is finite, not infinite. It's cool to think about, but it doesn't come very close to answering the question of this video, which is how many possible different songs can we create and hear the difference between. So for that, we're going to need to narrow down our hunt. On Everything 2, Ferris Lepidoptera made a calculation that involved some assumptions that I think helped narrow the field down in a really nice way. She took a look at the total number of possible different melodies you could create within one octave, containing any or all of the intervals we divide octaves into. Of course, sound frequencies can be divided much more granularly than that, but giving ourselves more notes might mean we could make more technically different melodies, but they wouldn't necessarily sound any different to our ears. Now, given a single measure containing any combination of whole, half, quarter, eighth, 16th, or 32nd notes, she calculated that there would be this many possible unique measures, which is a smaller number than we had before, but to put it in perspective, this is how many seconds old the universe is. Uric DE's calculation is even more specific. He stayed within one octave, but instead of looking at a complete measure, he only considered the number of unique combinations of 8 notes. He also assumed that typical melodies as we know them today only contain about 3 different types of note length. For instance, quarter, eighth, and 16th, or whole, half, and quarter. To be sure, that will most likely not always be true. Musical tastes hundreds, thousands of years from now will most assuredly be different. But given melodies as we know them today, across 8 notes, over 12 intervals, there are about 79 billion possible combinations. We're getting relatively small here. I mean, under this definition of melody, 100 songwriters creating a brand new 8-note melody every second would exhaust every possible melody within only 248 years. But it's still a huge number, way bigger than the total number of songs that have been written that we know about. So you can quite safely say that no, we will never run out of new music. But here's the rub. If that's the case, why are there so many commonalities between songs, even across hundreds of years? How come so many songs kind of sound the same? I mean, if we have more possibilities than we could ever exhaust, why is Twinkle Twinkle Little Star, the Alphabet Song, and Baa Baa Black Sheep all the same melody? My Country 'Tis of Thee and God Save the Queen, interestingly enough, are the same song. Love Me Tender is exactly the same as the old American Civil War song, Aura Lee.
Sunshine came along with me, and I always will.
And a seemingly uncountable number of songs merely sound like other songs. The SpongeBob SquarePants theme has a very similar cadence to Blow the Man Down. SoundsJustLike.com is a great resource for exploring this further. It'll show you two songs and how they sort of sound alike. And when it comes to musical chords, it's almost as if there's no variety at all, as was famously shown by the Axis of Awesome's 4 chords. I've linked it in the description. It's worth a watch if you haven't seen it already. These guys sing more than 40 different songs using the same 4 chords. Even though the number of possible different melodies is gigantic, us humans tend to gravitate towards certain patterns that we like more than others, and we are influenced by what came before us. Kirby Ferguson has a fantastic series looking into this called Everything is a Remix. I've also linked that down in the description. The commonalities he shows are pretty crazy. Well, even when it comes to lyrics, to writing, even though mathematically there are more possibilities than we could ever exhaust, we have gravitated towards a few. In fact, there is a form of poetic meter that is so common, it's called common meter. I've composed a verse using it to explain what it is. Line 1 contains 8 syllables. The next contains just 6. For emphasis, iambic stress, that's it, no other tricks. Here is a list of songs that are written in common meter, also known as ballad meter. The commonness of common meter is the reason you can sing the Pokemon theme song to the tune of Gilligan's Island, or House of the Rising Sun, or Amazing Grace. You could also use almost any of Emily Dickinson's poetry. Sure, they're different melodies, but their lyrics are written in the same meter. There's a great video here on YouTube that I've linked below in the description that uses captions to let you see just how these all fit together. Oh, and don't forget one of the greatest compositions taking advantage of common meter's commonness, Stairway to Gilligan's Island. And you know what? Our brains may also be keeping us from enjoying the entire mathematical space of available songs. For instance, research has shown that the way a song compresses using software can help us predict how enjoyable it will be. Too simple, too easy to compress, like, say, a rising scale, and the song doesn't challenge us, it's boring. But too complicated, say, white noise, and the file won't compress very much at all, and likewise, we don't seem to enjoy it. There's a magic zone where a file is compressible by a computer and also happens to be enjoyable by us. So, interestingly, even though mathematically speaking, there are so many possible unique melodies that we can safely say there will always be room for new music, we don't seem to be wired to care. We enjoy certain patterns and melodies, and calculating how many there could be is a lot less interesting than how connected and similar all the ones that we enjoy are. It's as if we have more space than we need, more space than we could ever hope to see all of, or visit all of, or know all of. But no matter what new place we go, in a general sense, new popular music will always remind us a bit of home. And as always, thanks for watching. Fantastic, you're still here. If you want to hear music from people like you, from Vsaucers, go check out Vsauce. You can submit music, animation, short films, anything that you're making and putting on YouTube to us, and we'll feature it on Vsauce. It's like a trailer for what Vsaucers are doing. Speaking of which, Jake Chudnow, who does all of the music in these videos, has a brand new song out over on his channel, which I highly suggest you go give a listen.
Hey, Vsauce, Michael here. This point of light in the sky is Earth, as seen from the surface of Mars. And this is Earth as seen from Saturn. Here's an image taken only 45,000 kilometers away, the famous blue marble. But what does Earth really look like? Well, it depends on how you define look. The word look comes from the old Breton word lagud, meaning eye, the human eye. And that's part of the problem. Images like this are based on light humans can see, but we don't see everything. There's a fantastic episode of Radiolab that uses sound to illustrate just how different other creatures' visual spaces are from our own. When we talk about the way something physically looks, we are talking about the visual perception of emitted or reflected electromagnetic radiation, specifically visible light. Light we perceive as red has a longer wavelength than blue or violet. But what if I crank the wavelength even shorter? Does it stop being light? No, it just becomes light you can't see. Ultraviolet, X-rays, gamma rays. Going the other way, you get infrared, microwaves, and finally, radio waves. In principle, the spectrum of possible electromagnetic wavelengths is infinite. But even within the range of wavelengths we observe, the breadth is breathtaking. If the entire practical spectrum of wavelengths was laid out linearly from New York to Los Angeles, the visual portion we see would only be the size of 100 nanometers, small enough to slip through a surgical mask. Point is, when it comes to what there is to see, our eyes miss out on a lot. For instance, take a look at a remote control. Many of these things communicate with light of wavelengths we can't see, but mobile phone cameras can. Try this at home. Push a button on a remote control and you won't see much, but use a mobile phone camera to detect wavelengths you can't see and have them rendered visible. There's a whole lot going on we miss out on. Our night sky is full of frequencies we can't see with our eyes alone, but chromoscope.net allows you to extend your vision. This is the Milky Way as we see it, the visible light it gives off, but slide to see how it would look if our eyes sensed other frequencies. Of course, we are having to represent these other frequencies with visible colors, because even electromagnetic pretend time is bounded by our puny limits. As for Earth, if we only saw infrared frequencies, it might look something like this in our minds. Ultraviolet and extreme ultraviolet vision would return unrecognizable spheres. With X-ray vision, auroras around the poles would shine brightly, and gamma-ray vision would give Earth a bright edge from high-energy electromagnetic radiation hitting the atmosphere at a shallow angle. So, which view is correct? Is there an absolute true appearance of the Earth? We haven't even started yet. Look back at the blue marble. What's with the tyranny of north meaning up? Perhaps it's because we often equate up with better, and many early map makers were from north of the equator. But upside down maps are equally true, no matter how strange they may seem to us. Funny enough, the famous blue marble itself is a product of north equals up bias. It didn't originally look like this. The crew of Apollo 17 originally took it like this. NASA rotated it to fit our traditional idea of up after the fact. Here's a visual of Earth that comes from the US Naval Observatory's live animation of our planet. You can see exactly what parts are in its shadow at this very moment. Other shadows fall on Earth as well, like the moon's shadow. Last week, Bad Astronomer shared this image. The dark smudge on the left is actually the moon's shadow during a solar eclipse as seen from above Earth. There's another problem with the blue marble. It's flat, and the Earth is three-dimensional. A globe is the best way to represent the Earth, but globes are difficult to carry around, and even when displayed in 2 dimensions, well, you just can't see everything at once. A flat map of the Earth is really convenient, but it requires projecting a globe onto something flat, and a sphere's surface cannot be represented on a plane without distortion. The West Wing famously pointed out the limitations of flat maps. There is no such thing as a perfect flat map of the entire world. Some maps are useful for some things and other maps for other things, but it is really fun to pick on the Mercator projection, mainly because it's so popular, and is even used by Google Maps, mainly because it's so easy to zoom in on. It preserves shape decently well, but suffers when it comes to area. As I've shown before, Africa is huge. Its area is so large, the entire contiguous United States could fit inside of it, along with all of China, India, Japan, and much of Europe. But on the Mercator projection, scale near the poles is pretty wonky, distorted, which means Greenland appears to be as large as Africa, even though in reality it is only 1/14 the size. There's more. Check out Alaska and Brazil on a Mercator projection. They appear almost the same size, but in reality, Brazil is nearly 5 times bigger than Alaska. Areas near the equator are minimized, whereas areas closer to the poles are exaggerated. To have fun with this problem, play the Google Maps Mercator puzzle. The red pieces are countries projected outside of their usual locations. Now, what the heck is this weird shape? Well, let's pull it away from the North Pole where scale is distorted a lot, and oh, it's Australia. You can see how the math behind map projections distort Earth by interacting with them on Jason Davies' brilliant site. Notice how small Greenland appears on the Mercator projection when pulled down to the equator, and how exaggerated it becomes when moved to the edge. To be fair, the Mercator projection is great for navigation. If you want something that is more fair when it comes to area, try the Gall-Peters. Here, land masses are the right relative size, but shape is sacrificed. Everything looks a bit too narrow. Enter the Mulvide. This projection shows equal areas and is a bit more pleasant shape-wise. If you interrupt the Mulvide around the oceans, relative area is preserved and the shape of land masses becomes even more accurate. When it comes to the shortest route between 2 places on the surface of the Earth, mnemonic projections are really cool. Every straight line journey taken on Earth's surface is actually part of a great circle. On Mercator projections, actual straight line paths look curved, but every straight line on a mnemonic projection is also a straight line in real life, the shortest route. If you want a compromise between shape and area, you might try the pleasant Winkle triple, which the National Geographic Society has used for maps it produces since 1998. Or a beautiful butterfly map that can be a ball until it's flattened, say under a pane of glass. The Dymaxion map can unfold to show how nearly connected Earth's land masses are. It's a great way to visualize human migration over time. It's quite impressive how far and wide humans have traveled on Earth, but it remains a bit of a disappointment to realize just how narrow our slice of visual perception really is. But don't feel bad. This brings us to the story of Julian Bayliss. Yes, hello, is this Dr. Julian Bayliss?
Yeah, speaking.
Bayless told me about how one day, while using Google Earth, he spotted some dark green vegetation. It looked like a rainforest. An expedition was scheduled, and it turned out to be just that, a rainforest we had previously never seen. I asked him more.
So what have you found there?
To date, we found about 12 new species, just from Mabu. So we found about 3 snakes, 2 chameleons, a bat, about 4 butterflies, 2 new species of plants. And we've only really just been into the forest edge. So I read a paper the other day, a scientific paper. They estimate that there's maybe 8.5 million species in this world, but we've only actually discovered 1.5 million, or between 1.5 and 2 million. So we've actually only discovered maybe 1/5 of everything that's living on this planet.
Wow, our eyes only see a tiny fraction of what there is to see. But within that tiny fraction, there are still an enormous number of things left to find. So keep searching, keep looking.
And as always, thanks for watching.
Hey, Vsauce, Michael here, and subscribing to Vsauce is a no-brainer. Or is it? I mean, you would need your brain to understand the words that I was speaking, and you would need your brain to decide whether or not you liked what you were hearing. You would also need your brain to move your muscles in just the right way to click the subscribe button. In fact, you need your brain to do a lot of stuff, and without a brain, well, you can't do much of anything at all. So, literally speaking, is there really such a thing as a no-brainer? Let's begin with no headers. Decapitation. It's a macabre subject, I know, but what's the matter? Are you chicken? Okay, good, because Mike certainly was. In 1945, farmer Lloyd Olson went out to grab a chicken for supper. He cut the chicken's head off, and it didn't die. Mike the headless chicken lived for another 18 months. He toured the country and surprised onlookers. He could walk and perch and was fed by putting little drops of water or pieces of grain down his throat. But here's the thing. Mike the headless chicken's actions weren't a no-brainer, because even though he didn't have much of what we would call a head left, he did have a bit of his brainstem. If we want a clearer no-brainer, we're going to have to look at an even more simple creature, the cockroach. These guys don't even breathe through their heads, so without one, they're fine. Instead, they breathe through holes all over their bodies. And instead of being controlled by a big, massive brain, they have little bundles of nerves, ganglia, throughout their body. And so even without any head parts, even when completely decapitated, a cockroach can live for weeks. It can walk around, respond to movement. Really, its only problem is that without its head, it will eventually starve to death. Us humans are not nearly as fortunate. Without a head and brain, we die within seconds, if not instantly. But before you get jealous, keep in mind that with our heads intact, we are capable of some actions that don't necessarily require the brain. Reflexes. When you snap your finger moves at about 20 miles per hour, and a really big sneeze can expel air at nearly 30 to 40 miles per hour. But nerve impulses, they're really quick. They can clock in at 250 miles per hour. But sometimes that's not even fast enough. For instance, if you accidentally put your hand on a hot stove, cells are dying quickly, and 250 miles per hour doesn't cut it. You need to take an action fast. It's not worth it to tell your brain what's happening right away. And so instead, your immediate reaction to pull away is mediated by other parts of your nervous system. The same can be said for involuntary and unconscious processes. So, in a way, these unconscious, involuntary, or reflexive behaviors could be considered no-brainers.
but I'm not quite satisfied yet because they still require that your brain be there, keeping you alive. So, what if you weren't alive? Well, in your dead, brainless body, your muscle cells still contain a little bit of energy in the form of ATP. Backyard Brains, right here on YouTube, demonstrates this with insect parts. This leg is no longer connected to a brain or a body, but energy remains in the cells, and so researchers can detect electrical signals when the leg is touched or even simply breathed on.
Whoa, that popping sound you're hearing is the spontaneous discharge rate of the living neurons in a still living leg.
The muscle cells of a human limb would respond in just the same way. But you don't need wires to observe behavior like this. Salt can also do the trick. The introduction of sodium ions can cause a process similar to an action potential in a living animal. Salt added to these fresh frog legs makes them dance. Though not for very long. The cells will eventually run out of energy or simply decay. But to be sure, there are many other brief candidates for no-brainers at the moment of death. For instance, muscles relaxing, causing a person to soil themselves. Technically a no-brainer, but it's a misconception that a corpse continues to grow fingernails and hair. Instead, it's actually the skin itself shrinking as it dries, making hair and nails appear longer. But let's take a closer look at these skin cells, because we might be onto a quite satisfactory no-brainer. Your skin cells live on the periphery of your body, and they don't require a constant stream of new nutrients from your blood. And so even though you are dead and your brain is no longer calling the shots, your skin cells can continue to live, gathering nutrients through osmosis and dividing for days. In fact, you can harvest skin cells from a corpse after 24 hours. On a related note, digestion. Sure, a lot of the digestive process is completed by you being alive and having a nervous system that works. But part of the work is done by bacteria that just happens to live inside your gut. And when you're dead or your brain is gone, they'll continue digesting. So in a way, making poop, at least part of that process, is a no-brainer. But here's the thing. These bacteria that live inside you are foreign bacteria. Are they you? For that matter, what about the skin cells that can continue to live after you're dead? Are they you? Or are they merely cells that you have made a good home for? We're getting pretty philosophical here because we're basically asking if you are merely your brain, and everything else that goes on when you no longer have one is just other stuff that you aren't doing. You could argue that without a brain, your body no longer has your intentions. It no longer does things because you have decided to do them. In other words, a no-brainer may be impossible for you to do because it requires not using you. If you are merely what your brain does and not what your cells do off on their own when the brain's gone, then in a way, being you, being alive, is a yes-brainer. Another great yes-brainer is checking out Vsauce 3. You can find some scientific video game analysis, some gamer loot, and some pretty cool apps to download. Go check that out, and as always, thanks for watching. Hey, Vsauce, Michael here. I've been watching Bravest Warriors on Cartoon Hangover lately. It's great. It was created by Pendleton Ward. And in the show, teenagers zip around the universe visiting star systems and planets. And here is my question. When will we do the same? Us humans in real life. I mean, we've managed to put people on the moon and land robots on asteroids and Mars, and even Titan, a moon of Saturn. Interplanetary travel is scary cool, but will we ever travel interstellarly? Certainly it will happen, right? I mean, Voyager 1 is expected to reach interstellar space sometime this year, or maybe in the next year or two, and it was launched way back in 1977. So shows like Bravest Warriors are pretty much just a glimpse of our future, maybe even one within our lifetimes. Right? Well, we're going to need a dong for this one, something you can do online now, guys. The Hayden Planetarium's digital universe allows you to explore a three-dimensional map of our Milky Way. Now, there are about 81 visible stars within just 20 light years of our own sun. The nearest is Proxima Centauri, which is only 4.3 light years away. Getting there? Piece of cake. Piece of difficult cake. Because a light year is an incredibly long distance. It's the distance that light in a vacuum will travel in an entire year. And in just 1 second, light can travel so far as to circle the entire equator of Earth. 7 times. Now, a fast bullet can travel at about 1,500 meters per second. And Voyager 1 is traveling at about 17,000 meters per second relative to the Sun. Also relative to the Sun, our Earth is orbiting at a speed of 29,800 meters per second. That's pretty fast. But the fastest man-made object ever was the Helios 2 solar probe, which traveled at a maximum speed of 70,220 meters per second. Impressive, right? Well, even at that speed, the fastest speed ever reached by any man-made object, crossing this little old gap and reaching Proxima Centauri would take 19,000 years. But technology in the future is bound to be improved, along with the maximum speeds we are able to obtain. Even using what we know now, a solar sail could easily provide the acceleration needed to reach near light speed speeds. And our current understanding of physics theoretically allows for things like wormholes, which in theory could move a spacecraft from one point in space to another faster than light normally could. And who could forget the famous Alcubierre drive, an idea that fits within most models of our universe and proposes a way to deliver a spacecraft to a distant object faster than light can get there, not by moving the spacecraft, but instead by collapsing and expanding space itself. Things like wormholes and Alcubierre drives are theoretical, but if they could one day become a reality, how far away might that day be? It matters, and figuring out exactly when in time we should begin an interstellar journey is called a weight calculation. Leave too soon, and before a ship launched today full of frozen embryos ever got to its destination, it would be passed by astronauts who left hundreds or thousands of years later at a point in time when technology was advanced enough to lap what we have today. Andrew Kennedy calculated that given the pace of our progress as far as travel velocity is concerned and Earth's mean annual economic growth, the soonest human civilization might ever reach Barnard's star, 6 light years away, is 1,104 years from today, which isn't within any of our lifetimes. It might also be a bit optimistic because it assumes that we not only solve the problem of speed, but that we also solve problems like how to survive interstellar radiation for years, or how to avoid collisions with interstellar material at high speeds. It also assumes that before we achieve the technology needed to successfully interstellarly travel, all of humankind isn't wiped out by some cataclysmic natural disaster. It may sound unlikely, but we're not talking about the near future, we're talking about thousands of years from now. Let's put it this way, even given our current
slow means of space travel. It's estimated that within 5 to 50 million years, we could theoretically explore and colonize our whole galaxy. That's a lot of time, though. In fact, statistically speaking, within the next 500,000 years, it's very likely that Earth will encounter a meteorite nearly a kilometer across. Hopefully, when that happens, we have the prevention abilities needed to keep ourselves safe. But given all of this information, it's easy to see why the 2008 Joint Propulsion Conference concluded that it was improbable that humans would ever explore beyond the solar system. It's quite depressing to think that scenes like this one from Shutterstock may be destined to only ever remain that, science fiction. Wait, how quickly is the camera moving in that clip? We're used to seeing science fiction scenes like this, but a nebula tends to be light years across, which means that in this clip we are traveling at least the speed of light, if not faster. Would it really look like that? I covered this briefly in my black hole video, but not completely. If you were to travel at the speed of light, or near the speed of light, the universe ahead of you wouldn't look like it usually did. First of all, your field of view would increase. It would appear as if the universe was receding away from you as you accelerated. At the same time, all of the light reaching you would be blue shifted until you were left with this. You may have seen this on Vsauce too. It's the cosmic background radiation blue shifted all the way up into the visible range. MIT Game Lab offers a free downloadable game that puts you in an environment where the speed of light can be lowered all the way down to typical walking speed. You can experience all of the visual effects I just discussed, but I wanted to know what it would look like if the speed of light was where it is, and I took a journey from Earth to the moon. So I enlisted my friend Liam from World of the Orange and New Music to put together a simulation of what it might actually look like to accelerate to nearly the speed of light and then slow down during a trip from Earth to the moon. Enjoy. Whether or not you should believe that all the right factors will come together and humans will one day travel that quickly or reach interstellar destinations largely comes down to whether you want to be an optimist or a pessimist. But what we've accomplished so far is quite amazing, considering how weak, flimsy, and vulnerable the human body is in the vacuum of space. Bad Astronomer and SciShow have great videos discussing this topic. And now, thanks to the brilliant team at Bravest Warriors, I'm going to go to space. But not while wearing a Vsauce suit. No. I'll do it naked. Well, okay, no, not that naked. And also maybe some muscles? Yep, so that's pretty much what I would look like. The moment I'm exposed to the vacuum of space, my body would not inflate and explode. Now, the body's a very nicely contained system, but those parts of me that aren't well contained, they'll be the first to go. The air in my lungs and digestive tract would quickly rush out. Moist, soft tissues would rapidly lose water. My mouth and lips and eyes would dry out and swell. As water was pulled to the surface of these things, it would vaporize, and the decrease in its pressure would cool my mouth and eyes to near freezing. My body would inflate to about twice its normal size as gases in my blood came out of solution, slowly evaporating away, cooling the surface of my skin. Oh, and the blood vessels in my eyes would likely burst, spilling blood into my eyes, which along with all the other fluid in my eyes would be rapidly vaporizing on the surface, freezing and drying them out. Within about 15 seconds, I would go unconscious because oxygen wasn't reaching my brain. And as far as I'm concerned, that would be the end of the entire ordeal. For another 90 seconds or so, I would still technically be alive, but I wouldn't be aware of it or remember any of it. My dead body would remain internally quite warm for a while, because in the near vacuum of space there isn't much matter to conduct or convect heat away from me. Instead, I would really only lose heat through radiation, a much less efficient method. It would take hours for me to cool down to the temperature of space, and by then I would be nothing but a dried up piece of slightly bloated and stretched, desiccated human jerky. If I was exposed to the sun's full-on radiation, not filtered by the usual atmosphere of Earth, I would be a grossly sunburned piece of jerky. In case that makes you hungry, let me give you some nutritional facts. 200 pounds of human meat in outer space would eventually become about 120 pounds of freeze-dried jerky. And given what would be left of me that would be edible, as a snack, I'd be worth about 115,000 calories. Maybe humans are the only intelligent life in the universe. But if you believe that intelligent life could have arisen on other planets, an interesting idea occurs: the Fermi paradox. Enrico Fermi calculated that given the number of planets believed to exist in our galaxy, at least some of them must have been habitable to life as we know it, and in many cases, millions and millions of years before life on Earth even existed. So if interstellar travel, traveling between stars in different solar systems, really is possible for intelligent life to do, why have we not been visited by aliens yet? Well, maybe we have been visited. Maybe they're here right now and we just can't perceive them. Or maybe we haven't been discovered. Or maybe we are alone. Or maybe we're just not worth visiting. So what are you waiting for? Live your life in a way that makes traveling light years just to hang out with you worth it. And as always, thanks for watching. Hey, Vsauce, Michael here. Eating your own boogers is gross, but it might be smart. Assuming you have clean fingers, lung specialist Frederick Bischinger points out that snot contains antiseptic enzymes that kill or weaken bacteria. Reintroducing those crippled microorganisms may allow your immune system to develop antibodies in relative safety. Now, that is good to knows. But is eating your own snot cannibalism? Self-cannibalism? Just like a cow or chicken or fish or fruit or vegetable, you are made out of a lot of edible things. The meat on an average human body contains 77,000 dietary calories worth of nutritional energy. Yum. If you decide to become a cannibal, just don't show up late for dinner or you'll get the cold shoulder. Jokes aside, cannibalism is a major taboo. It's off-putting at a visceral level. Humans have dignity. They are more than just skin bags full of organs. They're more than just something to put on a plate. But human meat has been put on plates and in bellies. There are reports of cannibalism occurring in times of famine, as a last resort, and because of curiosity and art. In the late 1980s, artist Rick Gibson publicly ate human tonsils and other donated human parts in London and Canada. In 2006, artist Marco Evaristi cooked and canned meatballs prepared with his own body fat, removed via liposuction. In 2011, Dutch TV presenters Dennis Storm and Valerio Zeno cooked and ate pieces of each other on a TV show whose title meant guinea pigs. Because both of them lived and both consented to the act, they didn't do anything illegal. 1 year later, a Japanese man posted this tweet. 5 diners took up his offer, and on April 13th, 2012, they were served a $250 per plate meal consisting of his genitals. A darker story occurred in 2001 when Armin Maivis ate and killed a volunteer he found on the now defunct Cannibal Cafe. Although his meal ostensibly consented to the menu, Mivus was convicted of murder, and now, serving a life sentence in prison, has become a devout vegetarian. Disgust aside, one question remains. If you were to use your taste buds to taste your bud, what would it taste like? To be clear, taste is a sensation caused by something in your mouth chemically reacting with receptors in your taste buds. Flavor is the even more complex experience of taste combined with smell and information from the trigeminal nerve about things like temperature, texture, pain, and pungency. As far as the cooked but otherwise unadulterated, spiceless, sauceless flavor of human meat, the late William Seabrook provided, in my opinion, the best description. While in West Africa, Seabrook interviewed members of the Gyr tribe, people who had eaten human flesh, and found their descriptions unsatisfactory. So, when he returned to Paris, he struck a sneaky deal with an intern at the Sorbonne and obtained a chunk of human meat from an otherwise healthy body recently involved in an accident. He carefully prepared the meat and wrote that, quote, "It was like good, fully developed veal, not young, but not yet beef. It was mild, good meat with no other sharply defined or highly characteristic tastes, such as, for instance, goat, high game, and pork. The steak was slightly tougher than prime veal, a little stringy, but not too tough or stringy to be agreeably edible. The roast, from which I cut and ate a central slice, was tender and in color, texture, smell, as well as taste, strengthened my certainty that of all the meats we habitually know, veal is the one meat to which this meat is accurately comparable." Seabrook never gave us any recipes or complimentary flavor recommendations, but that brings us to this video's title's second meaning. What does human taste like? What does the human palate prefer? Interestingly, of all the possible combinations of identified flavors we consume, human cuisine only features a relatively small number of recipes. A couple years ago, Scientific Reports published a great paper on the chemistry and networks behind food pairing. Researchers took 381 ingredients used in 5 global cuisines and 1,021 molecular compounds known to contribute to their flavors and created a flavor network. The size of the bubble represents the ingredient's prevalence in cooking. The thickness of the lines connecting ingredients reflects the number of flavor-inducing molecules they significantly share. The researchers' flavor network backbone spans 14 different food categories and is quite interesting. By comparing this network to tens of thousands of recipes, they found that North American and Western European dishes tend to combine ingredients that share flavor compounds, while East Asian cuisine avoids them. But that trend was caused by a few outliers in each cuisine that, if ignored, caused the difference in amount of sharing to lessen. Those few ingredients tend to be the most authentic. They tend to be the most responsible for the taste palette of a regional cuisine and contribute to this illuminating visualization. But some flavors don't go together in any cuisine. For instance, orange juice and toothpaste. Why does orange juice taste so disgusting right after brushing? Well, most toothpastes contain sodium lauryl sulfate, a chemical that helps the paste get sudsy and frothy during use. That action helps pull brushed off debris away from your teeth, but sodium lauryl sulfate also suppresses sweet receptors in your mouth and destroys phospholipids that inhibit your bitter receptors, making sweet orange juice taste not so sweet and grossly bitter for up to an hour after brushing. What interests me the most about flavor is the fact that the things that cause it eventually become you. You are what you eat, scientifically. Your body is always losing dead cells, but the elements and molecules you ingest are processed by your body into new body. Here's a fun way to think about it. Under the direction of DNA, a cat is made out of air, water, and cat food. That's it. Cats have less varied diets than humans. We can taste sweetness, but cats lack the gene required to do so. However, they can taste ATP, a molecule that moves around chemical energy for cells to use in the body, which may be a sign to them that they're tasting meat. The point is, sights and sounds and textures and shapes and smells are the names we give to things that eventually become our memories. But flavor is the name we give to the experience of things that eventually become our bodies. Contemplating the flavor of human meat is gross, but think of it this way: you are currently tasting human. You are tasting human right now. Your tongue and taste buds are in contact with your mouth almost constantly. Now, granted, it's more of a passive thing. Your mouth just happens to contain your tongue. You're not actually eating yourself, but you kind of are. Your body is constantly swallowing your own mucus and digesting pieces of your body like dead cells from your tongue and cheek. But that's nothing compared to the self-cannibalism of the sea squirt. The sea squirt lives a sort of self-cannibalistic flowers for Algernon life. When born, it resembles a tadpole and has a notochord, putting it in the same phylum as humans. It swims around until it finds a nice place to adhere, a rock, a plant. Once stuck, it begins retrogressive metamorphosis, literally digesting its own nervous system, eating the closest thing it ever had to a brain, and lives the rest of its life in a sensile, unlocomoting clump. It is a bit of a downgrade, but they are prime evidence that the evolution of the brain was spawned by the need to move. As soon as these guys don't need to move around, they eat their brains. That is way more extreme than the self-cannibalism you participate in every day by swallowing, but don't feel bad. About every 3 months or so, you swallow and digest your own body weight worth of you. That means that every day you are a little more than 1% of the mythical Ouroboros, the snake eating its own tail. You are what you eat, but you are also a thing that you eat. And as always, thanks for watching.
Hey Vsauce, Michael here, coming to you from my hotel room in London with a little camera that I taped to a bunch of furniture I stacked up, which is better than nothing, and as you can tell from the title of this video, it's also what we're going to discuss. Nothing. Can there ever be nothing? I mean, we're surrounded by matter all the time. Even this glass is not empty. I know you might think there's nothing in it, but it's full of air, and air is packed. 1 cubic centimeter of air contains almost 30 quintillion molecules. But if I remove the air from this glass, I can create what is known as a vacuum, an awesome word that uses a double U, but not a W. The challenge, however, is removing all of the air. To this day, the best scientists have been able to do is to create what they call an ultra-high vacuum. At this point, 1 cubic centimeter of space contains not 30 quintillion molecules, but a mere and amazing 100. To put that in perspective, a vacuum cleaner like you use at home hardly changes the thinness of the air at all. In fact, if you use a vacuum cleaner at sea level, the vacuum created inside the operational part of the machine only has the thinness of air found in Denver, Colorado. If you want thinner air, if you want even fewer particles per cubic centimeter, you're going to have to leave Earth. But before we go too far, let's talk about high altitude flying. When you're in an airplane 30,000 feet high, the outside air is very thin and dangerous, so by law, the airplane must keep the inside of that commercial aircraft pressurized so that it only feels like you're no more than 8,000 feet high. The reason it's dangerous is that when air gets that thin, there's not enough oxygen for your brain. This man is about to remove his mask, temporarily and with supervision, in the actual thinness of the air around him. Within less than a minute, he suffers from hypoxia, a lack of oxygen. And even though he appears to be awake and alert, when told to put his mask back on, or else he will die, he does nothing.
Put up the switches, or you will die. Put up the switches. Put up the switches.
But a lack of oxygen, a lack of air, a lack of matter can get even more dangerous when you go above 60,000 feet, about 19,000 meters above the surface of the Earth. This limit is known as Armstrong's limit. We all know that the boiling point of water decreases as your altitude increases, and at Armstrong's limit, the boiling point for your own blood drops all the way down to the temperature of your own body. If you reach that altitude without wearing a special suit, bubbles will form inside your blood, and your body will inflate to twice its normal size. But because your internal organs and your skin are flexible, you won't explode. So let's talk about outgassing. Outgassing is why it's so difficult for us to reach an ultra-high vacuum. If you remove so much air from this glass that there's fewer than 100 particles per cubic centimeter, the glass itself, or whatever material your chamber is made out of, will start to lose its own trapped gases. But materials don't need to be inside partial vacuums to outgas. It happens all the time, and is especially noticeable in confined spaces. For instance, a car. All of the adhesives and chemicals used to make that car will outgas and collect inside, creating what we know as the new car smell. Alright, time to leave Earth for good. Let's go into the space between planets. Now remember that in a laboratory, the best vacuum we've been able to create is about 100 particles per cubic centimeter. Well, between the planets and our solar system, there is space that only contains 10 particles per cubic centimeter. And if you leave our solar system into interstellar space, you're only going to find about 1 particle per cubic centimeter. The real winner, though, is intergalactic space. Leave the Milky Way altogether, and you can find regions where there's only 1 or 2 particles per cubic meter. Okay, that's cool and all, but would it be possible to find a region of space where there is absolutely and literally nothing, no matter at all? Well, according to quantum mechanics, no. First of all, you've got gravitational and electromagnetic fields that extend forever because the particles that cause those fields to happen have no mass whatsoever. And this is what's really mind-blowing. There's a thing known as virtual particles that's happening all the time, even around us right now where there's no vacuum. These virtual particles come into existence and then disappear. And we believe they exist for a couple of reasons. One big reason is the fact that our universe continues to expand, even though that shouldn't necessarily happen. Where are we getting that extra force that pushes it, that causes it to keep expanding? Well, these particles that pop into existence and disappear may be the answer. Even crazier is an effect we've observed known as the Casimir force. If you put 2 pieces of metal nanometers apart inside a vacuum, they will be pushed together. One of the most popular theories for why this happens is that these virtual particles popping into space and then disappearing are actually reflecting off of the metal. But because the plates are so close together, particles with wavelengths longer than that gap don't get reflected. So there's more virtual particles pushing on the outside than the inside, and the metal plates contact. I know these concepts have gotten pretty crazy, but rest assured that really all it means is that whenever you feel down and feel like nothing matters, you're scientifically incorrect. Nothing matters. There can't be nothing. There's always matter. There's always something. And as always, thanks for watching.
Hey, Vsauce! Michael here. According to the US Census Bureau, right now, in America, there are 106 people named Harry Potter, 1,007 named James Bond, and 8 people named Justin Bieber. There just aren't enough names to go around. There are more than 300 million people in America,
But 150,000 last names and 5,000 first names is all you need to name 9 out of every 10 of them. When are we going to run out of names? Perhaps it's already happened to you. If it hasn't, when? 10 years, 20 years, 100, 1,000? When will someone with your exact name become famous? So famous, in fact, that your legacy changes forever to just being not the person people think of when they hear your name. And for that matter, when will every reasonably memorable, pronounceable band name or brand name be taken? When will authors have no choice but to just start reusing book titles? According to Rovi Corp, owner of AllMusic.com, the most used band name is Bliss, followed in order by Mirage, One, Gemini, Legacy, Paradox, and Rain. In the past, when fewer bands had already been created and you couldn't just Google up every single band, overlap was easier to get away with, and one-word band names were plentiful. But now, after years and years and years of band formation, well, we have the who, but we also have the what, the where, the when, the why, the how, and even the. In order to stand out now and have your own unique name, you have to be a bit more creative. Oh, Diarrhea Planet. Or Betty's not a vitamin. Which, by the way, is no longer true. Betty became a vitamin in 1994. What about Twitter handles or email addresses? Have we already reached peak username? We already find ourselves often having to use abbreviations, initials, numbers, or just choosing something completely different. Will our children, or our children's children, live in a world where the only remaining Gmail addresses are just random strings of alphanumeric characters? Are we approaching a name crisis? And if so, should we even call it a name crisis, lest we use up yet another precious name? Maybe you already share your name with someone famous, but if you don't, how long will it be until you probably will? I mean, new famous people are popping up all the time, faster now than ever before because of the internet, and they are gobbling up top Google search billing. Maybe it won't happen until long after you've been dead, but shouldn't the reservoir of names not taken by notable people eventually run out? Computer scientist Samuel Arbesman approximated how many famous people there are alive today, and I think his calculation will be helpful. You see, he points out that if we allow famous to simply mean being notable enough to have your own Wikipedia page, well, because there are 700,000 living people with Wikipedia pages right now, that means 1 out of every 10,000 people on Earth today are famous. Assuming at the least that that proportion remains constant, since 255 people are born every minute, that means every hour a future famous person is born. Their name destined to become primarily associated with them, not everyone else who shares their name. All of those people will be relegated to disambiguation or the postnomial, not the famous one. Luckily, if you do the math, you'll find that even at a rate of 1 future famous person born every hour, it would still take dozens of millennia for most of us to expect a future famous person with our exact name to emerge. Plus, names change. New ones become popular, others obsolesce. But for fun, let's not focus on names we popularly use and instead look at how many possible names there can be. The Social Security Administration allows up to 36 letters for a complete name. Now, including spaces, 27 letters filling 36 spots with repetition allowed means 3 sextillion possible combinations. That's more than Earth has atoms. So let's refine our limits. How many pronounceable names are possible? For that, I say we look at what Randall Munroe, the author of the fantastic What If, did when asked about naming stars. If you want to give every single star in the observable universe a unique but pronounceable English name, how long would the names have to be? His approximation is really fascinating. If we define a pronounceable word as a word that contains consonant-vowel pairs, we can roughly figure that there are about 105 different such pair possibilities. 105. That's not too much different from 99. So, funny enough, there are about the same number of consonant-vowel pairs possible as there are two-digit numbers, which means we could give every star in the observable universe a sayable, unique name with just 24 letters, the same number of digits it would take to just number all of them. So the bottom line is, we may each have to give up uniquely owning a word or name that's common today, but the potential number of names that can be made is really hardy. In fact, before we run out of those, our species will likely evolve to communicate in a completely different way. Also, names aren't just labels. A name on a screen, a username, a handle, a screen name, doesn't always act exactly like its owner. Usernames can travel more quickly and more widely than flesh and blood people and do things that their puppeteers wouldn't normally do away from the keyboard. It's called the online disinhibition effect. If you can't see the people you're interacting with and they can't see you, you're all just online hiding behind different names than usual, why hold back? I mean, clearly such a system can't be serious business. On the internet, no one knows you're a dog. Why be nice or tell the truth? The subreddit Karma Court investigates and uncovers people who may think that the less face-to-face nature of the internet makes lies easier to get away with. Like this person who posted an image suggesting that they'd been single for a year, but had, users found out, posted 3 months earlier a picture of my girlfriend's cat. These behaviors aren't just what humans do when they can be anonymous or can hide behind different names. These behaviors can also be caused by the names themselves. Studies have found that the username you use can impact how you behave. Your own pre-existing stereotypes and expectations of certain words, shapes, colors can be confirmed by your behavior, in the same way that studies have found NFL and NHL players play more aggressively when wearing black uniforms. Studies have also found that the more sexualized an avatar is you make someone use, the more conscious they will be of their own body image. And the more an avatar resembles you, the more correlated you watching it exercise is with you being more likely to exercise more. It's called the Proteus effect. The features of a cyberspace version of yourself, a username, an avatar, can actually change you, the meat space IRL you. Usernames and avatars then aren't just handles attached to us. Psychologically, we often interact with them as if they're friends, distinct beings we created. They help us out, but they also can influence us, egg us on, dare us to do things we wouldn't normally do because they offer us protection, entertainment. Some make us feel safe, professional, funny, dangerous, attractive. We want cool ones. The cool ones make us look cool. As we go about our daily lives and vie for attention, we are more and more frequently doing so with another name, and exclusively through that name only. So it becomes quite interesting that we're not going to run out of them anytime soon. In fact, they might run out of us first,
and may, in many ways, run us. And as always, thanks for watching. Hey, Vsauce, Michael here. But you are actually right there. Well, at least the camera is. Mirrors are amazing. In fact, the word mirror comes from Latin mirari, meaning to wonder at, to admire. It's also where we get the word miracle. Mirror-a-cole. Like when mirrors face each other and transform a toilet room into infinity. I love this kind of stuff. But what if, instead of a rectangular prism, the room was a sphere, mirrored all the way around? What would it look like? What would you see floating around in such a room? The first question we should ask involves the light source. If you were in this room using a flashlight and you turned the flashlight off, would the light keep bouncing around off of the mirrored walls, illuminating the room until your body absorbed all of it? Or, if you left the flashlight on, would light continue bouncing around, building up, getting brighter and brighter until you lost your vision and cooked? Probably not. Every time light hits a mirror and reflects off, a tiny, tiny amount is absorbed. Even if your mirror spherical room was the size of a giant stadium and its walls reflected 99.99% of light on each reflection, light's speed is just too fast, meaning that the reflections will happen rapidly. A little bit of light being lost each time, the room will go dark in a fraction of a second. To you and me, it would seem instantaneous. As for what it would look like, let's pretend you begin with your face up against a wall of the sphere and float backward toward and past the center. At first, you would see your face quite clearly. The surrounding reflections would be very distorted. As you moved away, at a certain point, your face would cease to shrink away and appear smaller in the mirror, and instead would grow larger and become magnified until you reached the center, at which point your face would fill your field of view. As you continued on past the center, your image would flip upside down and continue receding away. It would look a bit like this. But don't get too enamored with your reflection, because mirrors don't show you as you really are. Have you ever wondered why you like the way you look in a mirror, but don't like how you look in photographs or video? It might be because of the mere exposure effect. You prefer what you are used to. And most mirrors you look into don't show the real you, the you that other people and cameras see. Instead, a mirror shows you a reversed version of yourself, and you've become more comfortable with that version of you. A version of you that is flipped left to right. Mirrors reverse along axes perpendicular to their surfaces, like left and right. They don't also flip things upside down. They don't also reverse up and down because those directions are parallel to the surface of the mirror. When it comes to the way you and other people look, the difference can be startling. NPR pointed out that Abraham Lincoln looked like this. Mirrored, he would have looked like this. Now, to us, something seems noticeably strange about it, but it is the Lincoln would have preferred. It's what he saw every day in the mirror. But here's something really cool. You can take a flexible mirror and unreverse its image by folding the mirror into a cylindrical shape. Take a look at this. Here I am with a reflective material, and there is the camera with some text taped underneath. As you can see, everything is flipped left to right. But as I fold the sheet into a cylindrical shape, the image separates, revealing an unreversed version. It becomes a true mirror. Finally, here is one last piece of everyday mirror trickery. When you look into a mirror, how big is your reflection, your image on the surface of the mirror to you? Surely it depends on how far away you are from the mirror.
but it doesn't. When you look into a mirror, your reflection on the surface of that mirror is always the exact same size. In fact, it is always about half of your actual size. This is because when light reflects off a mirror, it comes in and reflects back out at the same angle, which means that in order to reach your eyes at the top of your body, light from your feet at the bottom must hit the mirror halfway between the two. The triangles you form with a mirror are similar regardless of where you stand. You can demonstrate this effect by outlining the size of your own head as it appears on the surface of a mirror using a bar of soap. Now, because you aren't here, let's pretend that this phone is your head and its camera is your eye. We begin up close. The camera looks really big from this perspective. Let me just carefully trace around the outside so we can compare later. Good, good, good. Okay. Now, I'm going to pull away from the mirror. Clearly, the phone is smaller, right? Well, if I reach out and once again carefully trace the edges, there we go, I will find that I have drawn a rectangle that is the exact same size. Your image on the surface of a mirror from your own perspective is always the same size, whether you are a few centimeters away from the mirror or a few kilometers away. Your image on the surface of a mirror, in fact, is always half your actual size. Okay, enough about light returning to our eyes. What about light that never returns? Could we use a telescope to resolve individual aliens on a planet light years away? Well, over on Vsauce 3, Jake investigates this question with Star Wars. And my friend Rusty investigates the potential for Star Wars becoming real in his episode of Science Friction. And Vsauce 2 has a brand new loot all about cool Star Wars stuff. Check them all out, and as always, thanks for watching.
Hey, Vsauce. Michael here. No rocks from Mars have ever been brought back to Earth, and no human has ever touched anything on Mars. But that's about to change. National Geographic has asked me and Jake and Kevin to talk about Mars because they have a show coming out soon all about how we are planning to turn Mars into a home. A place where humans will soon be living and working. It's a plan set to become a reality in the 2030s. That's cool, but beyond just how, there are everyday life questions raised. We would be literally beginning society all over again on a new planet. Whose laws will Martian colonists follow? What kind of watches, clocks, and calendars will they use? And what will be lost if we as a species gain Mars? Is it okay to touch Mars? What will its flag look like? In 1998, Pascal Lee designed a flag for Mars that was flown at the Hutton Mars Project Research Station, where how humans might live and work on other planets was studied. The flag is a nod to Kim Stanley Robinson's famous Red Mars, Green Mars, and Blue Mars trilogy. Should we have the technological and political ability to do so at some point in the future, we could terraform Mars from a red planet into a green with life and then blue, watery, Earth-like one. This flag has since been used by a number of Mars exploration societies and was even flown into space aboard Space Shuttle Discovery by astronaut John M. Grunsfeld in 1999. That all makes it a pretty good contender to be the first official flag of Mars. The Outer Space Treaty, of course, prohibits national appropriation of celestial bodies, but it doesn't necessarily stop private individuals or companies from doing so. But since it takes months at best to actually go between Earth and Mars and minutes to even communicate at light speed, how would and who would enforce laws on Mars? If Martian colonists did things that we here on Earth disagreed with, what could we do to pressure them otherwise or punish them for being criminals? One idea, extraterrestrial liberty, is to just give up control and release those headed to Mars from all current Earth-based laws their nationalities hold them to allow them to become Mars citizens, able to make laws, elect, live, and die the way they want, free from any currently existing state. That might be reasonable, but it raises another question. When is Mars now? What time is it there? For colonists on Mars, an Earthwatch would be of very little help. A day on Mars, the time it takes the planet to turn around once, sunrise to sunrise, is about 2.7% longer than on Earth. I mean, that's pretty close, but over time it adds up. Gradually, an Earthwatch on Mars would drift, and the time it said would tell you very little about night and day on the red planet. To combat this, scientists on Earth who work with robotic rovers on Mars use Mars time. They actually live by it. You can download a program that tells you solar times on Mars, or do what many scientists have done. Get yourself a watch that runs 2.7% slower than usual. If every second, every minute is 2.7% slower than it should be, it'll be perfect for matching Mars's rotation. That could spell trouble for Martian colonists, though, who wish to tune into live events on Earth, like sports or award shows. But again, given the immense travel time between the two, Earthlings and Martians may find that having similar timekeeping systems just isn't really that necessary in their everyday lives. Okay, right now on Earth, it is 2016. As we know, one trip through all the seasons from now will have been a year. But in that same time, Mars will have only traveled part of the way through its seasons. If Martian colonists continue to use Earth years, that's okay, but it would mean that for them, years would feel a bit arbitrary. They wouldn't contain environmental cycles like ours do. Perhaps, if they feel disconnected and emancipated from Earth calendars, they'll just use their own Martian year system as well. A few such calendars have been proposed, some divided into familiar week and month lengths, but with about twice as many of each per year. The thing, however, that fascinates me most about putting humans, living things on Mars, is a more touching topic. Literally, humans will likely touch the red planet in our lifetimes, and the first to do so will be famous. But joke's on them? I mean, we, me, you, we're all already touching Mars. Let me ask you this, where did you get that body? That one you're in right now? It's made of atoms and molecules, but they come and go. You eat and breathe and absorb things, use them for a while, but eventually shed or exhale or otherwise pass them through. A month from now, your skin will be completely different skin, all new cells. The red blood cells you've got now will only be with you for about another 4 months. Like a water wave, you're a temporary arrangement of stuff, a really neat thing that dirt does. But not all of this dirt that you are, the dust in From Dust to Dust, is Earth dirt. New stuff is always falling to Earth, anywhere from 5,000 to 300,000 kilograms of space rock, dust, debris, asteroid fragments a day, some of which inevitably winds up being you, part of your body for a while. Now, that may sound like a lot of material, but compared to the mass of Earth, it's small. Some of these ET rocks are debris that's been floating around our solar system since the planets formed. Some has come from asteroid collisions, some has even come from interstellar space, beyond our solar system. What's neat is that because atoms and molecules are so small, even the tiny amount of interstellar material landing here adds up to a lot at the atomic scale. Ask a Physicist estimated that if only 0.01% of all the extraterrestrial material falling to Earth comes from beyond our solar system, and even if only 10% of that stuff is water, that would still mean that 50 billion with a B, of the water molecules in your body right now, as you watch this video, were in interstellar space fewer than 1,000 years ago. Some of the space material falling to Earth comes from planets like Mars. When powerful enough impacts occur on its surface, Martian material can reach escape velocity and begin an interplanetary journey. Rarely, but occasionally, this journey terminates on Earth. It's been estimated that Martian meteorites only fall to Earth about once every 50 years or so. That's a long time in human years, but in planet years, that's nothing. Your physical body, right now, likely contains billions of atoms that used to be on Mars and arrived here on Earth in the last 1,000 years. If you consider stuff from Mars that's been here on Earth for less than a millennium as being Martian, well, it's tenable to say that you are 0.0000000000000000001% Martian. But before you get too excited, there's a difference between Martian debris that was roasted and exploded in our atmosphere centuries ago and actual still on Mars material. The difference might be small, or it might be big. When Apollo 11 astronauts returned from the moon, they didn't splash down and then run into the arms of family members. Instead, they were locked away in quarantine for 3 weeks, just in case the moon harbored any kind of previously unknown or unthinkable life form, an organism or virus that could have come back to Earth with them. One that Earth life had never encountered and thus never been naturally selected to resist. The threat of a moon bug pandemic wiping out life on Earth was just large enough that NASA took precautions. Though later, Buzz Aldrin admitted on Twitter that their quarantine facility wasn't perfectly sealed. Luckily, no moon germs escaped and infected all Earth life, probably because there weren't any to begin with. After Apollo 14, the moon quarantine requirement was lifted because it had become sufficiently clear that the moon was devoid of life. But Mars? Well, we still don't know exactly. We haven't found macroscopic life on Mars, but the possibility of tiny things hasn't yet been ruled out. And the incredible consequences contamination could have means it remains a serious concern. There's even an advocacy group of scientists from all over the world called the International Committee Against Mars Sample Return. But it's not just bat contamination that matters, the transfer of extraterrestrial organisms to Earth. There's also forward contamination, the transfer of Earth organisms to things in space. Any life that might currently exist on Mars could be incredibly vulnerable to things we here on Earth barely notice, but accidentally bring there. How sad would it be to one day find life on Mars, only to realize that it's all dead? Everything it had to teach us about itself, about Mars, about the solar system, about life, wiped out just a few years ago by a virus stowed away unbeknownst to us on one of our robotic missions. Extremophile organisms have been found that may be able to survive such a trip. Life here on Earth may have even arrived from space in that way, a concept called panspermia. So should we be scared of monsters beyond our atmosphere? I'm reminded of the glowworm. In their larval stage, the glowworms stick to the tops of caves and leaves, usually above water sources. Their glow resembles the night sky, the tempting expanse of other worlds beyond our own. Like us, bugs are attracted to this vista, believing it's a way out of the cave. Of course, it's not. The glowworms dangle sticky mucus strings from their perches, snares that capture their prey. Are the real stars no different? A clever trap that keeps alien predators fed? Probably not. But that hasn't stopped space agencies like NASA from forming divisions like their Office for Planetary Protection, a group that oversees plans for missions that might bring Earth and alien life into contact. Currently, all missions to Mars must satisfy the Coleman-Sagan equation. This sterilization restriction works to ensure that the probability of us contaminating places like Mars with foreign earthly organisms is not 0, but at most 1 in 10,000. That was considered acceptable given the number of Mars missions we'd probably do before fully understanding its exobiology. So far, we have no evidence that anything is alive on Mars right now, or has ever been. But that brings us to ANSMET, the Antarctic Search for Meteorites, an effort that since 1976 has found more than 20,000 extraterrestrial rocks in Antarctica. The first one they found in Allen Hills in 1984 was special. For one thing, it's believed to have originated on Mars. It's estimated that about 17 million years ago, this piece of rock was blasted off the surface of Mars by a meteor and reached terminal velocity about 5 kilometers per second, fast enough to leave Mars entirely. After flying through space for a very long time, 13,000 years ago, it got captured by Earth's gravity and fell to our planet's surface. 12 years after its discovery, the presence of what looked like microscopic fossils were discovered on the rock. Could they be evidence of Martian life? The claim didn't convince everyone, but to this day, the structure's exact origins haven't been explained. How exactly to tell whether they're caused by living things isn't agreed on either, but the finding was a major event in the field of astrobiology and the public's understanding of it. The discovery was possibly so momentous that US President Bill Clinton gave remarks about it, saying,
"Today, Rock 84001 speaks to us across all those billions of years and millions of miles. It speaks of the possibility of life. If this discovery is confirmed, it will surely be one of the most stunning insights into our universe that science has ever uncovered."
After his statement, these are the 2 questions he was asked by the press. Did he believe abortion rights were under attack? And where did he get his tie? The thing is, alien nanobacteria don't wear ties. They don't legislate or govern us or control our lives or look anything like us. If they exist, we'll most likely be in control of them and probably actually not even notice them under our boots. So does protecting or preserving them not matter? I mean, should we just not let them get in the way of our progress as a species? Well, that's a fundamental question that touches upon what we want our purpose to be in this universe. Labeling parts of Mars "don't touch" as parks would be a great way to preserve it as it was before we came, so that our grandchildren and their children can see what Mars was like for, well, most of human history. Others have argued that we shouldn't go at all, that Mars is best left to itself. Humans ruin things, and what right do we have to alter Mars if we can help ourselves? Still, others say, why stop at natural parks? If we find viable life on Mars, it may be struggling to survive. A rare relic, perhaps from a time when Mars was more hospitable to life. They argue that we should help change Mars so that those remaining Martian organisms can thrive and multiply and be their best selves. With our technology, intelligence, and sapience, we perhaps alone in the solar system have the power to help them, and we should help ourselves to Mars second. These aren't just hypothetical philosophical problems, by the way. With plans for manned missions to Mars just a bit under 2 decades away, they're questions we will actually need to answer quite soon. Should humans go to Mars? It would be a great way to spread out, to diversify our habitats so we're still around should anything happen to Earth. And of course, it does give us more space for more people. But for what? Ultimately, Jupiter doesn't care if there are 7 billion humans or 7 trillion. The volcanoes of Io will continue erupting whether or not we write any more poems about love. If humans were wiped out today, the fundamental forces of the universe wouldn't change, and distant galaxies would continue their journeys into the abyss, beyond the observable universe, just as they already are and always will. What good is life to the universe? Perhaps it has none. But we are possibly its greatest and only hope to find out. We may not treat life as well as we could, but whatever this darned life thing is, keeping it around might very well be up to us. We owe it at least that much. And as always, thanks for watching. For more on how we plan to make Mars home, check out National Geographic's new global event series, Mars, premiering Monday, November 14th at 9/8 Central. Hey, Vsauce, Michael here, but what could be out there? The likelihood of extraterrestrial intelligence has been the subject of an equation, and the current lack of any communication with aliens the subject of a paradox. But here's a different question. If we were to hear from intelligent life beyond Earth, what would really happen next? Well, no government has ever officially adopted a post-detection policy. And when asked how they would deal with a confirmed message from extraterrestrial intelligence, the United Nations Office for Outer Space Affairs simply said that their job does not include any issues regarding the question you pose. So are we unprepared? Would chaos ensue? These things are unlikely, but the way we prepare for and anticipate our species encountering one from beyond Earth is important and illuminating, even though improbable. Historically, we have acted as though alien life exists. Back contamination is a concern that a man-made object returning from space could carry with it undiscovered alien life forms, especially viruses and bacteria that could wipe out life on Earth. This was a serious concern felt by serious people when we first sent humans to the moon. When Neil Armstrong, Michael Collins, and Buzz Aldrin returned from the lunar surface, they didn't immediately hug their families and join a public parade. Instead, they were sealed up in biological isolation garments and flown to a quarantine facility to be locked away for 3 weeks in Houston, Texas. By Apollo 15, the practice was discontinued, but forward contamination has also been a real concern. When NASA sent the Galileo spacecraft to survey Jupiter and its moons, it got amazing data, but there was a problem. It had never been sterilized. Because life, even liquid water, could exist on these moons, NASA made the decision to avoid contaminating an alien biosphere, and when the mission was over, steered Galileo into Jupiter, where it burned up and was destroyed, along with any Earth life possibly on board. So protocols and decisions have been officially made in the past under the assumption that aliens might exist.
When it comes to actually hearing from aliens, receiving a message from technologically advanced life forms capable of sending us, say, a radio signal, groups like SETI, the Search for Extraterrestrial Intelligence, are the ones actively listening. They have an ear to the sky.
And they are prepared. The SETI Committee of the International Academy of Astronautics created a declaration of principles concerning activities following the detection of extraterrestrial intelligence. No government has officially adopted any of its recommendations, but if something were to happen, it would likely be the first place authorities went. It's one of the only handbooks they'd have. Seth Shostak explained the philosophy and atmosphere at SETI, predicting that because verifying a signal is slow, and the media are fast, you will be media blasted about a possible detection days before the people who find it are certain it's for real. In the midst of rampant media speculation, elation, and panic on the part of the public, the most likely string of official events after the discovery of a message from extraterrestrial life would follow SETI recommendations. First of all, the individual or team who discovered the message would continue to assess the credibility of the message and alert all parties to SETI's declaration. Next, once they were certain the message was real, the Central Bureau of Astronomical Telegrams would be alerted, so as to inform observers all over the world. They would also inform the Secretary General of the United Nations, because Article 11 of the Treaty on Principles Governing the Activities of States in the Exploration and Use of Outer Space, including the Moon and other bodies, says they should. The first official news we got, the public, would likely be in terms of the Rio scale. First presented to the International Astronautical Congress, the Rio scale measures the significance of consequences of evidence of extraterrestrial life, making it a likely tool to be used because it neatly manages public reaction. There's a great online calculator you can play with to see how the Rio scale works. It takes into account the credibility of the message on a scale from believed extraterrestrial origin to hoax, how repeatable the observation is, what type of message it is, for instance, is it uninterpretable or clearly for us, and how far away it is. Is it extragalactic or near enough that we could respond and hear back within the length of a human lifetime? Seth Shostak and Ivan Almar applied the Rio scale to fictional and historical events. It's a great way to get a feel for how the Rio scale will affect the vocabulary authorities use when reporting on an extraterrestrial message. They considered the moon monolith, discovered in 2001, A Space Odyssey, a 6 on the Rio scale. Noteworthy. In the movie Independence Day, the initial unidentified signal would be about a 4 to 8, moderate to far-reaching. Once the message is confirmed to be no further than the moon and moving, it would be an automatic 10. Extraordinary. In real life, the Martian face discovered in 1976 was a 2, low, until high-resolution images from 2001 revealed it was nothing. Just a thing that looked funny under the right conditions, and was immediately downgraded to a 0. No significance. So if we were to receive a message from extraterrestrial intelligence, those things and those words would likely be used. But who would be in charge? Although she denies ever being selected or prepared for such a role, Maslin Othman, the director of the United Nations Office for Outer Space Affairs, is a pretty good candidate, as is Paul Davies, the chairman of SETI's Post-Detection Task Force. Were it to be necessary, both of those people are in positions to become ambassadors for Earth-alien relations. So what do we say back? Well, if we want to show that we are intelligent, perhaps we should send back a string of information representing pi, or the Fibonacci sequence. Or maybe we shouldn't say anything at all. Stephen Hawking warned, quote, "If aliens visit us, the outcome would be much as when Columbus landed in America, which didn't turn out well for the Native Americans." And Professor Simon Conway Morris, a Cambridge University paleontologist, has said that if the cosmic phone rings, we shouldn't pick it up. Observations like that are at the core of the importance of this video's question. We can learn a lot by looking not just at how we prepare for a space message, but how we imagine actual contact with aliens going. Anthropologist Catherine Denning frequently points out that the ways we imagine contact with aliens happening often says more about ourselves than it does any hypothetical aliens. We do this all the time. When we project our own modern-day ambitions and fears onto prehistoric people, Christopher Ryan and Casilda Heta call that Flintstoning.
So let's piggyback off of that phrase and label any projection of modern human behaviors, desires, anxieties onto futuristic, technologically advanced beings capable of visiting us jetsoning. Some examples of jetsoning involve thinking that any aliens out there trying to contact us might want to hurt us. Maybe that's simply because whenever we have met new people, we often enslave them or pity them or take advantage of them. It's also possible to think that aliens will be friendly. They'll want to help us. The ways we imagine them helping us say a lot about the kind of help we think we need. There's a poetic idea that from space, Earth looks peaceful. All of the boundaries we have put up don't exist. You can't see them. But that's not entirely true. The old boundary between East and West Germany is still visible from space, each side using different light bulbs. And this is the boundary between Pakistan and India. You can see from space India flooding the border with lights to deter smugglers from bringing across weapons and ammunition. We don't all get along together here on Earth. We are afraid of each other, we don't trust each other, and the wrinkles and scars that causes are visible from space. Imagining how aliens would interpret that, communicate with us, and how we would or should respond teaches us a lot about ourselves. It makes our struggles strange again, less ignorable, and that is the entire point of fantasy. G.K. Chesterton said that the function of the imagination is not to make strange things settled, so much as to make settled things strange. And as always, thanks for watching. Hey, Vsauce, Michael here. Why do humans wear clothing? Sure, we need it for protection from the elements and fashion, to show our personalities, but no other animal makes and wears clothing. More importantly, why do we feel embarrassed to be naked around other people?
The word embarrass comes from the Portuguese root embaraça, which means to entangle or entwine.
And feeling embarrassed often feels like being tied up or exposed. But how can a healthy amount of embarrassment be a sign that you are likable, forgivable, and trustworthy? This t-shirt and hoodie come from the YouTube Space LA, which opened in November of 2012. But clothing has been around a lot longer than that. For at least the last 100,000 years. Clothing protects us from the cold, from rain, from the sun. And it can also be an ornament, a way of accentuating certain parts of our bodies or showing off wealth, status. It can even help us build our own identities. But today, I'm interested in another use of clothing, modesty. Why are humans afraid to be naked? Why are we ashamed of nudity? Especially because animals pretty much walk around naked all the time. Why aren't animals embarrassed to be naked? Well, let's take a closer look at embarrassment. Embarrassment is a fascinating emotion, and an extremely social one. You don't really ever feel embarrassed alone when no one's watching you or listening to you. So, embarrassment probably evolved because it is such a good influence on social cooperation. We feel embarrassed when we violate little social rules of conduct, and each of us individually hoping to avoid that, to avoid embarrassment, has helped all of us live together better. Healthy brains experience embarrassment. Neurodegeneration of the frontal and temporal lobes can lead to less awareness of yourself. So a healthy amount of occasional embarrassment is a good thing. It's a sign of a socially adept and normally functioning brain.
A famous experiment involved participants watching an actor receive praise for achieving a very, very high score on an exam. In some cases, the actor was told to feign pride in the achievement, and in others, they acted embarrassed to have attention put on themselves. Later, the actors and the participants played games together, and the participants were more pro-social, friendly, and cooperative with actors who earlier expressed embarrassment. It suggested that the actor was to be trusted, that they desired to fit in and work together. Now, the fact that embarrassment displays our knowledge of others and our desire to be liked may explain why evoking embarrassment in others, whether it be flirtation or playful teasing, is so common when we kind of like the other person. Shame is a stronger emotion, and shame, when it comes to our private parts, the kind nearly every society, Western or not, shares to some degree, is related to the root of our question today: modesty. Havelock Ellis's writing on the evolution of modesty is a bit antiquated when it comes to vocabulary, but he discusses quite well two possible reasons for our fear of nakedness, both of which predate clothing and are not unique to humans. The first is the vital phenomenon of refusal. Before mating, many animals play a game of chase, hard to get, a game of acceptance and then flight, forcing the pursuer to keep up and prove their determination before being chosen as a desirable mate. So when it comes to humans, we can think of clothing, paradoxically, as both a means of drawing attention to one's body and simultaneously as a way to cover the body modestly, making us less available to every and any potential mate, rendering breeding more selective. Ellis also mentions the fear of evoking disgust, and it's easy to see why individuals of a species who avoid things we consider disgusting would survive better. Fecal material, waste, rubbish, other bodily secretions can spread disease. For instance, animals whose poop likely contains dangerous parasites avoid grazing around or hanging out around their waste. Habits like that lead to more sanitary conditions and a species more likely to survive. It's a satisfying piece of evidence as to why clothing, once invented, was so quickly used to cover private areas. In 2009, the BBC investigated another influential factor: raising children. In species where the young are born pretty much ready for life, it makes more sense to spend your time making babies as opposed to sitting around raising them. They don't need it. Super precocial animals like the megapode hatch with full flight feathers and can fly on their own within hours of hatching. Human babies, on the other hand, are pretty darn altricial. We are born barely able to do much besides swallow food put directly into our mouths. Newborns can't walk or talk or cook meals for themselves or drive themselves to work. It's ridiculous. Why are human babies born so unready for life? Why is so much development time still needed after human kids are born? Well, one explanation is that it's because we are so brilliant. Brain size is correlated with body size. Bigger bodies require bigger brains. The shrew has a smaller brain than a human, but us humans have smaller brains than whales. Of course, a bigger brain is not indicative of intelligence. For one thing, larger animals literally just have more cells they need to worry about and control. What matters more when it comes to intelligence is the proportion of brain size to body size. Compared to the size of our bodies, our brains are gigantic. They're outliers, they're off the charts. It's crazy. And a consequence of this is that in order to have a brain as big as ours come out of a mother as small as a human, we have to come out with brains that aren't fully
deformed, brains and heads that aren't as big as they will eventually grow to be. And this is why human babies require so much care and so much time to develop before their brains are ready for them to go off on their own. Under this theory, being naked and mating all of the time might be a little bit less of a priority for humans. Humans and societies that privilege modesty would have more time and resources to put toward raising children and avoiding extra mates instead of just conceiving more kids, allowing kids to develop properly and reproduce themselves. Clothing serves this purpose quite well. It conceals the privates and allows more time to be spent on other things. Clothing, may, in a way, actually be a consequence of our unique intelligence. So the next time you put on clothes, keep in mind that one of the reasons you're not running out into the world butt naked is because you have such a big brain. No matter how dumb the clothing is that you're putting on, it's a reminder that we are smart. And as always, thanks for watching. Kevin, thank you for joining me.
Thanks for having me.
I hear that there is an insect wing that can naturally shred bacteria.
That's right. I talk all about that and other mind-blowing things over on Vsauce 2 in the new episode of Mind Blow.
All right, well, let's go over there and watch it. In fact, you guys can come with us too. Click this annotation or the link at the top of the description for Mind Blow number 60. I hope to see you there.
Let's go.
Let's go. Hey, Vsauce, Michael here.
And Jake. And Kevin.
And we are in Santa Monica, which of course means that the V in Vsauce will stand for the Roman numeral 5, as in 5 questions from you guys. Our first question comes from Notch. He didn't ask this of me in particular, but I love how non-intuitive the answer is. Assume an Earth that's perfectly spherical and a rope stretched around the equator snugly. What would happen if that rope was just, say, 6 meters longer? 6 meters isn't very much, but because of the relationship between a circumference and a radius, 6 meters of extra rope would allow the entire rope to not fit snugly around the Earth, but 1 meter above it all the way around. That's cool, but what if instead of a rope, we used something more rigid, like a structure, a bridge, and we built the bridge all the way around the Earth, and then all at once destroyed its supports? Would it float? Clearly, the Earth's gravity would pull the structure down, but down is in the opposite direction for the other side of the bridge. Well, it turns out such a scenario would be incredibly unstable. Earth's gravity isn't equal everywhere, and if you follow @TweetSauce, you saw some great graphs showing just how much gravity changes simply based on the density of rock below. When you factor in the sun and the moon, you wind up with a bridge structure that is not gonna stay where it is. If the bridge itself was indestructible, it would start violently hula hooping around the Earth, crushing things. But there's no known material strong enough to do that. Instead, you would wind up with bridge pieces flying everywhere. A sphere around the Earth would be a bit more stable, but a ring, not so much. The ring, even if spinning, would rapidly break apart into smaller pieces. Last week, you guys asked me a question that I have always wondered. Let's say I was stranded in the mountains waiting for rescuers to arrive, but it was going to take a while. I had plenty of snow and plenty of water, but I was hungry, dying of starvation. Would it make sense to amputate one of my legs and eat it? I mean, it kind of makes sense, right? I'd have my entire leg to eat as food, which would probably fill me up, and I would have one less limb that I would need to keep alive. The only problem is that the trauma your body would endure
from the loss of a limb would greatly exceed the benefit you would get by eating the food. You're better off keeping that limb on your body because your body's process of using reserves of energy is more efficient than the process of digestion. So keep the leg on and let it wither away, keeping you alive. Don't cut it off and eat it and digest it. How does hair know when to stop growing? It's a good question, because the hair on my arm, which there's a lot of, never grows any longer than this. And if I were to shave my arm off, it would grow back and stop right where it is right now. But head hair is different. For instance, my hair, what's left of it, would keep growing if I didn't cut it. But no other animal has that situation. You don't see wolves out in the forest saying, wow, look how long my hair is getting, I better get to the barber shop. So why do humans have head hair that grows so long, but body hair elsewhere that stops seemingly right when it's supposed to? Well, first things first, the hair on your head will not keep growing forever. Typically around 6 years of growth is the limit. When hair grows, it is in what is known as its anagen phase. And for hair on your head, that phase can last up to 6 years. But the anagen phase of hair elsewhere on your body, eyebrows, eyelashes, is much shorter, except in cases like this guy, whose eyebrows grow like head hair and have allowed him to set the world record for longest eyebrows. Humans probably lost their fur coats, their thick body hair, because it didn't really help us hunting and running around sweating on the savannah. And unlike other animals, us humans had discovered fire and could make clothing to keep ourselves warm without needing a built-in fur coat. To be sure, long hair that falls over your ears and neck can keep you warmer, but leading theories also argue that long head hair may be our fault, a result of the fact that early humans picked mates that could grow longer hair on their heads. Mates that could do that were probably healthier, and in colder climates literally had a built-in hat to keep their body warm. One of the questions I get the most is about eye floaties, those little dots or squiggles that you see in your vision, especially when looking at a bland scene like the clear blue sky. Eye floaties are made out of little fibrils that occur in your eye as you age, and you can't look directly at them because they're inside the fluid of your eye. Turning your eye to look at them simply causes the fluid to move and the floaty as well. But the thing about eye floaties that I love the most is that they are almost always microscopic. You can't see them with the naked eye, except when they are inside your eye. If you were to pull an eye floaty out, you wouldn't be able to see it. But in your eye, it's close enough to the retina to leave a shadow on the retina, and that's what you see when you see eye floaties. Finally, how much would Wikipedia weigh if I printed all the text out and bound it into books? Well, luckily, there's a Wikipedia article about this very topic. The English language Wikipedia contains about 2,345,000,000 words, which, if printed at the density of the Encyclopedia Britannica, would equal about 1,759 volumes, which would look like this. Altogether, they would weigh about 7,000 pounds. If you're between the ages of 13 and 18, you may want to check out the Google Science Fair. It's an amazing competition. These guys are great. They actually helped make that Earth Bridge animation for me. So be sure to check out googlesciencefair.com. And I'll keep checking out Los Angeles. I'm here with Kevin and Jake from Vsauce 2 and 3 for the first time ever. The three of us have never been in one location simultaneously until now. So be sure you're subscribed to us because amazing videos will come soon. And as always, thanks for watching. Hey, Vsauce, Michael here. I am at the White House in America's capital, Washington, D.C. America makes a lot of feature films every year, Hollywood. But
they don't make the most feature films every year. Nigeria makes more. But the country that makes the most films every single year is India. Every 2 years, the country of India fills up enough film with unique feature films to stretch all the way from this city, Mumbai, to where I live, in London. That's double what Hollywood produces in 2 years.
That is a lot of movies. But is real life a movie? I've discussed the frame rate of the human eye before, but how does the resolution of the human eye compare to a camera or screen? VHS? Laserdisc? DVD? Blu-ray? IMAX? Numbers like these are pixel dimensions. When multiplied, they tell us the total number of picture elements an image is made up of, a figure often used to describe digital cameras. It might sound like more is better, but to be sure, numbers like 1920 by 1080 are not resolutions per se. More pixels is only part of the equation. Resolution is about distinguishing fine details, and that depends on a lot of other factors. For instance, the amount of light, the size of the sensors, what the millions of pixels are actually encoding, and how close the subject is. I mean, up close, Salvador Dali's painting of his wife looking at the Mediterranean can be resolved into boxes, but from afar, well, it's Abraham Lincoln. For crying out loud, on a small enough screen from far enough away, low and high so-called resolutions on screens aren't even resolved differently from one another by your eye. How different nearby pixels are from one another also matters. This is called spatial resolution. For instance, if I go out of focus, the number of pixels in the video frame stays the same, but you can't resolve as much detail. Now, with all of this in mind, we can still compare human vision to a digital image by asking a better question. Assuming everything else is optimal, how many pixels would you need to make an image on a screen large enough to fill your entire field of view look like real life, without any detectable pixelation? Now we are getting somewhere. Kind of. The analogy is still cruddy because a camera snaps an entire frame at once, whereas our eyes move around. The brain amalgamates their constant stream of information into what we call vision, sight. In fact, the image created by the eyeball alone during a single glance would hardly even be acceptable on a broken TV screen. We think our eyes create images like this picture Guy took of me with a camera. But for one thing, unlike a camera, you've got some stuff in the way. For instance, you are always looking at your own nose, and maybe even glasses if you have them. Luckily, our brains process those stimuli out because they don't matter and they don't change, but thinking those are the only differences is a pitfall. Literally, Latinly. The fovea gets its name from the Latin for pitfall. The fovea is the pit on your retina that receives light from the central 2 degrees of your field of view, about the area covered by both of your thumbs when held an arm's length away. Optimal color vision and 20/20 acuity are only possible within that little area. When it comes to these limitations, XKCD has a brilliant illustration. It points out other problems like blind spots, literal blank spaces in our vision where the optic nerve meets up with the retina and no visual information is received. If you bought a camera that did this, you would return it. You can find your own blind spot by closing your right eye, fixating your left eye on a point in front of you, extending your left thumb, and then moving it left of center, slightly, slowly, carefully, until it's not there anymore. Crazy. But of course, we don't see the world horribly like this because our eyes are constantly moving, dragging foveal resolution wherever we need it. And our brain's complex visual system fills in details, merges images from both eyes, and makes a lot of guesses. What we actually see is a processed image, not computer-generated imagery, but, well, meat-generated imagery. The neon color spreading illusion is a great way to demonstrate this difference. There is no blue circle in this picture. The white here is the same as the white here. A camera isn't fooled, a screen isn't fooled, only you and the fleeting gumbo of ingredients you call perception is fooled. Our vision is not analogous to a camera.
But our reformulated question can still be answered because human anatomy allows us to resolve, to differentiate certain angular distances. Famously, Roger N. Clark used a figure of 0.59 arc minutes as the resolution of the human eye to calculate, based on the size of our total field of view, how many of these distinct elements could fit inside of it. The result was an approximation of exactly what we want to know: how many individual picture elements, pixels, our vision can appreciate. His answer? 576 megapixels. That many pixels, packed inside a screen large enough to fill your entire field of view, regardless of proximity, would be close enough to be undetectable by the average human eye. But we should factor in the fovea, because Clark's calculation assumes optimal acuity everywhere. It allows the eye to move around. But a single glance is more analogous to a camera snap, and as it turns out, only about 7 megapixels, packed into the 2 degrees of optimal acuity the fovea covers during a fixed stare, are needed to be rendered undetectable. It's been roughly estimated that the rest of your field of view would only need about 1 megapixel more information. Now that might sound low, but keep in mind that there are plenty of modern technologies that already use pixel densities better than we can differentiate. As Bad Astronomer deftly showed, Apple's Retina displays truly do contain pixels at a density average eyesight can't differentiate from typical reading distances. But the fact that there are screen sizes and pixel densities that can fool the human eye is not a sign that we see in any kind of megapixely way. Human vision just isn't that digital. I mean, sure, like a camera sensor, we only have a finite and discrete number of cells in our retina, but the brain adjusts our initial sensations into a final perception that is a wishy-washy, top-down processed blob of experience. It's not made of pixels, and furthermore, unlike a camera, it's not saved in memory with veracity like a digital camera file. Absolutely no evidence has ever been found for the existence of a truly photographic memory. And what's even cooler is that not only do we not visually resolve the real world like a movie camera, we also don't narratively resolve conflict and drama in our lives like most movie scripts. The point of all of this, what I'm getting at, is an idea that initially drew me to this question. We play roles in the movie of life, but it's a special kind of movie. Cinematic victories and struggles are often discrete, resolved, like pixels with unbelievably perfect beginnings and endings, whereas the real world is all about ear resolution. I like how Jack Angstreich put it in Cinemania. In a movie, a character can make a decision and then walk away from the camera across the street and have the credits roll, freezing life in a perfect happily ever after. But in the real world, after you cross the street, you have to go home. The world goes on. Life doesn't appear in any particular pixel resolution or narrative resolution. Things are continuous. The world was running before you came around, and it will continue running after you are gone. Your life is a plot only insofar as it begins and ends and occurs in medias res. Tamara Chopin's illustration for Charles McGrath's Endings Without Endings says it perfectly. In life, there rarely is the end. There is only the and. And as always, thanks for watching.
गुलाबी आंखें जो तेरी देखी शराबी ये दिल हो गया संभालो मुझको ओ मेरे यारों संभलना मुश्किल हो गया गुलाबी आंखें जो तेरी देखी शराबी ये दिल हो गया.
Hey, Vsauce! Michael here. Earth only contains 1,066 people. Earth, Texas, the only place on Earth officially named Earth. There are at least 2 places named Moon, but the Earth only has one astronomical moon. Or does it?
From September 2006 to June 2007, Earth had an additional moon named 2006 RH-120. It's a near-Earth asteroid that usually orbits around the Sun, but for 13 months, it fell into an orbit around our planet and became another moon of Earth. We can call it that because technically a moon is just a natural satellite, something in orbit around a planet that humans didn't put there. There's no official minimum size requirement for moon status. The moon? It's a moon. Sputnik, space junk, the International Space Station? Not moons, they are artificial satellites. Astronomers believe that most of the time, Earth has additional moons. These newcomers don't always stick around that long, and they tend to only be about a meter in diameter, so we don't always detect them, and they could less sensationally be called temporary asteroid moons. But the vagueness of the word moon means that yes, technically, Earth usually has more than one. Oh, and Earth is booking it. I mean, we are moving through space incredibly quickly. A light year is an almost unfathomable distance to put into human terms, but our solar system orbits around the center of the Milky Way at about 782,000 kilometers an hour. Which means that from the perspective of the center of our galaxy, about every 1,300 years, Earth travels an entire light year. In other words, the Great Pyramid of Giza wasn't just built 4,500 years ago, it was also built almost 3.5 light years away. Big deal. What's it all worth? Could we assign a price to the entire planet, to Earth itself? Well, Greg Laughlin, an astrophysicist at the University of California, Santa Cruz, devised a beautiful equation for assessing the value of exoplanets we discover. It considers their habitability, their ease of being studied, and of course, how much money we've already spent looking for them. Funny enough, you can solve for Earth and find out that compared to what we've already spent looking for exoplanets and what we know about them, Earth is worth about $5 quadrillion. The History Channel famously stuck to Earth and rang up all of Earth's resources like water, lumber, and granite. Using the current market prices, they arrived at a total of $7 quadrillion. If you removed and isolated all of the elements your body contains and then sold them each at market price, you could fetch about $2,000. Reddit user Shady Potato applied this math to Earth. If we could mine the entire planet and separate out all of its pure elements, and prices didn't change because of that, we could sell it all for $15.8 sextillion. Of course, calculations like these don't include every single possible thing Earth or any other planet has to offer, and they also don't consider supply and demand. If someone here on Earth, or some extraterrestrial group of planet shoppers, had quadrillions, sextillions of dollars, or the equivalent amount of power, well, they would have the option to shop in a much larger store. For crying out loud, there are more than 10,000 asteroids right here near Earth, and just one of them, 433 Eros, is estimated to contain a $500 quintillion worth of platinum alone, and by weight, even more iron. So to be more realistic, instead of calculating Earth's value on Earth, let's calculate its value on the galactic marketplace, or the universal marketplace. If you, or some hypothetical group of aliens shopping for a planet, could pick any planet in the entire Milky Way galaxy, what about Earth would make it worth anything? The Milky Way galaxy is estimated to contain a supply of around 100 to 400 billion planets. As far as Earth analogs go, Kepler's space mission data suggests there are probably 40 billion Earth-sized planets orbiting within habitable zones of stars in our galaxy. And within the observable universe, quadrillions. So from a raw materials and habitability standpoint, Earth probably isn't that rare. But Earth does have some unique selling points. For one, it's probably the only planet like itself within at least 12 light years, so its location might be prime real estate for an intergalactic rest stop or eminent domain. And secondly, statistically speaking, life as we know it might not be unique to Earth, but there probably isn't life elsewhere that formed exactly like it did here, with jaguars, palm trees, and hairless bipeds who made the same buildings and jokes and art and music that we have. These might be the truest unique selling points for Earth. Aliens wouldn't have to understand or appreciate any of it. If it merely amused them, it might be worth purchasing as a sort of museum or zoo at the least. Of course, interstellar planet shoppers wouldn't have Earth currency to buy it with, and space cash isn't worth anything here. But the technology it would take for them to get to us would likely be at least thousands of years ahead of what we currently have. So an equitable trade might be, say, limited use of Earth in exchange for their knowledge, or full use or abuse of Earth in exchange for their knowledge, and fair relocation of all Earthlings to some equally habitable exoplanet. Boy, this type of speculation is totally sci-fi. But you know what's not? The next part of establishing Earth's value: demand. Despite what Earth has to offer, despite what makes it unique, and despite National Geographic's list of 10 reasons other life forms might want Earth, so far we have received 0 offers. The Fermi paradox formally phrases this puzzle. With so many friendly to life as we know it planets out there, many of which have been around longer than even Earth, why haven't we been visited by or heard from intelligent life yet? Maybe Earth and its intelligent life really are rare and special. Or maybe Earth is so typical, so unremarkable, no other intelligent advanced life forms could be bothered to stop by. But this raises another question. Even if something came by, what makes us think it would make an offer? Why would it consider our wishes at all? In Star Trek IV, the aliens wanted to talk to whales, and humans were just an awkward third wheel. When Thomas Jefferson made the Louisiana Purchase, he didn't ask, say, squirrels in Nebraska for permission. He just did it, and all of those squirrels were suddenly in America without knowing it. For all we know, that may have already happened to us. Earth could be owned by some larger interstellar landlord. Furthermore, this entire question rests on an even more fundamental assumption: the assumption that other intelligent life forms share our concept of ownership, and the belief that physical things can be bought and sold. Amongst Earthlings, human bartering is pretty unique. Only we have developed complicated, socially agreed upon norms for the barter of goods, the use of currency for goods, or the concept that you can own a piece of Earth's surface. Sure, animals can be territorial, but they haven't developed that into a more rigorous, expansive sense of fair exchange. And when it comes to an individual owning more things than they could possibly hold or defend on their own, well, we humans have systems for that. We can teach some animals to use tokens as currency to exchange for treats, but left on their own, they don't incorporate economic ideas into their regular social lives. At the most, we observe animals bartering amongst each other for services, but not goods. Why? Well, they may lack the cognitive ability required to keep track of long-term transactional histories. But they also lack 2 other extremely important things: communication and enforcement. Services, like grooming, are difficult to steal, so animals can easily trade them. But without a language to facilitate snitching, non-humans can't easily report thefts or devise systems for reporting and punishing violations. Animals create some pretty beautiful things: bowerbird nests, pufferfish circles, termite mounds, or the dramatic costumes decorator crabs fashion out of seafloor debris. But ownership and the right to buy or sell what you make is only as useful as the power you have to enforce it. And if you don't have enough power, someone or something else will make decisions for you. For instance, we have decided that animals don't own the selfies they take. 3 years ago in Indonesia, a monkey stole photojournalist David Slater's camera. He later retrieved the camera and found that the monkey had snapped these fantastic images. Slater maintained that he should receive royalties from people who reproduce the images, like Wikimedia. But US federal regulators recently ruled that since a non-human animal created these photos, they're officially in the public domain. They belong to all of us. The same goes for selfies taken by elephants, or lambs, or Asian short-clawed otters named Musa. And it's not just selfies at play here. The same goes for paintings made by chimpanzees or dog artists. So maybe Earth is worth quadrillions or sextillions of dollars. Maybe it's worth renting in exchange for technological know-how. But the mere fact that we can conceive of ourselves selling our own planet is pretty incredible. I mean, we don't have a deed to planet Earth. We really only own it via finders keepers. But we didn't stumble upon Earth like a hermit crab in its shell. We really just emerged from it. We didn't build Earth. If anything, its selective pressures built us. Does that mean Earth is sort of like a womb? Does that mean us selling Earth would be the same as a child selling his or her parents? Well, not really, because we aren't here for the purpose of leaving, analogous to being born. Honestly, the most fitting metaphor might be not that we are Earth's owners, or children, or one and the same with it, but rather that we are Earth's first willful effluvia. In the context of the human body, effluvia are little emissions of things built up within. They often make us giggle and can be gross. And isn't that what we are? A sometimes messy, stinky presence that has built up within and will one day inevitably, and to an extent already have, discharged out into space. I guess what I'm saying is that putting a price tag on Earth is all speculation. We don't know if we will ever be Earth's salesperson. But what we do know is that we are Earth's first fart. And as always, thanks for watching. Hey, Vsauce, Michael here. If you core a sphere, that is, remove a cylinder from it, you'll be left with a shape called a napkin ring because, well, it looks like a napkin ring. It's a bizarre shape because if two napkin rings have the same height, well, they'll have the same volume regardless of the size of the spheres they came from. This means that if you cut equally tall napkin rings from an orange and from the Earth, well, one could be held in your hand, the other would have the circumference of our entire planet, but both would have the same volume. I mentioned this counterintuitive fact while making a kendama with Adam Savage. Check that video out if you haven't. Or better yet, just come see us. We're bringing Brain Candy live to 24 new cities this fall. It's gonna be busy, but right now we're talking about balls and coring them. I have here two napkin rings from very differently sized spheres. One is from a tiny ball, just a little tomato that I've cored, so it's got a little hole in it right there. The other napkin ring is made from an orange, but both napkin rings have the same height. The tomato has a smaller circumference than the orange, which means less volume, but its ring is thicker, which means more volume. Both of those effects exactly cancel out, so these two napkin rings have identical volumes. They take up the same amount of space. By the way, orange oil is flammable. To see why the napkin ring problem is true, let's discuss Cavalieri's principle. It states that for any two solids, like these two cylinders I've built here, sandwiched between parallel planes, if any other parallel plane intersects both in regions of equal area, no matter where it's taken from, well then the solids have the same volume. Now that's clearly true here. These cylinders are built out of stacks of Vsauce stickers, 100 in each stack, so their volumes are the same. If I skew one of them like this, its shape will change, but its volume hasn't. It still contains the same amount of stuff. I haven't added or subtracted stickers. And Cavalieri's principle ensures that they still have the same volume, because any cross-section taken from down here, up here, in the middle, anywhere, will always give us a region of the same area as the other, because those regions are always equal area circles. Now let's apply Cavalieri's principle to napkin rings. We can see that two napkin rings with similar heights have identical volumes by showing that when cut by a plane, the area of one's cross-section always equals the area of the other's. Now to do this, notice that the area of the sphere's cross-section minus the area of the cylinder's cross-section gives us the area of the napkin ring's cross-section. Depending on where we slice the napkin ring, the cross-sections will have different areas, but they will always be the same as each other. Let's calculate the areas of these blue rings. First of all, let's call the height of the napkin ring h, and the radius of the sphere they're cut from capital R. All right, perfect. Now, a cross-section of a sphere, like this, and a cross-section of a cylinder, like this, are both circles, so their areas can be determined by using pi times the radius squared. So if we want to find the area of the sphere's cross-section and subtract the area of the cylinder's cross-section, draw a little picture of a cylinder here, all we need to do is take pi, multiply it by the radius of the sphere cross-section, square that, and then subtract pi times the radius of the cylinder squared. But what are their radii? Well, if this is the center of the sphere, we can draw a line straight up to the corner of the cylinder, down the side of the cylinder, and then connect to form a right triangle. The Pythagorean theorem will really help us here. It tells us that the length of one side squared plus the length of the other side squared equals the length of the hypotenuse squared. Now, this distance right here, this side of the triangle, is what we want. It's the radius of the cylinder. So we'll call this the little r, radius of the cylinder. Beautiful little picture there. So the radius of the cylinder squared plus this side length, which is just half the height of the cylinder, so the height of the cylinder divided by 2 squared, equals the hypotenuse squared. The hypotenuse happens to be the radius of the sphere itself, which is capital R. Perfect. Now let's solve for the radius of the cylinder, which is what we want. We'll just subtract h over 2 squared from both sides. That'll give us the radius of the cylinder squared equaling the radius of the sphere squared minus half the height of the cylinder squared. We can take the square root of both sides so that we wind up with the radius of the cylinder equaling the square root of the radius of the sphere minus half the height of the cylinder squared. Perfect. Okay, now let's take a look at the area of a cross-section of the sphere. Now for this, let's draw a straight line from the center out to the edge of the sphere's cross-section, and then we'll go straight down and connect back up. Hey, look, another right triangle. Let's call this height y, and notice that this distance now, the side of the triangle down here, is actually the radius of the circle cross-section up here. They're both equal. So we want to solve for this, the radius of the circle that is the sphere's cross-section. Okay, so we know that the radius of the sphere's cross-section squared plus this distance squared, which is y, equals the hypotenuse squared. Well, what do you know? The hypotenuse is the radius of the sphere again, capital R. Okay, let's subtract y squared from both sides. The radius of the sphere's cross-section squared equals the radius of the sphere squared minus y squared. We'll take the square root of both sides and end up learning that the radius of the sphere's cross-section equals the square root
of the radius of the sphere squared minus y squared. Y is the height that this cross-section is taken from above the equator. The higher up we take these cross-sections of the sphere, the smaller their radii will be, whereas the cylinder's radius is always the same no matter where we cut from. Okay, anyway, let's take these two radii and plug them into our formula. Okay, the area of the cross-section of the sphere is what we want first. Okay, that's just the square root of r squared minus y squared. Not too bad. Now, the radius of the cylinder is the square root of r squared minus half the height of the cylinder squared. Now, what you might notice is that we're taking the square root of something and then squaring it. So these actually cancel each other out. Perfect. Much more simple looking. But now let's distribute pi to the terms inside the parentheses. So pi times r squared gives us pi r squared. Pi times negative y squared gives us negative pi y squared. And then a negative pi times r squared is negative pi r squared. Negative pi times negative h over 2 squared is positive pi h over 2 squared. Great, now we can keep simplifying, but what you might notice is that we have a pi r squared and a minus pi r squared. Well, that just equals 0. So these completely cancel each other out. But what we're left with are terms containing no mention of the sphere's radius. Whether the radius is large or small doesn't matter. All you need to know to find the area of the cross-section of a napkin ring is the height of the napkin ring. Y, of course, is bounded by the height of the napkin ring. These blue areas have the same area as each other. And this will be true no matter where we cut the cross-section across the napkin ring, meaning, by Cavalieri's principle, that both napkin rings have the same volume. Yay. With teeth. But what does this mean for you, for life and the universe? Well, as we know, if you like it, you should put a ring on it. But if you like it, don't know its finger width, and only want to offer it a predetermined amount of material, you should put a napkin ring on it. And as always, thanks for watching. On August 21st, 2017, there will be a total solar eclipse. The shadow of the moon will race across the contiguous United States. It's going to be incredible and a little bit scary, I'm sure. I will be viewing it from Oregon with my friends at Atlas Obscura. I can't wait. But keep your eyes safe. If you want to view the eclipse, you have to have special eye protection. The Curiosity Box comes with such glasses. These block 99.999% of visible light. That's what it takes to be able to look right at the sun. That's actually what I love about these glasses. If there's no eclipse going on, you can still just look at the sun. Notice that it's a ball. Maybe imagine what kind of napkin ring you'd like to make it into. The current Curiosity Box is my favorite. The one that you'll get if you subscribe right now comes with all kinds of cool stuff. It comes with a poster showing that all the planets and Pluto can fit between the Earth and the Moon. It also comes with science gadgets like these levitating magnetic rings. Ooh, pretty cool. Also, a portion of all proceeds go to Alzheimer's research, so it's good for your brain and everyone else's brain. Check it out. I hope to see you at Brain Candy Live, and as always, thanks for watching.
Hey Vsauce, Michael here. Now, one of my favorite treats of the holiday season is Gabriel's cake. It's a super solid based on Gabriel's horn that you can make right at home, as long as your home is infinitely large. Okay, all right, now the first thing you want to do is bake a cake. I prepared this cake earlier. It's a real beautiful cake. It's a little large, but I bet you I could eat that whole thing in a day if I tried. Am I right?
Okay, now the second step is cut the cake in half. Notice that while I cut this cake in half, you don't add or create any new cake, but the surface area of the cake has increased. It used to be completely covered, and now we've got two regions on the inside that aren't covered. The next step is to cut this half, one of the halves, in half. Here we go. Again, the volume of cake on the table is the same as it was in the beginning, but the surface area is going up. As you may be able to guess, the next step is going to be to cut one of these quarters of the original cake in half. Oh yeah, it's getting pretty thin, but all you have to do is keep this up, cutting halves in half and half and half and half forever, and once you've done that, well, you're almost there. When you finish cutting, stack the halves on top of one another in order, like this, to create a beautiful tiered dessert. Because you have an infinite number of thinner and thinner slices, when you're done stacking them, the cake's vertical height will be endless. Such a cake has an interesting mathematical property. Its volume, the amount of cake it contains, is clearly no different than the amount you started with, but its surface area is infinite. It's a cake you can eat, but not frost. You would need an infinite amount of frosting to cover the whole thing with a uniform coat. An object with finite volume, but infinite surface area doesn't need to be endlessly tall, by the way. There are bounded supersolids, like this cube with an infinite number of smaller and smaller circular holes. Of course, building these objects in the real world comes with some obvious difficulties. One is the fact that the amount of steps required to complete the construction of Gabriel's cake or any other supersolid is literally infinitely many. And infinity isn't a number that, you eventually get to. It means unending. There will always be a next step, another piece to slice in half again. By definition, an infinite sequence of tasks has no last task. So you could never finish making a supersolid. Or could you? Enter the super task. What if, instead of taking the same amount of time to complete each step, we accelerated as we worked and did each step in half the time as the last? For example, let's say you want to make Gabriel's cake in just 2 minutes. Well, that's easy. First, cut the original cake in half and then wait a minute before making the second cut. Wait half a minute before making the third, a quarter of a minute before the fourth, and so on. Always waiting for half of what's left to pass before cutting again. Since you can keep dividing in half forever, there will always be another step. Infinite actions within a finite amount of time is a super task. The strange thing, of course, is that while supertasking, no matter how many steps you've already completed, there will always be an infinite amount of steps ahead. But yet, when time's up, you will have finished all of them. What we've just described is similar to Zeno's famous paradox of the dichotomy, in which the Greek hero Achilles runs a short race that he can clearly finish. I mean, people finish races all the time, but how exactly it's finished is a mystery. Because first, Achilles must cover half of the race's distance, and then half of what's left, and half again, and again, and again. Since there will always be another halfway point to reach, the number of subdivisions is infinite, there is no final destination, after which Achilles' next stop is the finish line. But yet, Achilles obviously can finish. He somehow reaches them all, despite the fact that during his journey he always has an infinite number of steps left to reach. Think about it this way. What if at each halfway step along the way, Achilles is required to hold up a flag, at even steps a blue flag, and at odd steps a red flag? Blue, red, blue, red, blue, red. The flags will alternate faster and faster. But when Achilles finishes the race, which flag will he be holding up? To be holding up either flag would seem to suggest that a largest number not only exists, but is either even or odd. Now, to this, it is often suggested that the real problem here is that Achilles isn't actually doing infinitely many things. He's just taking a few strides or whatever. A true super task requires doing infinitely many distinct actions. Fair enough. But even if Achilles ran the race in a staccato fashion, stopping at each halfway point for half as long as he waited at the last one, the scenario would still be sensical and logical and would complete in a finite amount of time. It has even been shown how a staccato runner could move to avoid discontinuous velocities and accelerations. The point is, fine. Infinite, distinct actions are at least logically possible to do in a finite amount of time, but only logically, only as a mathematical abstraction. Super tasks are obviously just products of our imagination, because in the real world, there must be some smallest amount of space and or time that cannot be meaningfully divided in half again. Once you're within one of these distances of the finish line, the only possible next position you can have is the finish line. That certainly seems fair. After all, it's believed that in reality there is a smallest meaningful distance, the Planck length. Any interactions between or observations of particles more accurate than this span make no sense within physics as we understand it today. And the time it would take to travel a Planck length at the fastest speed possible, the speed of light, is the Planck time. So these seem to be the briefest pieces of space and time any known force in the universe could act across, whether that force is gravity or a force from Achilles' leg muscles. But does that resolve the crisis? Or is it just a way of avoiding the problem altogether by saying it doesn't matter because it won't be on the test? As John Earman has complained, it seems to me unattractive to make the truth of mathematical statements depend on the contingencies of space-time structure. Maybe Zeno's dichotomy tells us less about motion and time and space and truth than it does about our impressive abilities to confuse ourselves. And that's what makes super tasks important. They're a contact point, an uneasy handshake of sorts between the universe we live in and the brains inside us. Let's play around with some. They're not all the same. Some converge, like Zeno's dichotomy, others converge, but in ways you may not expect, and still others refuse to cooperate in any way. They diverge. A great example of a super task whose behavior diverges is Thomson's lamp, a famous super task devised by James F. Thomson. Imagine a lamp that can be turned on and off as quickly as you desire. What would happen if you turned such a lamp on and off Zenoianly? Well, let's find out. Just set a timer and turn the lamp on. Then wait 1 minute and turn it off. After half a minute, turn it back on, and then off again after a quarter of a minute. On again after an eighth of a minute, and so on, waiting half as long to flip the switch each time as you previously did. Now, as the number of switchings grows without bound, the total time elapsed approaches just 2 minutes. The lamp will be turned on and off an infinite number of times in just 2 minutes. So after 2 minutes, will the lamp be on or off? Well, by the definition of infinity, there is no last step. There is never a switching not followed by another. So the lamp can't be on because whenever it's turned on, it is immediately turned off in the next step, and it can't be off because whenever it's turned off, it's turned on right afterwards. What's the answer? It's easy to say something about a supertask when its partial sums converge, but when they just oscillate back and forth forever, Xeno-objects do this. Imagine building a meter-high cube. As with all supertasks, you construct at an accelerated pace. First, you put down a green half-meter tall slab. Then, a quarter-meter tall slab that's orange. Then a green 8th meter slab, then an orange 16th meter slab, and so on, until there are infinitely many layers of alternating color. Now, when you look at the cube from above, what color will you see? Orange? Green? Well, it can't be orange because every orange layer is covered by a green one. And it can't be green because every green layer is blocked by an orange one above it. What if we had a machine display each digit of pi in order at a super task pace? After its finite runtime, what would be on the screen? The last digit of pi? Well, that's impossible, right? But how could it be anything else? A super task allows us to exhaust an infinite sequence. Paul Benseroff delivered what is often considered the best response to these confusions. Is Thomson's lamp on or off? Is the cube orange or green? The answer is, we don't know, because these questions are incomplete. Thomson's lamp could be on or off or broken. The cube could appear orange or green or something else, but the super tasks, as stated, don't let us figure out which. I may as well ask you if a lamp hidden in a locked room is on or off. It's definitely one or the other, but I haven't given you enough information to do anything but guess. Super tasks like these describe an endless sequence of tasks and then ask us about the end. But we can't determine an outcome because although there may be an end to their duration, there is no end, no final member of their actions. They must be reworded or coupled with extra assumptions in order to be solved. For example, if we assume that the switch used on Thomson's lamp can only be all the way on or all the way off, we can't determine where it is after the super task. But if the switch is, say, a bouncing ball that completes the circuit, turning the lamp on each time it bounces on a metal plate, an outcome can be determined. If the physics here are ideal and the ball bounces half as high in half the time as it did on the previous bounce, its sequence of bounce heights will turn the lamp on and off an infinite number of times in a finite amount of time. Although this bouncing ball has no penultimate state, no second to last bounce, it does have an ultimate state, a final one, resting on the plate. The circuit will be complete and the lamp will be on. You can also describe a switch on Thomson's lamp that leaves it off. Sometimes the next state after infinitely many isn't paradoxical because of lack of information, but because of a surprising or non-intuitive discontinuity that occurs there. The Ross-Littlewood paradox is one of the greatest examples. Imagine a giant urn that can hold an unlimited number of balls. Now, imagine that you have an unlimited supply of balls, each with a unique natural number written on it. All natural numbers, in fact, since there's no end to how many balls you have. Now, working at an accelerated Zenoian pace, you move the balls to the urn 10 at a time, but in a weird way. At step 1, you place balls number 1 to 10 in the urn, but remove number 1. At step 2, a minute later, you place balls 11 to 20 in the urn and remove ball number 2. At step 3, you place balls 21 to 30 in the urn and remove ball 3, and so on. Upon the completion of the super task, how many balls will be in the urn? At first, the answer seems obvious. At each step, you are adding 10 balls and subtracting 1, so a net of 9 balls is added each time. 9 plus 9 plus 9 plus 9 forever. The series grows without end. Infinite nines means infinite balls at the end. But here's the problem. At each step, the ball with that step's number written on it is removed.
Ball 1 is removed at step 1. Ball 2 is removed at step 2. Ball 12 Google is removed at step 12 Google. Since there are an endless number of steps for any ball number, there is a step number at which it is removed. So although the urn's ball population grows without bound during the task, after the super task, the number drops to 0. It gets weirder. Here's a second, seemingly identical method. Instead of beginning with balls 1 to 10 and then removing 1, begin with balls 1 to 9. Then write 0 after the 1 on ball 1. For step 2, add balls 11 to 19 and draw a 0 on ball 2, making it say 20. For every finite step, both methods result in identical urn contents. But after infinitely many steps, the first leaves us with no balls, and the second leaves us with infinitely many balls written on which are all the natural numbers, each followed by an infinite string of zeros. Both are discontinuous at infinity, but dang, in very different ways. The bigger question now becomes, so what? Who cares? You will never have an infinite number of balls, and you will never have a large enough urn to hold all of them. You will never build a lamp that can turn on and off arbitrarily fast. We cannot investigate time or space past a certain smallness, except when pretending. So what are super tasks but recreational fictions, entertaining riddles? We can ask more questions than we can answer. So what? Well, here's what. Neanderthals. Neanderthals and humans, us, Homo sapiens, lived together in Europe for at least 5,000 years. Neanderthals were strong and clever. They may have even intentionally buried their dead. But for hundreds of thousands of years, Neanderthals barely went anywhere. They pretty much just explored and spread until they reached water or some other obstacle, and then stopped. Homo sapiens, on the other hand, didn't do that. They did things that made no sense, crossing terrain and water without knowing what lay ahead. Svante Pääbo has worked on the Neanderthal genome at the Max Planck Institute for Evolutionary Anthropology, and he points out that technology alone didn't allow humans to go to Madagascar, to Australia. Neanderthals built boats too. Instead, he says, there's, quote, some madness there. How many people must have sailed out and vanished on the Pacific before you found Easter Island? I mean, it's ridiculous. And why do you do that? Is it for the glory? For immortality? For curiosity? And now we go to Mars. We never stop. It's ridiculous. Foolish? Maybe. But it was the Neanderthals who went extinct, not the humans. Maybe it's only a fool who will perilously journey out to what might not be there. And maybe it's only a fool who will ask about super tasks, about infinity. But if you want to solve problems, you don't just solve the ones that are there, you find more and make more and go after the impossible ones. Fostering a love and obsession with problems is how you solve problems. Antoine de Saint-Exupéry wasn't a mathematician, but his advice fits nicely here. If you want to build a ship, don't drum up people to collect wood and don't assign them tasks and work, but rather teach them to long for the endless immensity of the sea. And as always, thanks for watching. Super tasks are cool, but super gifts are even cooler. That's why I'm excited to announce this year's Vsauce Holiday Box.
This thing comes loaded with exclusive Vsauce stuff and science gear, plus all Vsauce proceeds go directly to Alzheimer's research. I'm really proud of this box. You can pick one up at geekfuel.com/Vsauce, link down in the description. There's a limited amount available, so don't hesitate. And as always, thanks for watching.